Hello everyone. I wanted to do a quick video showing how you can start putting equations into Word specifically. I also will talk briefly about doing it in PowerPoint, but really I want to focus on Word because that'll give you the gist of what you need to do. So first, right here, you can see that we have a blank Word document. If I wanted to insert an equation, I would actually go to the top here. I can go to Insert, and over on the right here, we can click on Equation, and it will automatically put the equation editor here. You also could hit Alt Enter, and that will create the equation editor as well, open it up for you. Notice that whenever you do this, it's automatically going to center it on your screen. If you ever want it to, let's just gonna put a D here. If you ever want it to be left oriented, you could go into Home and change it there like you would anything else in Word, or just put any other text on that line. For example, a space, and you'll see that it automatically will jump it to the side. Now it does have some really interesting functionality that can be very helpful. For example, let's say you're doing a function, you could put something like f of x into your parentheses, and then watch what happens when I hit space. Notice it doesn't actually change the spacing of it, but it actually changed the size of the parentheses just a smidge. This is because what it's doing is when you have open and closing parentheses, it's going to try to create that entity where the stuff goes. That way, if I were to do something like this, say x divided by y, right? We have it like this. If I hit space, it's going to automatically turn it into a fraction, but those parentheses are going to grow with it. So this is something that can be really useful whenever you are creating your equations. You also could do something like this. You could do f of x, do open parentheses, close parentheses, hit space, and it will automatically put this little spot here for you to start typing in your equations. Now, in order to actually do your equations, you're oftentimes going to need to use your equation tool up top. So because I clicked off when I did the space, it went away, but if you look at the top here, you can see equation while I'm focused on this. Now, there's a lot of different functionalities that you can use with this. First and foremost, if you do this drop down, you can see that I have basic math up. This is going to have a lot of the different parts that we need, things like union, intersection, empty set. There's a couple of the main Greek characters that we use. For example, in stats all the time, we use mu. We might use pi, you got rho, you got sigma. If you do this drop down, you can see there are Greek characters. So you've got all of the lowercase and capital Greek characters. We have letter-like symbols. So this would be generally a little bit more of obscure math, but you might find something, or you might want to do something like real numbers, right? The set of real numbers, this is where you could find that because it's a letter-like symbol, similar with the natural numbers, things like that. Next, we have operators. This is going to be things like plus or minus, minus plus. You got different things like that. You got greater than or equal to, less than or equal to. A lot of these you can do with just typing them in and they'll automatically update. I'll show you that in a second. You've got basic in-array operators. You've got advanced binary operators, and you've got advanced relational operators. Following that, we've got arrows. This could be great if you wanted to have any sort of arrows in your equations, like you're saying this goes to that. You could draw arrows, things like that. You could have, a forward arrow. You could have an arrow going left and right, saying that it goes both directions, things like that. Next section, we have negated relationships. So this would be if you want to do something like not, if you want to do like not equals to, not less than, not greater than, not less than or equal to, this would be where you can do stuff like that. Next, we have scripts. This is just going to be script characters. I honestly never use this one, but it's there in case you need it. And then we have geometry, which has some special symbols for geometry, such as angle or, measured angle, stuff like that. Okay, so I'm going to go back to basic math. Now, if we look here on the right, this is going to be where you actually can put the different types of things you need in your equation. So I did a slash, which created a fraction. And I can do that even with nothing there, right? If I'm in my f of x, if I just hit slash enter, it's automatically going to put a fraction. But if you want to, you could come here to fraction, and you're going to see a couple different options. You could do a fraction like it did here, where it's one thing above another. You could do a fraction that's angled. You could do a fraction if you want to keep it in line next to each other. You can do bigger over smaller, and then you've got some common fractions, dy dx, delta y over delta x, things like that. Next, we have our script. This is going to be especially useful if you're doing things with like chi-square and things like that, where you need to have both superscript and subscripts. So if we click on something like this, for example, what it's going to do is give me two boxes, one for the regular, like whatever it is I'm putting there. Let's say it's E, and then you're going to have your superscript right there. So you could do something like e to the x. Now, like I said, you can do this without actually going into these. For example, if I want to do a superscript, I can just do e caret x, hit space, it automatically does that. If I wanted to do a subscript, let's say I wanted to do e, but it's sub 2, and it could do it that way. But if you wanted to, you could also do it right here, right? So you have your main character, and then you have your subscript. You also could do something like this if you wanted to have something with a subscript and a superscript. So this is actually one that I've found very useful. For example, when I'm teaching in stats, I might do something like this where I'll go into my Greek characters, and then I am going to put a chi, which is right here. And let's say that I want, it's going to be chi squared, and it has a power of n-1, something like that, like we do in math stats. This is exactly how we could do that. And of course, if I delete all this, it'll delete it kind of as a unit. There's also one option where you could have the superscript and subscript to the left. I've actually had to use this in the past where I didn't want the superscript, but I wanted the left subscript, and I also wanted a right subscript, so I kind of used it like this to kind of manipulate it, where I used this, left the top left box empty, and then put a subscript on the right, and I was able to kind of, for something like a combination or something like that. Then you've got your radicals, right? You got your square root, your nth root, and then some extra ones there. If you want to do integration, you've got integral symbol. You've got integral symbol with your limits of integration. You also have limits of integration in this one, but now they're kind of more above and below versus kind of to the side. You got double integrals, triple integrals, and then you've got your contour integrals and stuff like that. So these are all options available to you. Next, we have our operators. This would be things like your summation, same sort of options. You got your summation with your limits at the top and bottom, kind of off to the side. You could do just the bottom if you want to do like limit of n or summation over n, something like that. And then same thing off to the side. You've got your multiplication, same stuff. You got your code product. You've got union. You've got intersection. You've got things like your logic statements, things like that. Following that, we've got different types of brackets. So this again is one place I use a lot because you've got your general brackets, and most of these, if you can type them in, you can just type them with your computer like I showed you with the parentheses, do open, close, hit space, and it'll create this. But sometimes you're going to want things that aren't easily available to do on your keyboard. For example, when I'm doing something with like functions where I maybe have like a piecewise function, I could use something like this for 2 options or 3. And of course, if I ever am doing something like a matrix or I'm doing something like a combination, right? How we did in Intro to Stats where I do like n choose x, this is how I would do it. I would click something like this. I would get my parentheses. I'd have my top number, my bottom number, and I can put those there. And then there's also certain things which I just wouldn't know how to type in without looking it up, which would be things like your floor functions, your ceiling functions, stuff like that. Next, we've got, your trigonometry type stuff, sine, cosine, cosecant, and things like that. I typically don't use these because I just type them in. So I've never actually used one of these, but they are there if you want to click on them. Now we've got accents. Now this is tremendously useful, especially when I'm teaching about things like statistics. For example, if I wanted to do hat, I could do a hat operator, and now I could do something like x hat or something like that. Or more specifically, I can do, I'm going to go to my accents, and right here, you're going to see a bar. So if I wanted x bar, this is how you make your x bar. Now this is one place where Word is different than PowerPoint. The reason is because in Word, let's say that I put the X there, and I'm going to highlight it, and now I'm going to add the accent. I'm going to add my bar. Notice that it just puts the bar there. If I was in PowerPoint, which actually I do have PowerPoint up, let me pull it up. Okay, so we're in PowerPoint, and I'm just going to show you quickly what this would look like if you did the same thing in PowerPoint. So just like before, I'm going to hit Alt equals, and it's going to pull up my equation editor. If I did X, I'm going to highlight it. Watch what happens when I do my accent. I'm going to put bar, and it puts the spot for where I'm going to put the X. It puts the bar, but it just moves the X over. And it's just little inconsistencies like that. So it works exactly the same way for the most part, but there's little things like that where it's going to be just a smidge different. Next, on the right, we have our limits. So this would be something like if you want to do log or limits or min, max, things like that. These are useful to do. You've got operators. And then finally, you have matrices. And you'll see that you have ones here that don't have any brackets on them. So what you can do is you can actually just put 2 square brackets, hit space, it'll create the square brackets. Then within that, you can decide, like if I want a three by three matrix, I just click on this one, right? So if I do something like, actually, let me get rid of this real quick. Let's say that equals, I'll do that, something like that. I'm gonna do square bracket, space. Now let's say if I want to turn this into a matrix, I want it to be a 3 by 3 matrix, I can just click on this, and now I have a 3 by 3 matrix where I can put my different values. Another nice feature in this is if you go to the bottom, you can see these sparse matrices. These are great if you want to have a matrix where you don't want to write out an entire matrix, you just want to put like the corners and the dot, all that. This is something you can do right there. So for the next thing I want to do, I just want to do a quick example of making one of these equations together. So in my computational stats class, I asked students to specifically use distributions when using R, but also to go and look them up and then write out what the PDF was, the CDF, things like that. So we're going to do just that here. We're going to look at, this is the gamma distribution, and we're going to do the PDF for this. So notice that it's f of x equals 1 over gamma alpha, theta to the alpha, x to the alpha minus 1, e to the minus x divided by theta. So let's do it. So first thing we're going to do, we're going to do our f of x, hit space, equals. Now I want to do my fraction. If I'm doing my fraction, what you could do is you could just hit slash, hit space, and now it will automatically do the fraction for me. So I'm going to do 1 divided by. Now I need a gamma. So I'm going to go up here. I'm going to go to my Greek characters, which I'm already there. And then I'm going to get gamma, which is right here. So I'm going to do gamma, open and close parentheses. Notice I hit space, so now it gives me that spot. And I want alpha. So I'm going to go to the top here, and I'm going to put alpha. Next, I'm going to do theta to the alpha power. So what I'm going to do here is I'm going to find my theta. Let me actually expand this. It'll be a little bit easier because it'll be in order. And I got theta right here. So theta to the alpha, hit space. Okay, great. Now I'm going to hit right one time to get out from underneath the fraction. And now we're going to do the part that's next to it. So next thing we'll have is x to the, now because this is going to be alpha minus 1, I'm going to hit space first to create that superscript. And then I'll come up here and I'll do alpha minus 1. I'm going to hit right to get out of the superscript. And then I'm going to do e to the, and then it's minus x divided by theta. So again, I'm going to pull up theta. And now we have the function for our gamma distribution. Now notice I didn't hit space at the end because I actually like when I'm in the superscript to keep it kind of in line like this. If I were to hit space, it would actually create a fraction from it, but I don't think that looks as clean as before hitting space. So at that point, I would just hit to the right, and then now I've got my function. Hello everyone. As we finished doing the kind of simpler operations in R, now it's time to kind of move on beyond that in programming and start looking at things that get a little bit more complex. So now we're going to begin the section on simulation. We're going to begin by looking at using some of our built-in functions for distributions to create samples in order to simulate. We will then follow that by a lesson on the sample function, which is actually something I use quite a bit whenever I'm creating samples. In fact, I use it when I'm doing my courses so that I can randomly assign students whenever I need to create a random order or something like that. Following that, we will then look at bootstrapping, which is a method you can take your data and then create larger samples of your sample in order to try to test out different hypotheses and simulate things like that for different tests. We are going to then revisit some more of our distributions that we use pretty commonly, things like normal distribution, things like that, but we're going to go a little bit more advanced and actually start implementing a little bit of functions, though we'll talk more about creating functions later. We are going to look at how do you validate your models, and we'll look at different methods you can use with sampling in order to create validation sets. We will then look at loops, and following that, we'll finish off this part of the course by going over if and else if type statements and how they can be used in order to do all sorts of things with programming, specifically in this case, simulation, but also beyond that. So to begin with, we're going to focus on the random number generators that are in R. Those are your R functions. Now we've looked at these previously. These are things like R norm, R binom, and now we're going to talk specifically about R unif, which is for uniform distribution. So uniform numbers are ones that are equally likely to be in a specified range. Often these numbers will be by default between 0 and 1 for computers, and in practice we'll have some A or B. A is the starting point, B is our ending point, depending on our problem. So an example where you may have actually used uniform numbers before would be rolling a die. If I have a 6-sided die in my hand, I know that there are 6 possible outcomes: 1, 2, 3, 4, 5, and 6. Every one of those has a 1 in 6 probability of occurring. So therefore, it is a uniform distribution. If I were to graph the probability distribution, it would be pretty much a straight rectangle of 6 rectangles, each with a height of 1/6. And of course, this can then be kind of extrapolated to a continuous case where you have some starting point A, some ending point B, and between these 2 points, every outcome is equally likely. So the height would be 1 over n. This is actually really useful because if you have a bunch of data, basically what you can do is you can assign everything one of those possible points with it from A to B, and then everything is equally likely to be selected. In fact, we use this a lot of times whenever we're using the sample command later. It's actually treating it as a uniform distribution. All outcomes are equally likely. So let's do some examples now looking at exactly this. If we go to R now, you can see that I have R unif for R, which is creating random numbers. For a uniform distribution, I'm going to create one number, and I'm going to have a starting point of 0 and an ending point of 2. So if I were to run this, you will see that I get 1.433. So in this case, I said that it's the time that you're waiting at a light. Maybe it's 1 minute and 43 seconds, something like that. If I were to do this again, remember everything between 0 and 2 is equally likely. I get 0.656, or I spent 0.65 of a minute waiting at the light. If I do it again, I get 0.18. Okay, so this light I didn't have to wait very long. You can also, just like before with our R functions, you can actually specify the specific arguments. So in this case, I am again doing the exact same operation, but now I have that I'm going to use R unif. I'm going to select one number. Now I'm going to use the argument min to give me my minimum value. I'm going to do max for my maximum value. So this is the same exact thing as R unif 102, except for now we've actually put our arguments into our function. So if we do this again, just like before, I get 0.5017. Before we move on to doing the rest of these examples, let's actually do like we always do. Let's do question mark R unif. And if we run this, you can see that we have R unif here, and our arguments are n, min equals 0, max equals 1. So what does this mean? This means that in order to use a uniform distribution and create random numbers, I need to specify what n is. My arguments are min for the minimum value, that is your lower boundary, max for my upper boundary, so that's my maximum value, and it has min equals 0 and max equals 1. So these are my default values. This means that as long as I give it some number n of the number of values that I want it to spit out, it will work by automatically putting 0 for the minimum and 1 for the maximum. This is kind of what I was talking about the default being 0 to 1. So example of this would be if I want to get 5 numbers between 0 and 1, I could just do R unif 5, run that, and now I have 5 numbers between 0 and 1 with all of them being equally likely. So if we look at our next example then, we have R unif 502. So this is doing the same distribution we had previously with a minimum of 0 and a maximum of 2, but we're going to get 5 numbers from it now. So we do this, we get 0.831, 0.1668, 0.884, 0.7036, and 1.7233. Again, we're going to do it again, and you'll see that we get completely different numbers. If we run it again, we get completely different numbers. Just like I said before, if I have R unif and I do not have any arguments, it is going to default between 0 and 1. Now, the reason this can be so useful is because if you think about these numbers being between 0 and 1, you could think of them as where someone is on a distribution. Because these values are all between 0 and 1, you could almost think of them as probabilities, right? If I wanted to give some weight to things, I can do R unif, or I could, like I said, treat all things as equally likely, assign each one a value between 0 and 1. They're all likely to be selected. But again, we'll talk about a better method for that later on. But oftentimes we will use this to create the distribution where all things are equally likely. So to recap, our general form for a uniform distribution is RUnif. We need to put in the number of values that we want output. We have minimum equals 0 as our default, maximum equals 1 as our default. This can allow us to decide how many uniform random numbers that we want. That's by selecting our in. This will give us a range of possible values, so minimum to maximum. This will give you your range. This does not mean that you're going to get values that are necessarily near the minimum or the maximum, right? Because all things being equally likely, if I were to run this many times, sometimes I may end up with a lot near the maximum, a lot near the minimum, a lot near the middle, evenly distributed, because that's how randomness works. So next what I want to do is I want to generate 100 random numbers following a uniform distribution, and I'm going to save them to the object X. Then I'm going to draw a histogram using X with and without our probability being true. So let's do exactly that. So first things first, I'm going to do hist of RUnif. That's going to create a histogram of our uniform distribution where we're randomly selecting, and I have 100, so I'm going to select 100. Now, notice I didn't put any arguments in this. This means that it is going to be in the range from 0 to 1. So if we run this, you'll see that we get this histogram here, where it doesn't look like they're necessarily all equally likely. They're not equal because of randomness. The law of large numbers states that as my sample size increases and gets bigger and bigger and bigger, the empirical probability, which is the probability of an event happening based on the actual data, should approach my classical probability, or the probability of the actual distribution being that they're all equally likely. So the second example, real quick, we'll just do the same sort of thing. We have histogram. We're doing a uniform distribution, pulling 100 numbers. This one we just put probability equals true. One thing I want to point out while we're actually looking at this is you might think because we put probability equals true that it should automatically put probabilities on the left-hand side. This is kind of misleading and one of those kind of places people fall into problems whenever using R. So example would be like if I pull up the help for histograms, you will see that frequency, which is actually the opposite of what probability is, right? So it's an alias for frequency. You can do probability equals true, or you can do frequency equals false. And you can see here, logical if true, the histogram graphic is representation of the frequencies, the counts component of the results. If false, probability densities, component density, are plotted so that the histogram has a total area of 1. Again, it does say here, though, defaults are true if and only if. Breaks are equidistant and the probability is not specified. So it just causes some issues with this, but we're not going to focus on that at the moment. That's not really the point we're trying to make. I would suggest you play with this, though, and try to figure out why this is going wrong and what you can do to fix this. But what I wanted to show you, though, is that if I go back to my original histogram and I were to run this, again, this does not look very uniform at all. What would happen if I were to increase the size? Let's say instead of doing 100 values, I'm going to do 100,000. So you're going to see that it's now starting to look a lot more likely that everything is going to be equally likely to happen. Let's now go up to 10 million. So it's going to take a second. Notice what's happening is that as my n gets bigger and bigger and bigger, my empirical probability is going to begin to approach my classic probability, which is to say that it would make all of these outcomes equally likely. In the short term, this isn't going to be the case typically, though. So this is always one thing to kind of keep in mind, that just because something is uniform, meaning all things are equally likely, it does not mean that your actual graph, if you have a small sample, will be that all things happen equally. It just means that they are each equally likely. If I have 100 students and I'm going to randomly pick 5, all students have an equal likelihood of being selected. But it does not mean that everyone will be selected equally. If I pick 5 students randomly, and I do another sample and pick 5 students randomly, and I do another sample and pick 5 students randomly, I may end up with 2 samples that have a lot of overlap with each other. Or I may have samples with no overlap with each other, right? Because in the small scale, it's going to have a lot of randomness as part of it. Now let's talk a little bit more about normal distribution. So normal numbers are the backbone of classical statistical theory due to our central limit theorem. So a normal distribution has 2 parameters of interest. We've got the mean mu and we've got standard deviation sigma. And this will represent the location, that is its central tendency, that's mu, where it's located in actual real space, and its spread, that is our standard deviation or our variance, which would be sigma or sigma squared, respectively. An example of this might be something like IQ scores. So IQ scores may be normally distributed with a mean of 100 and a standard deviation of 16. And this is actually how IQ scores are normed, meaning that if you're comparing IQs for people now versus 30 years ago. They are normed this way, so they are always centered at the same place with the same distribution, meaning that it allows you to have some similar comparison with each other, but also it's not really showing you where someone is directly compared, because somebody 30 years ago may not have known something that people now would know just as a course of fact. But it's just an idea, of the example of like a normal distribution, what it means with our mean and our standard deviation. So the family of normals can be standardized to normal with a mean of 0, that's our mu, and a standard deviation of 1, and this is called our standard normal. So we standardize this in order to get things into the same scale, and also for most stats classes, especially lower level stats classes, so that we can use a normal probability table, a standard normal table, to use our standard normal table in order to find the probability of different intervals. This would be less than something, greater than something, or between two values. I mentioned the reason we use normal distribution so much is because of our central limit theorem. So what does our central limit theorem actually say? So the central limit theorem is a fundamental concept in statistics that describes the behavior of the mean of large sample drawn from any population, regardless of its underlying distribution. So there's actually two parts to our central limit theorem. The first is that if I have data that comes from a normal population, and I actually, when I'm teaching this in my classes, I usually say a known normal population, because even if it's a normal population, if we don't know that, then we would treat it as if it's not from a normal population. But if it is from a known normal population, that means if I do a distribution of sample means, which is to say that I take every possible sample of size n, and I were to take the mean and create that distribution, regardless of the sample size, meaning all the way down to a sample size of 1, it would have a normal distribution with a mean of mu and a standard deviation, in which case this is actually called the standard error of means, of sigma over the square root of n. If it is not a known normal distribution, that means it can be any distribution. It could be from a uniform distribution, a binomial distribution. It could be a normal distribution, but it's not known to be normal. Then if we have a sufficiently large sample size, we can assume that it also follows a normal distribution. So according to the central limit theorem, as sample size increases, the distribution of a sample mean becomes approximately normal, with a mean equal to the population mean and a standard deviation equal to the population standard deviation divided by the square root of the sample size. This allows statisticians to make inferences about a population mean based on sample mean using techniques like hypothesis testing and confidence intervals, which we will cover later in this course. So since we're using normal distribution and standard normal is so pivotal in statistics, let's do some examples on exactly that. So we're going to use our norm. In this case, we're going to pick a random IQ score from our IQ example, meaning we have a mean of 100 and a standard deviation of 16. Actually, before we move on to the normal example, I actually had one more quick example I wanted to do with RUnif and I forgot to do it. And rather than try to edit it in, I'm just going to talk about it really quickly. All the examples I had done with R uniform basically were 0 to 2. And I just wanted to give you one more example to kind of show you that when you change the minimum maximum here, I have a uniform distribution. I'm pulling 100 numbers. I've got a minimum of 20 and a maximum of 35. So if I were to do this histogram, you can see that it goes from 20 to 35. I just wanted to show this so that people don't always get into their head that it has to be these very low values of 0 to 1 or 0 to 2. You can have any starting and ending point based on whatever you're doing. So now let's go back to our normal distribution example. In this case, I'm going to assign x with our norm 100. So this means that I'm going to pull 100 numbers from a standard normal with a mean of 0 and a standard deviation of 1. So I do this, and if I wanted to, I could look at x, and you'll see that we have 100 numbers that are distributed with a mean of 0 and a standard deviation of 1. Next, I'm going to create my histogram where I'm going to put probability equals true. I'm going to put the color to gray 0.9, and this is going to be the histogram of that distribution. You can kind of see that it does look pretty bell-shaped and symmetric. Of course, just like before, there's always randomness when I have smaller samples. If I were to increase my sample size, this would begin to look more and more bell-shaped and symmetric. I'm going to actually overlay the density curve using the curve function. So curve, I'm going to use dnorm, which is going to give me the density function of x based on my data. I'm going to do add equals true. This will tell it to add it to the graph that is currently there. And then, of course, I'm just going to put color equals 2 so we can see it. So you do this, now you can see the histogram of what we're actually seeing from our data and the density curve that you would expect, the normal distribution you would expect based on our data. Now let's do another example for our IQ scores. So in this case, we're going to set X to, using our norm, we're going to pull 100 values where we have a mean of 100 and the standard deviation of 16. So if we look at our X, these are the IQ scores of the 100 random people that we selected. I'm going to create a histogram of X, probability equals true, and again, color gray equals 0.9. Here is our distribution of IQ scores. So just like before, let's put our density curve on top of this graph. So we do curve dnorm X, add equals true, and color equals 2. And when I run this, nothing happens. So why did nothing happen? Well, this is actually because just like when we're setting our R function, our norm, things like that, we have to set certain arguments and their defaults if we don't. Dnorm also has the same things. So if we do question mark dnorm, oops, I spelled that wrong. If we do question mark dnorm, you will see that it's dnorm X, so we have X, mean equals 0, SD equals 1. So it worked on the first one because the default was that it was assuming that we have a standard normal distribution. We don't have a standard normal distribution. We have a mean of 100 and we have a standard deviation of 16. So if we were to go back to our console window or our source window here, now we're going to change this to curve dnorm X, that's from our data, 100 for our mean and 16 for our standard deviation. Now we'll add this to our graph and you'll see that is able to actually do this. Okay, so I just wanted to point this out because one of the issues sometimes people run into is they learn how to do these commands. And we do these sort of simple examples where everything is standard normal, or we're doing like a QQ plot, and it doesn't work whenever you're away from that standard normal. You have to actually update it to work the way that it's supposed to. So I just wanted to show an example like that in order to kind of, show that. One other thing I also want to show you though is that whenever you are pulling these numbers, it is going to be randomly done. It's done with randomness or pseudo randomness really because it's computer. So if I were to run this again, create a new histogram and then put my curve, notice that it looks different. If I were to do it again, notice that it looks different. Every single time we do this, we get a different random set of 100 numbers because every time it is randomly doing this. I will talk later on about how you can set what's called a seed so that you would get the exact same value every single time. This can be useful if you're trying to show an example and you want someone to get the exact same values. I actually prefer to not use seeds because I want you to actually kind of think about it in terms of randomness. When you pull 100 numbers and somebody else pulls 100 numbers, you should not have the same distribution. You should have different, they might come from the same underlying distribution, but your sample data should be different. Another distribution that comes up a lot of times when we're simulating data will be the binomial distribution. So before we talk about the binomial distribution, let's talk about the Bernoulli distribution. Bernoulli distribution would just be a single experiment where you have one trial that has two possible outcomes with some probability P of success. This could be something like I'm going to flip a coin, and if you have a fair coin, you'll have a probability of 0.5. But let's say you have an unfair coin. I have a weighted coin, so the probability of getting heads is 0.7. A Bernoulli trial or Bernoulli probability would just, or a Bernoulli trial would just be flipping the coin one time. Binomial distribution is looking at what if I were to do this multiple times for n set number of trials. So binomial random numbers are discrete random numbers. They have the distribution of the number of successes in n independent Bernoulli trials where the trial results in success or failure. And in fact, you can actually, when you're looking at a binomial probability or binomial distribution, you can count the number of successes. That is what we're actually looking at. When we say we have 5 successes, we're looking at the fact that we could have, success in the first 5, success, 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 followed by a bunch of failures, or you could have success, 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 failure, success, and a bunch of failures, and every combination where it has 5 successes, and that's our condition we're actually looking for. Single Bernoulli trial is given with n equals 1 in a binomial. A binomial distribution number is the same as the number of ones in each of the Bernoulli numbers. There's 2 parameters that we need for our binomial distribution. We need n, the number of trials, and we need p, the probability of success. Every combination of n and p is a different binomial distribution. So these two are set. Once they are set, that determines the distribution that you are in. If I have n equals 10 and p equals 0.6, that is a different distribution than n equals 10 and p equals 0.7. If I have n equals 10, p equals 0.6, that is a different distribution than n equals 11 and p equals 0.6. So you have to think of it as this is a family of distributions based on the number of trials and the probability of success. Now, there are a couple things about the binomial distribution that have to be true. For example, like I said, your number of trials is set. Your probability of success must be constant for all trials. That means if I'm flipping 10 coins, it has to have the same probability of success for all 10 flips. In each trial, there are two possible outcomes, right? So each of those outcomes have a probability of success of p, which because each of these trials, if you think of it as flipping a coin, right? If I have a probability of success of p, that means I have a probability of failure of 1 minus p. So to generate binomial numbers, we're simply going to change our value n from 1 to our desired number of trials. So in this case, what we're going to do, instead of going through and putting the numbers hard-coded into our R binom to actually simulate those, we are going to set them ahead of time so we can just change them on the fly. So to do this, we have n equals 10, and I have semicolons, so on the same line, I can have another line of code, p equals 0.5. So in this case, I'm flipping 10 coins, and each one has a probability of success of 0.5. So the first command I have here is R binom, 1, and then n and p. N being the number of trials, p being the probability of success. So this is going to flip 10 coins, and I have 5 heads. If I were to do this again, this time I got 7 heads. If I do it again, this time I get 5 heads. If I do it again, this time I get 4 heads. We can actually do this automatically just by setting the number of times you want to, number of values you want to get. So our binom 5 in p, what it's going to do is it's going to look at if I have n coins, in this case 10, and I have a probability of success of 0.5, if I flip those 10 coins, how many successes did I get? And then I'm going to do this, repeat this 4 more times, so I have a total of 5. So doing this, the first time we flip those 10 coins, we have 4 successes. Second time we have 6, third time we have 7, fourth time we have 3, and the 5th one we have 6. Now going back to our central limit theorem, do you remember how I said that if we have a distribution that is not known to be normal, if we have a sufficiently large sample size, we can assume that it follows a normal distribution. In fact, we do this when we're teaching intro to stats. Well, this counts even for a discrete distribution like the binomial distribution. So in order to do this, we usually have some criteria that we need to meet. And we, in intro to stats, use n and p, so n times p must be greater than or equal to 5, and n times q must also be greater than 5, which remember, q in this case is just 1 minus p, it's probability of failure. So looking at my n and p, if I did n times p, I get 5. If I do n times q, which is again 1 minus p, I get 5. So in this case, this is a large enough sample that based on our criteria we use, we could assume that it will follow a normal distribution. We can approximate it by a normal, and we'll get pretty close to the actual probability. Now, some different materials will use different numbers. The two that you most often have are NP greater than or equal to 5 and NQ greater than or equal to 5, or you may see NP greater than or equal to 10 and NQ greater than or equal to 10. Notice that I use the term and, by the way. This is an and statement, meaning both must be true. If NP is greater than or equal to 5, but NQ is not, you can't do normal approximation. If NP is not greater than or equal to 5 and NQ is, again, you cannot do normal approximation. Both must be greater than or equal to 5 or 10, depending on whatever threshold you're using. I want to actually show why this is. You might notice that I didn't need a very large sample size for this to work. I have 10, n equals 10, and a probability of 0.5, and both of them were greater than or equal to 5, because both of them were equal to 5. But what would happen if I were to change my probability of success to 0.9? So let's do that real quick. So now I have a probability of success of 0.9, and I have 10 trials. When I do NP, I get a value of 9. So this part does succeed. But what happens when I do n times q, or 1 minus p, the probability of failure? I get 1, meaning this would not be enough data for me to be able to use a normal approximation. So what I would need to do to make this work to be able to approximate using normal distribution, I would have to increase my sample size. So what times 0.1 would give me at least 5? In this case, it would be 50. So now if I have a sample size of 50 with a probability of 0.9, You'll see that for NP, we get 45, which is greater than or equal to 5. And for NQ, we get 5, which is greater than or equal to 5. So basically what we're looking at is, do you have a big enough sample to kind of deal with the fact that if I have a P that is dead center, then that means if I kind of were to graph the histogram of my binomial distribution, I would have my center value and then it would go out equidistant, and it would basically automatically look like a standard normal curve, just discrete. If I have a probability that is further to closer to 0 or closer to 1, then I would need more data to kind of compensate for that. If you wanted to kind of dive a little bit deeper into what this is actually looking at, NP is the expected number of successes. NQ is the expected number of failures. So if I have a probability of success of 0.9 and I flipped 50 coins, I would expect, on average, that I would get 45 successes and 5 failures. It doesn't mean you always get 45 and 5. It just means that this is what I would expect. This is the expected value for successes and failures based on this binomial situation. So now let's actually dive a little bit deeper into binomial approximation. So the number of successes is discrete, but as n gets large, the number starts to look normal. This is the case of the central limit theorem, which states in general that x bar minus mu divided by sigma is normal in the limit, like for this above here, for a standard normal, meaning it'll be based on a normal distribution with a mean of 0 and a standard deviation of 1. The expected value given to us for binomial, which will be expected value equals of x equals to mu, is equal to n times p, right? Now I told you that n times p, which is actually something we just looked at checking for our assumptions. Well, that's looking at the expected number of successes. If I were to do this binomial experiment, I would expect on average this many successes. And the standard deviation is going to be the square root of n times p times q. Before we move on to this example, I do want to point out that if you want to dive more into normal distribution and binomial distribution and approximation, normal approximation to binomial, I do have videos for this in my Intro to Stats course where we talk a lot more about this. We talk about things like correction for continuity and all this kind of stuff. And I go into detail. I've got the light board. I do all sorts of drawings for it if you really want to try to understand this a little better. But we're going to be focusing here mostly on the code aspect of it. So next thing we're going to do is we're going to look at if we have n equals 5 and a probability of success of 0.25. So if I were to run this, what I'm going to do now is I'm going to pull 100. So I'm going to do 100 binomial trials where, again, I have 5 coin flips, probability of success of 0.25. If I were to do a histogram of this, you'll see that this does not look very normal at all, right? I could put sort of a bell-shaped curve, but it's heavily skewed to the right. And this is what I was talking about you're going to need a bigger n for this. So let's make n bigger now. Let's see what happens. Let's say that I have n of 1,000. If I were to do the same thing, notice that it's starting to look more like a normal distribution. Let's say that instead we did 100,000. What's going to happen with my histogram is that each time, there's still going to be some randomness each time I do it, but notice that it's starting to look a little bit more normal. I could kind of put a bell-shaped curve over this. What if instead of doing 100,000, I did 10 million? Okay, so again, the more skewed your data is, that means the closer your probability is to 0 or 1, really you need more and more data to kind of make it approach a normal distribution, right? And this is where the normal approximation does kind of fall apart, is that if your probabilities are very, kind of off to the edges, it's not as, you'd have to get n bigger, bigger, bigger. So for this next example, we're going to set the object xvals as 0 to n. So this is going to be 0, 1, 2, 3. It's going to be the sequence up to n. So let me actually go back and change my n back to 5 before we do this. So now looking at xvals, you're just going to see that it's a sequence 0, 1, 2, 3, 4, 5. Now what we're going to do is we're going to do points for xvals. We're going to do d binom. So remember, our d is going to give us our density function for x values, n, and p. So we have those values already set. And type equals h. That is going... So actually, I'll just show you real quick. So points, what it's going to do, actually, let me rerun this. What this is going to do is it's basically going to put a line to the height of where that density curve should be. And so instead of drawing the density curve as a curve like we did previously, in this case, what we're doing is at 0, 1, 2, 3, 4. In 5, we are putting a line up to the height of our density curve. Or if you look at the next line, same thing, points, we're gonna do xvals, dbinom, xvals, n, and p. Type equals p, this is going to give us a point at each of those. So of course, together, by adding it in, it's gonna be a line with a point at the top. If I were to recreate my histogram and just did the second one, you'll see that it would put a point for each part where my density curve would be. So you can kind of think about if I were to connect these with a kind of a curve, I would create a density curve overlaying this histogram. Another common distribution that we use a lot of times when we're simulating data is going to be our exponential distribution. So the exponential distribution is important, especially for like theoretical work. If used to describe lifetimes of things like electronic components for first order. So for example, let's say you have a mean life of a light bulb is 2,500 hours. You might think that its lifetime is random with an exponential distribution having a mean of 2,500, meaning that some light bulbs will last longer, some will last less. But you would expect that more light bulbs will fail the further time goes on, meaning that it's going to follow an exponential curve. Most will still be alive for a long period of time, and then what's going to happen is for you actually this direction is that it's going to start to decay, and then it's going to kind of peter out like that. So let's do an example of exactly that. First thing we're going to do is we're going to set our object x as our exponential. We're going to do 100 values, and we're going to have a rate of 1 over 2,500. Because as always, if we do question rx, you're going to see that we're going to need n, and we're going to have a rate of, and this is where you're going to put your rate. This is your vector of rate. So I'm going to set this as 1 over 2,500, which is the number of hours. So I expect that if it lasts 2,500 hours, on average, that means that the rate of decay is 1 over 2,500. So now if we look at our x values, you'll see that we have 100 values just of how long these light bulbs lasted. Now what I'm going to do is I'm going to create a histogram. Probability equals true, color equals 0.9 for gray, and this is what our histogram looks like. So I'm going to put a curve using curve for d exponential, right, because d gives us our density curve. And you can see the overlying exponential curve. If we were to rerun this again with all new data, let's do it again. Let's see what this new curve looks like. See? So every time we're doing this, we're simulating new data. And this can be how we actually can do simulations to test whatever it is we're interested in based on the distribution that we think might underlie it. Whenever we are about to do an experiment, for example, one of the things we'll do is called power analysis, which we will look at what is the power of a statistical test, meaning that what is the probability that if there is a false null hypothesis, that we will accurately be able to reject it. Well, one way that a lot of times people do this is they simulate it using something like Markov chain, Monte Carlo simulation, things like that. But one of the underlying ideas that a lot of people use is assume that everyone in this sample that we're going to have follows a normal distribution. What is the probability that blah, blah, blah? And you'll do this, and you might simulate it over and over and over again. We'll talk more about this with things like bootstrapping and stuff like that. But that's the underlying idea, is you're looking at, if I simulate this data based on some assumption of the distribution, what is the expected outcome, and what is the likelihood that, in this case, that I would be able to reject a false null hypothesis. So that's going to be it for this video. One thing I would like you to do as we kind of leave off is I want you to try this out yourself and try learning different distributions. So generate 100 data points using the following distributions and draw a density curve with those data points. So try it with a Poisson distribution. This would be things where you have rare occurrences. T distribution, student T distribution. This is related to the normal distribution. It's bell-shaped and symmetric, centered at 0, except for its small sample size. You have your F distribution. Try with beta distribution. Try chi-squared distribution, which, by the way, when I start doing more of the videos on mathematical statistics, we're going to talk a lot more about some of these other distributions. But then what I would also like you to do is look up the PDF, CDF, mean, and variance, and kind of look at it mathematically for each of these distributions. So, for example, let's say we want to look at the chi-squared distribution. If I go to Google here, I'm just going to put chi-square distribution, and I'm just going to go to Wikipedia because, it's simple. And if we go down here, you can see this is the PDF for chi-square distribution. You have 1 over 2 to the power k divided by 2, gamma k divided by 2 times x to the k divided by 2 minus 1 power, and then you have times exponential of minus x over 2. For the CDF, you have 1 over gamma k over 2, blah, blah, blah. You've got the mean, you've got the median, and you can look all of this up for any of these distributions, right? If I instead decided to do the F distribution, again, I'm just going to go to Wikipedia because it's first, it's easy for the example. You can see all the information right here. You've got the PDF for your F distribution. You've got your CDF, which you got an index function in this one. You've got the mean, and you've got the mode. And I just kind of want you to be doing this because this is where these topics can become so useful, because in statistics class, we focus on the distributions, the understanding, the assumptions, all the things about them. In this class, computational, we're looking at actual implementation. I can randomly create 100 numbers from an F distribution in moments versus trying to do this by hand, something like this. So this is where a lot of times you're kind of bringing the two things together. Your theoretical knowledge you learn in class with the application of being able to do it on the computer to simulate some actual data and actual outcomes, which can then be used usually for things like preparing a pilot study, stuff like that, for actual research. Hello everyone. In this lesson, we're going to be jumping into sampling and looking at a function in R that I use all the time. So the sample function in R is a useful tool for randomly selecting a subset of data from a larger data set. It can be used for a variety of purposes, such as selecting a random sample of observations for analysis, creating a randomized control group for an experiment, or testing the performance of machine learning models on different subsets of data. So first thing we're going to do is we're going to look at our basic syntax. So the basic syntax of sample is sample and then parentheses, and the first thing is X. This is going to be your data. This is going to be what you were sampling from. Then you have size. This is the number of values or things you want to pull from that data for your sample. So if I have 100 people in my survey I did, let's say, and I wanted to sample 10 of those, the X would be the data I have from those 100 people. The size would be 10, how many of them that I actually want to sample. Following that, we have replace equals false. This means that by default, when I do a sample, when it pulls one of the data points out of the sample to use, it will not replace it. So if I had 100 and I pull one of them out, now I have 99 to select for the second option. I pull one out, now I have 98, then I have 97. The default of this, as you can see, is false. If I were to change this to true, this means that it will in fact replace. This would be with replacement or without replacement. If I do true, this means that once I've selected that data set or that object, then I would put it back in and it's possible that I could sample it again. And then the last argument we have here is prob, which is a vector of probabilities for each element of X. This is used to weight the sampling probabilities. So this would be if you wanted to give different weights to your different observations that you were sampling. So how does this all work together? Well, if you have some larger amount of data and you want to take this subsample, you would think about things like, do I want to do this with replacement or without replacement? And this can be used to simulate data, much like we've been talking about. If I create a die, a six-sided die, so I have values 1 through 6, and I want to sample rolling that die, if I did without replacement, that would mean when I roll a 6, that means if I roll that die again, I only have 1 through 5 with the option of the data left. But if I'm rolling a die multiple times, that 6 doesn't go away. So I know in this case, it needs to be with replacement. So I would do replace equals true, and each time I would sample from that six-sided die, I would get all 6 possibilities as something to be sampled. And as we kind of were discussing in the previous slide, there are a lot of reasons we would use this. One example is for this actual class, when it comes time at the end of the semester to do project presentations, this is exactly how I do it. I take a roster of the class, so that's my data, and I sample it with the size of the roster. So let's say I have 28 students, I would sample 28 with replacement equals false, because once a student is selected for slot 1, 2, 3, 4, whatever, I don't want them to be on the list anymore to be selected for another slot. So in this case, I would do replace equals false, or I'd leave it as default, and then I just do it for every single student. Another place that I use this all the time is whenever we're doing what's called a validation set. So in machine learning, oftentimes what we'll do is something like an 80-20 split. We will train our model on 80% of the data. And then we will test it on 20% of the data that was pulled out that the model has never seen, and we will test how well does it do in its task. So if I'm doing something like a classification algorithm, this would be what I'm testing it on. I trained it on 80%, and I tested it on the other 20% that was left over. And I can do this using sampling. R has the ability to sample with or without replacement. That is, choose at random from a collection of things, such as numbers 1 through 6, when a die is rolling. This could be an example of this. The sampling can be done with replacement, again, like the dice rolling, or without replacement, something like a lottery. If I'm looking at trying to create some numbers to simulate a lottery draw, once a number is drawn for a lottery, that number is no longer available. So by default, samples without replacement, which is that each object has an equal chance of being picked, and we talked about this, in Intro to Stats with sampling methods. Technically, if you have resample set to false, this means that it actually technically isn't equally likely for every selection, because again, if I have 100 and I select one, now the next pick has a 1 in 99 chance of being selected. Third one has a 1 in 98 chance of being selected. So it's technically not actually equal, but it's pretty close to it. If you do with replacement, this means that everything is equally likely to be selected, but you can end up with overlap. So if I'm picking from 1 million people that, again, let's say I did a survey and I want to select 1,000 of them, I might end up getting some repeats, which means I wouldn't actually have a sample of 1,000. And these are kind of things you have to think about when you're deciding whether you're doing with replacement or without replacement. So you need to specify replace equals true if you want the sample to be with replacement. And then furthermore, we can specify separate probabilities for each outcome if that's something we desire. For example, if I wanted to simulate that instead of just having a 6-sided die, I have a loaded 6-sided die where the probability of getting a 6, let's say, is 40% instead of 1/6, and the outcome of getting a 5, and I can change the probabilities based on, let's say you have a weight at the bottom of the die. What is the likelihood of something happening? You can do that by adding in that prob argument. So let's look at a couple examples. We're going to look at some with and without replacement. So the first example, what we're going to do is we're just going to roll a 6-sided die. So you see we have sample parentheses 1:6. So that's just going to give us the values 1 through 6, right? This is going to give us the sequence 1 through 6. We're going to sample 10 of them, and we're going to do replace equals true. That means we are going to sample from 1 to 6. It's going to pick a value. We're going to sample from 1 to 6 again. It's going to pick a value, and it's going to do that 10 times. If I did this replace equals false or left it as the default, it would not work because it would go through, would sample all 6, and then would run out of things to sample. So if I run this, you will see that we get 5, 2, 1, 3, 4, 3, 5, 4, 1, 1. Now, what would happen if I got rid of this replace equals true? Notice what's going to happen is it's going to give me an error because I didn't have enough data in order to sample this without replacement. I'm going to run out. If I have a smaller sample, let's say I'm only going to sample 3 of the numbers. If I were to run this, I get 2, 6, and 3. Because once 2 was selected for the first part of my sample, it is no longer available. So then it's selecting from 1, 3, 4, 5, 6. Then it selects 6. So now it's gotten rid of 2 and 6, which means I have 1, 3, 4, and 5. And the third one, it gets a 3. That means the only values left that I didn't sample are 1, 4, 5. My next example, we're going to toss a coin. So in this case, we have sample. We're going to concatenate the character strings, H for heads, T for tails. We're going to sample 10 of those. And again, we're going to do it with replacement because if I flip a coin and I get heads, well, now I only have one option left with tails if I don't have replacement. So I'm going to do with replacement, and I'm going to sample 10 coin flips. And you can see here that we get heads, tails, 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 heads, tails, tails. And each time that I do this sample, it is creating a new sample. For example, if I do it again, now I have heads, 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 heads. I got all heads. Wow, that's pretty random. Okay, so that was, remember we talked previously, this is actually a perfect example of how randomness works, right? Just because both of these are equally likely to be selected, because I didn't put a probability on there, sometimes you're going to get that really rare case where you get all heads. So in this case, it's like I just flipped 10 heads in a row. Let's do it one more time just to see what this next one is. Okay, so this one, a little bit more we'd expect. Tails, 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 heads, heads, tails, heads, 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 heads. So seem to be getting a lot of heads today. Need to do some wagering on some coin flips apparently today. Okay, so the next one, we are going to be doing an example of a lottery. So in this case, the lottery has the numbers 1 through 54. We're going to pick 6 of those numbers. But when we do a lottery, once a number is selected, it is no longer available to be selected. So we are not going to change replace equals false, which is the default. If you wanted to be sure, you could always just put a comma, replace equals false, and you'll be good to go. But it is the default, so we don't have to add that. So we run that. This means the lottery, we got the numbers 4, 20, 1, 17, 22, and 9. Let's say we do another lottery. This one, we got 18, 36, 14, 7, 34, and 30. So as I said, this is a good way sometimes if you want to do simulation. If I wanted to simulate rolling a die 10,000 times, I could do exactly that, right? I can go back up to my sample. I could tell it to roll 10,000 dice, and now I have 10,000 dice rolls. And if I wanted to, let's say I wanted to create a histogram of that. I can just do hist and then put this within it. Run that, and you can see what my outcomes were. So it was kind of equal. I'm going to make it a little bit smaller. I'm going to say I'm going to flip 100. I'm going to roll 100 dice. Let's see what happens. There you go. Here are the outcomes that I got for my histogram of my outcomes of 100 dice rolls. And you can see it's not all even now, right? Law of large numbers. We've talked about this. This is the empirical probabilities. So next I'm going to do is, much like before, we looked at creating cards, right? I had you guys do an example like this, and I showed you 2 different ways to do it. Well, here's another way we can do it. So in this case, what we're going to do is cards, the object, is going to be assigned as, we're going to paste. So we're going to concatenate ace, so character string, so quotes ace, the numbers 2 through 10, jack, queen, and king. And then what we're going to do is we're going to concatenate, so we're going to repeat hearts 13 times. We're going to repeat diamonds 13 times. We're going to repeat clubs 13 times. We're going to repeat spades 13 times. And then we are going to separate them with nothing. So there's going to be no space, anything like that. So let's do that. And let's look at our cards. So you can see here that we have an ace of hearts, a 2 of hearts, a 3 of hearts, 4 of hearts. We have all the heart cards. Then we have ace of diamonds, 2 of diamonds, 3 of diamonds. We've got the diamonds. Then we've got our clubs. Then we have our spades. So what I'm going to do now is I'm going to get a hand of cards, which is 5 cards. Suppose we're playing poker, we're playing 5-card draw, and what is my hand? I have a 7 of spades, a 3 of diamonds, a 10 of spades, a jack of diamonds, and a king of diamonds. So I've got 3 diamonds, so in that case, maybe I'll go for a flush with, replace the 2 spades. I also have a 10 jack king. I could possibly go for the straight, I don't have any pairs or anything like that. Let's draw another hand of cards. So in this case, we have a king of hearts, 2 of clubs, 2 of diamonds, ace of clubs, and 9 of clubs. So we've got 2s. Right now we got a pair of 2s. Let's do another sample. Queen of spades, 10 of spades, 8 of clubs, 2 of clubs, ace of clubs. So you can see how we can use this sample on our made up system to simulate different outcomes, right? We simulated rolling dice, we've simulated flipping coins, we simulated lottery, and we've also simulated drawing a deck of hand of cards for something like playing poker or something like that. If you were instead, you wanted to play Texas Hold'em, let's say you only wanted to look at your 2 cards, you just change it to 2, and now we get 10 of diamonds and 2 of hearts. We get another hand, we get 7 of hearts, queen of clubs. Do another one, we get 6 of diamonds, ace of hearts. Notice when we did the cards, we did not put replace equals true. And this is because if I have a deck of cards, what happens when you give somebody a card when you're playing cards? Well, now that card is no longer in the deck. So we specifically want it to be replace equals false for a problem like this. Oftentimes when we're doing stuff like this, we're going to want to create a function to allow us to kind of do this simulated, whatever it is we're doing, more than one time. So we'll talk more specifically about functions in a later lesson, but for now, just know that this is what we're doing. What we're gonna do is we're gonna have a sample of the values 1 to 6, and we're gonna take 10 of those with replacement. So that means we're basically just gonna be rolling a die 10 times. Instead of doing this though, every single time I want the dice rolls, what I can do is I can create a function. In this case, it's gonna be called roll die, which I've got the R and the D canceled. And this is gonna be a function of n, where n is gonna be the number of dice that I wanna roll. And then what it's going to do is within the function, it's going to sample the values 1 to 6 n times, replace equals true. So let's do exactly that. So just an example, this is what my dice rolls would look like. I'm sampling, 10 dice. Now we're going to set up our die roll function. Notice that it didn't give me any output. And this is because that n has to be specified. So the way we call on this function, now we've created a function like you've been using in R, is I'm going to use roll die, and then whatever number I put in here, that will be how many dice that I'm going to roll. And each of those rolls, what it's going to do is it's going to do this. It's going to sample 1 to 6 n times, whatever that n is that I put. So in this case, n is 5. So we do roll die 5 times. It's going to give me 66255. If instead I wanted to roll 20 dice, I could just change it to 20, run it again, and I get 624, 62344, so on and so forth. If I wanted to roll 100 dice, and this is where using functions and things like this can be really useful, because if there's something I'm going to be simulating a lot of, then this could be something that I call on all the time. For example, let's say that I wanted to create a program for poker hands. Then I could just do poker, something like this. And what I'm going to do is I'm going to assign this as a function of n, and then I'm going to put my curly brackets. And then within that function, what I'm going to do is I'm just going to take this. I already got cards labeled, so I don't need to add that. So what I'm going to do is I'm going to put that here, but n is going to be this number of cards that I'm going to do. So if I run this, now I can just do poker, and if I want 2 cards drawn, I got 7 hearts, 10 of hearts. If I want to do 5 hearts, let's say I'm doing, again, 5 card draw, now I've got 5 cards. Let's say I'm playing a weird variant game where you get 2 hands and you want 10 cards, something like that. That's fine. I can put 10 in here. I just drew 10 cards. And this actually can be really useful for when you're teaching statistics, because if I ever need to make up a problem, this is oftentimes exactly what I will do. I will do something like, let's say that I need 10 numbers randomly for a problem on standard deviation. What I can do is I'll do something like this. Sample. And now I need my data. So what I'm going to do here is I'm going to round our unif, and I'm going to pick 10 numbers. Let's say I want those numbers to be between 40 and 60. So 40 and 60. And I'll do 0 for my rounding, and I'm going to do replace equals true. And this allows me to randomly create 10 numbers that I can ask my students to find the standard deviation for. So all I did is I just used all the concepts we've talked about so far. I created a uniform distribution where I am picking 10 numbers between 40 and 60, something like this. And then I used the round function so that with a round of 0, so that it only gives me the integers. And then from there, I just did a sample of those values where I did replace equals true, which if, let's say I wanted to do it even more often, I might say, I don't know, let's pick, 100 of them. Oops. And now I've got 100 values that I just did doing exactly that. And this is kind of what I've talked about previously, of that all these things that I'm teaching you, I'm giving you like little building blocks. And the idea is that you can put these together to do whatever it is you're trying to do, right? If I'm trying to draw a bunch of cards, let's say that I am looking at blackjack, where I know that I'm going to be getting 2 cards. But I also know that there are going to be, let's say you're at a casino where they use 6 decks of cards in each shoe is what it's called. In that case, I can do that. I can make my cards, which I did, and maybe your cards is all of that repeated 6 times. That way you have 6 of every card. And now from that, what I'm going to do is I'm going to sample 2. And I can do without replacement. So those cards are now out of those 6 deck of cards. And I can take whatever is not those 2 cards I took out, and that'll be whatever's left in the deck. And then from there, I can do it again and again. And this will be something where we look at later on with functions where you could do something just like that, putting all these little building blocks together to create something more complex. So next what we're going to do is we're going to look at how we can use sample to do our different sampling techniques that we've talked about, or at least to simulate them. So a simple random sample is just where every observation that is possible in our population is equally likely to be selected. That means that if I have 1 million people to choose from, everybody has a 1 in a million probability of being selected. As I mentioned previously, technically it's not exactly 1 in a million, because if I do without replacement, then each subsequent person I select has, 1 out of 999,999, and then so on and so forth from there. Or if I do with replacement, then there's the possibility that I'm going to get overlap, so I might have to oversample. And these are just things you have to think about. But for a simple random sample, this is exactly what we've kind of been looking at, where we're just going to have some values, we're going to sample from them, where everything is equally likely. So to do this, we have my data, which is going to be the sequence 1 to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I have semicolon my data, so it'll print it out. So you have 1 through 10. And then I'm going to create my sample. And this is, by the way, one of the ways that I would do something like this if I was creating a validation set, is you create your validation set, you pull the data out, and then whatever's left, that's what you use for your training. So my sample is I'm going to sample my data 5 times. And then I'm just going to print this out, and you'll see that we get the numbers 8, 9, 2, 4, and 10. In our next example, we're going to be doing a stratified sampling. So if you remember from Intro to Stats, stratified sampling, what we're first going to do is you're going to break the different the parts of the population into different groups called stratum. And this is usually some sort of group that it might be, for example, the example I give a lot of times in class is freshmen, sophomore, juniors, and seniors. And you might wonder, why do we break these into groups? Well, because within each of these groups, you are then going to do a simple random sample, and you're going to combine all these together to make your actual sample. So the reason we might want to do stratified, so while simple random sample adds the least amount of bias of any sampling method we have, it's not always going to be necessarily representative. Remember when I flipped those 10 coins in the example earlier and I got 10 heads? The same can happen if I'm sampling students at a university. I could sample 100 random students, and I might randomly get 100 freshmen or like 95 freshmen. So instead, what I can do is to make sure that I'm getting a representative sample that at least has some number of students in each group. I can break it up into groups first, my stratum. So let's actually look at this example. So first thing we're going to do is we have my data, and we're going to create a data frame, which is X values, which we're just going to pick 100 values from a standard normal. Then my Y data, I'm going to use sample, concatenate 0 and 1 100 times, and I'm going to do replace equals true. So each of these, whatever this random normal values represent, it's going to have an outcome of 0 or 1. So let's actually look at our data. So you'll see that for our X values, we have values, numbers from a standard normal. And for my Y, each of them have a 0 or 1. This could be classification. It could be something like will pass the class, something like that. It could be, does habit X, yes or no. So now what we're going to do is we're going to break our values into stratum. So stratum 0, we're going to assign as my data, which is what I just showed you. Square brackets, we're going to subset this, and we're going to use my data money sign Y. So for the Y values in my data is equal to 0. So we're going to do double equals to 0. And then comma, because we're not selecting a column. We're just taking any of the rows where Y is equal to 0. And if we do that, now if we look at stratum 0, you will see all of the outcomes that we had that had a Y value of 0. So the first one had Y value of 0. The fourth observation had a Y of 0. The 6th, 7th, 9th, 10th, 11th, 14th, these all had a Y observation of 0. Similarly, I'm going to create stratum 1, which will be the same thing, except for it will be where Y is equal to 1. So again, if I look at stratum 1, you will see that it is all of the objects that have Y equals 1. So that'd be 2, 3, 5, 8, 12, 13, so on and so forth. So now what I've done is I've taken all of my data and I've split it into these 2 stratum. Those who have a 0 for Y and those who have a 1 for Y. Now for those with a 0 in Y, I'm going to do sample 0, which I'm going to sample the stratum 0 for X, and I'm going to pick 5 of them. All right, so if I look at my sample, let's see what we got. We got 1.5639156. You can see the 5 numbers here. We're going to do the same thing for when my Y values were equal to 1. And then I'm going to create my entire sample. So I got the sample from stratum 1. I've got the sample from stratum 2. Now I'm going to put it together for my entire sample, which is going to be these 10 values. 10 of them where I had a y value, or 5 of them where I had a y value of 0, and 5 of them where I had a y value of 1. And this is how I could create a stratified sample. And this would be something I could actually do in real life. If I have some observations, let's say that I'm doing data from the CDC, and I have 10,000 possible observations. I could group them by something, do they smoke? Yes or no? Bam, there's 2 groups that I could possibly do. Or I could do something like, has diabetes? Yes or no? Right? And it doesn't even have to be 2 groups. I could break it into 4 or 5 stratum, whatever it is based on whatever the grouping is. It could be something like ethnicity. And I could have ethnicity 1, 2, 3, 4. And I split each of the data into those 4, and I make sure to grab some amount from each of them. Now, one thing you might want to consider when you're doing stratified sampling, though, is in this case, I pulled 5 sample from stratum 0 and 5 sample from stratum 1. What you might want to do is sometimes people will do a proportional sample within each, which would be something like, this makes up 20% of the data, I'm going to pull 20% from this. This makes up 10%, so it makes sure you have at least some representation from each, but also to keep it kind of proportional. Generally, though, all you do is once you create your stratum, you are going to just do a simple random sample within each, meaning each within a stratum is equally likely to be selected. And this is, again, to limit bias, because anytime you are adding a step or making a decision in your sampling, you are adding bias to it. For my next example, we're going to do a weighted sample. So sometimes you want to give certain observations in our data set a higher probability of being selected than others. You can do this by setting a vector of probabilities for that prob argument. So what we're going to do is we're going to do that. We're using our mtcars data. So going to our code here, you see that first thing first, we're going to load our mtcars data. Okay. Now what I'm going to do is I'm going to create an object called weights, which is going to be mtcars miles per gallon divided by the sum of all the miles per gallon. So when I do this, what it's going to do is it is going to give me the relative frequency or relative weight of each of these miles per gallon. So it's taking the miles per gallon of a car, let's say it's 28 miles per gallon, and it's dividing it by all of the miles per gallon of all the cars. And that way I will get a sort of percentage of the total as a decimal. So the first car, for example, has a total relative amount of 0.03266. Second one has 0.03266 also. Third one has 0.03546, so on and so forth. Next, what I'm going to do is I'm going to take the object sample row indices. I'm going to sample 1 through the number of rows of mtcars. What this is saying is however many rows on mtcars there are, I want to sample that. So from 1 all the way to the last row, right? If I just do number of rows of mtcars, all it's going to do is it's going to give me a number of how many objects are in it, which is 32 rows. There's 32 rows in mtcars. Size equals 3, so I'm going to pick 3 of the cars. Replace equals false, because once a car has been selected, I won't select it again. And then prob equals weights, which is what we just assigned a minute ago. So now if I do this, let's look at our sample. So I'm going to set my sample as mtcars. For the rows, I'm going to pick those sampled row indices, right? Because this is just going to give me the indices. So I'm picking car 23, car 8, and car 4. Now I'm going to do is I'm going to take my mtcars data, subset it with just those rows that I created the indices for, not touching the columns, and I'm going to set that to my sample. And then the last thing I'm going to do is I'm going to print out that sample, and these are the 3 cars that were selected based on the weighting that we did of miles per gallon in mtcars. And of course, we don't have to touch the weighting again, but if we did the sample row indices, if we did this again, you'll notice that we got different cars this time. This time it was 12, 18, 21. So if we did, now we have the Merc 450 SE, the Fiat 128, and the Toyota Corona. Versus before that, we had the AMC Javelin, the Merc 240D, and the Hornet 4 drive. This is actually going to lead on to the last thing I wanted to talk about in this lesson, which is setting a seed. I mentioned earlier that I don't like to set a seed because I like randomness to be part of this. Whenever we're doing this, every time I do it, it will be different. But sometimes you are going to want to set a seed in order to make it so you have replicable results. And the way you would do this is you use the set.seed function. You do set.seed, parentheses, and then you just put something. So instead of doing that, because I don't want to set the seed right now, if I do question mark and I run this, you will see that this will create a random seed, which you could use random.seed. And then from that, you can just put all sorts of things like what kind of seed, all that kind of stuff. But the most common thing people do is they just put like a number, 1, 2, 3, right? They say set.seed 1, 2, 3. And then if you put set.seed for the same thing, you would get the exact same values that I get when I do something that is a random process. Because what you're doing is you're setting that starting seed, so both of them will follow the exact same steps. Even though it's random, you will get to the same place through its randomness. And this is where I kind of talk about the fact that it's pseudo-random, it's not actually random. Anyone who's played video games has probably dealt with this. If they're ever in a game where you make a map, for example, let's say you play something like Terraria. If I have a seed and it's labeled my world and you start a game and you put it as my world, guess what? You'll have the same starting seed. We will both end up with the same world, even though our computers generated them individually and separately from each other. So hopefully from this lesson, you can kind of see why the sample function is so powerful. And there's some functions and things that I teach in this course that I use occasionally, but I will tell you right now for a fact that this is one that I use a lot. I use it a lot in my research. I use it a lot in my classes. I do use the sample function more than a lot of other things in R, right? The sample function in R, it's a versatile tool for randomly selecting subsets of data from larger data sets. It can be used for simple random sample, stratified sampling, weighted sampling, and other applications like that. And later on when we're talking about validation methods, guess what? We're going to touch on this again. So by understanding how to use sample effectively, you can ensure that your analyses are based on representative samples of your data. Hello everyone. In this lesson, we're going to continue on talking about sampling, specifically focusing on bootstrapping. So bootstrapping is a method of sampling from a data set to make statistical inference. So the intuitive idea is that by sampling, one can get an idea about the variability in the data. So this process involves repeatedly selecting samples and then forming a statistic from those samples. So what we're going to do is we're going to look at an example where we're going to look at the eruptions data from the Old Faithful data set. And in this case, we have the variable eruptions, which is going to measure the time between eruptions for Old Faithful at Yellowstone National Park, and see that it has an unusual distribution. And one note is that bootstrapping sample is just a sample with replacement for those given values. Now, I know it sounds like it's kind of a simple idea, and it is, but it can actually be very powerful, because what allows us to do is we take a sample of our actual data, and then we take samples from this and create other subsamples, usually of the same size, and we can extrapolate by creating a sample of samples. In fact, I actually have an entire book right here on doing bootstrapping by Tib Shirani, where it covers a lot of topics about this. Now we're just going to briefly touch on it, but it's used in a lot of methods that we will encounter in things like machine learning and statistical learning. Things like when we're doing random forest or boosting and things like that, we'll be using bootstrap samples. So let's start by looking at our example. We have our data, which is the faithful data set. So I'm going to load that data up. So we have data, faithful, and let's look at the names of that data. You're going to see that there are two columns or categories, which are eruptions and weighting. So eruptions are the amount of time that the Old Faithful geyser will erupt for, and weighting is how long of a wait there is between those eruptions. So if we were to take faithful and just take the first 20 rows, this is what we would see. You see that we have eruptions, we got 3.6, 1.8, 3.333, and then the waiting time for each of those respectively, 79, 54, 74, things like that. So now what we're going to do is we're just going to name the object eruptions as faithful and then money sign eruption. So all this is going to do is it's going to take those eruptions from faithful and put it as its own object called eruptions, so we don't have to put faithful every time we want to reference it. So let's do that. What I'm going to do now is I'm going to use sample of eruptions. I'm going to pick 10 of them randomly with replace equals true. This means that of these, I believe it's 172. Let me double check this real quick. Dimensions of faithful. Okay, you can see that there are 272 different eruptions that we can look at. So what I'm going to do is I'm going to sample 10 of those with replacement. You can see that we get the different amount of eruption lengths. We have 10 of them here. And of course, if we were to do this sample again, we would have a different sample. Now what I'm going to do is I'm going to create a histogram of eruptions with breaks of 25, and this will be for our data set. You can see this is what the Old Faithful data looks like, not doing any sort of bootstrapping. This is just plotting the Old Faithful data set, and you can see that it's sort of a bimodal data set. It's got two modes. You got this up here, right? You got the left side where there's the small eruption times, and then you've got sort of this distribution of the upper eruption times. So now what we're going to do is we're going to do a bootstrap sample. So we're going to do histogram. We're going to sample 100 of those eruptions. We're going to replace equals true, and then we're just going to do this again. And you can kind of see that this will allow us to take samples of this data, and then we can kind of use these sample of samples. So you could do this many times. You could create a bunch of different samples, all with slightly different behavior, to try to get a better feel for the actual data. And that's kind of the idea behind bootstrapping. A lot of times what you'll do when you do bootstrapping is you'll do it the size of the sample. Meaning if I have 100 data points, I might make a sample of 100 data points from the original 100 data points with replacement equals true, meaning I'm going to have overlapping data points. Then I'll create another sample and another sample and another sample, and I can do this, and then this sample of samples will allow me to then analyze the data to get a better feel for not only sort of just the shape of the data, but also, you know, the skew, how much the data varies, all sorts of information about it. It can actually be really helpful. In fact, like I mentioned previously, if I were to go to Google and put something like random forest, then you can see here it's versatile supervised machine learning algorithm that builds multiple decision trees during training and merges them together to make a highly accurate and stable prediction. And the way that it does this is it starts by first bootstrapping. So actually, let's jump onto Wikipedia real fast and let's see what it says here. So you can see that if you look at here at the random forest or random decision trees, this is the part I actually wanted to focus on, is that random forest is an extension of bagging. And this is actually the underlying step that you begin when you're doing random forest. So bagging, also known as bootstrap aggregating or bootstrapping, is machine learning ensemble meta algorithm designed to improve the stability and accuracy of machine learning classification and regression algorithms. It also reduces variance and overfitting. Although it's usually applied to decision tree models, methods, it can be used for any type of method. Bagging is a special case of the ensemble averaging approach. So you can see that like this is one of the most commonly used machine learning methods, and it relies on bagging, which is really just bootstrapping. I know we already previously talked about our R, D, P, and Q functions within R, but I wanted to touch back on them again while we're talking about simulation. So let's focus first on the D functions. So the D functions are used to plot the theoretical densities. So as with our R functions, where we create those random numbers from our different distributions, you need to specify the parameters. But what's different is you also need to specify your X values. This is usually, of course, something that we simulate using our R functions in R. The P and Q functions are cumulative distribution functions and quantiles. So as mentioned, the distribution of random numbers is specified by the probability that the number is between A and B for an arbitrary A, starting point, lower boundary, and B, your ending point or upper boundary. So to kind of put that in other words, we have this probability where A is less than X is less than or equal to B. So we have some interval where X, our random variable, is between two values, A and B, and we want to know what is the probability that that is true. Well, then we have our f of X is just equal to the probability X is less than or equal to B is enough to actually do this. So the P function answers what is probability that a random variable is less than that X that we're looking at. This would be something like, for example, if we were looking at standard normals. So suppose we are looking at a normal distribution. What's the probability that it's less than 0.7? So we can do that by using our P function, or pnorm 0.7. So we go to pnorm 0.7, and you will see that we get a probability of 0.7580363. And this would be analogous to if you were to use a z-table, which I actually just got up and picked one up. And I have a z-table right here. So if I were to go to 0.70, you would see I get the value 0.7580, which is exactly what we got when we did it in R. All this is doing is your p function is giving you what you would find on the table, so the probability to the left of this. Now we could also put lower.tail equals false, and this would then tell us the probability to the right, so 1 minus that. Suppose that instead of looking at a standard normal, you wanted to find the probability to the left of 0.7 on a different distribution. Suppose that we have a normal distribution with a mean of 1 and a standard deviation of 1. Well, we can do that in R by using pnorm 0.7, 1, 1. And now we get a value of 0.382086. Why is this important? Well, because when we teach this in Intro to Stats and things like that, we have to convert everything to a standard normal so that we can have it in terms of this table. But with R, you don't need to do that. You can directly look up these probabilities, and you can do it for more than just a normal distribution, right? You could do P binom, you could do P chi-square, you could do P Poisson, whatever distribution, you can find these probabilities. What about if I wanted to know what is the probability to the right of 0.7? Well, like I said, you could do lower.tail equals false, and this would give us the probability to the right, where if we were to add these two up together, right, we have 0.7580363 plus 0.2419637, they should sum up to 1, because you're looking at the probability to the left of something and the probability to the right of it. It will be all of the probability, or 1. I could instead take the probability to the left, which again, just to remind you, is this, subtract it from 1, and you will see that we get the same thing, because all we did in this case is we said, what is the probability to the left? Now subtract that from everything, which would be 1, and you'll be left with whatever is to the right. If we wanted to know what the quantile was at something like 0.75, we could just do qnorm 0.75, and this would give us the quantile of that particular value. Now, one thing I want you to caution you about and be careful about, because in my original slides later on when we talk about QQ plots, I actually had qnorm and it wasn't working. And when I was looking through, I couldn't figure out why. And it's because I was inadvertently putting this command here, qnorm, when it should have been qnorm. So we'll talk about that later, but just I wanted to kind of bring this up mostly so you're aware of it, to keep track of that. Whenever you have this data, you can standardize your random variable. And to do this, usually you're going to subtract the mean from your data point, and then you're going to divide by the standard deviation. Or depending on what distribution you're doing, it might be the standard error. For example, if I'm doing the standardization for x bar, it'd be x bar minus mu over sigma divided by square root of n. So to do this requires knowledge of the mean and also the standard deviation. You can also standardize a sample. So there's a convenient function in R called scale that will do this for you. It will make it your samples, you have a mean of 0 and a standard deviation of 1, and this can be useful when comparing random variables on different scales. Now, the reason we're kind of touching back on this, even though we've talked about it multiple times, is because this is where a lot of the power comes in learning how to program in R, because all the things you've learned in your stats classes, all the things you've done by hand, R can do them for you. If you have two values that you want to compare directly, but they are from different distributions, they're not from the same scale, you can use scale to bring them to the same scale. It will standardize them for you. If you are trying to do anything with probabilities of a distribution and you don't want to have to convert it to a standard normal to pull out a z-table, guess what? R can do that as well. Let's go back to a prior example we did on IQ scores. And if you remember, IQ scores have a mean of 100 and a standard deviation of 16. So suppose that we select 5 of these IQ scores. So we select 5. First one's 103, 113, 138, 107, and 75. If we wanted to scale these using the methods that we normally do, we would take some object z, and we would set this as x, those 5 data points, minus 100, the mean, divided by 16, the standard deviation. And if we do this, we would get these z values. These are now the z scores of these 5 IQ scores. I could do pnorm on my z, which will then give me the probability to the left of each of these IQ scores. That means that the first IQ score has an IQ score where 59% of people have a lower IQ. Second one, 79% or lower. Third one, 99% or lower. Fourth one, 67% or lower. And fifth one, 6% are lower. Okay. But instead of doing that, I could use the original X data, just include the mean and the standard deviation. So I could do pnorm X, that's the original IQ scores, comma 100, comma 16, and you'll see that we get the exact same thing. So this is important again because when you're doing stuff like this, you can always go back to your base principles in R and you could build it exactly the way you've learned it. But oftentimes R can jump straight to whatever it is you're trying to do. So we don't have to first convert it to Z in order to find the probability left. We can directly look it up as long as we know what the mean is and the standard deviation. So one of the biggest strengths of R is its ability to help us with simulation. The ability to simulate different types of random data allows the user to perform experiments and answer questions in a rapid manner. It's a very useful skill, but it can oftentimes be hard to learn, and even harder sometimes to know when it's appropriate to do what type of simulation based on what you're trying to do. So as we've seen, R has many functions for generating random numbers. For those random numbers, we can view the distribution using things like histograms and other tools. What we want to do now is we want to generate new types of random numbers and investigate what distribution they have. So to start, we'll recap our central limit theorem very quickly, which is that if we have some data, xi, so remember the index I just means which one it is, right? So if I have 100 data points, I equals 1 to 100. I equals 1 is the first data point, I equals 2 is the second data point, I equals 3 is the third data point, up to I equals 100 or n, the last data point. So if these x sub I are drawn independently from a population where mu and sigma are known, then the standard of the mean would be x bar minus mu divided by sigma divided by square root of n, which should look similar to what we had when we were using the central limit theorem for a single data point x. In fact, if you go to my videos from Introduction to Stats, I actually talk about how that formulation that we looked at previously is actually a special case of this one when n equals 1. Because when n equals 1, x bar equals x. So we have x minus mu over sigma divided by the square root of 1. Square root of 1 is just 1. It ends up being the same thing. So it is asymptotically normal with a mean of 0 and a variance of 1, which is standard normal. That is to say that if we have our distribution of sample means, so x bar, even if it is not coming from a known normal population, if your n is sufficiently large, it will follow approximately a normal distribution with a mean of mu and a standard deviation of sigma. For example, let xi be normal with a mu of 5 and a sigma of 5. Then we would need this function, which is x1 plus x2 plus x3 plus x4 plus x5. Those are my indexes, I1 through 5, divided by n minus mu divided by sigma divided by square root of n. This first part, the x1 through x5 added together, so sum of x1 through x5, divided by n could be rewritten as x bar. So we can actually find this using x bar minus mu over sigma divided by square root of n. If we were then to translate that into what we could put into R, it would look something like this. We have mean of x minus mu, whatever it is that we've assigned, in this case 5, divided by sigma, which we also assigned as 5, divided by sqrt for the square root of, and then within that we could do length of x, how many values we got. And this would allow us to have a general form that we could take any amount of data. If we know the mean mu and we know the standard deviation sigma, I could give you 10 data points, I give you 1,000 data points, and this would work. Now, of course, we don't have to do this manually because R can do it itself, but let's say that we wanted to. So let's look at an example of doing exactly that. So the first line of this, we have the object results, and you can see that we are going to assign it, we're going to concatenate with nothing in it. So if we look at results, what we're going to see is nothing. There's nothing inside of it. We've assigned an empty object. Now you might wonder, why did we do this? Well, we did this because if I wanted to run this again, right, I'm going to assign my mu, I'm going to assign my sigma, and then I'm going to do what's called a for loop, and I'm going to get results. If I wanted to do this again, those results are already assigned. So what I can now do is go back to the beginning of this where I assigned it as an empty vector, and it will wipe anything that's in it. So this is the reason we started with results equals an empty vector, just to kind of give us a blank slate if we wanted to rerun this. So let's do exactly that. We got mu equals 0. We have sigma equals 1. So this is from a standard normal. So for this for loop, which we will talk more about for loops later, what this is saying, you can think of it sort of like a summation or any sort of formula that we do in mathematics. For I in 1 to 2,000. So think of a summation, I equals 1 to 2,000. That's exactly what this is doing when we have a for loop. So from 1 to 2,000, what it's going to do is it's going to take x and it's going to use our norm and pick 100 data points from our distribution, our normal distribution, with mu, which we set to 0, and sigma, which we set to 1, and it's going to generate this random data. Then it's going to take results I, so result 1, result 2, result 3, up to 2000. With each of those results, it's going to take the mean of x minus mu divided by sigma divided by square root of 100. So let's run that and see what we get. Okay, so now what this has done is it's actually gone through a loop. It did it for I equals 1. It did it for I equals 2. It did it for I equals 3 and 4 and 5. And it does this for all 2000. Meaning that if I were to go right here and type results 1, I will get the result of the first when I equals 1. If I go and put result 2, this is the result from when I equals 2. If I do result 3, this is the result. So there's 2,000 different results in this, right? So if I just put results, you'll see that it's going to give me 2,000 different results. So now let's graph that as a histogram, and let's see what this data looks like. And you'll see that it looks like a normal distribution centered around 0 with about a standard deviation of 1. What if we were to change it? Okay, well, first thing I'm going to do, I'm going to change my mu. Let's say we make a mean of 22. And we'll do a standard deviation of 3. So just like before, if I pull up my results, I could do results 1, run that, I get the first result, results 2, get that result. I'm going to create my histogram and see what happens. So looking at this, what's happening is each time we do this, it's going to run through, we start by, clearing our results. We set our mu to 22, we set our sigma to 3, we run through this loop for all 2000, and then we create our histogram. And what it's doing is it's standardizing it, right? Because if we look at this mean x, so x bar minus mu divided by sigma, or standard deviation, divided by the square root of 100, which is going to be how many data points we're pulling, then for each of these x's, then what it's doing is it's just giving us our standard z-score for each of these. What about if we wanted to do the same thing using a normal approximation for a binomial distribution? It's going to be s sub n minus n times p divided by the square root of n p q. So as a reminder, in this case, Sn is going to be our random binomial value. So we're going to take our one number from our binomial based on n and based on p. N times p is going to be the expected number or the expected value or mean of our binomial distribution. So it's just the number of trials you have times probability of success. At the bottom, we have square root of n times p times q. This is going to give us our standard deviation of the normal, of the binomial distribution. For this example, we have 10, which means we're going to have 10 trials. We have a p of 0.25, means we have a probability of success of 0.25. S is going to be our binom. We're going to pick one number from our 10 trials with a probability of success of 0.25. So if we were to look at S, you would see that we got a 3. Now if we were to standardize this for normal approximation, so right, we take S minus n times p divided by the square root of n times p times 1 minus p, which is q, you'll see that we get a value of 0.3651484. With this, we could then find our probability, right, using our p-norm, and then we just got to plug this in, so 0.3651484. And you will see that we get a probability of 0.6424997. Okay, now repeating this, we're just going to do the same thing, but now we're going to do a histogram for it. So I'm going to get my x value here. Let's create our histogram, and this is what our histogram will look like as we standardize each of these binomial values. So in this case, what I did is I actually made 100 values. So you'll see that we have 100 different standardized values. If we go to the originals, here's my original 100 binomial trials. So in each one of them, first one I got 1 success, then 2 successes, then 4 successes, then 3 successes. Each time of these, I'm doing 10 trials with a probability of success of 0.25. I'm doing this 100 times, so I'm getting 100 of these. I then standardized each of these, plotted them on my histogram, and it looks like this. Let's do it all over again. And you'll see that we have a different histogram, because every single time what it's doing when I get to this S stage, the stuff up top is set. But when I do this S stage, it is randomly selecting 100 new values. Standardize those, give me my histogram. We can also create variables in which our results will store our answers. So then for each I between, in this case, 1 to 100, it can create a random number, and that's to say a new one each time, and it will store it as a vector of our results in the ith entry. Then we can review the results using histogram, right? So hist for our results. So let's do exactly that. Just like before, I'm going to create an empty vector, in this case, results, which is just going to be a numeric vector with nothing in it. So if I look at results, you'll see that just says numeric 0. Awesome. Next, I'm going to set n equals 10 and probability of success of 0.5. So now we have what's called a for loop. So for I in 1 to 100, what it's going to do is it is going to first run S, which is our binom 1 with n equals 10 and p equals 0.5. And then result I, because remember we're on I equals 1 right now, it is going to standardize it and it's going to assign it to results I, which is 1. Then it's going to move on to 2. It's going to, again, randomly pick a number from our binom with an n of 10 and a p of 0.5. Then for results 2, because we're on I equals 2 now, it's going to standardize it. Then it's going to do it for 3. Then it's going to do it for 4. It's going to go through this loop from I equals 1 to 100. So let's do that. If I were to go here, just like before, if I do results square bracket 1, I can get the results from the first binomial draw. And I got, after standardize, so I got negative 1.2649. If I do result 2, this will be the standardized result for the second binomial random draw. If I do result 3, and it will do this for each of them. And of course, if I were to just run results, it will give me all 100 of those standardized values from my binomial draw. Now you might wonder, why are we talking about this right now? Well, remember, this whole point of this section is about simulation. We've talked about simulating data using our distributions. We've talked about simulating using sample and getting subsamples from this. We briefly talked about bootstrapping. And we also can take this data and do more complex things with it by using for loops, going through these looping sort of systems, standardizing the data, using different functions that kind of standardize as part of it. You might, again, you might wonder what all this means. It's because I want you guys to have an understanding that when you're using these R functions, right? For example, we used p-norm, and I showed you that you could use the standard values, put it in there, or you could put X in there, plug in your mean and plug in your standard deviation, and you'll get the same answer. And the reason is because that's what it's doing under the hood. By understanding the steps we're taking, the methods and all this kind of stuff, you can create these functions all your own. In fact, when we get two functions, that's exactly what we'll be doing. We'll be creating our own sorts of functions, much like you've already been using in R. Now, suppose that you got some data and you need to determine whether it does follow a particular distribution. Specifically, you generally want to look and see if it follows a normal distribution. Well, one of the tools you can use for this is what is known as a QQ plot, or a quantile-quantile plot. And it's a graphical technique which can be used to compare your distribution from your sample to a known distribution. And then from that, you can kind of determine whether you can visually assess whether the sample data seems to come from that certain distribution, for example, a normal distribution. So in a QQ plot, the sample quantiles are plotted against the theoretical quantiles of your known distribution. These theoretical quantiles represent what the quantiles of the sample would be if the sample came from that known distribution. If the sample distribution matches the known distribution, the points on your QQ plot will be a straight line. And the closer it is to the straight line, the stronger the evidence that it does in fact follow that distribution. The more it curves away from that straight line, the more it seems to point that this may not be the distribution that it actually comes from. So if sample distribution deviates from the known distribution, the points will deviate from the line in some way. So we're going to start with the most basic example, which is we're going to randomly select 100 numbers from a normal distribution. And then we are going to use the command QQ-norm to do a QQ plot of our sample. And then we'll put a QQ line, which will put a line that we are kind of assessing it against. So let's do that. So first things first, I'm actually going to set a seed for this one. So if you do seed one, so set.seed 1, 2, 3, you will get the exact same results that I do. It won't be close, it will be the exact same thing. So we do set.seed 1, 2, 3. And then I'm going to take my normal sample of 100 numbers. So this is from a standard normal with a mean of 0 to standard deviation of 1. Here's my 100 numbers. Now I'm going to create my QQ plot using QQ norm of my sample, and you can see that this is a fairly straight line. Now remember, we did randomly select 100 values, meaning that there is going to be some randomness, right? It's not going to be a perfect line. Even though we know for a fact it came from a standard normal, because of that randomness, there is going to be a little bit off. Let's actually put the line on though using QQ line, and this is the line that we're comparing it to. So if you kind of look at this, you can see that in general, this does seem to follow very closely with a straight line, meaning that this, if you were visually looking at this data, which we know is normal because I made it from a normal distribution, but suppose that it's not. You got it from someone else. You don't know this normal. Looking at this, this is strong evidence that this in fact does come from a normal distribution. And while we're actually talking about this, there's one more thing I wanted to discuss, which is in this problem, you saw that I did set.seed so that we would all get the exact same values. If I change this, actually, let me rerun this. I'm going to take a new sample and run it again. Notice what's happening. Every time I do, I'm getting the exact same results. And this is because I have this seed set. If I were to change the seed, let's say we call it 1, 2, 3, 4. Now when I run this, I'm going to get a different set of results. But notice that every time I do it, when I have that seed set, it doesn't change. If I did some other sample, let's call it QA4. Oh. Let's call it sample or set seed 2. I will get something else. Again, so the seed is just something you can set this starting point for the randomization so that we'll all get the exact same results. If you set a seed and then you want to get rid of that seed, you can do it with this command, set.seed, so parentheses, seed equals null. And this will wipe the seed so that if I were to go up and run this without running the seed, it will give me different results each time, because I have wiped the seed. So every time I do this QQ plot, because I'm doing a different sample. But notice, because they're coming from a normal distribution, they all follow this line pretty closely. So when we're doing QQ plot, the QQ norm function creates the QQ plot, and the QQ line function adds a line to that plot representing the expected values of the sample if it were normally distributed. QQ plots are commonly used to assess the normality of a distribution, but they can be used to assess the fit of any distribution of a sample. For example, if you have a sample of data that we believe comes from a Poisson distribution, we can create a QQ plot of the sample against the Poisson distribution and assess how well that sample matches our theoretical distribution. So overall, QQ plots are a useful tool for assessing the fit of a distribution to a sample and can help us make decisions about which statistical methods to use for our data. If you are not comfortable using graphical methods, right, we're just visually analyzing, determine does this appear to be normally distributed, for example, there are other methods you can do. For example, for normal distribution, if you wanted to do a unitary test, which say you just want to check one variable and see if it's normally distributed, you could do something like a Shapiro.test. If you have multivariate data, you could do something like a Royston test or an energy test. There's a lot of different tests that you can do, and they're pretty easy. For example, if you want to do like a Shapiro test, it's Shapiro.test for a Shapiro-Wilk test, and you could just do it mathematically. So let's do a comparison now of some different distributions. So the first one, just like before, we have our norm with a mean of 0 and a standard deviation of 1. We're going to draw 100 data points, and we're going to do our QQ norm and our QQ line. And just like we did last time and what we'd expect, it looks like it follows a normal distribution. For the second one, we have our norm 100 with a mean of 10 and a standard deviation of 15. So in this case, we're going to get 100 values from a mean of 10 and standard deviation of 15. Let's see what this one looks like. Okay, so still relatively straight line. Let's add our QQ line. Okay, it does appear that it's mostly normal looking, but it looks like as we go further out to the right and the left, it does start to deviate a little bit. Now, this could just be random noise, which is why you always should be careful when you're looking at visual tests. Let's say we did it again. Okay, it seems to have the same sort of pattern, right? Each of these, it kind of seems to deviate the further we get from our mean. But overall, it's still kind of following a general straight line trend. What about if we have exponential data? So in this case, we're going to use our exponential, so REXP, and we're going to pick 100 data points with a rate of decay of 1/10. So we're going to do QQ norm, and you're going to see that this one is not straight. So we're trying to say, does this appear to be a normal distribution? Let's add our QQ line. No, right? Because what's happening is this line is what represents, if this were from a normal distribution, this is roughly where the data should be. But what's happening, because we're having exponential data, is that it's going to curve away from that. This shows us that this is in fact not from a normal distribution. In the next one, we have our UNIF 100, 0, 1. This means we have a uniform distribution with a lower boundary of 0, an upper boundary of 1, and we're going to select 100 data points. If we QQ norm this, again, it looks like it's mostly straight line. If we put our line, look what's happening at our extremes. On the left side, what's happening is that it's kind of curving, kind of doing concave up curve. On the upper part, it's kind of concave down curving, showing that this does not look like it actually is normally distributed either. This is actually a really useful way if you get some data to quickly assess whether it looks like it might come from a normal distribution. So this is something I might do. Someone sends me some data and I want to quickly see if it looks like it follows a normal distribution. Now, if I actually wanted to display any of this kind of stuff, like put a QQ plot within a paper or something like that, I would do more to make it look nicer. For example, we could use main to add a title. You could use xlab to add an x label, ylab to add a y label. You can actually also add these bands, which kind of tell you whether it falls within the realm of values that you would feasibly say looks like it follows a normal distribution. Or more realistically, I would use this as just a piece of evidence, but then probably do some sort of mathematical test, like a Shapiro-Wilk test, to actually show the strength of my conviction that it follows a normal distribution. But let's just say, for sake of argument, that we just want to make a graph that looks a little bit nicer. So let's do this next example, which we do exactly that. So here we have non-normal data. So we know that this one is going to be data coming from an exponential distribution. We're going to select 200 data points with a rate of 0.2. So that's our rate of decay. So we do that. And of course, if we were to just look at our data, you'll see that we have 200 data points. Now we're going to do QQ norm using our non-normal data. So we're going to set the title, main equals normal QQ plot for skewed, that's exponential data. Our X label will be our theoretical quantiles for our standard normal. Our Y lab will be our sample quantiles from our data. So if we create that, again, you can see that's curved, which we would expect. It's an exponential distribution. And then I'm going to add my QQ line. But in this case, I'm going to add the color where it's going to be red. And I'm going to increase the line width a little bit up to 2. And this will now give us this graph we could use to show that this, in fact, is not from a normal distribution. So in this lesson and the prior lessons, we've talked a lot about simulation of data and looking at data in R, right? We've looked at how we can simulate data using our R functions in R, as in R norm, R binom, within R, the program language. We've also looked at how we can use sample. We've looked at all sorts of stuff about these distributions. We've looked at how to even glance quickly and determine if they follow a normal distribution. Next, what we're going to do is we're going to say, let's say that we have the data. We want to do some analysis. How can we actually validate our data and our models? And I know that a lot of the stuff we're talking about, it might seem like we're kind of hitting on the same topics, and it's because each time I'm trying to add just a little bit more to it. Because this is really kind of trying to help you bridge the gap between your programming and all the things you've learned about in statistics in order to do some really great analysis with R and RStudio. When building a predictive model, it's important to validate its performance on data that was not used in training the model. This will help us assess the model's ability to generalize on new data to avoid overfitting. So in this lesson, we're going to cover some common techniques for model validation, specifically looking at cross-validation and how to properly split your data. Let's begin with data splitting. So properly splitting the data into training and validation sets is crucial for model validation. This split should be representative of your data so the model can learn patterns that will generalize to the new data that you've set aside for validation. In addition, it's important to ensure that there's no overlap between your training data and your validation data. So the most common method we use is what's called the holdout method. And this is where we take a certain amount of the data to train it, usually 80%, and the rest of it, the part you hold out, is your test data. This is what you're going to validate it on. So you'll take that 80%, you will train the model up, so you want it to be representative of whatever your population is, And then you will apply it to that 20% the model has never seen, which is why you have to make sure there's no overlap, because you don't want to cheat where the model's already seen the data, so therefore it should get the correct answer. You want to test if it's generalizable by using this data to train, the 80%, and testing on the 20%. So this is one of the methods we can use for validation. So how do we actually go about splitting the data? Well, this is where we can use things like we talked about previously, such as sample. We can take the entire set of our data and we can sample a certain amount of it by percentage, for example, in this case, 80%. And then the rest of it we would leave out for our test set. And this is one of the main ways you can do easy validation. Now, of course, there are methods you can use to make sure that it's representative. You could do things like stratified sampling whenever you're doing this. And there's a lot more you can do with this validation. These are only going to be a small snippet of what's available, but this is generally what will be used most. So first, we're going to begin by looking at the iris dataset. So the iris dataset is looking at 3 different types of iris and looking at the petals of those plants to try to classify them. This is a commonly used dataset for training classification algorithms in practice. So first thing, let's actually look at that data. So we're going to load our data up. So we have data iris. And now if I look at iris, let's say we look at names for iris, you're going to see that we have sepal length, sepal width, petal length, and petal width. And then of course, species. And if I just do the head command, let's just do 10. This is going to give me the first 10 outputs for the iris dataset. So you can see that we have sepal length, and this will give us a numeric value. We have sepal width, a numeric value, petal length, a numeric value, and petal width, a numeric value. And then of course the species, which will tell us what type of species of iris this is. Now, in order for us to all be kind of on the same page, in this example, I'm going to set the seed. So if you follow along, you should get the same training and test set data set that I did. So I'm going to do set.seed is 1, 2, 3. And remember from prior, if you want to get rid of this, you would do set.seed. Within the parentheses, put seed equals null, and it will wipe the seed. So now what we're going to do is train indices. This object, we're going to sample the number of rows for iris, and we're going to sample 100 of them. So if we look quickly at our dimensions of iris, you'll see that we have 150. So we're taking 2/3 of it as our training set. So we do train indices. We're going to run this. And now let's look at those train indices. And these are the rows that it's selected by sampling without replacement. So we have row 14, row 50, row 118, row 43, so on and so forth. So now this classifies which of our rows will be part of the training set. Now we need to actually make the training set. So we're going to make a new object called train data, and this is going to be iris, and we're going to subset within it. And remember, before the comma, that is your rows. After the comma is your columns. So we're going to select all the rows that are in train indices. So we'll run that. And now we can actually look at our training set. And you can see the different values we have here. So we have 100 of them right here with various parts of the iris, right? We have versicolor, virginica, and setosa. Those are the 3 types of iris in this data set. And just because, double check it, let's do dimension train data. We run that, and now you can see that we have a 100 by 5 data frame. Now we're going to make our validation set. So our validation set is going to be iris. Again, we're going to subset it, but this time for our rows, we're going to use everything except what's in train. So we're going to take our train indices and we're going to subtract that out. This will be our validation data. And so just like before, if I do dim valid data, you'll see that it's a 50 by 5 data frame. So now that we've split this data with 100 of the iris data points going to training and 50 going to testing, what we could do is we could train a model on those 100 in our training set, test it on the 50 in our validation set, and this will allow us to determine how generalizable it is from training this data to actually being able to properly classify things on this data it has never seen before. So holdout validation involves splitting data into 2 parts, our training set and our validation set. The model is trained on the training set, and its performance is evaluated on our validation set. Now, the advantage of the holdout validation is that it's simple and it's quick, right? So its simplicity and its speed are its main advantages. But this may lead to overfitting if the validation set is too small, or it may not be representative of the data, right? Because just like any time, there's randomness when we're using sample. There are ways you can get around this. For I mentioned previously, you could do stratified sampling to make sure that you include a little bit of each group, things like that. But if you just do it the way we did, you could end up where all of one type of iris, in this case, ended up in the training set and none were in the validation set, something like that. Or you may have the opposite occur. Nothing of a certain type ends up in the training set and they all end up in the validation set. So you have to kind of be careful. And this is why usually we do an 80-20 split. And we just kind of double check and make sure that it is representative before we actually do our modeling. Now, as always, there are tools that can actually make this even easier. So what we're going to do now is we're going to look at a particular package called rpart. This is used for doing tree-based classification and regression. So we're going to first load up rpart. So I already have the command here for install.packages rpart. I've already installed it, so I'm not going to run this one, which is why I commented it out. Just like I talked about previously, I like to put it in the code so that if I'm ever sharing this, somebody who doesn't have it, if they tried to run library rpart, it didn't work, they could just highlight this and run it. Okay, so let's load up rpart. And now what we're going to do is we're going to take the object tree model. We're going to use the rpart function. And from our iris dataset, we're going to say that species is, and we'll talk more about this in linear models, but species is being modeled by everything else, where our data is our train data, which is what we have up here. We're going to train this classification tree. Okay, now if I were to actually go and look at my tree model, what you're going to see is it's going to show you how these are splitting. So this is the decision tree. So what it's saying is that in the first split, we started our root, and then it's going to take petal length less than 2.45. Anything that is less than 2.45 petal length goes to one branch. Anything above or greater than or equal to will go to the other branch. Then we're going to have another branching path for petal length, where if it's, so this is our to the right. If it went to greater than or equal to 2.45, then it's going to have another branching path at the petal width. If petal width is less than 1.75, it goes to another branch. If petal width is greater than or equal to 1.75, it goes to a different branch. And you can actually display this, and I'll talk more about this maybe in a future video, but this is what's called a dendrogram, where you can actually display this tree diagram. So what I like to do whenever I'm using some new package like this is I like to go and look up the documentation. So I'm going to just put R, and I'm going to put rpart. And what we want to look for, so you have this R documentation, stuff like this. What I actually prefer is to go to CRAN, and this will take me to the official R network of documentation, all that kind of stuff for the different packages. And I'm going to go right here to this rpart, either PDF or HTML. I'll do the PDF. And this will pull this up. Get rid of this. And this can allow us to go straight to the function that we actually want to look at. So we're using rpart. So I'm going to go over here. I'm just going to click on 20. And this takes me to exactly where the documentation is for this, so I can actually look it up. So rpart, we've got our formula. Again, we'll talk more about formulas when we get into linear models. We've got our data. You can add weights, subsets, na.actions, what to do if there's NAs. The method, right, because there's going to be different methods. This is where you could set whether you would use ANOVA, Poisson, whether it's classification, exponential, things like that. Model equals false, x equals false, y equals true, parms, so on and so forth. And this will break down all of the different arguments that we have for this function. And then just like always, whenever we do documentation within R, it will also have examples that we can use. So you can kind of follow along. And oftentimes this is actually how I figure out how to use a new function. I go into this, I use the example, I try to break down what it's doing, and then I actually look at the documentation to figure out all the different options that I can do. So now that we've made our tree-based model, what we're going to do is we're going to assign the object pred, which is going to be a prediction. So we're going to predict using tree model, which is the model that we created on our test set. And then we're going to apply this, so our new data is going to be our validation set. And then we're going to set type to classification. That means that when you're doing a prediction, it can either do a regression type prediction where it's going to try to give us an actual value, or it can do a classification, right? We're grouping into A, B, or C. So we're going to do classification. So we run this, and now if we just were to look at pred, you can see that what it's going to do is for all of the different data points that were in our test set, it's going to predict what it was. So the first row, it's predicting it's Setosa. Second row, Setosa. Third, Setosa. Fifth, Setosa, so on and so forth. As we get to 59, versicolor. Eventually, we get to Virginica. So what we're going to do now is we're going to make a table with our predicted values. That's what pred is. And our validation data, and specifically just species. And we're going to compare them. So what this is going to do is it's going to take all of our predicted values. It's going to take the actual values, and then we're going to create a table from that to see how well our model did. And you can see here that it did very well. So reading this table, on the left side, these are our predictions. So these are the ones it predicted as Setosa. These are the ones it predicted as versicolor. These are the ones that are predicted as Virginica. At the top, these are actual values. So these are the ones that are actually Setosa. These are the ones that are actually versicolor, and these are the ones that are actually Virginica. So if we look at Setosa, that are so they are Setosa, they were predicted Setosa. We got 16 correct. We got 0 that we predicted as Setosa were versicolor, and 0 that we predicted as Setosa were Virginica. If we move to our prediction of versicolor, we have 0 inaccurately predicted as Setosa. We have 20 correctly predicted as versicolor, and we have 1 that was incorrectly classified as Virginica. If we go to Virginica classification, we had 0 inaccurately classified as Setosa, we had 1 inaccurately classified as versicolor, and we have 12 accurately classified. So this is exactly what we mean when we're talking about using holdout method for validation. These 50 data points that we tested this on were not part of our training set. They were completely randomly selected out, right? We hold them out, what's called a holdout method. We trained it on the 100 data points that we had for Iris for our training set. And then when we tested it on this, it was all brand new data. And we can see here that this classification tree did a pretty good job. It wasn't 100%, but it was pretty close to it. Now, we talked about the fact that there are some shortcomings to the holdout method. So one of them, some of the nice things about it is that it is quick and it's really relatively easy to create and run. You saw how fast that was. We just create 2 sets using sample, no big deal. The problem though is it might not be representative. So is there a way that we could make sure that all the data gets used in training and also in validation to make sure that nothing gets missed? This is where it brings us to what's called k-fold validation. So cross-validation involves partitioning the data into multiple subsets or folds, and then using each fold in turn as a validation set while the remaining folds are used for training. So what this would mean is something like this. With an 80-20 split, you take your 100% of your data, and let's say that we hold the first 20% as our test data, and the other 80% will be our training data. Then you go to the next 20%. So this way you have 20% training, and then the other 60% training makes up 80% training. And you do this for these 5 different folds. Now, it's not going to be like I just explained it, where it's going to be the first 20%, second 20%. What it would be is that you're going to randomly take 20% of the data out, and that will be your fold 1. Then whatever's left, you're going to take another random 20% out, and that's going to be your second fold. You're going to take 20% out of the 20% of the original, not 20% of the new values. So let's say I have 100 values. I'm going to take 20 out for fold 1, and then I'm going to take those 80 values that are left. I'm going to take 20 out for fold 2. Now I have 60 left. I'm going to go 20 out for fold 3, 20 out for fold 4, and now I have 5 folds. Then what I'm going to do is I'm going to use fold 1 through 4 for my training, and fold 5 will be my test. The next one, I will use fold 2 for my test, and everything else will be the training. For the third one, fold 3 will be the test set. Everything else will be training. For the fourth one, fold 4. Fifth one, fold 5. So what you're doing is you're actually using every single bit of information you have as training set for all the folds except the one it's in, and it'll be a test set for 1. So everything gets used in both training and tests. So this process is repeated multiple times with each fold used once as a validation set. The advantage of cross-validation is that it uses all available data for training and validation but it can be more computationally expensive. And this is the kind of trade-off you have to think about when you're doing computational statistics, is sometimes it's going to be a balance of what works best and what is actually feasible to do. And this is why oftentimes we'll just, if you have a relative amount of data that you can do the analysis on, we'll do what's called five-fold cross-validation, like I was explaining, 20%, 20%, 20%, and so on. But you can do any amount of folds you want. You could do 10-fold cross-validation, where you take 10% data chunks. You could do 5% validation sets and do 20-fold. There's no specific number of folds you have to do. The only key things is, one, making sure that it's computationally feasible to actually run it, and then making sure you have enough data to actually do your analysis. Could you do k-fold cross-validation in base R? 100%. You would just do the exact same steps we did when we were creating our validation sets and our training set, except for what you would do in this case, you would just do something like fold 1, take 20% of your data. Fold 2, take the remaining 20% from the remaining data, and you would just kind of do that. Once you figure out what 20% of the data is, you can just pull that out from each one, and whatever's in the last one for your last fold. But there's easier ways to do it. So what we're going to do is we're going to look at the caret package, which I will warn you, caret does a lot. So as always, I've got my install.packages, but before we jump into that, I do want to show you the caret package in R. So R caret, because this is anything and everything you could think of. Actually, I'm not going to go to here. I'm going to go to this page here. It is almost anything and everything you could think of when it comes to machine learning. So you can see here that we've got stuff for pre-processing, visualization. It's got parts for data splitting, model training. It's got train models by tag, and these are all the different things it could do, accepts case weights, bagging, Bayesian model, binary predictors only, boosting, categorical predictors only, cost-sensitive, discriminant analysis, ensemble model, feature extract. You can see that there are a lot of things that are included in the caret package. It is a almost completely comprehensive package. There's most things that it does. I'm personally not the biggest fan of it. Oftentimes, I prefer to use individual packages that are built for a particular use case. But honestly, a lot of people do use this, and it works perfectly fine. So what we're going to do now is we're going to load up caret, and it's going to tell us that we got some warnings, but those aren't going to stop us from using it. It's just telling us that it was built under prior versions. We're going to set the object control, and we're going to use the command train control, which is from the caret package. You would need to look this functionality up. And we're going to do method equals CV for cross-validation. Number equals 5. This is saying how many folds we want. So we're doing 5-fold cross-validation, and that means that we're going to have 20% per fold. Next, we're going to set up our model. So we're going to use the train function. And again, just like before, we're going to have species, and it's going to be modeled by everything else. Our data is going to be from Iris. Our method is we're going to use rpart, which again is going to be for regression and classification trees. And then our train control, we're just going to use control here, which is what we did previously. We're telling it how are we actually training this. So let's run that. And now, if we look at our model, let's see what it looks like. So what this is going to tell us is that it used CART, which is classification and regression trees. We had 150 samples with 4 predictors. We had 3 classes, Setosa, Versicolor, and Virginica. There was no pre-processing that was done. Our resampling was cross-validated 5-fold. Our summary of sample sizes, we had 120 for each of them because, again, we had 150 total data. It took 120 for training, 30 for testing, and then that's how big each fold was. We've got our resampling results across tuning parameters. So this is doing, a lot of times whenever you're doing tuning, you'll do what's called hyperparameter tuning, or you'll use like what's called a grid search, and it'll basically home in on what is the best training for the algorithm while also balancing other things like cost and model complexity, stuff like that. Then accuracy was used to select the optimal model using the largest values. What this was saying is that it focused on using accuracy. It was trying to maximize accuracy. This is actually a pretty interesting topic I do plan on talking more about later, which is whenever you do like a confusion matrix, we have a lot of different things we look at. So you have model accuracy, you also have model precision, you have predictive power, you have things like F1 score, and these are all things that describe how well a model does. The problem is that sometimes what seems like it would be best, like accuracy seems like it would always be the best. It's not always, right? Because you have to look at things like positive predictive power. If I make a prediction of this, how often am I correct? Versus accuracy is if something is, let's say, Setosa, how often is one of the predictions I had correct on that? And I know it sounds like they're the same thing, but they are different. One of them is I make the prediction, how often am I right? One of them is how often, if it's this, is it correct on that? And then the final value was used to model was CP of 0. So this is your cost parameter. So this is just a small snippet of some of the cross-validation methods that you can do for model validation. So model validation, of course, as I mentioned, is an essential step in building predictive models. You want to do proper data splitting. You could use things like holdout validation or cross-validation. These are the two most common used for model validation, but they do have trade-offs between simplicity and computational expense. By using these techniques, you can assess a model's ability to generalize to independent unseen data, which is the ultimate litmus test of preventing overfitting of your data, which is always going to be a big thing, especially when you get into learning algorithms in your predictive models. Now, let's talk a little bit about trade-offs. For your holdout method, it's highly simple and computationally cheap, but it's structurally vulnerable to high variance based purely on how the single split occurred. This means that sometimes you'll do holdout, works amazing. But there's always that chance that you get a bad split. And unless you're doing something else to kind of double check your validation, you're kind of validating your validation, you could run into problems there. K-fold cross-validation minimizes the splitting bias by ensuring every single observation is used for both training and testing across different iterations, but it does increase the computational expense by a factor of K, right? If I'm doing 1 model training versus 5 model trainings, you would expect it to be 5 times more computationally complex. Now, one of them I didn't talk about, and we use this more often in academia, it's not often used in the real world, is what's called leave one out cross-validation. It takes the idea of K-fold cross-validation to the extreme, where if I have 100 data points, I will have 100 folds, meaning I have one test, one object is my test set. So one observation is my test set for the first one, a different observation, and you go through every iteration of one. So it's 99 out of 100 is your training set, 1 is your validation set, and you cycle through every iteration of this. So a deterministic extreme case of K-fold cross-validation where K equals N, the sample size, for every iteration, the model trains on an N-1 observations and is evaluated on a single remaining holdout data point. The cycle repeats N times so that every observation serves as a validation set exactly once. Now, of course, while this completely eliminates the randomness of our arbitrary data splits, it does require fitting in different models. This makes it computationally prohibitive for most cases, especially if you have larger data sets or if you have slow or complex estimators. An example of this would be if you're doing something that's more computationally intensive, like k-nearest neighbor, something like that, then this becomes quite unreasonable quite quickly. And this is something that you could actually encounter even, doing stuff like this for a class like this. So just wanted you to be aware of this, though. This is like the gold standard. If you can show that a model is good with leave one out cross-validation, it does make a strong case for validating the model. But again, it's not generally feasible because when you start getting into bigger data, more complex models, you're always going to have that trade-off of being right versus being able to actually do it. And sometimes good enough is good enough. An example of this is not recently, since they've kind of jumped more into the AI stuff, but before we were doing things with AI, Google, when it was doing its natural language processing work, would oftentimes use naive Bayes in order to classify a lot of its language things. Naive Bayes is a good model, but it's not great. But they would specifically choose it because not only is it good, it's also very efficient and fast. Because when you're at the scale of Google, being 89% correct quickly is way better than 93% correct, but very slowly. So in computational workflows, the choice of validation structure is dictated entirely by your sample size N. So with massive data sets, clean holdout split is sufficient. With smaller high variance data sets, iterative resampling in general is preferable. And sometimes you're going to need to do it one way or another just to kind of really test or show that a model is valid. An example of this is I was doing some work recently with AI systems and natural language processing, and I got really good results whenever I originally created the model using a holdout method. The problem is the next time I ran it, my results weren't as good. They were still decent, but they weren't as good. So this led me to believe that maybe I just got a lucky split, or maybe the fact that the second time I just got a bad split. I don't know. So what I ended up doing is I ended up doing a k-fold cross-validation, which meant, of course, more model training, more model time. So instead of taking 15 minutes to train, it took well over an hour. But I was then able to more confidently talk about how valid this model was when I was presenting the research at an AI conference. So putting this all together, this kind of concludes our section on simulations. We've talked about how to simulate data with inbuilt functions in R. We've talked about how to sample from data to create sort of subsamples or randomly create samples from population, things like that. We've looked at how, some of the advanced methods you could use whenever you are generating data for simulation. And we've even talked about how you would validate this data once you actually have it for your model analysis. So with simulations, you can create hypothetical scenarios based on known or even assumed probabilities and study how they would play out in practice. And this is one of the real strengths of having a tool like R versus what we teach and learn in statistics classes, where a lot of times we're giving you, again, what I call toy examples, where we give you this sort of small scenario. We know the data will work. We've kind of done it for you. But if you wanted to start to scale up and things like that, R is a perfect tool for doing exactly that. We've talked about things like generating random numbers, right? Before you can simulate data, you often need to generate random numbers. And this R has, again, several functions for generating those random numbers. These things are like RUnif for uniform distributions, RNorm for normal distribution, RPoise for Poisson distribution, RBeta for beta distribution, or RGamma for gamma distribution. And there's many other functions that are available, right? Anything you can think of that you want to test out or create data to simulate and then test whatever it is you're interested in, R generally can do it. And if R can't do it, I almost would guarantee that there will be a package that does do it. So now that we've talked about how we can generate this data and simulate and even validate our models, now it's time to jump back into more of a programming focused topic, which is we're going to start looking at loops and then functions. Oftentimes when you're programming, you're going to want to iterate through many numbers for some operation. This is where we're going to focus on for loops. So in general, the mechanism to create something like 100 random numbers may not be so simple, and we need to create them one at a time, which would be tedious and be inconvenient to do. So how can we generate lots of these all in one step? So for this, we're going to use what's called a for loop, which you may be familiar with if you have any previous computer classes where you've done any sort of programming. This is sort of one of those fundamentals of programming, but our users also can apply them for many of the things that we need to do. So the R command for, what it does is that it iterates over some specified set of values, such as the numbers 1 through 100. We then need to store those values somewhere. Generally, we're going to use a vector, and we will assign each of those values one at a time in this loop. So in R, a for loop is used to iterate over a sequence of values and perform a set of instructions for each value in that sequence. So what it's going to do is it's going to start at that first number, it's going to run the instruction. It's then going to go to the second number, it's going to run the instructions, it's going to go to the third number, and so on and so forth. And this is what we do when we're doing a for loop. For loops are useful when you want to repeat a task a fixed number of times or iterate over a set of data. So in this lesson, we're going to learn how to write for loops in R and explore some of the common use cases. First, let's begin by looking at the syntax of a for loop. So a for loop has a very simple syntax where it's for, and then you put a space followed by variable in sequence. This would be something like, generally in math, we use I for index. So we'd use for I in, and then what is the sequence that you want to run? It might be something like 1 to 100, or it may be something like the values within a vector or across all the data. You might start from 1 to the length of the data, something like that. Then you put a space and you put this curly bracket, and then between the open curly bracket and the closed curly bracket, this is where your set of instructions will go. This is what it's going to perform on each index of our for loop. So the variable, this is a variable name that will be assigned to each value in the sequence for each iteration of the loop, and your sequence is a sequence of values over which the loop will iterate. Now, before we start actually talking about doing for loops and all that kind of stuff, I actually want to show you some of the cool features in RStudio, making things like creating loops and functions that much easier. So for example, let's say we do for and then I in 1 to 5, much like I have in my upcoming example. And then I'm going to put a space and watch what happens. When I do my curly bracket, you're going to see that it opens and closes a curly bracket, which RStudio always does. But if I hit enter, what's going to happen is it's going to automatically jump a blank line for me to put instructions, and it's going to put the closed curly bracket on the next line. And this follows one of the conventions of how loops and functions are written in programming to kind of make them clean and readable. So notice it automatically indented one space. This means that any code that is indented like this shows that it is clearly part of this for loop. And we'll talk about that later when we talk about nested loops. So what this is going to do is this for loop would be for the index I from 1 to 5. So you can think of this like when we're doing something mathematical, like a summation. We have the summation I equals 1, 2, and then whatever is at the top, n. And you could do the same thing here. It would be I from 1 to n. Or because we're programming, right, we might use something like length of my data, right? This would be something to tell it going from 1 to what, and it's going to iterate through I. So we're going to start by first doing a very simple example. We're going to do a loop in R. So suppose that we just want to print the numbers 1 through 5 in a loop. So what we're going to do is we're going to set it up just like we did a second ago. For I in 1 to 5, that is telling it index I 1, 2, 3, 4, 5. What's the instruction it's going to do? It's just going to print I. So if I were to run this, it's going to go I is 1, print 1. I is 2, print 2. I is 3, print 3. I is 4, print 4. I is 5, print 5. So if we run this, you'll see that we get 1, 2, 3, 4, 5. And we can change this to whatever we want it to be. Let's say we did this to 12. It's then going to print the values 1 through 12. Easy peasy. Also, our index does not have to be I, right? We chose to use I as our index because that's what we commonly use in math. But a lot of times we use I, J, and K. And we'll use that again later when we do nested loops. But if I use J, it works just as fine, right? Actually, if I use J, I just have to change my print to J, and it works perfectly fine. I equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the loop starts by assigning the first value in the sequence, which is 1, to the variable I. Then the loop executes the instructions inside those curly braces, which in this case is to print the value of I. After the instruction is executed, the loop increments the value of I by 1. Then it will repeat this process with the next value in the sequence until it reaches the end of that sequence. Now let's look at an example that's a little bit more complex. So if we go into R, this is going to be a function to look and see if something is a prime. Now we haven't talked about functions yet, but it does follow some similar syntax, right? So is prime is an object that we're assigning, right? We got the arrow operator. We have function of num. We're calling our argument in this case num for whatever number it is. Curly bracket, and because what? If I hit enter, it's automatically going to put a space, and then it's going to put the curly bracket on the next space. Within that, we have the instruction. If num is less than or equal to 1, and then we have another curly bracket because this is a nested function, right? So we have a function, and then within it, we have an if statement. We'll talk more about if statements later. If the number is less than or equal to 1, return false. Now here's our for loop, I in 2 to the number minus 1. So what we're doing is we're taking whatever our number is, num, and we're subtracting 1 from it. That's going to be the end of our indexing for our for loop. So we're going to start at 2, so 2, 3, 4, 5, 6, up to whatever n minus 1 is. Then if the number we have, num, and this is a modulo operator. I do have a slide later on about this, but basically what it's going to do is it's going to take the whatever is left over from dividing out the numbers, and if it's equal, and I'm setting here, if the modulo of I to our number is equal to 0, we will return false. That means that if it is divisible by something with no remainder, that means that it is in fact a prime. Otherwise, right, so this is going to end this one, this is going to end this, and then we'll return true. So let's run that. This is going to, of course, not run it. It's going to create the function. So now we have this function is prime. So what we're going to do now is we are going to run a for loop using this function. So for I in 2 to 200, if is prime I, print I. So what this is saying is that the is prime is looking at, is a number a prime number? If it is going to print that number out. And we're going to look at the numbers 2 through 200. So if we run this, you will see that we didn't include 2 because in this case, we start at 2 and all that kind of stuff. And this is a failure of this one because this system doesn't have to take into account that 2 is the only even prime, because what's going to do is it's going to look at 2 equals 2 divided by 2 based on modulo. It has a remainder of 0. And I will talk more about creating more robust systems later on, but I just wanted to show this as an example because it's quicker and it's easier and it's kind of combining a lot of the stuff we're working on now. So you'll see that it printed out the values 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, so on and so forth. And it did this for all the numbers up to 200 because that's where our index ended. Our index ended at 200. Therefore, it stopped at the highest prime before it hit 200. Once it hit 200, it stopped moving on. Let's say that we were to change this. Let's say instead of 200, we went to, I don't know, 400. If we were to run this again, you will see that, again, it's going to list out all of the primes from, above 2 up to 400. And so the highest prime before 400 is 397. So then just recapping on this example, this is going to print all prime numbers between 2 and 200 is what I had. We first defined a function called isPrime that checks if a given number is prime. We then used a for loop to iterate through the numbers between 2 and 200, and we used isPrime function to check if each number is in fact prime. If a number was prime, we then used a for loop, to print out the numbers where it was true that it is prime. Now, a lot of the examples that we're going to cover when we're doing things like loops, for loops, while loops, if statements, stuff like that, are going to be sort of mathematical tools you can play with, novelties, things like that. But one of the common uses you're going to want for loops are going to be to manipulate data. So one of the common use case for loops in R is to manipulate data. For example, suppose we have a vector of numbers and we want to square each number in that vector. We could use a loop to accomplish this task. In this case, what we're going to do is we're going to use the length of numbers. This will tell, that way we don't have to hard code what the actual end index value is. In this case, it would just be 5, but if you had a lot of data, this might, or if you have a lot of data coming in, so every time you have a different number of values in your vector, then that way you don't want to hard code it. So looking at what we have here, I'm first going to set up a vector, which is going to be 1, 2, 3, 4, 5. And it's just called numbers. So for our for loop, we have for I in 1 to length of numbers. So just a reminder, length is just going to tell me how many values there are. So if I do length of numbers, you'll see that we get 5. If I change this to 1, 2, 3, 4, 5, 6, and then I do length of numbers again, now it's going to say 6. All this is going to do is just going to give me the number of values that I have in whatever this object is. So for I, the index, from 1 to length of numbers, which is now 6, curly bracket, now we have our instructions. Number subset I, so we're going to take numbers, so subset I, so the first one will be 1, second one will be 2, right? So we've got square brackets, subsets. We're going to assign the numbers value of I, so 1, 2, 3, 4, 5, 6, squared. So what we're going to do is we're going to take numbers 1, 2, 3, 4, 5, 6, first index 1. What are you going to do? It's going to square it. It's going to replace it with that 1, right? Because 1 squared is 1. Number 2. Now we're going to take that number 2. We're going to square it. We're going to replace that 2. And now we're going to have 4. Next one, you're going to take 3. You're going to replace it with the square. So let's run our for loop and let's see what we get. So we're going to print those numbers and we're going to get 1, 4, 9, 16, 25, 36. So all this did is it went through the iteration of first value, square it. Second value, square it. Third value, square it. Fourth value, square it. Fifth value, square it. Sixth value, square it. Before this, what we did though is we also assigned it to replace that value. So we didn't just square the values, we replaced it. This means that if I now look at numbers, watch what happens. Numbers, it's 1, 4, 9, 16, 25, 36. We didn't square numbers, we squared and replaced numbers. And this is why it's different than just doing something like, if I go back to the original numbers and then do numbers squared, If I do that, I get the same output, but watch what happens now. Numbers didn't change. And this kind of goes back to that being immutable versus immutable, is that in R, numbers is immutable. When I square it, it gives me the output of numbers squared, but it doesn't change numbers. But if you look at our for loop, what we did is not only were we squaring that number, we were then assigning it to that same number spot. So 1 stayed 1 because 1 squared is 1. 2 was replaced with 2 squared, or 4. 3 was replaced with 3 squared, or 9. So we actually were replacing it piece by piece. Every index, we replaced the first one, the second one, the third one, until we got to the last one. You can also have nested loops. So in some cases, we may need to use nested loops to iterate over multiple sequences of values. For example, suppose we want to print all possible combinations of two numbers between 1 and 3. Then we can use a nested loop to basically kind of go through every iteration. So you go through index 1, and then you do, for the second index, 1, 2, 3. Then you go to index 2, you do the second index, 1, 2, 3. Then you go to index 3, second index, 1, 2, 3. So in this example, we're going to use two nested loops to iterate over all possible combinations of two numbers. So let's actually break down what this is doing. So we have for I in 1 to 3. So our index I, it's going to go 1, 2, and 3. Curly bracket, what are instructions? Well, instructions are another loop. For j in 1, 2, 3, right? So 1 to 3. What are the instructions for j? Well, what it's going to do is it's going to print, and we're going to paste the value of I and j with a space separating it, right? Because paste is going to be, what are you pasting together? I and j. And then sep equals whatever's within the parentheses will tell us how it's separated. In this case, I put a space. So what this is going to do is this is going to go I equals 1. So for j equals 1, paste the two together. So 1, 1. J equals 2, paste together. 1, 2. For j equals 3, paste together. 1, 3. Once it's gone through this entire iteration, it's going to go back up to our outer part of our loop, and then index I is going to jump to 2. Then we're going to get 2, 1, 2, 2, 2, 3. It's going to go back up. Index is going to jump up by 1, 3, 1, 3, 2, 3, 3. So let's do just that. And you can see here, 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And this is an example of what you might use a nested loop for. So oftentimes when you're doing loops, functions, if statements, stuff like that, you're going to want to have this sort of branch of logic of, you have to kind of think of it sequentially, right? Whatever's happening on the outside, it's going to progress based on what's happening within it. So typically if you're just doing a single loop, it's just going to be index 1, do the thing. Index 2, do the thing. Index 3, do the thing. If you were doing a nested loop, it's going to say index 1, do the thing. Oh, it's a loop. Okay, cool. I'm going to do the thing, go through its iterations. Then I'm going to increase my index by 1. Go through all of them and increase the index by 1. And you're going to do this over and over and over again until the entire loop has finished. What if I don't want to have some set number of iterations though? This is what brings us to while loops. So in R, as in many other programming languages, we often need to perform repetitive tasks. And this is where while loops can come into play. So one of the most basic forms of loops in R is our while loop, and the while loop will basically repeatedly execute whatever block of instructions you give it as long as certain conditions are true. Once the condition comes as false, it will instantly end. The basic syntax of this is while, and then you have to set the condition. So what is the condition? While x is even, while x is less than 5, while x is a prime number, right? Some condition where while it's true, it will run whatever code you want. Then once it hits the first case where it's false, the loop instantly stops. This condition is checked before each iteration. If the condition is true, the block of code within the loop will be executed. If the condition is false, the loop is terminated and the program control proceeds to the next line of code after the loop. It's important to ensure that the condition in a while loop eventually becomes false. Otherwise, the loop will just continue on indefinitely, creating an infinite loop. Which, by the way, if that ever does happen, whenever you're in R, there'll be a little stop sign at the top right of the console window. You can click that. It will do what's called a break command, and it will stop whatever operation you have going. So here we're going to look at two simple cases of a while loop. So if you look at the top right of the slide, first, we have x being assigned as 1. And then our while loop is while x is less than or equal to 5. So that is our condition. X is less than or equal to 5. The instructions are print, and we're going to paste, x is And then, of course, we're going to paste in whatever x is. In this case, it's going to start with 1 because that's what we assigned x. Then the second instruction is, once it's pasted, x is 1, it is going to take x, it's going to add 1 to it, so x becomes 2, and it's going to replace x with that. So now x is 2. Then it's going to run, is x less than or equal to 5? 2 is less than or equal to 5, so it's going to print x is 2. It's going to jump the iteration up to x is 3, and it's going to do this until the condition becomes false. So let's do just that. So we're going to set x to 1, right? So if we look at x, you'll see that's 1. So while x is less than or equal to 5, so it's going to do this. So it's going to say x is 1, x is 2, x is 3, x is 4, x is 5. And then it stops, right? I didn't tell it to stop at x is 5. And the reason is, note if I look at x now, what is it going to be? X is 6. Because when we're actually running these instructions, right, it's going to print x is and then whatever x is, and then it's going to increase by 1. So when we had x is equal to 5, 5 is less than or equal to 5, so it ran the instruction. When it got to x plus 1, that became 6, x is 6, then it ran it again. While 6 is less than or equal to 5, that is false. So that's where it ends. So it ended on x is 6 because that was the instruction that we ran last, which was 5 it worked, increase it up by 1, now it fails, so x is 6. And this is why I talked previously about sometimes beforehand, I'll have something where I put like a null vector or some blank numeric vector, something like that. And this is because whenever you're doing these sort of things, if, while loops, things like that, oftentimes you're going to be changing the actual what's within your object, and you want to kind of just have a way you can kind of clean slate it. So I want to run this somewhere else. I could just run x back to 1, do it again. Now x, of course, is again 6. Our second example is a little bit more complex. What we're going to do with this one is we have x is equal to 1. We have y is equal to 5. Then we're going to use the while loop, which is while x is less than or equal to 5, and also y is greater than or equal to 1. So right now, it's going to start out, x is equal to 1. Is that less than or equal to 5? Yes. Y is equal to 5. Is that greater than or equal to 1? Yes. Great. Both statements are true, because it's an and statement, which means both have to be true. Then it's going to run the instructions. We're going to print, paste, x is blank, so whatever x is, and y is whatever y is. Then it's going to increase x by 1 and replace x. It's going to decrease y by 1 and replace y. So now x is 2 and y is 4. 2 is less than or equal to 5. We're good. Y is equal to 4, which is greater than or equal to 1. We're good. It's going to run the instructions again, increase x, decrease y, and it's going to do this until at least one of them fails. So if we ran this, let's see what happens. We have x equals 1, y equals 5. Now we're going to run our while loop. And you're going to see x is 1 and y is 5, x is 2 and y is 4, x is 3 and y is 3, x is 4, y is 2, x is 5, and y is 1. Now the problem with this, though, is I want to show that this logic statement, being an and, means that if either of them fail, then it stops. So what we're going to do now is, instead of starting y at 5, let's put it to 4. Let's run it again. So x is 1, y is 4. What do you think is going to happen? Well, remember, what's going to happen is each time we run the instruction, x is going to go up by 1, y is going to come down by 1. So x is going to go from 1, 2, 3, 4, 5. Y is going to go from now 4, 3, 2, 1. So what's going to happen is that y is actually going to hit a false statement first. So notice that it's stopped. So we have x is 1 and y is 4, x is 2 and y is 3, x is 3 and y is 2, x is 4 and y is 1. So while x could still go up by 1, because x is still less than or equal to 5, y is no longer greater than or equal to 1 after this, when it's subtracted 1, right? If I look at what x is right now, x is going to be equal to 5. If I look at y right now, it's going to be equal to 0. Because it did, the last step it did was it increased x by 1 when it was 4, up to 5, and it decreased y by 1 when it was 1, taking it to 0. So y failed its condition, its while condition. For our next one, similar to what we've done so far, we have I, which we're going to set equal to 1. And then we're going to use while I is less than or equal to 10, we're just going to print I. So I is 1, print 1. Then increase I by 1 and replace it. So then I is 2. is 2 less than or equal to 10? Yes. Print 2, increase I by 1, so it becomes 3. It's 3 less than or equal to 10? Yes, and it's going to do this until it stops being true. So if we run that, you're going to see it's going to list 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The next example, we're going to set sum to 0. Now we're going to set I to 1 again, because again, I is currently 11. So we're going to set I to 1. And now this while statement is while I is less than or equal to 10, what we're going to do for our instructions is we're going to take our sum, which remember is currently equal to 0, and we're going to increase this by I. So it's going to be sum, which is 0, plus I. Well, I is starting at 1. So now we're saying sum is equal to 1. We're going to take our I and we're going to increase it by 1. So now it's going to be 2. We're going to check our condition. 2 is less than or equal to 10. So now we're going to come to this first instruction. Sum, which we said right now is equal to 1, is 1 plus I, which is 2. So 1 plus 2 is 3. Sum becomes 3. I goes up to 3. This becomes 3 plus 4, which is going to be 7. So what this is doing is this is adding up all the numbers together. It's taking 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the way up to 10. And what we're going to get is we're going to get 55. And this would work for whatever values we wanted to. For example, let's say we wanted to add up all the numbers less than or equal to 100. So first thing I'm going to do, I'm going to reset sum and I. I'm going to run my while loop. So what it's doing is it's adding up all the numbers, 1, 2, 3, 4, 5, 6, 7, up all the way to 100. And I'm going to print sum, and the values add up to be a total of 5,050. And this is actually really one of the cool things about doing something like this is something that would not be easily done by hand, and I can do it for much bigger numbers, right? So we have 1,000, 10,000, let's do 1,000,000. Okay, so, oops, I forgot to reset my sum and I. Don't forget to do that. And you saw how quickly that did, right? I can pick any number I want. If I wanted to change it, maybe I do 9,999. Oops. Again, I got to change my sum and I. And you'll see that it will just add up all the numbers from 1 to whatever, while this condition is true. Right? Now, I doesn't have to start at 1. I can start at any number we want as well. I could I could add up the numbers from 56 up to being less than or equal to 9,999, or less than or equal to, and it can do that as well. So we're going to stop with loops right now. Here we've done for loops and while loops, right? So we've got for, where we have a specific beginning and end. We have a sequence of values we're going through. We have while loops, where it's going to loop while some condition is true. Following this, we're going to jump into if and else if statements, things like that. But what I want you to do is go and actually try building out some loops from here. Things like write a while loop that prints the even numbers from 1 to 100. Try writing a while loop that sums the odd numbers from 1 to 100. Write a while loop that checks if a number is prime. Or try to add an endless loop or do an endless loop and see what happens, right? Find something where the condition will always be true and see what happens. Test it out. Like I always talk about, whenever you're learning to program, best thing you can do is try different things, right? Have a project that you're trying to do that a lot of times cause you to seek out things you don't know how to do and you're kind of pushing past your comfort zone. But then the other aspect is when you're learning something like this, when you start learning about loops, start looping everything. Try to figure out all these different loops you can do. Try to make them more complex. Try to do nested loops. Try to find an example that breaks whatever you have. For example, going back to my isPrime function, I mentioned that it specifically fails because it doesn't have 2, and 2 is a prime number. Think about a way that you could fix that. How do you get it to include 2, but then not include any other numbers divisible by 2? Right? And we'll talk more about this in the next lesson, but this is something we have to think about. You have to think about those what are called edge cases, those cases where something generally works, but does fail. And I really want you all to keep practicing doing this. Hello, everyone. We're going to continue now with looking at if-else statements. So this is actually made up of 2 parts. You have the if statement. The if statement in R tests a condition, and if the condition is true, it then will execute the block of code. If the condition is false, it will skip the block of code, and then it will move on to the next part, which is usually followed by the else statement. The else statement in R is used in conjunction with the if statement. The else statement contains a block of code that will be executed if the condition in the if statement is false. And you can see the syntax of both of them on this slide here. So we have if and then condition, whatever it is that we're looking at, x is greater than 5. Then within your curly bracket, you have the code to be executed if that condition is true. If the condition in the if statement is false, it then will skip this block of code and go on to the else statement. And then similarly, after the curly bracket, you have else, another open curly bracket, and this is where the whatever it is will be executed if the original if statement condition was false. Now, the nice thing about an if-else statement is that you can actually have this sort of branching logic by adding in else-if statements. So the else-if statement in R is used to add additional conditions to an if statement. If the condition in the if statement is false, it will go ahead and skip that code block, and then it will check the condition in the else-if statement. If this condition is true, it will execute the block of code. If it's false, it will skip that block of code and move on to the next one. So you could have if, else, if, else. So if is the initial condition. If this one is false, it checks else if. If this one is false, it then goes to the else, and that's your final conclusion. If the if condition is true, it just runs that block of code and you're done. If the if condition is false and it goes to else if and that condition is true, it will run that. And you can actually have more than one else if. So you could have something like x is greater than 5. And let's say that that's false. Then it might say, okay, well then is x greater than 0? So that'd be your else if. And let's say that that one is also false. You'd say, okay, well then x is clearly a negative number. Or it might be something like, let's say that x is 2. You say x is greater than 5. Or if x is greater than 5, false. Else if x is greater than 0, yes, 2 is in fact greater than 0, but not greater than 5. So then it would run whatever you have to execute based on that. And this is how you can make some of these really interesting systems based on these sort of logical conditions. You might say something like, do this if numbers are odd or even, or an example might be if you're trying to make something like an absolute value. If x is greater than 0, then leave x the same. Else, multiply by -1, something like that. So we're going to start with a really simple example. First, we're going to set our object x as 10. Then we are having the if statement with the condition x is greater than 5. If this is true, it will print x is greater than 5. Else, that is, if our condition is false, it will print x is not greater than 5. So if we were to run this, let's see what happens. Right now, x is 10, and if we run our if-else statement, it'll say x is greater than 5. Well, what about if we make it a number that is not greater than 5? Let's try 0. So we run it again, and we get x is not greater than 5. And always what I would like to do is I'd like to try a couple different conditions. Let's test out if we have a negative number, see if it still works. Works fine. What about if I make it exactly 5? Because I put in my condition that x is greater than 5. 5 is not greater than 5. If it were greater than or equal to, that'd be fine, but it's not. So let's try it. X is not greater than 5. Seems to be working fine. Next, we're going to expand on it just a little bit, and we're going to now add in an else if statement. So again, we're going to start by setting x equal to 10, and we have if x is greater than 20. So if x is greater than 20, it will then run this next block, which is print x is greater than 20. If that condition is false, we now move to the else if. So else if x is greater than 10, so not greater than 20, but greater than 10, it will print x is greater than 10, but less than or equal to 20. If this condition is also false, that's when it goes to the else statement. Else, print x is less than or equal to 10. Let's try it out. So first things first, we are going to make x equal to 10. And so this should be false for our if statement, and it should be false for our else if. Therefore, it's going to print that it's less than or equal to 10. So x is less than or equal to 10. Awesome. Let's now try putting x as 11. So if we make x 11, now we're going to run our if else statement, and we get that x is greater than 10, but less than or equal to 20. Now let's try doing one that's over 20. Let's try 22. So we do 22. Run that, we get x is greater than 20. So you can kind of see how you can create this like branching logic. Like I said, you can do like an absolute value, positive values, negative values. You could do an else if for 0, something like that. There's all sorts of options. And this is actually where you kind of start getting really into how you can, set things up, but you have to really kind of think programmatically. Because recall, when you're doing these, it's going to go in the sequence, if, else if. And if you have more else ifs, else if, else if, else if, else. Meaning that you have to kind of take into account all the different possible conditions. And if one higher up in the list is true, it's going to run that. So if you actually wanted it to run this, you have to really kind of think of the order and the sequence that it's going to run these things in. So I have a couple other examples just to kind of show the same sort of thing, but with different conditions. So the first one we have here, we have x is 15, and we have if x is greater than 10, print x is greater than 10, else print x is less than or equal to 10. So same basic idea, just I use different numbers before I end up changing them for you all. So nothing really new here. This next one though, same idea, except for we're looking at character strings. So we have x is equal to the character string hello. If x is equal to hello, print x is equal to hello. Else, print x is not equal to hello. So we can do just that, and you'll see that x is equal to hello. But let's say that we changed it up. Let's just get rid of the h, and you'll see that now it's not going to be equal to hello, so it should fall into our else statement. X is not equal to hello. And then finally, in this next one, we have a vector, which is so we're going to concatenate 1, 2, 3, 4, 6. So in this case, we have if 5 in x. So what this means is that if 5 is in x, and notice that it's the modulo, this means that it's in x, but not some other part of something else. It is purely either 5 or not 5. It's not going to be something like 55, and it will count that. And we'll test that. Actually, let's add it now. So we're going to add 55. Okay, so if 5 is in x, print 5 is in x. Else, print 5 is not in x. And I actually created this vector, so we're actually going to get a sequence of true or false statements based on that. So if we run this, we'll see that 5 is in fact not in x. And this is because none of these numbers are 5. Now, yes, this number includes 5, but it's not 5. As always, let's test out the other condition. Let's put a 5 in now, and let's see what happens. So now we do have a 5, so the values are 1, 2, 3, 4, 6, 55, and 5. So if 5 is in x, and look, it does, 5 is in x, because when it checked this first condition, it found this 5, it was true, and it tells you this. Now, I know these examples that I'm doing are kind of basic, where I'm just saying, like, is this in this? But you could do this for anything you want. For example, if you're looking at like odd numbers, like if this value is odd, and you don't just have to print out that it's odd. It could be something that if it's odd, do this operation. Else, let's say it's even, do this other operation, something like that. So on that note, what I would actually like everyone who's viewing this to do, as I always talk about, playing with, trying new things, try to figure out how to do things without looking it up. See if you can do these exercises. Write an if-else statement that checks if a number is even or odd. Write an if-else statement to check if a string is a palindrome. Or write an if-else statement that checks if a vector of numbers contains all unique values. And these are some interesting things because you have to kind of think about, what does it mean to be an even number? Well, anyone who's taken mathematics, especially anything with proofs, an even number can be defined as 2 times n, because no matter what value I put in there, as long as it's an integer, then it will be an even number. If I want an odd number, I could make it 2n plus 1 or 2n minus 1, and that will make it automatically an odd number. For something like a palindrome, you'd have to figure out how can you find something where it's the same going forward and backwards, stuff like that. Vector of number contain all unique numbers. You're looking in this case for anything that overlaps. Are there any values that are the same? And you could use something like is.unique or something like that to test this out. And you have to kind of think about how would you actually create this logic statement. And this is one of the big parts of programming that causes some difficulty, is you have to kind of think about how would you tell a computer, which is completely literal, to do what you want to do. And this is where things on a computer can be very different from how we think as humans. An example of this would be in machine learning, one of the easiest methods I can teach somebody would be something like k-nearest neighbor. It's a clustering algorithm that for a human is very easy to understand, but for a computer can be pretty computationally intensive to do, and you have to go through a lot of steps and iterate and stuff like that. It's not difficult, but it's just you have to kind of think in a very logical, okay, how do I do this? I got to check the distance from all these, take the 2, take the mean, stuff like that. There's a lot of steps you have to kind of consider, And you can do it with these sort of if-then conditions. For our next example, we're going to find the largest number in a vector. So this can be done using a while loop and an if-else statement. And the while loop will iterate over the vector, and the if-else statement will compare each number to the current largest number. Then the number that is larger will be the new largest number. So let's actually look at what this is doing. So first things first, we're going to set the object largest number to negative infinity. So if we look at this, we'll see that it is negative infinity. So right now we know that it's not larger than anything else. And then we're going to iterate over. So we have for number in vector. If number is greater than largest number, whatever it is then going to set this as the largest number. So largest number becomes that number. So this is just written in general form. So this isn't actually the example. This is just sort of like the logic behind it. So let's actually now do that example. We have largest number, negative infinity. I'm going to create a random set of data where I'm going to take the values 1 through 1 million, and I'm going to randomly select 10,000 of them with replacement. So if we look at our random data, you'll see that it's just a bunch of random numbers between 1 and a million. And there are overlaps. There will be things like that possibly, but I don't know what all these numbers are, right? There's 10,000 of them in here. So what I'm going to do is for number in random data, so I'm using my random data here, if the number is greater than the largest number we currently have, which currently, because we said it beforehand, is negative infinity, that is going to become the largest number. And then it's going to cycle through every one of these numbers and check it. Okay, this is the biggest number. Is this one bigger? Yes or no? If no, move on to the next one. Is this one bigger? Yes or no? If no, move on to the next one. If yes, this now becomes the new biggest number that things are compared to. And it's basically going to keep doing this until it gets to a point where you get the number where nothing else is bigger than it. So let's do that. So we have our for, and then we have our if. And then, of course, we don't really have an else here because we don't have this otherwise condition that we're including. So now let's see what our number is. And by the way, I have no idea what this is because this data is completely randomized. So our largest value is 999,955. So let's do another case. Now, if we look at largest number, you're going to see that it's that number we just did. So I'm going to reset it to negative infinity. I'm going to grab a new random sample, and now we're going to run this again. This time we got 999,961. Let's try it one more time. Okay, so we're getting a lot of really big numbers. I'm going to do just one more change just to make it a little bit more interesting. I want to see what happens if I just randomly pick, I don't know, 100 numbers. Okay, well, so we still got one in the 900,000s. Seems to be pretty common. 990,000. So, actually, you know what? Let's do one more thing. Let's change it to 10. Let's see if we can get something that's under the 900,000s. There we go, 730,680. Now, you will notice that I did put a note here. There's one problem with the way we currently have this set up, and that is this will fail if I had an empty vector. So suppose that instead of having random data, I'm going to put it as a numeric with nothing in it. So now if I look at my random data, you're going to see that it's an empty numeric vector. Change my largest thing. Now, when I run this, watch what's going to happen. It's going to tell me the largest number is negative infinity. And that's because what's happening is when I have this empty numeric vector, it is going to basically fail, and it's going to completely bypass this for statement, this if statement, and just jump straight to print largest number, which is using the default that I already had placed there. So this is kind of what I was talking about checking for edge cases, because there's going to be something, you're going to test it a bunch of times, it's going to seem like it works perfectly fine, but there could be somewhere that it does fail. So I want you thinking like statisticians, mathematicians, and also programmers trying to figure out where these might fail. So now what I'm going to do is I'm going to make a minor change in order to fix this. So first things first, I'm going to now have a new object called myVector, which I'm going to concatenate to -5, 12, 0, -14, 22, and 7. If I run this, this is going to be if length of my vector is equal to 0, then largest number is NA. So I added this if statement to begin with. If this is an empty vector, just put NA. Else, That is to say, if it's not an empty vector, then it's going to run the same thing. Largest number is my vector for 1, and then it's going to, for number in my vector, if number is greater than the largest number, then you're going to replace largest number with that number. Okay, let's try it out. So first things first, we have my vector, which is the concatenated values into one vector. We print out, and we get that our largest number in this vector is 22. Now let's run it again, though, where this time I have my vector is an empty vector. So right now, it's an empty numeric vector. If we run my if, else, and for loops, this is what we're going to get. NA. I've now added this if logic to find this case where it's if this is the case, just skip everything else, tell me it's NA. I don't have any numbers to actually test what is the largest number, so the output is not available. Just as a recap, this failed because the for loop had nothing to iterate over, so the entire loop block was just bypassed, and this caused it to move straight on to just printing our print statement, which was negative infinity. For our next example, we're going to find the first positive integer for which a condition is met. So suppose we want to find the smallest positive integer n, such that the sum of the integers from 1 to n is greater than 1,000. So what this means is we want to take all of the numbers and add them up. And we want to know what is the smallest n that if we add all of them up will be less than 1,000. So if we go 1 n bigger, we suddenly cross 1,000 when we sum it up. So the way we're going to do this, let's look at our code. We're going to start by setting our n equal to 1. We're going to have my sum, and we're going to set this to 0. Now with our loop, we have while my sum is less than or equal to 1,000, what we're going to do is we're going to execute my sum, and then we're going to add n to it. So right now my sum is 0. So 0 plus n, which is 1, this now becomes 1. We are then going to increase n by 1. So it becomes 1 plus 1 is 2. So n is now 2. We then look at 2. Is 2 less than or equal to 1,000? Yes. Then we go to my sum, which is going to be that my sum, which we said was equal to 1 currently, plus 2, that's 3, increase n by 1, and we're going to do this until we get to an n where it's no longer true that it's less than 1,000. Then we're going to print out the smallest number of n is with whatever that n is minus 1. So let's do it. Okay, so then this looks like the smallest number of n is 45. And if we look at my sum now, which should be adding all these values up from 1 to 45, you'll see that we actually went over 1,000. Okay, so quick correction I actually wanted to do on the spot. While doing this, I actually found that it was giving me a value that was 1 too high. And it's because, just like I was talking about earlier, my sort of programming logic got a little bit mixed up. So you'll see that I made one minor change to this. So I still start with it equals 1, and my sum is 0. And then what I'm doing is, again, while my sum is less than or equal to 1,000, I'm starting by incrementing n up by 1. Then I am taking the sum of those values. And it's because what was happening is that I was summing it up for n that was going to make it go too high. Then I was going up, then the logic was failing, where I had to increase it first. And what it was doing is was giving me the value n is 45, which if we sum it up would give us 1,035. Now it should work, where I'm going to get that n is equal to 44. Let's test it out. So what we can do now is we'll just do the sum of 1 through 44, and you'll see that we get 990. Whereas if I had the original 45, I would get 1,035. So even then, even though I understood the logic completely, you can see how these minor things can cause issues. And the only reason I found it is because I didn't just trust what the program gave me, I tested it. And this is exactly what I was talking about, is test extreme cases. Make sure the answers make sense. Because sometimes, even if you understand the logic, you can still mess it up with something minor like this by just putting the logical operations in the wrong order. For our next example, what we're going to do is we're going to generate a Fibonacci sequence. So the Fibonacci sequence is a series of numbers in which each number is the sum of the two preceding ones. Usually it's going to start with 0 and 1. Then we're going to generate our Fibonacci sequence up to a certain number while using a loop and if-else statement. Real quick fun fact, actually, before we do this example, if you actually read Fibonacci's original book, the Fibonacci sequence is only brought up like 1 or 2 times, and it's not even something that it focuses on a lot. It's actually a textbook that was written in order to help like merchants and stuff like that understand math and use a lot of examples. And the Fibonacci sequence came up as an example of rabbits propagating. And it wasn't like a big thing. It wasn't some big, grand proof he did, even though it's what he's known for. That's basically, it was a small singular problem as part of this entire work, and it became basically what his name is known for. But anyway, on that note, let's actually jump back into our problem. If we look at this, we're going to start by setting our value a to 0 and our value b to 1. If we look at our loop, we have while a is less than or equal to 100, we're going to print a. Then we're going to set up a temporary object, which is going to be a plus b. So we're going to add b to a. So it's going to be right now 0 plus 1. Then a will become b, and b will be replaced by temp. And then we're going to do this until a is, no longer less than or equal to 100. So let's do that. And you'll see that we get the values 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. Or let's say that we wanted to get the first, let's do it with under 1,000, less than or equal to 1,000. So we'll do the same thing. Let's start by, again, resetting our a and b, because right now they have something assigned to them, right? A is 144, b is 233. So we're going to set those back to 0 and 1. Let's run it again, now with a less than or equal to 1,000 as our condition. And we will get 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233, 337, 377, 610, and 987. I will point out this is not an overly robust while statement. And this is because if I started with different numbers or had different conditions, I could actually completely mess this up. For example, let's say that my a and b I didn't start as 0 and 1. It's not hard-coded in any way. I just knew to set this to do a Fibonacci sequence. So if you were to change a and b, this would completely fall apart. You could do some sort of if statement. If a is not equal to, 0, put in a. If b is not equal to 1, or else if b is not equal to 1, put in a. And then you could do your while loop based on that if you wanted to make it more robust so it didn't try to run if a and b weren't properly set. Because right now, if we look at a and b, right, there are different values. If I run my current while loop, it is just going to not work, right, because my a is too high. But let's say it was something different. I don't know, I'm going to start with like 2 and 3. Well, now it'll run, but it's not going to be a Fibonacci sequence because it didn't start with our original correct values. Okay, so next example we're going to be checking for prime numbers. So a prime number is just a natural number that's greater than 1 and has no positive divisors other than 1 and itself. So first of all, we're going to check if a number is prime while using a while loop and if-else statements. So let's jump to that. First thing I'm going to do, num is going to be 29. This is going to be the first value I'm going to test. I'm going to set I equal to 2. And I'm going to put is prime as the default is true. The way it's going to work is we have while I times I is less than or equal to whatever our number is, in this case 29. We are going to put an if statement. If the number, so we have this double percent sign is modulo, I is equal to 0. That means if I divide that number by I and it's equal to with a remainder of 0, then is prime is false. And then I have this break here because if it ends up that our value is not prime, we can just stop the operation right there. We don't have to iterate through every single possibility. If it doesn't end up being false here and break, then we go to I becomes I plus 1, and you go on to the next value. So let's try it out. Okay, and then, so we've done this. Now if is prime, we're going to print, paste, num is prime, else print, paste, num is not prime. So we've actually gone through our loop. We have a value. What we're going to do now is we're going to, so if I look at is prime, it's going to have a value either true or false. So 29 is in fact prime, so this still should be true. So if I do my if else statement, this will then just print out the answer. 29 is a prime number. What about if I did one that I know for a fact is not prime? Let's say 30. So I'm going to do all this again, do my while loop, and then 30 is not a prime number. Awesome. Now, here's where this is going to break down, though, because let's say that instead of 30, I tried 2. I know for a fact that 2 is prime number. It's the only even prime. So if I do this, I get 2 is in fact a prime number. Good. What about if I did something like 0, right? Because 0 is not a prime number, and it says 0 is a prime number. What about if I put a negative number? Let's do -2. So if I do -2, it will tell me that -2 is a prime number, right? So we're running into some issues here where this is great if you have a positive value that is greater than or equal to 2, it works great. But it is failing because it's not taking into account those edge cases. The edge cases being, what if it's 0? What if it's 1? What if it's negative? Things like that. So in this example, we started with the number equal to 29. I was equal to 2 and is prime was equal to true. In each iteration of the loop, what we did is we checked the number and see if it's divisible by I. If it is, we set is prime to false. Basically, we're going through the iterations of I. I is 1, I is 2, is it divisible? No. I is 3, is it divisible? I is 4, is it divisible? If any of those divide into it, meaning we have a remainder of 0, it breaks the loop, it becomes false. If it isn't, we increment I up by 1. Then this loop will continue until I times I is greater than that number. After the loop, we check the value of is prime, determine if it is in fact a prime number. Algorithms often work perfectly for typical inputs, just like we originally started with, like 29, but will fail at the mathematical boundaries. So by definition, a prime number must be a natural number strictly greater than 1. So if num is 1 or num is 0 or num is -5, for example, the loop condition I star I, so I times I, is less than or equal to num is false immediately. As soon as it checks that condition, right? -5 times -5 is it 0 times 0 is it less than or equal to none? It will fail immediately. This will cause the code to completely bypass the loop and it'll leave the is prime as true. This is why those statements that didn't make sense were giving us true, because when that condition failed, it instantly just skipped all of the code block with it. So in this case, what we want to do is we want to introduce an initial safety check using an if statement to instantly catch and classify any numbers that are less than or equal to 1 before the loop even runs. So let's do exactly that. First thing I'm going to do, I'm going to set num to 1. And then if we look at our code with the guardrail in place, we have if num is less than or equal to 1. Is prime is false. Else, that means that it's not less than or equal to 1. We can actually run the code we wanted to check for primes. I will set I to 2, is prime to true, and then we will run exactly what we did. Okay, so let's try it out. Right now we have num is equal to 1. So when I print this out, you're going to get 1 is not a prime number. What about if instead I put our number to -4? You'll see that -4 is not a prime number. Let's try 0. Zero is not a prime number. Okay, now let's test the cases where it should be prime. Let's go back to what we originally had. Let's put our 29 back. 29 is prime. Okay, so now it seems to be working because what we did is we put these guardrails in ahead of time to check for those edge cases we found. Eliminate them because we'll check those first. If our number is less than or equal to 1, just automatically we know it's going to fail, bypass all of this and change it to false. Otherwise, now go through the actual condition of checking whether each iteration of values multiplies to give you a remainder of 0 with this number you have. If none of them do, then it means that it's prime. So with this concluded, you basically have most of the tools you are going to want in your toolkit as an early programmer. There's still one more big thing that we have to cover, which is functions, which is going to be a big one, and it's a big part of programming. In fact, I talked about it a little bit in my clean code part about never writing the same thing twice. If there's things that you are doing often, you want to create a function of. In fact, R is built on functions. Every time you're using something with the parentheses, that's a function. You want to find the mean and parentheses, that's a function that was built for R. You want to find the median, you want to find the standard deviation, you want to take the square root. Those are all functions that do a certain operation. And the next thing we're going to look at is we're going to look at how do we create those. And once you have these loops, for statements, if, else, and functions, you can build almost anything given enough time and thought about what you're trying to do. Hello everyone. In today's lesson, we're going to be going over functions. This is going to be the last topic we're really going to be focusing on for this course, where we're focusing more on the programming aspects and R than we are in the actual statistics. So we've kind of covered a few little statistical things here and there, but we've mostly been focusing purely on how to program, how to implement things in R, how to do loops, things like that, and then we'll do functions. Following that, we're going to be transitioning over to a more statistical focus of how to do things like confidence intervals, hypothesis testing, ANOVA, things like that. Functions are a fundamental concept in programming languages, including R. These are things that you will use in any programming language you decide to use. So if you focus on Python, you also will be implementing functions. If you go into C or go into even like Pascal, for example, you likely will be using functions. Function is just a block of code that performs a specific task and can be reused throughout a program. Remember when I brought up in the clean code kind of section about not repeating yourself? This is a big part of it. They can be reused. So the beautiful thing about a function is you can create it one time and call on it over and over and over again. In fact, you've been using functions in R already. Anytime you do some, function where you have like the parentheses afterwards and you have your arguments, which can either be named or not named, they're positional, you're using a function that somebody created and they added to the base R programming language. So in this lesson, we're going to explore the basics of functions in R, including creation of functions, calling on functions, and some advanced uses of those functions. So as always, let's first start by looking at our basic syntax. A function is just a named sequence of statements that take a set of input values or arguments and returns a single value or a set of values. Functions are an essential building block in R, and they help make your code more modular, reusable, and also efficient. So if we look at our actual syntax here, you can see that I have function underscore name. So whatever your function is named. This is, again, callback to the naming conventions where I talked about clean code. This is something you want to have a name that would make it understandable, right? For example, it might be something like average underscore values or numbers. It might be something like take underscore average, things like that. Something where if I looked at the name, I would have an idea of what this function is doing from the get-go. To actually create your function, you will use the function. So you'll use function, and then you'll be parentheses. Within those parentheses, you will put each of your arguments. So you see arg1, comma, arg2, comma, arg3. This is where you are designating what the user is expected to input. And this is where you can actually determine if you have named arguments or if it's just positional, and also if there are any defaults. Once you've closed your parentheses, you open curly bracket, just like before. If I hit open curly bracket, hit enter, it will automatically create a blank line where I can start putting my instructions and then the close curly bracket below. In that blank space in between, this is where you want to put the body of your function. This is what it does. Now, one thing I will kind of mention beforehand as we kind of get into functions though, is a lot of times students will start doing functions and they won't get the output that they're expecting. What's happening is that it'll do the operation, but if you don't explicitly tell it to do something, it's not going to. For example, in this one I have return parentheses value. And that's because once it's run, whatever operation I put within this, I need to tell it to one of its functionalities is to actually return or print or concatenate or whatever other command the value that I want to actually see. So to define a function in R, we're going to use the function keyword followed by a set of parentheses, which may contain our arguments. The body of the function is enclosed in our curly brackets, and I have a very basic function to begin with. It's just my function is what we're going to call it, right? Because this is just throwaway code. We're just doing it for an example. We're going to do our arrow operator, and then it's going to be function A, comma, B. So what's saying is we have two arguments that we are going to need for this function to work. We need A and we need B. Then within the curly brackets, this is going to be what it does. It is going to return A plus B. So A plus B means you're just going to add whatever A is and whatever B is, and then return means print it out. So let's actually try that out. So you can see my function here in R. Watch what happens when I hit this. When I run this, nothing seems to run. But if you look at the top right in my global variables, you will see my underscore function. And it just says the function of A and B. This is because I've created this function, but now I have to actually call on it. And the way you call on it is with that name you gave it, my underscore function. So I'm gonna do my underscore function. I'm going to input my two arguments, A, which is gonna be 2, and B, which is gonna be 3. And if I do this, what it's going to do is it's going to return A plus B. So it's gonna do 2 plus 3 is 5, and it's gonna return that value to me. And you'll see that we get the value 5. If we were to change this, let's say we do 4 and 3. If I do my function 4 and 3, all it's doing is it's just adding these two values up. If I wanted to edit this, let's say that I wanted to add another number. I'm going to have C. Then what I could do is something like A plus B minus C. Just clean it up a little bit. Again, I'm going to run my function. Now, if I try to run this, you'll see that I'm missing my C. I need this extra argument. So I'm going to make this 2. So what it's going to do is it's going to do 4 plus 3 is 7, minus 2, and I'm going to get 5. And there you go. For the example I just did, it works perfectly fine. The problem, though, is that if I were to go back to this, an hour later, 3 days later, a year from now, I'm going to actually have to go through and try to find what this function is because it is not named anything very useful. It's just called my function. And while I can look at it right here easily and kind of determine what it does, because it's a very simple function, it just returns A plus B minus C. If I have a lot of code and I don't know exactly where the function is, I have to go find it, all this kind of stuff. An easier way to do this would just be give it a name that makes sense. So I've actually redone the exact same thing, except for this one I'm calling on X and Y, and I've called it add numbers. So we have add numbers, and we have our arrow operator, so it means this is defined as a function of X and Y. So what's with the function? So open curly bracket, this is going to be what it's going to do. Now I'm going to actually do it in a two-step process. Instead of returning, A plus B, what I'm going to do is I'm actually first going to create a new object called total, where it is going to be X plus Y. And then I'm going to return total. So let's do that. So now we have our new function, add numbers. We go to the top right here, we can see add numbers, it's a function of X and Y. So that means that if I want to actually figure out to use this function, I need to input an X and I need to input a Y. So we're going to do result is going to be add numbers 3 and 5, and I'm just going to put result here, so we'll run it at the same time, and you will see that we get 8. There's not really a lot of difference here. There's only 2 minor things that I changed. The first was I split up the functions what the actual function is doing, and this is because sometimes I actually like to do it in a more logical order. Take these 2 numbers, add them together, label it as something here. Now return that. That way, if I run into an error, it's a little easier to find. But also it's because within that function, if I wanted to expand on this, I can call on total and I could do something with that. I could say total is X plus Y, and then squared is, take whatever total it is and square it, and then I can return the square or something like that. So let's actually do that real quick. Squared is going to be total, and we'll just do a square, and then we'll do return squared. And now you're going to see that we got 64 because it took 3 and 5. It added those two together to give me 8. And then the second part of my function was that it squared it and then it returned that value. This is actually really useful, this return. And you kind of have to think about the flow and order of things, kind of going back to loops. Because remember how I told you could have like nested loops? Well, guess what? You can have loops nested within functions as well. And this means that if you're going to be returning values, you need to consider the order that it's doing. Do you want it to go and do a loop and then return the value and then go to the next step of the loop? Or do you want it to go through the loop and go through every single step and then return afterwards? And this would actually change how you were going to set up this function. What about if we wanted to create a function that calculates the area of a rectangle? So we know that if we want to find an area of a rectangle, it's just going to be base times height, or length times width, however you want to consider it. So what we're going to do is we're going to call this function area underscore rectangle. So that way, if I see this function, I know that it is the area of a rectangle. It's going to be a function of length and width. And then it's going to be area is length times width. And then I'm just going to return that area. So let's run that real quick. And next we're going to do is we're going to say, okay, what is the area of a rectangle that is a length of 4 and a width of 6? And we're going to get, oops, forgot to output, we're going to get an area of 24. And if I change this, right, let's say that I change this to 7 and 6, it will automatically update. So I don't have to go and change my code every single time. All I have to do is change the inputs, changing the arguments. The reason this can be very useful is because, again, these are very simple examples, but if you have a much more complex set of operations that you're doing, all you have to do is go and change those arguments and make the call. Looking back again at our function, you can see right here, area rectangle, it's a function of length and width. This is where you can see what are the different arguments that you would use within your function. As I mentioned a little while ago, you can also use functions with for loops. So functions can be used with loops to perform repetitive tasks. For example, let's say we want to create a function that takes a vector of numbers and returns their squares. So in this case, what we have is we have a function called square vector. So it's a function of x. All we need is whatever that x is. In this case, it's a vector. It could be an integer or a real number, something like that as well. So we're going to have, within the function, I have result is an empty vector, C, and then parentheses, which means I'm basically setting result as empty. I'm doing this because that way, whenever I run this function, it will go through each time and it will wipe whatever was there, and it will then go to the next thing. So then after it's done this, what it's going to do for my instructions is for I in x, so whatever these values are, I am going to get the result, which is going to be concatenate the result that I currently have and I squared, whatever index I'm on in my for loop. Once this is done, it will then return the result. And notice that kind of how the ordering is on this. So I have it where it starts by wiping result, so there's nothing there. Then in my for loop, I am assigning result as the first one is going to be, there's nothing there, I squared, so 1 squared. Then it's going to go to 2. So this is going to be result, which is just currently 1, and 2 squared, so 4. And then it's going to do this through each of them through x. And then once this loop is done, notice that the loop open and closes. The next line of the function is return the result. So let's try it out. So we're going to use our square vector. And now let's actually put a vector within that. So our square vector function, we are going to apply that to the vector, which is 1, 2, 3, 4, 5. So we do it, and we are going to get the output 1, 4, 9, 16, 25. And now I know I did this in order here, but there's nothing to say you have to do this. You could have some other vector. Let's say we have like another 3. Oops. Let's say we have a 12 in here also. Okay. Now we can do the same thing, square vector, and it will automatically square every single value within that vector. And this is where, again, that can be very useful, because if you write it in sort of a general form where you're not actually hard coding things in, I can now enter as many values as I want in the vector. I could do decimals. I could do something like 0.6. And in this case, I get my last value is 0.36. Now, I do want to point out that the output made all the values decimals. This is because, remember we talked about coercion, a vector has to be all of the same thing. So instead of being integers now it's giving us those floating point numbers or numeric values we talked about previously. Another example we have using a for loop. In this case, we have sum underscored squared. So sum squared is going to be my function, and it's going to be a function of n. Okay, so n, and then I'm going to take sum of squares, and or sum sq. This is going to be assigned to 0. Then I'm going to have my for loop for I in 1 to n. It is going to take sum sq, and it's going to take that value plus I squared. And this is just the same thing we just did, but now what it's going to do is I'm just going to put one value in, and this is going to go through the sequence of 1 to that. So in fact, if I think the original example I did last time was 5 originally, I could put 5, and this would automatically give me the sum of the squares of 1, 2, 3, 4, and 5. So let's try it out. So we have sum squared, it's function of n. And then what I'm going to do is I am just going to put in the value 1. So I get 30, because what it's doing is it's taking 1 squared plus 2 squared plus 3 squared plus 4 squared, and it's adding them all together. So if I want to know what are the first, let's say the values 1 through 12 squared, I can just put sum squared 12, and I will get 650. If I want to know what the first 127 squared values are, I get 690,880. And this is kind of like the beauty of functions. Once you've set it up, as long as it's set up well, you can just change your argument in it and run it, right? This is what you're doing. Every time you're using R and you run a mean, you're doing this. Somebody made a function that added up the numbers and divided by the length of n, right? You could easily do that by just doing something like this. You could just say sum of whatever your x value is divided, or whatever the values are in your x's, divided by length of x. And then if you were to run that, right, so x doesn't exist, but let's say x is just going to be, I don't know, we'll just do sample. I'm going to do 10 values, 1 to 50, without replacement. Okay, oops. I always do this. I always do it backwards. 1 to 50, and we're going to pick 10 of those. Okay. Now right there, I've got the mean of these numbers. And all I'd have to do is I just put that into a function. And that way, whatever x values I put into my function, it automatically does the mean. Easy. Another useful thing that functions can be used for is doing the stuff like we've talked about previously, like simulating data. For example, functions can also be used to simulate data. For example, let's say we want to simulate a vector of 100 random numbers drawn from a normal distribution with a mean of 10 and a standard deviation 2. So in order to do that, all we have to do is we're going to simulate data. That's going to be our function, and it's going to be a function of, now notice I don't have an argument in here. That's because in this one, you're not inputting anything. What it's going to do is it's automatically just going to run whatever it's told to run, and that's it. So we have our set our seed 1, 2, 3, 4, and then it's just going to do our norm, which you remember is going to draw some number, in this case 100 values, from from a normal distribution with a mean in this case of 10 and a standard deviation of 2. So if we run this, now if I actually run this function, notice how I wrote it. I wrote simulate underscore data, open parentheses, close parentheses, but nothing in it, because this one doesn't have any arguments. It just runs it and it randomly picks 100 numbers from a normal distribution with a mean of 10, a standard deviation 2. If I run it again, I'll get, in this case, the same numbers because I set the seed. Let's say that we got rid of the seed. Now you're going to see each time I do this, I'm getting new random 100 data points. And this can be useful if you have some sort of experiment you're doing where you know you're going to constantly have to pull in data of some sort. You can set it to simulate it, and either with or without arguments, depending on whatever the case is that you're looking at. If you didn't want to have it hard-coded in for a particular normal distribution, we can do that too. So in this case, what I did is I have it simulate data. It's going to be a function of n, mean, and SD, which is kind of what it already would be if I'm doing the mean or our norm. So data, which I actually should change this to my data, because remember we talked about not coding in things will cause masking. But for now, I'm just going to leave it. Data is going to be our norm made up of n, mean, and standard deviation. And then I'm just going to return that data. And I can change any of these I want. In fact, you know what? Let's change it right now. Let's change it on the spot. This is going to be n. We're going to call this mean1, SD1. Then I can do my data, which I'm going to call my data, is going to be our norm based on mean1, SD1, and we will return my data. Okay, so now what I'm going to do is my simulated data is going to be made up of, I'm going to use so notice it's simulated data. It's the data we've actually simulated. I'm going to use my function, simulate data, and I'm going to tell it to give me 100 data points with a mean of 50 and a standard deviation of 10. So if I run this, print out the results, I get my 100 data points. The nice thing about this one, though, is because nothing is hard-coded in, if I said that instead I wanted 1,000 data points, done. Now I have 1,000 data points. If I said, oh, actually, you know what? My mean was actually 72, and my standard deviation was 11. Guess what? I can do it. It's because the arguments are already there. And just like before, because these are named arguments, I can treat it just like the functions you've looked at previously. Meaning I could do SD1 is equal to 11, and mean is equal to 72, and it will still work just like we did it before. In fact, I'm actually going to do something. I'm going to show you by changing n, because that'll be the most noticeable. I'm going to put n at the end. N equals 5. And you'll see I only got 5 data points. So even though I changed the order, when I made that function, whenever I put the names as for the arguments, those are the names. And you can use them for your arguments just like you did before. You can use positional. So the first one is n, second position is mean, third position is standard deviation. Or I could call them by name. N for how many, mean 1 for the mean, and SD1 for the standard deviation. Okay, this example, making just a little bit more advanced, we're actually going to call on another package, the Doppler package, and what we're going to do is we're going to use that to implement the select command. So we're going to have select columns. It's going to be a function of data and calls for our columns. So what does our function actually do? Well, it's going to actually name an object selected data. I'm going to take my data. I'm going to use the pipe operator to select just calls. And then I'm going to return the selected data. So what this means is that it's going to go into my data, which is going to be a data frame. And then I'm just going to select that column. So let's look at that real quick. First things first, let me load my package. Let's run our function. Now let's look at our data. Our data is going to be a data frame for, the values are going to be 1 to 5 for A, 6 to 10 for B, and 11 to 15 for C. So if I look at my data, this is what it looks like. Okay. Now what it's going to do is my result is going to be, I'm going to select columns, which is that function we just made for our data, and I want to only select the columns A and C. So I'll do that, print the results, and it gives me A and C. So you can actually use packages from R within your functions. You can call on them just like anything else. What about if I wanted to make a function that models some data? So functions can also be used for modeling. For example, let's say we want to create a function that fits a linear regression model to a data set. So what we're going to do for this one is we have fit model. That's going to be our function, and it's going to be a function of data. So whatever our data is, this is going to be the placeholder for it. This function is going to be, we're going to use model, which again, not my favorite name, but model. It's going to take the object model and is going to assign it as LM, which is a linear model, which we will have a lesson on later on, where Y is modeled by X, and then our data is equal to data, whatever we put within this, which again is why usually we don't want to use the term data. It might be something like my data, because data is something that is actually a function within functions a lot of times, and we're setting data equals data. It'd almost be better to call this my data, and then data equals my data. That would make the code a little bit better. Okay, so now what we're going to do is we're going to make our my data, which is just going to be a data frame made up of X is 1, 2, 3, 4, 5, Y is just 2, 4, 6, 8, 10. So if we look at our data real quick, now what we're going to do is we're going to model our data. And it actually looks like I forgot to update this real quick. So my data, sorry about that. And now we have our model. So if we were to look at this, now you can see we have our model with our y-intercept and also our beta value. If I do summary, it's going to give us a better understanding of our intercept and our x value. It's going to give our standard error, t value, our p value for this model. And then we'll talk more about that when we get to modeling. It's going to give us our r squared value, multiple r squared, f statistical, all that. And notice that it also gives us a warning message. In summary, LM model, essentially perfect fit. Summary may be unreliable. And this is because this is made up data. But it does perfectly match, right? Because 1 goes to 2, 2 goes to 4, 3 goes to 6. Each of them just goes to 2x, whatever the value is. So yeah, it does perfectly match. But if you had like some random data and it perfectly matched, that would honestly, for me, a lot of times be a red flag. Now for our next example, I actually have a really big function made up of actually showing up on multiple slides. And I wanted to show you this because I wanted to show that you can actually put a lot within a function. It is advisable generally to have smaller, more modular functions, but I just wanted to show this as an example of kind of combining a bunch of stuff. It could do a lot of steps at one time. So you have this function, whenever I get my data, it's going to go in, it's going to do this, it's going to do this, it's this, this, this. And you can almost set up like a process where it goes through all these different steps. And I will talk about each of these, but I'm going to talk about them in R. You'll see that we have second slide and we have the third slide with what each one does. So let's look at our code. So first thing, what I'm going to do is I'm going to load ggplot because that's something we're going to be using. So our function is called simulate and analyze. It is going to be a function where we are going to need n, we're going to need a mean equals 0, SD equals 1. So now what's different about this one? Well, before I put n, mean, and SD. But notice that now I have this equals 0 equals 1. This is how you set a default, meaning that if I don't put mean, it's automatically going to be 0. If I don't put a standard deviation, it's automatically going to be 1. So all I actually have to put is n. But I can put a mean and standard deviation I want, or I can put one or the other, right? And I have names, so if I just want to do like n and standard deviation, I can do n comma SD equals, and then put whatever I want the standard deviation to be. So what does the function actually do? Well, first things first, it's going to simulate some data. Based on my n, we're going to get our x is going to be just the sequence 1 through n. So if I put n as 9, it's going to do 1, 2, 3, 4, 5, 6, 7, 8, 9. Y is going to be, it's going to use our norm, so it's going to take n data points. So again, if n is 9, it's going to get n data points, 9 data points from whatever my mean is and whatever my standard deviation is from a normal distribution, and it's going to select those. Then I'm going to create data, which is going to be a data frame made up of x values for my first column, those y values for my second column. Once that's done, it's going to calculate the mean of y. It's going to calculate the median of y. It's going to find the standard deviation of y. Then it is going to create a linear model where y is modeled by x, and our data is this data. Once that's done that, it is going to use ggplot to create a plot. So we're going to ggplot, take our data, we're going to use aesthetic, which is x and y. We're going to do geom points, it's going to be a scatter plot. We're then going to have geom smooth, so it's going to put our regression line with method of LM for linear model. And then it's going to be color blue. I'm going to title it scatter plot with linear model. X is going to be, X label is going to be X, Y label is going to be Y, and it's going to be a minimal theme. Then I'm going to print those summary statistics that I calculated earlier. So it's going to print out mean, and then it's going to put whatever the value mean Y is. Second part, it's going to say median. It's going to put whatever the value for median Y is. Third one, standard deviation, and it's going to put whatever the standard deviation of Y is. Linear model summary, and then it's going to print that summary of my linear model. And then last thing it's going to do is going to return that plot that I created, right? Because notice the ggplot, I assigned it to plot. I didn't actually tell it to print the plot. Now I'm going to tell it to return that after it's done every other step. So let's do it. So this whole function does a whole lot of things. Oops. Okay, so now we have our function. We're going to have our result, which is going to be simulate and analyze 50. This means that we're going to get 50 data points for our data. Standard mean is going to be equal to 0. Standard deviation is going to be equal to 1. So let's run it, and we're going to print out our results. Okay, so in this case, if you kind of look at our function, we got our mean, we got our median, we got our standard deviation, we got our linear model here, and then we've got our plot. If I changed this, let's say that instead of doing just 50, I wanted to actually change the mean and standard deviation. Then I could go, and I don't have to put mean, I can do it positionally, but I'm doing it just so it's more readable. I'm going to do a mean of, 16 and a standard deviation of, let's do 1.7. So I'm going to simulate that, and I'm going to print my result. And now you can see that we got our new scatter plot, and we got our new mean, median, standard deviation, and our summary of our linear model. When you're using functions, you do need to consider that a function is actually acting as what's called a sandbox. So when you call a function, R does not execute the code directly in the visible workspace. Instead, what it does, it spins up a completely isolated temporary, you can think of it like a memory bubble called a local environment. These variables created inside this local environment are completely invisible to your primary global environment. Then this local environment can look out and read global variables, but your global workspace cannot read those local variables. So what does this mean? This means that, remember before our function, I would do some command where I'd say something like, here's my data, run the function. That function can call on that data. But whatever I'm doing up here, I can't call on something within that function. So this is actually for a couple reasons. One, for clean garbage collection. The millisecond a function reaches its closing curly bracket, what's going to happen is that entire local temporary sandbox is going to go away. It's going to be deleted from the RAM, and it's no longer going to exist. Why does it do this? This helps prevent your primary workspace from becoming cluttered with thousands of temporary immediate calculation variables, and we also, when running complex, simulations, simulation loops, stuff like that, and also partially for memory management. It's because as we're building out these functions, you're just going to build up all this garbage, but what it does when you finish with the function, it wipes it all. So it's not keeping a bunch of stuff stored there like it would if it was a global variable. So let's actually look at a quick example of just that. So here, what I'm going to do is I'm first going to set a global variable called threshold. So threshold is 10. Now we're going to create a function called evaluate data, and it's going to be a function on x. And then what it's going to do is it's going to do this temporary calculation. It's going to be x, whatever that is, times 2. So it's just going to multiply it by 2. Then it's going to update temp calculation. We're going to check whether temp calculation is greater than threshold. That's it. So let's do it. Now we're going to evaluate our data, and we're going to use the value 6. So 6, we're going to look at our temp calculation, times 2 is 12. Is 12 greater than our threshold? Yes, so we should get a logical statement of true. And we do. The next one, what we want to do is we're going to try to print that temporary calculation. Right here, we're going to try to print this out right now. Notice what's going to happen. We're going to get object temp underscore calculation not found. And it's because if you look at all of the global variables that we have, temp calculation is not in here. It is only in existence when the function is running. When the function spools up, it will run through the instructions. As soon as it is done and that curly, we have that closing curly bracket, it wipes all of it. So when I'm doing evaluate data 6, it is specifically running the function for that, wiping the results. If I do it for another value, let's say instead I do 2. Well, 2 times 2 is 4. It should get a false logical answer, and we get false. But again, there's nothing left there once the function is done running. So functions in R can accept arguments just like we've been doing in this class so far. These are just values that are passed to the function when it's called. There are 2 types of arguments in R. There's positional arguments and there are named arguments. Of course, I've already talked about this a little bit, but when you create your function, you are deciding the order. So when I did n, mean, sd, that is the order. It is also the names. N is the first one, mean is the second one, sd is the third one. There's nothing to say it has to be in that order, though. I could have just as easily made a function where I have sd in mean, or sd mean n, or n sd mean, whatever I want to do. In that case, that tells what order I put them in, right? So think about, like, for example, when you do question mark R norm, something like this. We have R norm, n, mean equals 0, sd equals 1. This is the order. This is position 1, this is position 2, this is position 3. They are also named, meaning n equals gives me whatever n is. Mean equals, and I can set a value there. SD equals, I can set a value there, and if I use the names, I can put them in any order I want. The reason this might be useful, it'll make more sense when you actually start doing more programming, but it is very useful. And then finally, if I want defaults, I can just set those named arguments equal to something, much like this. This is literally all this mean function is. It is a function that somebody created where it calculates the mean. They set a named variable n, which is how many data points you have, or how many data points you want. You've got the mean, which is by default 0, and the standard deviation, which is by default 1. So then going back to our square vector example, we have square vector n. This is going to be a function of x and n. So what we're going to do is we're going to take the result. It's going to be an empty vector. We're going to then, for I in 1 to n, it's just going to take the result and add in the square of the next index. So the first one, it's an empty vector, so you get 1 squared is 1, puts that in the result. Then second index is 2. 2 squared is 4. Puts that in the result. And it's going to do this until it gets through all of this sequence 1 through n. And then it's just going to return the result. So we do that. And then we can do square vector n. And notice that we have 2 different things here. We have this concatenated vector, 1, 2, 3, 4, 5. That is our x. And then n is 3. It's going to tell us how many of these do we want. So if I just changed this to 4, it's going to do the first 4. If I change it to 5, it's going to do the first 5. What happens if I change it to 6? It's going to get an NA because I only had those 5 values. But notice how it worked is that I have these just by order. I didn't have to put something equals to something. I'm using positional arguments. Similarly, I could use named arguments. Something like if I have this, simulate data params, I've got a function in mean equals 0, SD equals 1. What it's going to do is I have set the seed, R norm, in mean equals mean, SD equals SD. Again, not the best naming convention, but it's fine. In this case, I can run my function by calling on them n equals, mean equals, SD equals. And if I do that, it will do exactly what I want. If I go and I change this though, because they are named, I don't have to rely on position. SD equals 2. So if I run this, notice that I get the exact same values, right? My last value, 14.242234. My last value, 14.242234. And this is because I set a seed. If I hadn't set the seed, then it would be random based on whatever distribution I'm using. You can actually use a little bit of both positional and named. So for example, for the first one, I'm going to get rid of the n equals. And what's going to happen, so notice that it's n is the first position. I've switched the position of the second two. So let's see what happens. We get the exact same thing. Now, one thing I also want to talk about briefly is returning values. Functions in R can return values using the return keyword. A function can return one or more values, which can be of any data type. For example, let's modify our fit model function to return both the model object and the coefficients of the data. So we're going to do just that. We're going to go back to our fit model coefs. And this one I actually had to create some data. This isn't in the slide, but we have our fit model coefs. So for coefficients, it's going to be a function of df underscore input. That's going to be our data frame input. And what it's going to do is going to make a model. So model, which is a linear model where y is modeled by x, data is df input. Coefs is going to be coef, but notice it was 1f. That's actually the command to get the coefficients of our model. And then it's going to return a list of our model and our coefficients. So we do that. Okay, let's actually create some data. We have our x values. There's going to be a sequence of 1 to 10 with a length of 15. So you'll see that we got some data points here. Then our y values are going to be 3 plus 2 times our x values plus our norm, where we're going to get 15 data points with a mean of 0 and a standard deviation of 1.5. And then we're going to put it together into a data frame. So we're going to have my underscore experiment is data.frame. We're going to take our x values and our y values. So looking at our data frame now, we have our x values and our y values. Let's run our updated function. And what we're going to do is result is going to be, we're going to take fit underscore model underscore coefs, that's our function, on our data that we did here. Okay, so if I were to look at result, you're going to see that it's going to call on this function, it's going to put the model, and it's also going to list out the functions because we told it to return both the model and the coefficients. This means that if I look at result, names, result, you're going to see that there are two named entities, model and coefficients. Meaning if I wanted to call on a specific one, I could use result money sign model, and this will just give me the model. Or I could do result money sign coefs, and this will give me just the coefficients. So hopefully from kind of going through this lesson, I know we only just kind of scratched the surface, and a lot of this is going to involve you playing with stuff, but functions really are a powerful and essential tool in programming, and specifically in this case, programming with R. We covered some basic things like defining, calling, and returning values from functions, as well as things like using for loops, simulating data, the select command, and also basic modeling. But honestly, of all the things we cover in the course, this is the one that students struggle with the most. I really do highly recommend that you go in and try to create things with functions. Try to recreate functions that you find in R already. See if you can create your own function that does the same thing, right? Because you're implementing these all the time. Can you make them yourself with your knowledge of statistics and your knowledge of programming? One more thing I want to show you is if you do the edit command, you can actually pull up functions and things within R. Specifically, I will say it doesn't work so well with the base R. It does work very well with packages. And the reason is, let's say we do something like this. Let's do edit mean. All it's going to do is going to tell you it's a function of X and other stuff. It's going to use method mean because it's already kind of built in. So you can't really see the function. But if we did it on our function, edit fit underscore model underscore coefs, which is going to be this one, watch what's going to happen. It's going to pull up the exact function that we're using whenever we are calling on this function. You can actually edit here and change it. Why is this important? Well, because when you're learning about functions, go grab like another package and try doing edit on its functions. See if you can understand what it's doing. Let's say something like edit ggplot. Okay, and this one, again, still not telling us much because it's telling us uses ggplot. So, but some packages you find what other people did, it will have it more accessible where you can actually see it, edit, and look at the underlying functions that they're using. And you're going to see that they're a lot like yours. So now that we've covered all of this from starting with R up to using functions within R, loops, functions, everything like that. We've covered all of the main programming topics we're going to be doing, and now it's going to be time, starting on our next lesson, to dive into actually applying this to statistical concepts. Hello everyone. In today's lesson, we're going to be looking at confidence intervals and how to implement them in R. But before we do that, let's actually talk a little bit about confidence interval. So what is a confidence interval? Well, the definition is that a confidence interval is a range of values derived from a data set that's used to estimate an unknown population parameter. That is to say something like population mean, population proportion, things like that. The confidence level will usually be expressed as a percentage or a decimal. I generally am going to focus on doing decimals, and it represents the probability that an interval contains the true proportion parameter. So what does this actually mean? It means that if we had a 95% confidence interval, this would be as if we repeated our sampling process infinitely many times and calculate an interval from each sample. Approximately 95% of those calculated intervals should contain our true population parameter. Now, what confidence level do we use? Well, typically, the gold standard is that we're going to use 95% confidence level, meaning that we're 95% confident that the true proportion parameter will lie within our interval. Other commonly used confidence levels are 0.90 or 0.99 or 90% or 99%. One thing I kind of want to clarify here, and this is where the language is kind of misleading when a lot of people are learning about confidence intervals. We say that we are 95% confident that any interval we make will include the true parameter. But realistically, the true parameter is either in the interval or it's not in the interval with either a 0 or 100%. But the problem is, because we don't actually know what that population parameter is, what we're doing is we're saying that if I were to get this confidence interval and then take another sample and create a confidence interval and repeat this infinitely many times, then 95% of them should include that population parameter. So therefore, I can be 95% confident that any specific interval that I made would contain it. But obviously the truth is it either does or does not. But I don't know that because I have no idea what the actual parameter is. So this image is kind of give an idea of what I'm talking about. Each of these lines on this graph represent a different confidence interval. And you'll notice that we have some that are kind of to the left, some to the right, some that are kind of centered. But then we have these red confidence intervals, which these are the ones that do not include our population parameter. That middle line that you see, that is the actual parameter. So in this case, it would be 10. This means that if I were to just randomly go out and gather some data and do a confidence interval, I would be 95% sure that whatever interval I made would include this population parameter of 10. It doesn't necessarily mean that it will, though, because 5% of the time I would create an interval that doesn't. This is, of course, one of the issues with kind of trying to understand a confidence interval is that you still have that chance that you got the 5%, right? Just because of randomness, you may have gotten one of those red ones if you ran your one confidence interval. But confidence intervals do actually give us a lot more information because unlike a point estimate, let's say we're focusing on mean x bar. Unlike the point estimate, which is just a single value, now I have a range of values based on the other information, the standard deviation, things like that. But I still don't lose that point estimate when I have my interval because what I can do is I can take the average of those two values, my lower bound and my upper bound, and I will get that middle value, which is my starting point, the point estimate. So when we're doing a confidence interval, we do have to have a couple more definitions that we need to keep in mind. The first is sampling distribution. So this is the distribution of a sample statistic. This would be something like our mean from multiple samples drawn from the same population. So if we were to take all possible samples of a specific size n, and we were to find the mean of them, if we created a distribution of those samples, this would be a distribution of sample means of sample size n. Our central limit theorem, CLT, states that if we have a large enough sample size, the sampling distribution of a sample mean approaches a normal distribution regardless of its underlying population distribution. This means that, remember, our central limit theorem, we have two parts. If we know it comes from a normal population, then we can assume that the distribution of sample means will also follow a normal distribution. If it is not known to come from a normal distribution, the second part says that if we have sufficiently large sample, regardless of that underlying population distribution, if we have a large enough sample, it also will follow a normal distribution. The standard error is the standard deviation of our sampling distribution. What this means is that it measures the variability of our sample statistic. And this standard error will be dependent on what we're actually measuring. What's our sample statistic? For example, if we're doing a distribution of sample means, so X bar, or an X bar distribution, this means that our standard error would be our standard deviation, sigma or S, divided by our square root of n. That's where whenever we're doing our Z transformation, we divide by sigma divided by square root of n, or S divided by square root of n. That's the standard error for a distribution of sample means. We also may use the student's t-distribution. So the t-distribution, also known as student's t-distribution, is a family of continuous probability distributions that arises when estimating the mean of a normally distributed population in situations where the sample size is small. The population standard deviation is unknown. Because if we have the population standard deviation being sigma, then we can assume that this comes from a normal population. The t-distribution is bell-shaped and symmetric around zero, just like a standard normal, except it has fatter tails and a shallower peak, right? Because by having the fatter tails, meaning higher probability on the extremes, but we know that the area under the curve must remain 1. So if we're extending the probabilities to the end, that means the probabilities in the center have to come down. The larger your sample size is for your data, that means you have higher degrees of freedom for that student t-distribution, which is n-1 degrees of freedom, the closer it will get to a standard normal. So if I have a low degrees of freedom, let's say 5, it would have much fatter tails and a shallower peak. As n gets bigger, so we have n of 30, 50, 1,000, it is going to get closer and closer and closer to being that normal distribution that we're so fond of using. In our intro classes, generally what we'll use is n is greater than or equal to 30 will be a large enough sample size to assume that it follows a standard normal. That being said, if you're dealing with real data, you oftentimes will want to do a check, something like a QQ plot, Shapiro-Wilk test, something like that, to test whether it appears to be normally distributed. And the reason is because even though we have the central limit theorem says we have sufficiently large sample size, sufficiently large isn't some set threshold like we teach in class. This means that you would actually need to test, because if you have highly skewed data, you would need a much bigger sample for this to actually happen. Now, one of the effects of using a student t-distribution is that it actually will give you more conservative estimates for your smaller sample size. And just a fun little fact about the student t-distribution, the reason it's called the student t-distribution is that the person who originally discovered it was a brewer for the Guinness company, and they would not let him publish the results after he sent it off to Pearson, and therefore the person, not the company, and then in order to publish it, he published it as a student of statistics. So that's why it's actually referred to as the student's t-distribution and not whatever his name was, which I can't remember off the top of my head. So our next definition is about our standard error. The standard error measures the dispersion of the sample mean and is calculated as the standard deviation of the sample divided by the square root of the sample size. That is because if I have a larger sample, then I will have less dispersion of my data. Even if I have a higher standard deviation, the larger sample size will kind of compensate for that. That's why we divide by the square root of n. It's important to know that the standard error is used to construct confidence intervals for our population mean. Now let's actually get into the math a little bit. So for our formula for a normal distribution with a known population standard deviation, or it comes from a known normal population, the confidence interval for the population mean will be given by x bar plus or minus z times sigma, or standard deviation, divided by the square root of n. So what you'll do is you'll have your point estimate for your population mean mu, so x bar, and you will subtract the critical value for the standard normal, which is z, times the standard deviation of your data divided by the square root of n. And then that'll give you your lower bound. Your upper bound will be x bar plus z times standard deviation divided by square root of n. So in this case, x bar is our sample mean, z is our critical value from the standard normal distribution. This would be something like 1.96 if you're using 0.95. It would be 1.645 if we had a confidence level 0.9, and it would be 2.58 if we have a confidence level of 0.99. Sigma is our population standard deviation, and n is the sample size. One thing I want to point out here is that if we do not have sigma, but we have a large enough sample size, and we know it comes from a normal population, we still write it as sigma, even though we're actually using s, because instead of using sigma, which we don't have, we use the next best thing, our point estimate for sigma. And that's because we have a sufficiently large sample size. We assume that the standard deviation sigma can be, accurately modeled by our standard deviation or our point estimate of it, so we use that in place of it. But we still generally write the formula as sigma, just because we are treating it as from a normal population. So for a t-distribution, so this is when we don't have a sufficiently large sample size to assume that it follows a normal distribution, and we do not have our standard deviation sigma, the confidence level or interval for the population mean is given by x bar plus or minus t times s, our standard deviation of the sample, divided by our square root of n. So this is where x bar, again, is our sample mean. T is our critical value for the t-distribution, which will be based on your confidence level and your degrees of freedom. And you can actually, usually in class, we'll use a student t-table for this, but you can actually use the computer to find this as well. One thing I do want to point out, though, is that your student t-table, for example, has less information, because unlike a standard normal table, which is just for the one distribution, a standard normal, which is a normal distribution with a mean of 0 and a standard deviation of 1, a student t-table actually has a whole family of t-distributions. So when you look at a t-table, every line on it represents a different t-distribution. Now, if you want to know more about that, I would suggest going to my Intro to Stats class videos where we talk more about that. But because we're focusing on R here, we're going to be using the computer to find anything like that. So we're not going to be finding our critical value for Z or even our t-distribution by hand or using a table. So let's jump into some examples. So I'm going to jump into R real quick. And for this first example, we're going to do it like you would by hand. So first thing I'm going to do is I'm going to have some sample data. So my sample data, so I'm going to concatenate or create a vector of the values 22, 28, 32, 35, 39, 41, 42, 44, 46, 49. Now, if I wanted to get my confidence interval, I know that I need to have x bar plus or minus z times sigma divided by square root of n. So the first thing I'm going to do is I'm going to figure out what is x bar. And I'm going to do that by using, so I'm going to set the object sample mean as the mean of my sample data. So now if I actually highlight sample mean and run this, you will see that we have a sample mean of 37.8. Next thing we need to do, we need to figure out what the standard deviation is, which I labeled as sample underscore SD. We find this by using the function in R, SD. So if we run this, again, I can figure out what my standard deviation is. Okay, I have a standard deviation of 8.482662. Next thing I'm going to do is I'm going to just create an object called sample size, which is going to be the length of our sample data. So if I run this, you can see that it is going to give me the size of my sample, which is 10, right? I have 10 data points. Now I need to figure out what my standard error is. So the standard error is just going to be sigma, in this case, or our standard deviation, divided by the square root of n. So that's exactly what I do. I take my sample standard deviation, which we already found, divided by, and I use sqrt for the square root of my sample size. And this will give me a sample error of 2.682453. Now, one thing I want to quickly show you is we look at our standard error, 2.68 something. If I were to change my sample size, let's say instead of having 10, I had a sample size of 25. So I'm just going to put 25 in here. What happens to my standard error? My standard error goes down because by having a larger sample size, I have, even though my standard deviation has not changed, my standard error has, because it is dependent on the standard deviation divided by the square root of my sample size. Let me just rerun this so it's back together. Okay, next we're going to get our confidence level, which I'm going to just define as 0.95. And then we're going to find our Z critical value. And we can do this by using Q norm, and it's going to be 1 plus our confidence level, and we're going to divide that by 2. So just real quick, if we do that real fast, if we look at our confidence level, we have that it's 0.95. Now you might wonder, why are we taking 1 plus our confidence level, which would just be 1.95, and divide by 2? And that's because when we do this, when we're actually looking at this, we have to consider that a confidence interval is what's considered a two-tailed test. Meaning, if I were looking for where the critical value Z is, and I'm looking to the left, I'm not looking for the value where 95% of the data is to the left of it, because I need the two values where 95% of the data is between it. That means if 95% of the data is here, that means 0.05 of the data, or 5% of the data is out here. Meaning if I want this critical value, I have to take into account that there's 0.95 of the data plus that 0.025. And that's why we actually use the number 0.975 to get our Z value. So we can use Q norm to find our Z value where 0.975 of the data is to the left of it. And notice I put it's Z dash. I didn't want to actually define Z because that's used for things in R. So we get that it's 1.959964, or when we do it by hand, we usually just do 1.96, which again, this is something you could just look up directly in a Z table if you have one. Okay, so now we're gonna find our margin of error. This is just gonna be our Z critical value times our standard error. And then we have our confidence interval, which we're just going to concatenate our sample mean minus our margin of error plus, or up to our sample mean plus our margin of error. And then if we look at our confidence interval, we will get the values 32.54249 up, and that's our lower boundary, up to 43.05751. And then of course below this, I just put round, because a lot of times when we're talking about this, we might want to round it to some values that make sense. Let's say this is representing money or something like that. So what I did is I used the round function. I put my confidence interval in there, and then comma 2 will tell it to round it to 2 decimal places. So this would just make it 32.54 to 43.06. And then as just an added comment on this, whenever we're teaching this to intro to stat students, we also tell them to interpret the results. So in this kind of problem, because I don't know what this data actually represents, I would just say something kind of generic like, we are 95% confident that the true mean, which would be mu, falls between 32.54 and 43.06. If I knew what this data actually represented, let's say it was salary data, we'd say that the actual salary on actual average salary is between this and this amount, something like that. Now for our next example, we're going to actually use some actual data. So first thing I'm going to do is I'm going to use my MT-cars data, and I'm going to load up MT-cars. So just as a reminder, MT-cars is just going to be a bunch of data about cars, where it's going to be looking at miles per gallon, cylinders, displacement, horsepower, weight, things like that for the cars. I'm going to be specifically doing a confidence interval for the miles per gallon of these cars. So I'm going to take sample mean by finding the mean of MT cars, money sign, MPG. So that's going to tell it specifically in miles per gallon, which as a reminder, if we want to see what our options are, if we do names, MT cars, this will tell us the different things that we can pull up. So we're doing specifically MPG. So our sample mean is going to be the mean of MT cars, MPG. Our sample standard deviation, we're going to use SD for MT cars, MPG. And now I'm going to find the length of this sample. So my sample size, I'll use length of MT cars, money sign, MPG. And this is going to give me a sample size of 32. I'm going to get my degrees of freedom, because in this case, now we're going to be using a student t-test, because this is all from sample data, and I'm going to go, not follow the assumption from intro to stats that we would use a standard normal because n is greater than or equal to 30. So what we're going to do is we're going to set up an object called degrees of freedom, which is just going to be our sample size minus 1, because our degrees of freedom is n minus 1. So our degrees of freedom, since our sample size was 32, we're going to have a degrees of freedom of 31. Next, we're going to find our t critical value. So instead of doing q norm, because we were using a normal distribution, we're going to use qt, because this is going to be from a student t distribution, right? The q function will give us the critical value to the left or right, whatever it is amount that we have. So instead of doing the whole 1 plus conf interval time divided by 2, I'm just going to put in 0.975. So we have qt for 0.975. So we want the critical value for t, where 0.975 of the data is to the left. And then we're going to use df, which is our degrees of freedom, as degrees underscore of underscore freedom. So then now we get our t critical value of 2.039513. Now I'm going to calculate my margin of error, which would just be my t critical value, times the sample standard deviation divided by the square root of our sample size. And this will give us, which actually, we call it margin of error, but it's actually called the maximal margin of error. And this is because when we are doing a confidence interval, remember, the true parameter is somewhere in this interval. We're 0.95 confident true parameters within this. So we're not saying that this is the interval. We're sort of saying, well, if we want to be 95% confident, what value would we at most need to go out, and how far out would we need to go out from the center to be that confident? So that's what we do. We take the worst case scenario, the maximal margin of error. The actual margin of error would be how far off your point estimate is from that true proportion. So if I knew that true proportion was this, and I took a sample and this was my sample, my point estimate, then the margin of error would be that distance. But because we don't know the population parameter, we can't find the margin of error, so we're finding the maximal margin of error. So we find our maximum margin of error, we get 2.172946. Now that we have our maximum margin of error, we just need to take our point estimate, x bar, subtract this maximum margin of error, that gives us our lower bound. We need to take x bar plus our maximum margin of error, that will give us our upper bound. So we get our lower bound by taking our sample mean minus our margin of error. We get our upper bound by taking our sample mean plus our margin of error. And then we're just going to combine this together in a statement using the cat function. So we'll say cat 95% confidence interval for the population mean, and then we will put the lower bound and the upper bound. And of course, we will separate this by no spacing. So we get a 95% confidence interval for the population mean is 17.91768 up to 22.26357. What about if we wanted to find a confidence interval for the parameter p, or proportion of our data? So the formula for a confidence interval for population proportion is given by p hat, which is the point estimate or sample proportion, plus or minus, or again, our z critical, times the square root of p hat times 1 minus p hat divided by n. So what this is now looking at is that the standard error for our proportion is going to be p hat, our point estimate for our proportion, times 1 minus p hat, which is q hat, which is our proportion of failures, divided by our sample size, all under the square root. So in this case, p hat is our sample proportion, z is our critical value from the standard normal distribution, and n is our sample size. So for this example, again, I'm going to create some sample data. So you can see here we have 10110101111. So I'm going to load my sample data. Then going to figure out what is the sample proportion. And I can do this by just taking the mean, because if you think about the proportion, all it is the number of successes divided by the total number. Well, if I take the mean of this, the mean is just add up all the numbers, which if you think about it, it's either 1 or 0. So if I add up all the numbers, it's the same thing as taking the sum of all the successes divided by the total number. So if I do mean of sample data, you'll see that we get a sample proportion of 0.7. Similarly, I could just take the sum of my sample data, and I can divide this by the length of my sample data, and you will see that we are going to get the exact same thing. So that's all it is. It's just a shorthand way, because I know that if I'm ever dealing with data that's binary, 0 or 1, I can take the mean of that and it will be the proportion of the successes, or the ones. Okay, so next thing we're going to do, we're going to find our sample size, doing what I just did here, which is the length of our sample data. We're going to set our confidence level for 0.95. And then we're going to find our z-value, much like we did previously, where we're going to do q-norm, because we're assuming that in this case we have enough data to use a standard normal distribution. Now, do we actually have enough data? It depends. In intro to stats, usually what we do is we look at do we have np greater than or equal to 5 and also nq greater than or equal to 5. So if we wanted to check that really quick in R, not a problem. We can do length of our sample data. This is going to be our n. And then we're going to multiply that by our proportion, which, if you remember, is just our sample prop. And you're going to see that we have a value of 7. Okay, that's greater than or equal to 5. Now what we need to do is we need to do the same thing, except for it's n times q. So it's not going to be times our sample proportion. It's going to be times 1 minus our sample proportion. Because if you think about whenever you have binary operators, if you have a proportion of the successes, then the proportion of the failures has to be 1 minus the proportion of successes, because they have to sum to 1, because it has to represent everything in the probability distribution. So if I do my n times q, I get a value of 3. So in this case, we really wouldn't be able to use a normal approximation for doing this confidence interval. But we're going to assume that we can anyway, because we're doing this example. So again, I'm going to find my z-value, and I'm going to find my margin of error, which is z times the square root of our sample proportion times 1 minus our sample proportion divided by our sample size. And then just to be safe, I'm going to do one more thing. I'm going to add an extra set of parentheses around this multiplication, just because I want to make sure that it's multiplying before it divides. Okay, so if we do our margin of error, we now get a margin of error of 0.2840258. Now we can do our confidence interval, which is just going to be the values, our sample prop, so our sample proportion, minus our margin of error, comma, and then our sample proportion plus our margin of error. And then figure out what our confidence interval is. We have a confidence interval of 0.4159742 up to 0.9840258. And of course, we were to interpret this, we would say that we're 95% confident that the true proportion of whatever this represents is between these two values. Now for our next example, what I'm going to do is I'm actually going to go back to empty cars, where I'm going to be looking at whether it is automatic transmission or not. So if we look at empty cars and we look at AM, which is automatic manual, you can see that we have 111, bunch of zeros, one. So this is whether it has an automatic transmission or a manual transmission. So what we're doing is we're saying, okay, take all the values of empty cars that are for the transmission that is equal to 1. Take the mean of that, and that will be our sample proportion. Now I want to show you something really quick. If I run sample proportion now, you'll see we have a value of 0.40625. If I were to get rid of setting it equal to 1, watch what happens. We're going to get the exact same value. It works perfectly fine. This is just me being a little bit more precise, where I'm saying I specifically want to focus on the successes, but in the end, when you take the mean, it already takes into account the successes, the number of failures. By including the failures, you're dividing by a bigger value because it includes the ones and the zeros for the length, and you end up getting the exact same thing. Next, we're going to calculate our sample size using length of empty cars, money sign AM. We're going to get our z value, same idea. It's Q norm, 0.975. We're then going to get our margin of error by multiplying our z critical times the square root of p hat times 1 minus p hat or q hat divided by n. We'll get our lower bound by taking our sample proportion minus our margin of error. We're going to get our upper bound by taking our sample proportion plus our margin of error. And then, as before, we can get our confidence interval, which is going to be 0.236 for our lower bound up to 0.576. So before we move on, there's some exercises I would like you all to try. I specifically focus these on empty cars, so that way everyone will have access to these directly within R. So first, calculate a 90% confidence interval for the population mean of WT, which is the weight of the cars variable in the MT cars dataset. Calculate a 99% confidence interval for the proportion of cars in MT cars dataset where cylinders value is 4. So you basically want to set it as a binary operator. 4 is a success. Anything that's not 4, so 6 or 8 cylinder, would be considered a failure, something like that. And then what I want you to do is create those confidence intervals and then interpret those confidence intervals that you just calculated in terms of what the data actually means. So it'd be like, I'm 90% confident that the true mean, the average weight of the cars is between this and this, or I'm 99% confident that the proportion of 4 cylinders is between this and this, something like that. Now, I do want to bring up one last point about confidence intervals before we move on to actually how to make this easier in R than how we're doing it. We're basically, so far, we've been replicating what you would do by hand with code. And the reason I wanted to do this is I want to show you that anything that we're doing, you can create your own systems to do. And when you're using functions, you could create a function that does all this from some input data. Now, R does already have built-in functions that will do this, and we're going to talk about in a second. But the point I wanted to make about confidence intervals is the goal of a confidence interval is you want to be as confident as possible. But when we increase our confidence, we increase our critical value. And that makes our interval get bigger. But the other goal is we want to have the smallest interval possible. So generally, the only thing that we can control to make both of these things true, right, because we set a confidence level, which we want to be high, but we also want to have a narrow confidence interval. And we can do this by increasing the sample size. Now, the reason I bring this up is because you'll notice some of these intervals, which I'm making, which a lot of it's just kind of made up data. It's not as helpful if you have this very large interval, right? If I want to be 100% confident, I could say the value is somewhere between negative infinity and infinity. I mean, I'm correct, but that's literally not helpful. But similarly, if I said that the average height of my students is between 4'5" and 7'5", true, but not useful. But if I said something like the average height of my students is somewhere between 5'7" and 5'9", okay, I still have an interval, but now this is a lot more useful because we could use stuff like this to say, okay, well, what is the average height of a person? If I'm designing something where I'm building it in mind of the average person, then I want to know, okay, roughly where does the average person fit? And we might have this interval. If the interval is too large, it might be true, but it's not very helpful. A smaller interval gives me a lot more useful information. So now let's look at simpler confidence intervals. In statistical analysis, we often are interested in estimating population parameters based on a sample. However, the sample statistic alone is not enough to draw conclusions about this population parameter. So confidence intervals will provide a range of values that the population parameter is likely to fall within based on our sample data. So now we're going to look at how we can actually calculate and interpret confidence intervals in R, specifically again using proportion, mean, and median in this case. I do want to point out that you can do a confidence interval for any population proportion. You can find a confidence interval for standard deviation, for variance, for anything you can think of. But we're going to be focusing on these specific ones because these are the most common cases we're going to look at. So if we want to find the confidence interval for mean, the way we can calculate this, we can use the t.test function. So the way that it will be is t.test and then parentheses, and you have to set what your actual data values are. So we have x equals and whatever those scores are, we're going to call it. And then comma, and then conf.level, and this is where you put your confidence level. And then you would get some output where it's going to give you your confidence level. So before we actually go and test this out, let's do our handy dandy question mark and do t.test. So by running this, you'll see that it performs 1 and 2 sample t-test on vectors of data. So it's t.test x. This is what you need. At minimum, you need your data. So we have test x, and this is what you have to enter your data. Y by default equals null. If you include another set of data, this would be your y value. This would be for a t-test where you're doing a comparison between groups. So by default, it's null if you're just doing a one sample t-test. Alternative, two-sided, less or greater. This would have to do with when you're kind of thinking of it in terms of hypotheses. Are you assuming that, are you testing the hypothesis that it's two-sided, which confidence interval is, looking to the left and the right, some amount. Remember I talked about splitting the data, or splitting the part to the outside. A left tail test, which is less, or a right tail test, which is greater. It has a default of mu equals 0. Paired equals false. This would be if you wanted to do a paired t-test, but we're focusing on confidence intervals right now, not t-tests. Var.equal equals false. This is saying that are we assuming that they have equal variance? By default, it will be false. If you were doing a confidence interval like we do in like intro to stats, you would want this to be equal, var.equals equals true. And this is because unless you're doing like math stats where we're assuming that they have unequal variance, then we actually would use the same variance for both samples, in this case, like a pooled sample, something like that. Again, unless we're using, unless we're assuming that they're unequal variance, in which case, again, I teach how to do that in math stats. And then we have our conf.level by default is 0.95, right? So then, of course, you also could do your t-test slightly differently. T-test, t.test, formula, data, subset, NA data action, stuff like that. This would have to do, again, if you're doing a t-test, not a confidence level or confidence interval. Okay, so before we do that, what I'm going to do is I'm going to load up some data now. This data is called exams, and I'm going to do read.csv, and my file is c:/ I have it in my temporary folder, so temp / exam _ data.csv, and I have header equals true, meaning that this in fact does have a named header at the top. So let's run this. And now let's look at exams real quick. So if I pull this up, you're going to see that we have 49 data points where we have an exam score, we have study hours, and we have sleep hours for some students in this data. Next, what I'm going to do, and we can see it at the top there, but I'm going to use names exams. Let's say you didn't want to go through all the data and you just wanted to figure out what are the things that I can choose from. So I have exam score, I have study hours, and I have sleep hours. So I am going to do this on exam scores. So let's look at our exam scores. We do exam, money sign, exam score, and we get the various exam scores the students got, 75, 80, 85, 90, 85, 90, stuff like that. It's just made up data still, but it's made up on a scenario. So we're going to use t.test. We're going to set our x as exams, money sign, exam score. So we're specifically going to use the scores. And our confidence level is going to be 0.95. So you can see that we're going to get some information. This is a one sample t-test. Our data comes from exam score. We have a t-value of 97.307. We have degrees of freedom of 48, n minus 1. It has a p-value of less than 2.2 times 10 to the negative 16. Alternate hypothesis would be that the true mean is not equal to 0. A 95% confidence interval, we have 84.14305 to 87.69368. And then, of course, the mean of our x is going to be 85.91837. If I wanted to do a 90% confidence interval, all I have to do is change this to 0.90. and I get a 90% confidence interval. If I want to do 99% confidence interval, I just, same thing. And this is actually one of the nice things about using R versus doing it by hand. By hand, we generally use those main three numbers, with 0.95 being the default for pretty much everything. But if we don't, we usually do 0.9 or 0.99. You can find different confidence levels using a z-table or something like that. But the nice thing about R is that we can do values that you couldn't even use for a z-table. Let's say I wanted a 0.93468 confidence. I want to be, for specifically, 93.468 confident. Guess what? R can do that. Similarly, if we wanted to do a proportion confidence test, we can use prop.test. And in this case, we have x is 70, n is 200, and we need conf.level. So before we actually do this, let's do prop.test. We're going to run this, and you're going to see that we have prop.test, x in p equals null. So it's assuming that it's null by default. Alternative, just like before, we can do two-sided, we can do left tail, or we can do right tail. Conf.level, we have 0.95 as our default, but we can change that. And we have correct equals true. This is because when you're using proportion data, which is to say discrete data, and we're using a continuous method to test it, specifically at standard normal, we have two options. You can do with correction for continuity or without. So correct means are using correction for continuity. By default, it is true. Okay, so now let's look at our actual example. Before we do this prop.test, because if you look at the slides, for some reason it has the incorrect values. So I decided let's do it like we would by hand. So first thing first, I'm going to set my x to 70. I'm going to set my n to 200. I'm going to get my lower boundary by taking x over n, which is the proportion of x over n, right? So 70 over 200, minus 1.96, because it's a 95% confidence interval. So z value is 1.96, times the square root, so sqrt, of x over n, p hat, times 1 minus x over n, 1 minus p hat, divided by n. So this would give me my t-test lower bound, which I call t-test lower. And then I'm going to do the same thing, except for now it is going to be plus 1.96, and this will give me my upper bound, so t-test upper. And then we concatenate it together, and I didn't put all the special words and stuff, I just did the boundaries. So this one is a confidence interval of 0.2838954 up to 0.4161046. Okay, so we have our confidence interval of 0.283 up to 0.416. Now let's use our prop.test. So same thing, prop.test. We have x equals 70, n equals 200, and our confidence level is 0.95. And you'll notice that we get a confidence level of 0.2849 up to 0.4209, which is a little bit different than what we got, right? Why is that? Well, it's because when I did the test, I didn't do the correction for continuity. And basically what this means is when you have discrete data, right? So we think about some value, we go out 0.5 to left and right. That's how we create the bar if we were to like create a histogram. Well, when we do it continuous, we cut it right down the middle and everything to the other side doesn't count it. So we just shift it by 0.5 either to left or the right. You do whichever one causes the interval to be bigger, right? Because if we're looking to the left, then we need to add 0.5. We're looking to the right. Sorry for you guys. Sorry, left for you all, right for you all. We're going to subtract 0.5. And if we're looking to the outside, what we need to do is we need to subtract 0.5 to the left. We need to add 0.5 to the right. So what if instead I did my prop.test, but I did correct equals false? Now you're going to see we have 0.2872882 up to 0.4183654, which is closer to what we had. It's not exact, and this is mostly because when we're doing this, there's minor things going on in the background. This is why I wanted to actually bring you to my note on this slide. If you calculate the Wald formula for proportions, which is what was in my previous slide, by hand, that's what I basically did the code to show by hand, this will likely differ from your R output. The Wald formula does not perform well for small sample sizes or when p hat is near 0 or 1. R used the Wilson interval with Yates continuity correction in order to calculate it. This is why it might differ from what you find when you do it by hand. When I did this example, this top part where I did it myself, this is equivalent without continuity correction. If I was doing continuity correction, I would change it a little bit, but this is the equivalent to doing it by hand. This is equivalent to what we were talking about in my note, where it's actually using the Wilson interval with Yates continuity correction. And I wanted to do one more example that's not on my slides just because I thought it'd be kind of fun. So first things first, as always, we're going to create some data. And we're going to use our binom. So we're going to use our binom, which we need in how many of the data points we are getting. We need the size of whatever it is that we're doing. In this case, I'm going to consider it like a coin flip, and the probability of success. So what I've done here is I'm going to set the object, flip coins, use our binom. I'm going to get 3,627 coin flips, single coin flip. So I'm doing one coin flip with a probability of success, or heads in this case, of 0.63. And I'm going to do that 3,627 times. So if I look at my coin flips, you'll see that I've got random data. And every time I do this, I will get a different set of coin flips, which will change the outcome. Then I'm going to do prop.test. I'm going to take the sum of those coin flips, which is going to tell me how many successes I have, 2,274. I'm going to do the length of my coin flips, which should be 3,627. And then I will do prop.test, and I will get my confidence interval of 0.6109 up to 0.6426. Again, if I were to do flip coins again, I will get completely different outcomes, and I will have a confidence interval of 0.605 to 0.636. If I do it again, I will have a different confidence interval. And this is what I was kind of talking about, is this is like taking those different samples. Every time I'm getting a different confidence interval, but should have, each of them have a 95% of them should include our true proportion. What about if we want to get the confidence interval for a median? So to calculate the confidence interval for a median, we're going to use wilcox.test. So as before, we are going to do wilcox.test. We run this, and it will tell us all about our Wilcox test that we're doing. It's actually called a Wilcox rank sum test. So in this case, what we're going to do is I'm going to load some more data. This is going to be for professor salaries. So I'm going to do profs. I'm going to read my CSV. So I'm going to take the CSV, professor salaries 2018 to 2019.csv with a header equals true. So if we do names, you can see that it's got field, job.title, all research, other.doctoral, and master.s. So I'm going to be looking at master.s, which is going to give me salaries for these people with master's degrees. And you can see the values here. Now, if I try to do wilcox.test, I have x is profs money sign master.s, conf.int is true, and conf.level is 0.95. Now watch what happens if I run this. It says in wilcox.test.default, blah, 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 x must be numeric. Well, if you actually look at these data points, notice the small discrepancy, these quotes. And this is what I was kind of talking about. You got to be careful about your type of data. If I do type of on my data, you'll see that we actually have character strings, not numeric values. So in this next example, I'm going to do the same thing, but now I'm going to do, for my x, I'm going to set as.numeric for my values. Now, another thing I do want to point out, though, we have two values here that are missing. We have a star there, and this is what you can't use is.na if someone used a star. So first things first, let's run it without doing anything else to it except making it numeric. And now you're going to see that it will tell you that it had NAs introduced by coercion, but it does give us a confidence interval of 72,038 and 78,297. Next, what I'm going to do is I actually cleaned up the data. So I did salaries cleaned, where I do as.numeric for those professor salaries, but I'm then going to subset within those professor salaries and money sign, or do not include is.na. And before that, I actually made it numeric, because if I do as.numeric masters, what it's going to do is it's going to coerce those stars into NAs. Then I'm going to tell from my masters subsetting that values as numeric, get rid of the NAs, and then I'm going to make the entire thing numeric. So now if I look at my salaries, you'll see that it is all numeric and it is not including any NAs. So now if we do our wilcox.test, you'll see that we get the same thing, 72,038 up to 78,297. So in conclusion, this is just an example of how you can do confidence intervals in R. There are other types of confidence intervals you can do. Some of them you may need different packages for, but anything you can do by hand, R can do it quicker, easier, but you do need to understand the assumptions that it's making and the underlying tools what it's actually doing, right? Because I showed you an example where it differed from what we would do by hand. Hello everyone. In today's lesson, we're going to be diving into hypothesis testing and how to do it in R. So first, let's start with the definition and purpose of hypothesis testing. So hypothesis testing is a fundamental concept in statistics used to make inferences about populations based on our sample data. Primary goal of hypothesis testing is to evaluate our evidence against a null hypothesis, which we write as H0 or H0, in favor of our alternative hypothesis, which we write as either HA or H1. And in other words, what this means is we just want to determine if there's sufficient evidence to reject our null hypothesis in favor of the alternative hypothesis, or if we fail to reject our null hypothesis. Now, hypothesis testing has numerous applications across various disciplines, including economics, psychology, medicine, and social science. It helps researchers and practitioners make informed decisions based on data rather than relying on intuition or anecdotal evidence. I always tell my intro to stat students that hypothesis testing is the most important thing we cover in the entire course. And in fact, I'm actually the person who evaluates students who are transferring in to see if they get credit for our introductory statistics course. And this is my one thing that absolutely has to be included. Some classes will have extra stuff that we maybe don't cover in an introduction course, like ANOVA, but we might be missing something else, like some of the modeling methods that we look at. But the one thing that is an absolute requirement for me is hypothesis testing. And this is because it's used in pretty much any field doing any sort of statistical work, and it's actually quite useful. In fact, a lot of times when we're doing research, we'll have to do things before we even, write a grant or any of that kind of stuff, which we have to do things like power analysis, which all this is looking at is, and we'll talk more about this later, is what is the probability that if your null hypothesis is false, which strengthens the case for alternative hypothesis, what is the probability that you would be able to correctly reject a false null hypothesis? And that's really the gist what power is, and yet whenever we're doing, trying to get a grant or starting a research project, this is always one of the first steps, is that we need to do this because it's so important. And this is actually one key aspect I want to talk briefly about with hypothesis testing, is that we have two real options. We can reject the null hypothesis, which then strengthens the case for what we actually believe, which is our alternative hypothesis, or we can fail to reject the null hypothesis. This does not mean that we're showing that our alternative hypothesis is true if we reject the null hypothesis, or that the null hypothesis is true if we fail to reject. This is the reason we use this language, because when we do this, we always have to take into account that we could be wrong. Because remember, we're doing statistical analysis. We're never going to have definitive answers. So let's talk a little bit now about our hypotheses. The null hypothesis represents the status quo, or the assumption of no effect or no difference. And which of these it is will kind of depend on what kind of hypothesis test you're doing. For example, generally, if you have some hypothesis test for like a parameter like mu, you will have some value that you're saying, okay, well, the assumption is that mu is equal to, let's say, 56. This might be something from a manufacturer. It might be a well-known value. It might be something from a prior study. This is what we're taking as sort of the given. It is, until we've shown otherwise, we assume that this is correct. Our alternative hypothesis is the opposite of the null hypothesis and represents the claim or effect that we want to test. So oftentimes what will actually happen if you don't have a null hypothesis is you'll have some claim that you believe is true, and you will set the null hypothesis as the opposite. So if I say, I believe that mu is greater than 87, then my null hypothesis would be that mu is less than or equal to 87. One other thing true is that generally when teaching hypothesis testing, we always have the equality sign in the null hypothesis. So we could write it as mu is equal to 56, or we could write mu is less than or equal to 56, but we generally don't include the equality in the alternative hypothesis. And this is because, and I teach this in my math stats class, if you have a null hypothesis that could be any possible value, let's say less than 56, that means that you have to contend with all these different possibilities. Whereas if we just say it's less than or equal to 56, by disproving it for 56, I've actually shown that it's not true for anything that is below 56, which I guess for you all would be this direction. So for example, suppose we want to test if a new drug is effective in reducing blood pressure. The null hypothesis would be that there is no difference in blood pressure reduction between the new drug and a placebo, while the alternative hypothesis would be that the new drug does have significant effect on blood pressure reduction. This is where your hypotheses are kind of coming into play, as what do you actually believe is true, and what would be the opposite, or the status quo, depending on how you're approaching the problem. Do you have this sort of default value and you think it's wrong, or do you have your thing that you want to show, and you're going to use the null hypothesis as like kind of the counter to this. And this is where like the no effect comes in. This one is testing the null hypothesis that there is no effect. The new drug does not change anything. Another place you'll see this is if you're doing a hypothesis test for like linear regression or something like that. The null hypothesis would be that beta 1 equals beta 2 equals beta 3 equals up to beta n equals to 0, meaning that your different parameters have no effect on modeling whatever it is that you're modeling. In fact, when we do linear regression and we do summary of our model, you're going to see that R will automatically do a hypothesis test and give you the p-value for that hypothesis test. Now, because this course is focused on the computational stats side of stuff, I'm assuming that everyone here has some background in hypothesis testing, right? Because this is something that we teach much more in depth in introductory statistics, or if we really want to jump in depth, would be mathematical statistics. But one thing we always have to keep in mind is that we never say that we prove or show something is true, because there's always going to be this possibility of error. And this is something we have to take into account with any hypothesis test. So when performing hypothesis testing, there are two types of errors that can occur. You can have your type 1 error, which has a probability of alpha. This occurs when we reject the null hypothesis when it's actually true. So let's say that your null hypothesis is true. If you erroneously reject it by having it fall into your rejection region, then this would be a type 1 error with a probability of occurring of alpha, meaning you're always going to have some alpha level of probability that you were incorrectly going to get a type 1 error. Our type 2 error occurs when we fail to reject a false null hypothesis. So let's say that the null hypothesis actually is false. If we fail to reject it, this would be a type 2 error, or with a probability of beta. Now, the reason that this can be difficult, though, is because much like anything in statistics, we don't know the true null hypothesis. We don't know whether that null hypothesis is in fact true or whether it is false. So all we can do is we can make a decision based on the evidence from our sample. But we do have to take into account that our null hypothesis could be true. And we have two decisions. We can fail to reject it, which is correct, or we can reject it, which is incorrect, and now we've committed a type 1 error. Or we could have a false null hypothesis, and we could correctly reject it, falls into our rejection region, we reject it, that's the correct decision. Or we could erroneously fail to reject it, giving us a type 2 error. So to kind of put into context some examples of what these types of errors would mean, it's going to be based on your actual null hypothesis being true or not. An example of this might be something like if we look at a court of law, we have the assumption is you are innocent until proven guilty. So the normal assumption is that you are innocent. That's your null hypothesis. You are innocent. Now there's two possibilities for that. You either actually are innocent, you didn't commit the crime, or you actually did commit the crime. You are not innocent. You are in fact guilty. Now we go through the court case and we have two possible decisions. They can find you not guilty, or they can find you guilty. So if you are in fact innocent, so the null hypothesis is true. If they say you are innocent, meaning they say we agree, then that's the correct decision. If you are actually innocent, you didn't commit the crime, but they find you guilty, you've now committed a type 1 error. You have erroneously rejected a true null hypothesis. If you did actually commit the crime, so the null hypothesis is false, right? We say person is innocent until they've been proven guilty, but you actually did commit the crime, so that's false. If we reject that and say you're guilty, we made the correct decision. But if you did in fact commit the crime and we fail to reject the null hypothesis, meaning we say that you're innocent, we have done a type 2 error. And this is actually where I kind of talked about power of the test. This is where this comes into play, because based on whether the null hypothesis is true or false will determine how we write the probability. So when you have a true null hypothesis, if you erroneously reject it, this is alpha. That's the probability of a type 1 error. So the probability of getting it correct would be 1 minus alpha. If you have a false null hypothesis, the probability of correctly failing to reject that null hypothesis is beta. The probability of correctly rejecting your false null hypothesis is 1 minus beta. And that 1 minus beta is the power of the test. It is the probability that if you have a false null hypothesis, that it actually falls into your rejection region. And this is where your alpha comes into play, because when we're doing a hypothesis test, we, as the person doing it, control alpha. We control the rejection region. So if alpha gets bigger, you have a better chance of rejecting that null hypothesis because it gets bigger, the area that things that can fall into it gets bigger, but it means that you are more likely to erroneously reject a true null hypothesis. If you make alpha smaller, then you have less likelihood that you will incorrectly reject a true null hypothesis, but you increase the chance that you incorrectly fail to reject a false null hypothesis. And this is where, again, you will never have a hypothesis test with no error. And this is why we tend to couch our language in things like we reject or fail to reject at some level of significance, because we may reject it at alpha of 0.05, but fail to reject it at alpha of 0.01. Now, sometimes you'll have other examples that are a little bit more murky of what the null hypothesis should be. And this might be based on societal conclusions. This might be things that are the most likely outcome. So for like the court case, I said we start with you're innocent until proven guilty. Well, another court system might have the null hypothesis be that you are guilty and you need to prove your innocence. In that case, a true null hypothesis would be they're guilty. A false null hypothesis would be that they're innocent. So that in that case would actually change what the type 1 and type 2 error is. It's all based on that null hypothesis. Sometimes, though, we are going to have cases where your null hypothesis is going to be what is most likely. This being something like if I have a cancer screening tool and I'm going to say, what is the default state? Well, most people at any given time do not have cancer. So we might say the default state is that you do not have cancer. And therefore, it's going to be based on that null hypothesis. And then, of course, the outcomes are either you do or you don't, and the test can make two conclusions. Either fail to reject, meaning, yep, you're found to be clean, or reject, which means you were found to, in fact, have cancer. Could be other things like if you're looking at doping in athletes, again, you might err on the side of just giving everyone the benefit of the doubt. We're assuming that every athlete's clean. That's your null hypothesis. It can either be true or false, and then you can either reject or fail to reject that null hypothesis. So there are three types of hypothesis tests that we generally do. So when we're looking at a parameter, for example, here I have mu, we can have where the alternative hypothesis, that's going to determine what kind of test we're doing, can be greater than some value k. We can have alternative hypothesis where mu is less than some value k, or we can have the where mu is not equal to some k. And this will determine the type of test. So if we say mu is not equal to k, this means that we can reject it in two directions. We can reject it either less than or greater than. We have two different places where we can reject it. If the value, if your test statistic goes too far down to the left, it can be rejected. If your test statistic goes too far to the right, we can reject the null hypothesis. So this is a two-tailed test. If we have that mu is less than some value k for our alternative hypothesis, this means that we can only reject it on the left side, meaning no matter how far a value goes to the right, we would never be able to reject it. We can only reject it in that one direction. And if we have mu is greater than some value k, then this is a right-tailed test, and we can only reject it to the right side. So this would tell us what kind of test we're actually doing. And then notice our alternative hypothesis is the counter to whatever our claim is that we think is true. That's our alternative. So if we have mu is greater than k for our alternative, then our null hypothesis would be mu is less than or equal to k. If we have mu is less than k for our alternative, it would be mu is greater than or equal to k for our null hypothesis. And if we have mu is not equal to k, the null for this would be mu is equal to k. In my introduction to statistics class, I actually just have my students write mu is equal to k for all cases. And this is because, let's say that I have my alternative is mu is less than k. So the null to it should be mu is greater than or equal to k. But if I'm looking to the left and I have my data, my test statistic is far enough to the left that I can reject mu is equal to k, then I also have enough evidence to reject anything greater than k, because by rejecting this, I've rejected this and everything above it. So it's sort of implied even if you do it as equals to. And then this part here on the right of the slide, this is just kind of showing some of the language we would use in problems to determine which type of statement this is. So greater than or equal to k, at least k, not less than k, not shorter than k. These are all kind of ways of saying something is, less greater than or equal to. For our alternative, at less than k, below k, fewer than k, shorter than k, things like that. These are just the language we'd use to actually kind of translate from, our, language, speaking about the problem to actually turning it into our hypotheses. When we're doing a hypothesis test, we have to determine what level significance alpha we're going to choose for our threshold that we can set before we conduct this hypothesis test. So it represents the probability of making a type 1 error. Common significance levels are 0.05. That's the gold standard. That's the default. If you do any sort of hypothesis testing with any program, this is going to be the default. We also sometimes will use 0.01 or zero point 0.1 sometimes, or 0.001. Those are the most common ones. We generally do things with a one of them. So the first one, 0.05, this would represent 5% probability of type 1 error, 1% and 0.1% respectively. How do we choose that level of significance? Well, again, most things people are going to choose 0.05. It's the default. It was chosen, I think, by Pearson when he was actually creating this idea a long time ago. But there's nothing that says you have to use 0.05. And there's nothing to say that you have to use one of these nice rounded numbers. You could do an alpha of 0.03 if you want. But generally, how you choose your alpha is going to be somewhat dependent on how much control you have on the actual experiment. If you are doing most research, 0.05 is enough to show that there's what's called statistical significance. But if you have data that might be not very controlled, very messy, you might just want to show that there's some indication that you could reject it. So you might choose something like 0.1. This might be something where you're dealing with people where there's a lot of things you can't control as a researcher. You can't control their biases, you can't control their upbringing, their diet. There's a lot of things you can try to control, but you really can't control. If you have a lot of control and you want to definitely make the case that what you're saying is probably accurate, then you might use a lower alpha, like something like 0.01, because if you can reject it at that smaller alpha level, it strengthens the case for alternative even more. Because remember, anytime you're doing a hypothesis test, you are rejecting the null hypothesis in favor of your alternative hypothesis. But that doesn't prove your alternative hypothesis. But if you were then to do another hypothesis test and it also rejects that null hypothesis in favor of, and every time you do that, you're strengthening the case. So you're not proving it, but you are showing that there's enough statistical or evidence to statistically kind of push it in that direction. When we're doing a hypothesis test, oftentimes what we're going to do is we're going to calculate a p-value. So your p-value is just the probability of obtaining a test statistic that is at least as extreme as the value that you got or more extreme. So assuming the null and this would be assuming that the null hypothesis is true. If the p-value is less than or equal to your significance level alpha, so p is less than or equal to alpha, you can reject the null hypothesis in favor of your alternative hypothesis. If the p-value is greater than significance level, then we would fail to reject our null hypothesis. Now, the way I always teach my students to remember this, it's silly, but think of p like it represents a pond. And alpha, if you kind of write it out, looks kind of like a fish. If the fish is smaller than the pond, makes sense, fail to reject it. If the fish is bigger than the pond, then that makes no sense. We have to reject it. So if the fish is bigger than the pond, you're going to reject the null hypothesis. I feel like when I'm teaching this, though, p-value is one of those things that kind of throws students off. Because what we're doing is there's a couple different methods you can use when doing hypothesis testing. There's three specific ones we generally can use. There is critical region method, which is you have some rejection region, and if your test statistic falls outside of that, you're in the rejection region, you reject the null hypothesis. If it doesn't go past that threshold, then you're in the fail to reject region, you fail to reject it. This will tell you whether you have enough statistical evidence to reject or fail to reject the null hypothesis. P-value, on the other hand, doesn't worry about that threshold value. It purely says, I have a test statistic. It's here. What is the probability that I would get a value that's this far away from the mean that we assumed was true or further? So we're saying, what is the probability that I would be this extreme or more extreme if that null hypothesis were true? And so the way we're kind of thinking about it is remember, we're assuming that that null hypothesis is true. So we're saying, if that null hypothesis were true, let's say it follows a normal distribution, then we know that based on our empirical rule that 68% should fall within one standard deviation, 95% should fall within two standard deviations, 99.7% should fall within three standard deviations. So if I get a value that's way out here, where it only has like a 0.002 probability of being true if that null hypothesis were, to occur if that null hypothesis were true, that's very unlikely. It definitely strengthens the case. Is it impossible? No, but it strengthens it. As I mentioned previously, R will actually automatically do hypothesis testing when you create pretty much any model in R. In R, we're going to be using the t.test function to actually do a lot of our hypothesis testing. In Intro to Stats, we usually start by teaching how to do a hypothesis test using normal distribution, and then we check our assumptions, see if we can use that, and if not, we use student t because we're assuming it's bell shape and symmetric, all that kind of stuff. But there's nothing to say that you can't do a student t distribution even with a higher, you know, sample size, anything like that, right? Even if your assumptions pass and you could use a normal distribution, a student t could still be used. In fact, remember we talked previously about the fact that as your student t distribution, as the degrees of freedom get higher, it will get closer and closer to representing the same distribution as a standard normal distribution. So the t-test function in R is a versatile and widely used function for performing t-test, which are statistical tests used to compare the means of one or more samples. The t-test assumes that the data is approximately normally distributed, and it is robust to moderate violations of normality when sample sizes are large. The t.test function can handle three types of t-test: one sample, two sample where they're independent, and paired t-test. A one sample t-test is a test that compares the mean of a single data set to a known or hypothesized population mean. This is the kind of hypothesis test we've been talking about so far. For instance, comparing the average height of a sample to the known average height of the population. A two-sample independent t-test compares the means of two independent data sets, for example, comparing the average test scores of two different groups of students. And then a paired t-test is a test that compares the means of two related data sets, for example, comparing test students of students before and after some intervention. So now let's talk about our actual syntax we're going to use for our t.test function. So we have t.test, and then you have x. X is the numeric vector containing the data for your first sample. This would be what your actual data you're using for your hypothesis test. Then we have y equals null. Y is a second numeric vector if you were doing a two-sample t-test, but by default it is null. So if you put t.test and put your data in there, it is doing a one-sample t-test. If you include a second data set, you're negating that null, and that would be your y. That's when you're doing either independent or paired t-test. Next, we have alternative equals, and this is where you can choose what type of hypothesis test you're doing. Are you doing a two-tail test, which we put as two-sided? Less would be a left-tail test, and greater would be a right-tail test. Next, you have mu, and it is equal to 0 by default. This is going to be your hypothesized population mean if you were doing a one-sample t-test, or the difference between the two population means for a two-sample t-test. Again, the default value is 0. Next, we have paired equals false. Paired would be whether it is a paired two-sample t-test or an independent two-sample t-test. So by default, it is false, meaning that we are assuming that they're independent. If you change this to true, this is how you would set it up to be a paired two-sample t-test. And then var.equal, this is going to tell you whether you're assuming that those two samples, if you're doing a two-sample test, have equal variance or not. So by default, it is false. Or if you set this to true, it will assume that they are equal variance. Again, this is something I teach in math stats, where if they are assumed to be equal variance, you would use pooled variance. If they are assumed to be different variance, then you would have to do a pretty big calculation to figure out what the degrees of freedom are to figure out what the value would be on your t-table. And then we also have conf.level. This would be where you set your confidence level. So the way confidence level works with alpha is 1 minus confidence. The two of them together equal to 1. So if I have an alpha of 0.05, that would mean my confidence level is 0.95. If I have an alpha of 0.01, my confidence level would be 0.99. So when you're doing R, you're going to do it by confidence level, but generally it's pretty simple to figure out which one you're doing. The output from our t.test is going to be a little bit more complicated than what we normally have seen in the class so far. So the output of our t.test function returns an object of class htest that contains the following components. We have our statistic. This is the t statistic values. When I talked about my test statistic, this is what I was referring to. The parameter, the degrees of freedom of your t-test. Remember, degrees of freedom for a t-test would be n-1. Your p-value, so or if you're doing a two-tail test, it'd be n1 plus n2 minus 1. Your p-value, this will be the p-value for your hypothesis test. You've got conf.int, this will give you your confidence interval for the difference of means. You've got estimate, this would be the estimated means of your samples. You have your null.value, this is the hypothesized population mean or difference in population mean. Alternative, this is the specified alternative hypothesis that we are testing. And then method, a character string indicating the type of t-test. So remember how I mentioned that there were 3 types of hypothesis tests we could do, but I only talked about 2? The third one is you can actually use a confidence interval for a hypothesis test, specifically if you have a two-tailed test. So if I have a two-tailed test and I create a confidence interval, this area, if something falls with it, right, we're 95% confident something falls in this confidence interval, well, guess what? That means we are 5% not confident, meaning that we're looking at the outsides for our hypothesis test. When you do a two-tail hypothesis test, your rejection region is that outside part. So similarly, you could use the confidence interval where if it falls within the confidence interval, you fail to reject the null hypothesis. If it falls outside of your confidence interval, you would reject the null hypothesis. Now, the problem is this one does not work well with a one-tail test because if I have a confidence interval, that means I can reject the null hypothesis if it falls out to the left or to the right. Whereas if I'm doing a right-tail test, so going that way, I can only reject it this way. But again, the confidence interval method could reject it if it's too far below. Similarly, if I'm taking my alpha in a one-tail test, let's say it's 0.05. Well, now if I'm splitting this between 2 sides, because my confidence interval will have half of it on the left, half of it on the right, that actually means that my rejection region has shifted. So a confidence interval method will actually have a smaller rejection region on the side you're looking at because it'll take half of alpha instead of full alpha. Again, I talk more in depth about this in my other classes and lectures and stuff like that, but just know that this is a thing. You could use a confidence interval if you're doing a two-tail test. If you're a one-tail test, I wouldn't do it. But this will automatically tell you what the confidence level is in R. So now let's jump into the actual doing these hypothesis tests. So we're going to start with a one-sample test. So one-sample t-test is used to compare the mean of a single data set to a known or hypothesized population mean. The assumptions for a one-sample t-test are: the data are independent and identically distributed, which we write as IID, and the data are approximately normally distributed. If the sample size is large, the central limit theorem can be invoked and the normality assumption can be relaxed. So let's do an example. Suppose we want to test if the average height of a sample of 30 students is significantly different from the known average height of 170 centimeters for the general population. We will use a one-sample t-test to test this hypothesis. So our null hypothesis in this case is we're saying that the average height, so the mean mu, is equal to 170 centimeters. Now, if you notice when we said we want to test whether this is different, or we might test whether this is true, we're testing the claim. This means that we can reject it if the average height of our sample is significantly lower, or we could do it if our sample is significantly higher. So our alternative hypothesis would be the average height of the sample is not equal to 170 centimeters. This is a two-tailed test. So now let's jump into the actual code. The way we're going to do it, I have some heights that I've set up. So I've got heights. By the way, this is in centimeters. So 168, 175, 166, 172, up to 190. And then what I'm going to do is I'm just going to do t.test. I'm going to include my height data, and then I'm going to set the mu. Mu equals to 170. So let's jump into R, and let's look at this. Now, before we do this, as always, even though we already talked about the syntax, I'm going to do $t.test. And the reason is this is going to give us what our defaults are. So now our alternative is it's going to be two-sided by default. I know it says alternative equals and it's the vector of two-sided left tail and right tail, but by default it will be a two-tail test. So I'm going to run my heights, and then just to get a little bit more information, let's make sure we have the right amount of heights. So I'm going to do length heights, run that. Okay, I've got 30 data points, just like the problem said. So my result is going to be t.test heights and mu equals 170. So if you remember, based on this, this means that we've replaced mu equals 0 with 170 by clarifying in our arguments. We have that it is not a paired t-test because that is false. Our y is null because we don't have a second sample. Again, the equal variance doesn't matter because we only have one sample. And our confidence level is 0.95 because we did not specify that. So if we run this, then we get our result, and then we're going to print it. So as we talked about, this is going to show you this is a one sample t-test. Our data comes from heights. We have a test statistic of t equals 2.8416, has a degrees of freedom of 29. Our p-value is 0.008131. The alternative hypothesis, the true mean is not equal to 170. We have a 95% confidence interval of 171.3266 up to 178.1401. And the mean of our x, or our heights, is 174.7333. So based on this, if we have an alpha of 0.05, because we had a confidence level 0.95, this means that we have sufficient evidence to reject our null hypothesis, because p of 0.008, right? P is less than alpha, so the fish is bigger than the pond. Doesn't make any sense. We have to reject it. So this means we could reject our null hypothesis. Let's say, though, that we wanted to use a different confidence levels. We might do something like conf.level equals 0. Let's do 99% confidence level, which means we have an alpha of 0.01. So in this case, well, everything else is basically going to stay the same, right? So we're going to have the same t-value, we're going to have same degrees of freedom, but our p-value will be the same. What's going to change is our confidence level will change, our confidence interval, because that's going to change our critical value, and our decision might change, because if we have a p-value of 0.008131, this is still going to be where we reject the null hypothesis. But if, let's say that my p-value had been like 0.0168, then this would be above my alpha of 0.01 at that point. So it doesn't change a whole lot in your output, but it does change a little bit. It changes the confidence interval, and it also changes what your actual decision would be based on this test. In my problem, I specifically chose to do a two-tail test, but you could just as easily have done a left-tail test. So in this case, what we do is we have t.test, we have our heights, our mu is still 170, but we have alternative equals less. Now, because I did not put conf.level in this one, it will go back to its default of 0.95. So if I do this, you'll see that it's a little bit different. This is, again, a one sample t-test, data's heights, t is same thing, test statistic, same degrees of freedom, but our p-value is 0.9959. So remember, we want a p-value that is small. And this is because by doing a left tail test, right, so left tail, well, we said that our value is actually somewhere over here. So we definitely are not going to have enough evidence to reject this null hypothesis. If we were to go and do a right tail test, on the other hand, watch what's going to happen to our p-value now. It's going to get even smaller, 0.004065, because by having a right tail test, it actually strengthens our case. One thing I want to talk about before we move on to the next example that we're looking at is when you are doing hypothesis testing. If you fail to reject your null hypothesis at a certain level, you don't just change your alpha to pick something where it would reject it. Meaning that if I fail to reject a null hypothesis at alpha of 0.05, I don't just say, but I would have rejected it at 0.1, so I'm going to use that alpha. That's not how it works. What you're supposed to do is then you go out, you gather new data, and then you would do the hypothesis test with that new alpha that you chose. Is that what most people actually do? No, because what a lot of people will actually do is they'll just jump into R like this, they'll do their hypothesis test, they will see what their alpha level is, and then they will just say, okay, well, based on this p-value, we can reject it at up to a 0.004065 level. That kind of gives you this threshold of ours has evidence to reject it down to this level alpha. The reason this is important is because let's say I have something like this. I'm going to do a linear model real quick, and I'm going to do MT cars, money sign, MPG, and I'm going to say that it follows MT cars, money sign, weight. Just very simple method. Actually, sorry, I need to do one more thing with this. I'm going to call this model 1. I'm going to assign this as model 1. Now, if I do summary model 1, what's going to happen when I actually run this linear model, which we'll talk more about linear models later, is to the right side of each of these, the intercept and our parameter, it's going to give us this star rating, right? So we have our p-value right here. So our intercept has a p-value less than 2 times 10 to the negative 16. Our weight parameter has a p-value that is 1.29 times 10 to the negative 10. And then the star values will tell me, so at 3 stars, I can reject it at 0.001. At 2 stars, I can reject at 0.01. At 1 star, I can reject at 0.05. With a dot or a period, I can reject it up to the 0.1 level. And if it doesn't have something, that means we just don't have enough evidence to reject our null hypothesis. What does this mean? Well, when you're looking at these, if I have anything that is like in this level, this gives me overwhelming evidence in favor of my alternative hypothesis. This one gives me extremely overwhelming evidence in terms of it. This one gives me strong evidence. This one gives me weak evidence, and anything below that would be no evidence in favor of our alternative by rejecting the null hypothesis. But the reason I wanted to show you this example very quickly is because this is oftentimes what people will do. Is they'll do something like, again, I'm going to do a new model. This one's going to be model 2, and this is going to be a linear model where it's MT cars, and I'm going to do, again, miles per gallon, and it's going to be described by everything else. So if I run, and then of course I'm just going to set data, so I can define it, is equal to MT cars. Okay, so now if I run this and I do the summary of this now, so this will be model 2, notice what's going to happen is we're going to have a lot of different parameters, and it's basically going to say that none of them really seem to be significant, except weight. Weight has some weak significance. Now, this is not the best example because it went from, the thing I did was completely significant to only one thing is weakly significant. But if I had made a model where it was like weight, cylinders, and something else, and it gave me, actually, let's do it real quick. Let's do model 3 is going to be LM MT cars, money sign MPG, follows MT cars. We'll do weight plus MT cars. Let's do, I don't know, cylinders plus MT cars. By the way, the reason I'm putting MT cars for each of these, you can always just put data equals MT cars and you wouldn't have to do this. Let's do horsepower. Okay, so now if I do summary model 3, let's try that. Okay, so now you can see that when I'm modeling the miles per gallon affected by a car's weight, cylinders, and horsepower, you can see that the weight is overwhelmingly significant. The cylinders is weakly significant, and the horsepower is not significant. So what a lot of times people actually do is they will run the model or run the hypothesis, whatever they're doing, they will find out the level of significance and they will just claim that. They'll say, okay, well, we've shown that the weight of the car is significant to the miles per gallon of a car, and there's some evidence that the cylinders also affects it, something like that. Versus what you should do when you're doing a hypothesis test is start with your hypothesis and your level of significance. Gather the data, do the hypothesis test. If it fails, you don't just change it, you go and gather new data, you run a new hypothesis test. Now we have another example. This one is for the weight of oranges, same basic idea. It's just that now we have a different data. In this case, we have our weight of oranges is this. So looking at our code, you can see that we are doing a two-tailed test. So t.test, we have the weights, which is our data, and we're testing the null hypothesis that the mean weight is 150. So if we print our results, we get it's a one sample t-test. Our data is weights. We have a t-value or a test statistic of 4.032. Degrees of freedom is 24. Our p-value is 0.000486. So that means that we would reject it at the 0.05 level of significance. Just like before, we could make this a left tail test by doing alternative equals less, and we would get a p-value of 0.9998. Or if we did a right tail test, we could switch it by doing alternative equals greater, and we would get a p-value that is even smaller of 0.000243. And then one more one sample t-test example. We have a mobile phone company wants to test if the average battery life of their latest smartphone model is greater than 8 hours. They collect data from random sample of 20 smartphones. The null hypothesis is that the average battery life is equal to or less than 8 hours. Our alternative hypothesis is that the average battery life is greater than 8 hours. So just like before, we are going to enter our data, battery life. We're going to do a t.test on battery life. Our mu is going to be 8. That's the 8 hours. And we're doing our alternative hypothesis, which would what we actually believe is greater. So we'll do this. We print our results. And we get, it's a one sample t-test. Data is battery life. T is 3.6055. Degrees of freedom is 19. Our p-value is 0.009423. So in this case, again, we would reject our null hypothesis. I know in all these examples I'm doing, we're rejecting our null hypothesis. Again, you're just going to be comparing your p-value to the alpha. If your p-value is smaller than alpha, you reject the null hypothesis, it's less than or equal to. If your p-value is greater than alpha, you fail to reject the null hypothesis. Now let's jump into the two-sample independent test. So the two-sample independent t-test is used to compare the means of two independent samples to test if there's a significant difference between them. The assumptions for this test are the data are independent and identically distributed. Again, the data from each sample are approximately normally distributed. If the sample sizes are large enough, the central limit theorem can be invoked and normality assumption can be relaxed. And the third assumption is that the variances of the populations are equal. This is called homoscedasticity. If this assumption is not met, a Welch's t-test can be used instead. Now, one thing I want to point out here for this part 2 that says that you either have normally distributed data or you have sufficiently large data. Unlike when we did a one sample test where we just needed the one sample for that to be true, in order for this to be true, it means that both samples have to be big enough. So if you have a very large sample, and it makes it so you can use a normality assumption even if it's not normally distributed, and you have a very small sample, then this means that this test would not be reliable because it has to be true for both data sets. Not in general, both of them have to be true. So you check your same assumptions like you would a one sample hypothesis test, but it needs to be for both samples. First example, suppose we want to test if there's significant difference between the average test scores of students taught by two different teachers. We have test scores for 25 students from each group. Our null hypothesis is that, right, default state, no effect. There is no significant difference between the average test scores of the two groups. Our alternative hypothesis, or H1, is that there is significant difference in the average test scores of the two groups. Notice we didn't say that one group did better or one group did worse. We said there's significant difference. This means that this is a two-tailed test because we could show that there's significant difference in the negative direction or the positive. One thing to be careful about when you're doing a two-sample t-test is that the order you are comparing them in will affect the type of test if you're doing a one-tailed test. Meaning if I'm doing mu1 minus mu2, that is group 1 minus group 2, that would have a different answer than if I had mu2 minus mu1, right? Because if mu1 is bigger, the first one would give us a positive number. The second one would give us a negative number. So the type of test will also depend on, whether you reject or fail to reject the ordering that you do it in. Okay, so let's jump to our code real quick. So we have our two group scores. So the first group, we have scores, remember these are exam scores, of 85, 90, 88, 91, 87, and so on and so forth. Second group, we have 75, 80, 78, 81, and so forth. There's 25 in both groups. So now what we're going to do is we're going to do t.test. We're going to do group 1 scores. We're going to do group 2 scores. We did not put a mu value here because this one, we are not comparing it to a known or accepted default state mu. We are comparing them with each other, meaning we don't need to include that. We did not include our conf.level, meaning where it's going to be by default a 95% confidence interval, and we did not include an alternative, meaning by default it will be a two-tailed test. So let's run it, and then we will get our results. Okay, you'll see that this is a Welch's two-sample t-test. Group 1 scores and group 2 scores were our data. We have a t-test statistic of 4.8038. Degrees of freedom is 48 because it's 25 and 25. So n1 plus n2 minus 2. P-value is 1.567 e to the negative 5, so times 10 to the negative 5. And that means that in this case, we would reject our null hypothesis, that they are the same, meaning that one of them is in fact significantly higher or lower than the other. So what we're going to do in this case is we're going to change this a little bit. We're going to change our alternative. So let's do alternative, and we're going to set this equals to greater. Now if we run this, you will see that our p-value is 7.835 times 10 to the negative 6, meaning that we can reject it with a right-tail test. This means that group 1 has a higher average score than group 2, right? You can see it at the bottom. Group 1 has an average score of 88. Group 2 has an average score of 78. If you had done a left-tail test, you would see that we get a p-value of 1, meaning that we 100% do not reject this null hypothesis. It does not show evidence, and it's not actually 1. It's like 0.9999 something, but it's just going to round it. So in this case, we definitely don't have, if we were doing a left tail test, we would definitely not have evidence to reject our null hypothesis that the first group is less than the second group. And then finally, we're going to look at an example for a paired t-test. So a paired t-test, or dependent samples t-test, is used to compare the means of our two related or matched groups to determine if their differences are statistically significant. So that first one, we had a two-sample t-test where we assume that they are independent from each other, meaning that we do not assume that they have equal variance. This means that Group 1 might have a variance of their test scores of being plus or minus 4. Group 2 might have been plus or minus 6, and it takes that into account. With a paired t-test, we are assuming that they are going to have pooled variance. Common scenarios, repeated measures. Measuring the same subjects before and after an intervention. This would be things like blood pressure before and after a medicine. Matched pairs, measuring naturally paired pairs. Twin study, husband and wife pairs, things like that. So structurally, a paired t-test reduces a two-variable problem down to a single variable by calculating the pairwise difference for each subject. That is to say, we have d sub I, so the difference is xi after minus xi before. So you're not looking at the value of group 1 and group 2, you're looking at difference between person 1 before and after, and that will give you difference 1. Then you look at the second person. Before and after for person 2 gives you difference 2. So you're kind of reducing it down to another single sample type problem. It then performs a standard one sample t-test on those differences against a hypothesized mean difference, which is to say that they are not different. Mu d, so mu difference, is equal to 0. The assumptions for your paired t-test are the pairs are sampled independently from the population, and the differences, di, are approximately normally distributed. Normality of the raw variables themselves is not required, only their differences. So this is one key aspect of this. We're not assuming that the underlying before or after, in this case, are normally distributed, but we're assuming that the differences between before and afters would be normally distributed. So the scenario for our example is you have a clinical psychologist wants to test if a new 10-minute mindfulness exercise increases cognitive focus scores. Our data is that a random sample of 10 participants is given a baseline focus test. They complete the exercise, and then they take an equivalent post-exercise focus test, and the scores will range from 0 to 100. Our null hypothesis is going to be that the true mean difference of the focus scores is less than or equal to, basically it's going to be equal to 0. There's going to be no change. So that means that the exercise does not improve focus. The alternative hypothesis would be that the true mean difference in our focus scores after the test will be greater than 0, and this will mean that the exercise did improve our focus. So just like before, we're going to have two different samples here. We're going to have our pre-scores and our post-scores. So we get our pre-scores, there's 10 of them. We have our post-scores, there's 10 of them. Now, one thing about this in R is if you're doing a paired sample t-test, you do have to have equal sample sizes. For the regular, like independent two-sample t-test, you don't have to have an equal amount. You could have 25 students for the first group and 20 students for the second group. It'll work perfectly fine. This one, because they're doing the differences between two, before and after kind of thing, it has to be the same number of observations in both groups. Next, we're going to do result. This is going to be t.test. We're going to start with our first data, which is going to be post-exercise. We're going to have our second data is going to be pre-exercise. The difference is going to be how they scored after the mindfulness exercise minus how they scored before the mindfulness exercise. We're going to use paired equals true. This is how we're telling it that is a paired two-sample t-test. And their alternative is we specifically are looking at, we believe that this mindfulness exercise is going to increase focus. So we're going to say that the post exercise focus will be greater than, so we're going to put alternative equals greater. Then we print our results, and you will see that it tells us we have a paired t-test. Our data is post-exercise and pre-exercise. We have a test statistic of t equals 4.6109. We have degrees of freedom of 9, because remember, it's not taking degrees of freedom of the first group and second group, it's treating it as differences. So we have 10 differences, so 10 minus 1 gives us 9. Our p-value is 0.006353, and our alternative hypothesis, the true mean difference is greater than 0. So our p-value of 0.0006 will definitely be less than, let's say, an alpha of 0.0, let's do 0.001. It's even less than that. So that means we have extremely strong evidence to reject our null hypothesis in favor of the fact that these exercises actually do increase focus or mindfulness or whatever the example was. Okay. If we look at our confidence interval, you will see that it gives us a value range of 1.988047 up to infinity. So this is, confidence interval sort of going up to, from some point all the way up to infinity because it's so extremely big. And our mean difference between our two groups is 3.3. So this was just a brief introduction to hypothesis testing and how to implement it in R. This was looking at 3 different types. We looked at one sample t-test, we looked at 2 independent sample t-test, and we looked at a paired 2 sample t-test. But just like I showed you in the sort of little sub example I was doing, that anytime you are doing a model or anything like that in R, it is also going to run a hypothesis test. And there are other hypothesis tests you can do. You can do a hypothesis test on different models where you're looking at, do the different parameters have any effect on actually modeling whatever it is you're modeling, where the default would be no. So beta 1 equals beta 2 equals 0. And then the alternative would be that they are in fact not equal to 0, meaning that one of your variables does in fact have significance. There are other types of t-tests, or there are other types of hypothesis tests that you can do, but we're just focusing on a few right now. But now that you understand this, you can kind of figure out how to implement it. Again, this is why we always look at our documentation, because this is how, if I'm running some new test, let's say that I wanted to do some new hypothesis test I've never seen before, I grab some package, guess what I'm going to do? I'm going to do exactly that. I'm going to look at the documentation, I'm going to figure out what the defaults are, what I need to include. I'll, of course, look up the assumptions. That would be something outside of R you need to look up to determine if it's the proper hypothesis test, and then you just run it by using all the tools that we've learned so far. Hello, everyone. In today's lesson, we're going to be introducing linear regression in R. So linear regression is a fundamental statistical technique that models relationship between a dependent variable, also known as the response or outcome variable, and one or more independent variables, also known as the predictors or explanatory variables. The primary goal of linear regression is to predict the value of dependent variable based on the values of the independent variables, or to understand the relationship between these variables. Now, one thing I want to caveat here before we move on is specifically it is looking for a linear relationship, which should be kind of obvious from the name. This is important because when we learn about, for example, correlation and correlation coefficient, this is specifically looking at, is the relationship between two, or in this case, 2 or more variables, but specifically in a linear fashion, meaning that there might be a relationship that could be modeled between, let's say, an X and a Y, so your independent and dependent variable. But if it's cyclical, for example, like let's say it represents like the business cycle, this would not have a high correlation because this correlation coefficient is specifically looking at linear relationships. This is what a linear regression actually is going to model. So if you think about X versus Y, it is going to give you a line that represents the correlation between these two things, how it regresses. So as X increases, does Y increase? As X increases, does Y decrease? Or as X increases, does Y not really change? Something like that. If you were to take this into higher dimensions, right, if I have more than one independent variable, you would just take this to a higher plane. So if you're looking at 3 dimensions, you have Y, X1, and X2. What we're looking at is you kind of think of like a 3D plane, and as X and Y, X1 and X2 change, how does this affect Y? So you think of it like a plane. And then, of course, you can have higher dimensions from there. So we first begin by looking at simple linear regression. So in its simplest form, linear regression involves a single independent variable and models the relationship between the dependent, which is your Y variable, and the independent variable, or your X variable, as a straight line. This is called a simple linear regression. So the equation for a simple linear regression is Y is equal to beta 0, that's your intercept, plus beta 1 x1 plus your error. Beta 1 is that coefficient that actually explains as X changes, so as X goes from 1 to 2, from 2 to 3, from 3 to 4, how much does this change Y? Because beta 0 is a constant. That's your Y-intercept. That is the value that you have when X1 is equal to 0. And then it is saying, as X increases by 1, how much would your graph change? As X increases by 1, how much would your graph change? And then you connect this with a straight line. So Y is your dependent variable, X1 is your independent variable, beta 0 is your intercept, this is the Y value when X1 is 0, beta 1 is the slope or coefficient of X1, this is the average change of Y as you get 1 unit of change in X1, and epsilon is the error term, also known as the residuals, representing the difference between the observed value and the predicted value of Y. So what does this actually mean? Well, if I were to take my X and Y values, and I made a scatter plot of those values. When I make my linear regression, this error term represents, or your residuals represent how far off your line is, which is your predicted value, from the actual values. And then what we're trying to do when we create a linear regression is we're trying to find the best fit line, which is the line that minimizes the residual error, or specifically the root mean square error is usually what we'll use when we're trying to create that best fit line. And that's actually how the computer will determine what is the best line that represents this data. When we have multiple regression, this is when you have two or more independent variables. This model is called multiple linear regression, not to be confused with multiple regression. That's a little bit different where you can have more than one y value. The equation for multiple linear regression is y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus up to and including beta n xn plus your error or your residuals. So y is your dependent variable. X1 through Xn are your independent variables, beta 0, still your intercept, and then beta 1 through beta n are the coefficients for their respective independent variables. And then, of course, again, we have our residuals. This works exactly the same way, it's just that, again, in a higher dimension. So whenever you're actually doing this, though, like, for example, when I'm teaching this in Intro to Stats, we talk about, perfectly positive correlation, strong positive correlation, things like that, to determine how strong is the relationship between our x and y and how well it can be modeled by using a straight line. So we will have stuff like that. We'll have these metrics we look at to determine how good of a best fit line, because there may be a trend whereas x increases, y also increases, but based on how far the actual values are away from that line, that linear regression, that would actually determine how strong a relationship. Is it perfectly one-to-one as x increases by 1, y also increases by 1? Is it, that there's some error to it, things like that. So when we're doing linear regression, our objective is to find the values of beta 1 through beta n that minimize the sum of the squared residuals. So you take those residuals, that's the difference from your actual values to the predicted value, which would be your line or plane, and then you want to square those terms because you expect, if it's best fit, that you're going to have some values above, some values below. If we were to just average those out, we would always get some value near 0. So what we're doing is we're going to square them. That way we have all positive values, and we're going to look for the line that minimizes those squared residuals. And this method is actually known as the method of least squares. Now, there's various techniques we can use to estimate those coefficients. These include things like normal equations, gradient descent, and maximum likelihood estimation. And these are actually all very interesting and important topics in their own right. For example, gradient descent is something that we use quite a bit in machine learning. And you learned kind of the gist of it when you took calculus, for example, when you learned things like maximization or minimization problems. You're kind of looking at a method of an analytic approach to gradient descent. But computers, a lot of times, will use other methods similar to like Newton-Raphson, things like that, where it's going to use different algorithms to try to determine where the maximum or minimum is. So gradient descent being the minimum. Maximum likelihood estimation is a topic we cover quite a bit in mathematical statistics. And these are ways that we can try to determine which is the best fit. And this is something to kind of think about, is that when you're doing linear regression in R, it's going to by default do all this under the hood. But it's good to understand what it's doing because this is how you can create something different. Or if you have options, you might be able to change which method you're using. For example, let's say that you wanted to know the shortest distance between 2 points. Most people would just say, okay, well, I'll take y2 minus y1 over x2 minus x1, or the change in y over the change in x, which is your Euclidean distance. It is the distance between 2 points is a straight line. But you might have a different distance, like a Manhattan distance, where you're looking at it sort of like city blocks. If I want to get from point A to point B, I can't drive this direction. What I have to do is I have to figure out what's the shortest path based on changes in x and y sort of independently. And these are the kind of things that can change your results, because if you have one assumption, you might get a best fit line. Using a different method, you might have a slightly different best fit line. And these are all things you would consider when you're doing this. This is where your strength in actual understanding of statistics is a real strength. Because when you're using R or Python or any other tool, by default, it's going to have certain methods that it uses. But understanding what those methods are, their assumptions, their weaknesses, their pros, cons, strengths, whatever it is, that can be very helpful. Now let's actually look back at hypothesis testing for a second. So hypothesis testing is used to determine the statistical significance of the relationship between the dependent and independent variables. If you watched the hypothesis lesson that I recorded, you would actually see a short demonstration of this, where when we create a model, if we do the summary, it is automatically going to run a hypothesis test. The null hypothesis is going to state that there is no relationship between your variables. That is to say, all your coefficients are equal to 0. Or if you want to write it mathematically, you'd write your null hypothesis is beta 1 equals beta 2 equals beta 3 equals up to beta n equals 0. Our alternative hypothesis is that there is a relationship between the variables, or at least one of the coefficients. So we just have beta 1, beta 2, beta, one of them is at least not equal to 0. And what this means is we're testing, does any of the independent variables that we have model relationship with our y variable with some statistical significance. And we're saying the alternate is that at least one of them does. R is going to automatically run this in the background when you create a regression. And it is going to give you a p-value to tell you what is significant and at what level it would be significant for your hypothesis test. So by calculating the t-statistic and p-value for each coefficient, we can determine whether the relationship is statistically significant. Again, this is not anything you have to do on top of your regression. It will be done automatically by R. Once you've actually created this linear regression or multiple linear regression and your coefficients have been estimated, the model can actually be used to make predictions about new data points. Because when we're looking at the residuals, we're looking at known data points and how far off they are from our regression line. Depending on how strong and how statistically significant that regression is, you can actually then make predictions about unknown data points. Now, one thing I do want to point out, when you are doing this though, you need to be within or close to the range of your original data. So if my original data goes from values from 9 to 864, that means that if I'm a little bit below 9, let's say it's 8, or a little above 864, like 866, that should be fine. But I can't then make some prediction about what it would be if X was equal to like 1,376. And this is where sometimes people get into problems, because you start with this, let's say we do a simple linear regression. You get this simple linear regression and your data is like here to here. And then they kind of extrapolate what's happening way out here. But this is an area where this test is, or this regression is not, we can't make any assertions based on that once we go beyond the data that we actually built our regression on. And this is very important because this is where you get to those kind of like ridiculous graphs where, let's say, in the last 50 years, we've had 5% growth annualized, blah, blah, blah. We can't extrapolate out that by, 100 years from now, we're going to be at this level, right? Because it doesn't have, we have no indication that it's going to continue that trend beyond a little distance away from where we actually are. This is where you have to be very careful when you're doing this sort of trend analysis. So additionally, confidence intervals can be calculated for the coefficients and predicted values, providing a range within the true values are likely to lie within a certain level of confidence. So like, for example, your confidence level is 0.95. So when we actually have our regression line, you can actually think of at any point we could put on there, we can get a point estimate and also a confidence interval to kind of estimate if this is what we believe the value is, and then this is sort of the interval that it actually probably falls within. When you are making a model, for example, like a linear regression or multiple linear regression, or any model really, you need to consider how you evaluate and select your model. So evaluating the performance of a linear regression model is crucial to ensure its validity and reliability. There are several metrics that we can use to assess the quality of our model, including things like R squared. This is also known as the coefficient of determination. R squared measures the proportion of the total variance in the dependent variable that is explained by our model. And R squared values will range from 0 to 1, with higher values indicating a better fit. And you have to be a little bit careful with this because sometimes you would actually want to use what's called an adjusted R squared. So adjusted R squared is a modified version of the R squared that adjusts for the number of independent variables in the model. It penalizes the addition of irrelevant predictors and is particularly useful when comparing models with different numbers of predictors. So what this means basically in a simpler way is when I have more variables and I just keep adding variables, they all might add just the tiniest little bit of change, almost insignificant, but my model would be seen as being more accurate. And this can actually lead to what is called overfitting. So what the adjusted R squared is doing is it is penalizing every time you add a new variable. And so it's kind of a way of balancing, did my model get better enough to justify adding that new variable? So it kind of focuses on having the best model, but also simplest model that you can to actually use for prediction. Right? This is to help us limit things like overfitting, where we just throw 1,000 variables at it and we're going to get a very accurate model, but it's not very reliable. And this is actually something I see all the time. You'll see things where you have some model and they're like, we've got 2.6 billion parameters. And all I can think to myself is, great, you've got 2.5 plus billion worthless parameters in your model. You, as a statistician, we want to focus on having the best simple model. And the reason we do this is because when you have a lot of variables that are contributing very little, you're basically adding what's called noise. So while you might be fitting those dots a little bit better, you can make a super complex model and it will perfectly fit the data points you have. But then give me any other new data point, and now suddenly this model is worthless. So we want one that might not be as strong of a model, right? It might have a little bit more residual or error in it because we have less of the variables modeling it, but it also means that it is more robust when we're actually applying it to something new, right? Because we don't just want to have a line that describes the data we have. We actually are doing it for a reason, which is usually to assume or predict what the models, the numbers would be for some other x values. Another way that we can assess our model is using mean square error. So mean square error measures the average square distance between the predicted and actual values of the dependent variable. The lower MSE indicates a better fit. So this is what I was talking about earlier about what we would do is we would take the square error. So we take the error residuals, which are the distance from your actual values to the predicted, which is on the line. And then once you square those, then you just take the average of those. Once you have your mean square error, if you did another best fit line, you do a bunch of them, the one that has the lowest mean square error would be the best fit line of those. You can also do the root mean square error, which is actually what we usually do. So then you take the square root of that and you're good to go. So the root mean square error is a square root of an MSE and is a useful measure of the model's prediction error in the same units as the dependent variable. So while both MSE and RMSE kind of measure the same thing, we generally focus on RMSE just because it's in the scale of the actual data. So it makes it make a little bit more sense. It's kind of like comparing standard deviation and variance. Variance and standard deviation both measure variability in data, but standard deviation is at the scale of the actual data. So while in a lot of equations we use variance, standard deviation oftentimes is what we'll actually talk about because it makes sense because it's in the scale of the data. You can also use things like, I'm not even going to try to pronounce this name, but AIC. So AIC and Bayesian Information Criterion, BIC. Both AIC and BIC are used for model selection and are based on the likelihood of the model while penalizing for the number of parameters. So lower AIC or BIC value indicates a better fitting model. So much like when we were looking at our adjusted R squared, this is looking for how well does the model fit while having a penalty for adding more variables. And a lot of times this is actually what we will use. When we're, like, for example, if I'm writing a paper and I want to show why a certain model is better for predicting something, whatever it is, oftentimes what reviewers will want to see is they will want to see the AIC or BIC, because this is a way to say that not only by adding this variable or these variables that the model got better, but also with the penalty by adding more variables, it was enough to significantly actually increase the accuracy of the model, not just, again, throwing more variables, getting a higher value without any penalty. When you are modeling, you may also, in some cases, have what are called categorical predictors. So in some cases, the independent variables may be categorical rather than continuous. Now, there's two types of categorical variables that you may have. You may have nominal variables, which are in name only. This would be something like, has diabetes, yes or no. This is a factored variable, but also you can think of it like a nominal, right? It's just a label, right? If we label people by some demographic information, I'm not going to say any particular ones, but it could be like group 1, group 2, group 3, and group 4. Now you have a factor that is in name only. You could also have ordered variables, which would be things where they are labeled, but there's some sort of ordering to it. First, second, last place, or, terrible, not, kind of bad, neutral, decent, amazing. These would be things where, again, these are just categories. There's no direct way to compare them, except for we now have an ordering to them so we can compare that this is better than that, this one is worse, things like that. So to include a categorical predictor in a linear regression model, we can use what's called a dummy variable, which are binary variables representing the presence or absence of a particular category. One category is chosen as a reference category, or your baseline, and the dummy variables are created for the remaining categories. The reference category is represented by the intercept, that is when all the others are 0, while the dummy variables represent the difference between the category they represent and the reference category. So actually, I do want to clarify here, there's actually two ways we can do this. If you have ordered data, sometimes you will have a single variable which represents a consistent change between them. So as I go from my baseline, which is a 0, and I go up to 1, go to 2, go to 3, they all have the same beta because they're all one variable. So therefore, we're saying as I increase this, it increases by this amount. This might be something like for every hour you study, your grade should go up by 3 points. So beta would be 3. So if you put in 1 hour, it goes up by 3 points. If you put in 2 hours, it goes up by 6 points. If you go up by 3 hours, study 3 hours, it goes up by 9 points. Or you could use a dummy variable. This would be something like, your baseline is when all of them are 0. So it'd just be your intercept. Or you could have when, they're part of group 1, this one is a 1, the others are all 0. When they're part of group 2, this one is 0, the second one is 1, the rest are all 0. And you only have that one dummy variable active showing which group they are a part of. And that way they can each have their own coefficient attached to them, meaning that one might increase, let's say it scores, your score by 4 points, while another one might decrease your score by 2 points because it might be detrimental. So this is the nice thing about dummy coding variables, is that you can have different effects, not just some jump, because that assumes that they would all be equal. You can also have interaction effects between your variables. So interaction effects occur when the effect of one independent variable on the dependent variable depends on the value of another independent variable. So to include an interaction effect in a linear regression model, you would create what are called interaction terms, which are the product of the interacting variables. Including interaction terms in our model allows us to capture and understand the complexity of relationship between variables. By the way, I do have a slide later on where I actually talk about how do you include these when you're doing your modeling in R. One thing I want to talk about, again, before we actually dive deeper into this, is I want to talk about the limitations, because every model, every statistical model that exists has certain assumptions. It has certain limitations. It has certain pros, it has certain cons. That's why we have so many models. There's no one model that is best, and anyone who tells you there is incorrect. So while some models might be very strong, like random forest or certain boosting algorithms, there's no one size fits all model. And they always will have some assumptions and limitations associated with it. So linear regression has its own. While linear regression is a powerful and widely used technique, it has some limitations, including linearity assumption. Linear regression assumes that the relationship between the dependent and independent variables is linear. That is to say, you could model it with a line. If the relationship is nonlinear, the model may not accurately capture the relationship, right? I already talked about that one. Multicollinearity. Multicollinearity occurs when two or more independent variables are highly correlated, which can lead to unstable coefficient estimates and reduced model interpretability. And I will tell you right now that multicollinearity is an assumption, or no multicollinearity is an assumption that many different models have. And this is actually one that will make a lot of models fail. Because remember, you will always get an output. But the question is, how reliable is it? So you should always check these assumptions before you do any modeling. If I have 10 independent variables, one of the first things we're going to do is we're going to do a correlation analysis to make sure that we don't have multicollinearity. And if we do, that means we might have to use a different model, because if it has decent or higher multicollinearity, linear regression is not going to be trustworthy. I'll get a result, but I can't trust those results. They won't be robust. And I might need to use a different model that can deal with a certain level of multicollinearity. Next, we have outliers. So outliers can have a significant impact on coefficients and overall model performance, potentially leading to biased estimates. Because remember, we are looking at that error rate, right, your residuals, and we're looking at something like the root mean square error, meaning if I have some outlier that's way up here, what's happening is it's going to pull the whole model up a little bit because it's going to be affected by outliers, because it's going to try to minimize all of the residual error. So that means that including that outlier, and that outlier is going to pull it up. Next, we have heteroscedasticity. So linear regression assumes a constant variance of the error term across all levels of independent variables, that is homoscedasticity. If the variance is not constant, heteroscedasticity, it can lead to inefficient estimation and incorrect inferences. And then finally, normality. The error term is normally distributed. So you can see that there are a lot of assumptions in using linear regression. And this is, again, one of the shortcomings a lot of people have is when they learn how to do modeling, especially when they don't focus on the statistical core and just focus on how do you implement it. I mean, again, if you give me data, I can make a linear regression or multiple linear regression anytime. It literally, as long as the data is all there and I don't have NAs and all that kind of stuff, it's going to work. But I need to check. Does a linear relationship actually seem to occur between my x values and my y? Is there multicollinearity that's going to lead to issues? Do I have any outliers? Is my data heteroscedastic? Do I have normalized error? These are all things that can mess up the reliability of your model, which is why we I focus so much on like model validation, because you need some way not only to see how well does the model work, we need a way to validate it on some data it hasn't seen before to actually test whether it actually seems to work. If some of these assumptions might not be true, it does not mean that the model is worthless. It just might mean that it's not as reliable. There's a couple things you could do. First of all, you could use a different model that doesn't have those same assumptions, and therefore you kind of just bypass it. Or you could rely on transformation. To overcome these limitations, various techniques can be applied, such as data transformations, regularization methods, or alternative modeling techniques, like I was just talking about. Things like, instead of using linear regression, you might use generalized linear models or even nonlinear regression. So data transformations can help address some of the limitations of linear regression, such as nonlinearity, heteroscedasticity, and presence of outliers. Some of the common transformations you might see are a logarithmic transformation. So taking a natural log of the variables can help stabilize the variance, it can reduce the impact of outliers, and it can linearize the relationship. So log transforms are especially helpful when the variable exhibit an exponential growth or decay pattern. So if you have data that seems to be exponentially growing, by sort of taking the log of it, it's going to flatten it all down quite a bit. It's going to lower the outliers, and this can actually be enough a lot of times to make it work the way you want it to. You could also do a square root transformation. Taking the square root of the variables can help address nonlinearity and reduce the impact of outliers. It's particularly useful when the variables exhibit a quadratic relationship. Or you can do something like a Box-Cox transformation. So this transformation is a family of transformations that include both logarithmic and square root transformations. By estimating a parameter lambda, the Box-Cox transformation can automatically determine the most appropriate transformation for your data. You also could use regularization methods. So regularization methods are used to prevent overfitting in linear regression models, particularly in cases of multicollinearity or when the number of predictors is large compared to the number of observations. So some common regularization methods include things like ridge regression. So ridge regression will add a penalty term to the least squares objective function, which is proportional to the sum of the squared coefficients. Penalty term shrinks the coefficient towards zero, reducing their magnitude and mitigating multicollinearity issues. Now, one thing I want to point out though, it does not reduce them to zero. Means that when you do ridge regression, it will, if you have a ton of variables, for example, lower their impact, but it will not do variable selection. Lasso, on the other hand, is going to have that penalty that actually can do variable selection. So lasso regression also adds a penalty term to the least squares objective function, but the penalty term is proportional to the sum of the absolute values of the coefficient. This can result in some coefficients being exactly equal to zero, effectively performing variable selection and producing a sparse model. And then, of course, you have elastic net regression, where it actually does both of these things. Elastic net regression combines the penalties of both ridge and lasso regression, allowing for both shrinkage and sparsity in the model. So mixture parameter alpha is used to control the balance between ridge and lasso. Now, there are other ways you can do this as well that are actually, possibly simpler. For example, some people will use what's called a stepwise regression, where what they're going to do is you start with a single variable and then you try adding every single other variable, see which one makes the model better, and then you keep doing that until you no longer pass some threshold of making the model better. You could also do your stepwise function the other direction. You can have every variable, and then you're going to try subtracting each one individually, see which one makes the model, change the least while still having less variables. And this is a way to kind of do variable selection as well. There are some issues with stepwise regression, but just know that it's also a possibility you could use. If your linear regression does not adequately capture the relationship between variables, there are alternative techniques that you might want to consider. For example, generalized linear models. GLMs extend linear regression to model a relationship between dependent variable and independent variables using a link function, allowing for non-normal error distributions and non-linearity. Examples of GLMs would be things like logistic regression for binary outcomes and Poisson regression for data count. In fact, if you ever take categorical data analysis, it's almost all GLMs. You can also have nonlinear regression. So nonlinear regression models the relationship between the dependent variable and independent variable using nonlinear functions. So nonlinear regression can capture more complex relationships than linear regression, but may be more challenging to fit and interpret. So the issue with non-linear regression a lot of times is you have to figure out what the nonlinear regression is. So is it squared? Is it cubic? Is it quadratic? You have to figure out what the actual non-linear relationship is to properly model it. Because my data looks like it, kind of arcs up like this. At what rate, right? Because you want it to be an accurate model still. You could also use something like tree-based methods, things like decision trees, random forest, and gradient boosting machines. So these can model complex relationships between variables that can handle both continuous and categorical predictors and are robust to outliers and multicollinearity. These methods can provide more flexible alternative to linear regression, but may be more computationally intensive and harder to interpret. So remember I told you there's no best fit or model, anything like that? Tree-based methods generally will outperform most other models. Their problem is they're what is called a black box method, meaning if I do a random forest, yes, technically I can go individually look at every forest, but the way that a random forest works, you start by bootstrapping your sample into a bunch of samples called bagging, and then at every step, it's going to make a decision. It's going to take a proportion of your total parameters, usually the square root of whatever the number of parameters is, and it is going to determine what is the best split. And it's going to do that until it gets a tree. And then you're going to repeat that, and you're going to make many, many, many trees, making the forest. And then when you have let's say I put a new data point in, it is going to check every tree. This one has this answer, this one gives this answer, this one gives this answer, and it's going to do that for all of them. And then it's going to aggregate them together, which we call an ensemble. And then from there, it's basically going to vote on what the best answer is by the one that happens most often. So this would be something like for classification. For regression, it works basically the same way, except for it's going to kind of average them out. Boosting, similar idea, except for, you're going to bag your sample, you're going to create the trees, and then you're going to go back with that new data starting as your starting point, and you're going to repeat this so many times. These methods work very well for most things. But again, they're hard to interpret because they're black box. You do not have some nice clean model like these other methods where you can say, as X changes by 1, it changes by this amount or something like that. The other issue is they can be computationally intensive. The one time I've ever actually crashed R doing any sort of computation was with random forest, because I was creating a very large forest of these random forest trees, and it holds all of that in the memory. So that means if you have 1,000 trees, you first of all have to create 1,000 trees, but then your memory is going to be holding 1,000 trees. So when you want to do that actual analysis, it has to go through and test on 1,000 different trees. So if you pick too many trees, it can actually fill up your memory and cause your computer to lock up. And of course, the issue with that is when you try to start back R again, what's going to happen is it's just going to try to load up whatever was in the memory last time you had R open. So what you'd actually have to do is manually crash R, tell it to start without anything loaded, and then you can start back up. Now's the part where we get into the R component of this. So we're going to specifically be looking at linear models, so linear regression. So we're going to be using the LM function. Now the syntax is we have LM, and then you have your formula. You put your data, then you can do subset, weights, na.action, method, model equals, and the default is true. X equals by default is false. Y equals by default is false. QR equals true. Singular.ok equals true. Contrast equals null. Offset. There's a lot of options you can do when you're doing linear regression. And this is where, when I kind of talked about the type of data you have and what kind of regression you're doing, this is why it's so important. The most easy, simple linear regression, it is literally just going to be LM, your formula, and then your data. That's all you have to include. But if you want to add any sort of weights to it, if you want to add any sort of subsetting to it, if you want to use a different method, like we talked about, remember we have different methods we could use to actually determine what's the best fit, things like that. This is where you could change it with these different arguments. And this is all part of the base R package. You can, of course, get much more complex models by loading in other packages. So let's dive deep into what those different arguments are. So formula, this is a symbolic description of the model to be fitted. The formula should be the format with a tilde and then predictors. So it's response, tilde, and then predictors. And how you connect those predictors will determine how it actually does the model. For example, model relationship between y and x1 and x2, you would write this as y tilde x1 plus x2. And that was going to basically look at, as x1 and x2 changes, how does this impact y? The data argument is the data frame containing the variables in the formula. If not specified, the variables are taken from the environment in which lm is being called. A lot of times when you see me doing this, if I want to specifically call it, I will do something like if I'm doing empty cars, I can do empty cars, money sign, and then what I want it to be my y and my x's. Or I could do, like mpg tilde wt plus whatever, and I can put data equals empty cars. Or if I have empty cars loaded as a currently in my state of where I'm at, it can refer to it there as well. So there's kind of three different ways, but if you want to be explicit, you can write it out. If you want to, you can also just use data equals and then put what the data is pulling from, and you don't have to put empty cars every single time. Subset is an optional vector specifying a subset of observations to be used in the fitting process. This would be something like, for example, if you only wanted certain observations, or if you were, maybe doing holdout method, you might want to specifically say only use the first 80%, something like that. Weights is an optional vector of weights to be used in the fitting process. Observations with higher weights are given more importance during the model fitting. Na.action is a function that indicates what should happen when the data contains missing values, or NAs. The default is set by na.action option in R, which is typically na.omit, meaning generally if you have NAs, it's just going to automatically omit that. And this is where like your data cleanup and transformation and EDA and all that kind of stuff is super important, because if you don't check the data first, you run a regression, you might lose half the data because they have NAs in them and you didn't even notice, because, it'll give you a warning that there were NAs, but it won't tell you how many. And what it does is just removes the observations with missing values from your analysis. So you're not even getting the full analysis. And then there are other arguments. So again, there are additional optional arguments such as method, model, x, y, qr, which control various aspects of model fitting and output. In most cases, the default settings are going to be what's appropriate for you, and you don't really need to change them. But if you do, this would be when you want to dive more into the documentation, because you'll want to understand what to use for your special case. Let's dive a little deeper into that formula part, though, because that formula part can be a little bit complex. So in R, a formula, and by the way, this is for all models, not just linear regression. A formula is a special data class created using the tilde operator, which splits your responses from your predictors in the sense that you have response, tilde, predictors. Your standard arithmetic operators, so plus, star, colon, and caret, take on completely different meanings when used inside our formulas. They are symbolic layout shortcuts rather than mathematical operations. This is going to be important, meaning that if I do x1 plus x2, it is not adding them together. If I do x1 star x2, it is not multiplying. If I do x1 colon x2, it is not giving me a sequence. And if I do x1, caret 2, it is not squaring my terms. So understanding these symbols allows us to express highly complex model architecture cleanly in a single line of code. So let's look at what they are. So the first one, which is one I mentioned when I was first introducing the formula, is the plus operator. So this will add a variable additively as a main effect control without any interaction between them, meaning that it is going to model, in this case, y tilde x1 plus x2 is going to model the effects of x1 and x2 on y. So it would be equivalent of y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus your error. The colon operator computes only pure interaction, that is the cross product between two variables. This will omit their individual main effects. So for example, y tilde x1 colon x2 will model y equals beta plus beta 3 and then x1 plus cross x2 plus your error. So if you wanted to have the main effects and an interaction, you would want it to be like y tilde x1 plus x2 plus x1 colon x2. Then we have our asterisk operator. This will compute the full saturation of variables. It will automatically build the individual main effects and their corresponding interactions. So this is another way you could do it. Instead of explicitly saying x1 plus x2 plus x1 colon x2, you could just say y tilde x1 star x2. And this would be equivalent to y tilde x1 plus x2 plus x1 colon x2. So the star will just basically say it is going to take every individual variable and all of the interactions between them. So if you have three variables, it's going to be x1 plus x2 plus x3 plus x1 interaction with x2, x1 interaction with x3, x2 interaction with x3. So it's going to be all of the individual interactions. And then it's also going to have the interaction between all three, x1, x2, and x3 together. So this one is everything. The next operation we have is the power operator. This will restrict full interaction expansions to a specific maximum degree. So for example, if we had y tilde x1 plus x2 plus x3, this is supposed to be caret 2, but it looks like PowerPoint automatically squared it. This will include the main effects of all two-way interactions, but it will drop the three-way interactions. So just like the star, it'll do x1 plus x2 plus x3. It'll do the interaction between x1 and x2, x1 and x3, and x2 and x3, but it will not go higher. So it means it will not do x1, x2, and x3 together interacting. Again, this is caret 2, but again, PowerPoint automatically made it a square. So it's not a square, it's the caret operator, and then at what level. So if I have 8 variables and I do caret 2, it is going to do all the individual variables, x1 through x8, so x1 plus x2 up to x8. Then it's going to do all of the double interactions, but it won't do any of the higher interactions. The dot shortcut is a time-saving shortcut, meaning regress against every single remaining variable found inside a specific data frame. So the way this one works is you will use lm y, whatever your output variable is, tilde dot. So if I have a data frame made up of 8 columns, one of them is my y column. That means I have 7 individual variables that are not y. Those are my x values. I can do y tilde dot, and it will use those 7. So it'd be like x1 plus x2 plus this up to x7 all together to model y. So it's just a shortcut that we can use. So this would be something like lm y tilde dot data equals, and then whatever your data is, like empty cars. So this will regress y against all other columns. So this is just, again, a shortcut. If you know you're going to be modeling everything, you can just do dot. In fact, I think when I showed my little mini example when we were doing hypothesis testing, I did exactly that. Next, we have the conditions or grouping operator, which is the vertical bar, which you can find above your backslash, usually above your enter. So shift, where your backslash is, you'll get your vertical bar. In standard LM, the vertical bar is not a valid regression operator and will cause parsing issues. Sorry, this is more for different advanced modeling techniques, but I wanted to talk about it while we're talking about different formulas for modeling. So in advanced packages, things like LM4 or mixed effects modeling or lattice for graphics, the vertical bar, indicates conditioning or grouping. So for example, you would have something like y tilde x bar and then group, whatever it's being grouped by. So it models the relationship of y on x and the condition on or grouped within each of those distinct level groups. So something like this might be something like if I'm doing a mixed effects model and I want to see what the effect of school and teacher is on student outcomes, I would have students grouped by teacher, grouped by school, or something like that. So these groupings would be then, instead of, I'm not looking at how well did the students do on their own, I'm looking at how well did the students do based on the fact that they are grouped by some other factor, let's say school or teacher. Now you might be thinking, based on what we were just talking about, what if you actually want to model a polynomial relationship? For example, when we did the caret 2, which looks like a square, because again, PowerPoint automatically did that. What if I actually wanted to do a square term? What if I wanted to do x squared? Well, the way you could do this, if you were to write y tilde x plus x, caret 2, R is going to interpret this as caret 2 as an interaction rule, and silently it's going to discard any duplicate main effect. Okay. So what you need to do is you need to wrap your true mathematical expression in the inhibitor operator, which is an I and then parentheses. So this will force R to temporarily drop its formula shorthand logic and calculate the raw math first. So if we did y tilde x plus I parentheses x squared, or x caret 2, again, PowerPoint, what this is saying is that I want you to model y with x and, using the inhibitor function, x squared. So I've added this polynomial in by using it within the inhibitor function. So this would model y equals beta 0 plus beta 1x plus beta 2x squared plus your error. So now let's get into some actual examples. So the first one we're going to do is a simple linear regression. We are going to create a model called model, and we're going to use LM for linear model, and we're just going to model the miles per gallon, how miles per gallon is affected by our deep independent variable, which is weight, and this data is going to come from empty cars. So let's do exactly that. So first things first, we create our model. And if I actually pull up my model, this is what you're going to see. It's going to tell you that the call was LM formula is miles per gallon is modeled by weight. And data is MT cars, it's going to give you your coefficients. You've got your intercept, 37.285, and you've got your coefficient for your variable, which is minus 5.344. So what this means is as the weight goes up by 1, my miles per gallon will go down by 5.344, which I think the weight is like by 1,000 pounds. So that's what this model looks like. Okay, great. So now I could actually write this model out. I could literally write y equals 37.285 minus 5.344 plus x plus my error term. So now let's run summary and let's see what it shows. So what this is going to show now is it's going to, like before, going to call in the formula so we can see exactly what our formula was. It is then going to give us information about our residuals. Remember, that's just our error. It's going to give us our minimum. It's going to give our first quartile, our median, our third quartile, and our maximum. It then is going to give us our coefficients. So for our intercept, we have a value of 37.2851. For our weight, we have a coefficient of negative 5.3445. So those are the two that we had when we just looked at the model. This will then give us our standard error for intercept and weight. We will then get a t-value for intercept and weight, and then we will get our p-value. Remember, that's that hypothesis test running in the background. So for our intercept, we have a p-value of 2 times 10 to the negative 16. Actually, less than that. Just that's why there's a less than. That's where it stops. And for our weight, we have a p-value of 1.29 times 10 to the negative 10. And both of them have a star rating of 3 stars, which means that this would be significant at a level of at least 0.001 for your level of significance. Then below this, we have our residual standard errors. We have 3.046 on 30 degrees of freedom. Below that, we have our multiple R squared, which is 0.7528, and our adjusted R squared. So remember we talked about our adjusted R squared? Notice it's not much different because we only have that one variable. If we added a lot of variables, you might see some difference between these. And then last, we have our F statistic of 91.38 on 1 and 30 degrees of freedom with a p-value of 1.294 times 10 to the negative 10, which, by the way, if you're ever doing prediction models and things like that, you oftentimes are going to be reporting F statistic. It has to do with confusion matrices and all that kind of stuff. So now let's actually kind of change things up a little bit. Let's do the dot operator we talked about. So I'm going to do model, and I'm going to do LM, and I'm going to again do MPG. I'm going to do tilde, and then dot, and then data equals MT cars. So now if I run this, notice what it did is instead of doing my model where it's just modeling based on how the miles per gallon are affected by the weight of the car, it is taking how the miles per gallon are affected by all of the other variables in MT cars. That means that I have my intercept, I've got my coefficients for cylinders, displacement, horsepower, weight, quarter second time, things like that. So if I were to run a summary on this model, it's going to be the exact same stuff, but it's now going to have all this information for every single one of the variables that were included in my multiple linear regression. So we've got our estimates, we've got our standard errors, we've got our t-values, and we've got our p-values. And then just like before, only one of them is weakly significant, which is, of course, weight, which is why I used it in the original example. But notice our multiple R squared, our adjusted R squared is a little bit different here. Now, this one, of course, is not majorly different because it's just not modeling very well. But we have 0.869, and it goes down to 0.8066, meaning if we consider the complexity of the model, it's not measuring as much of the variability in our dependent variable with all of our independent variables. And I have actually, a lot of times if on my slides for things like this, I actually have information about the output so the students can like go through and like read it individually, stuff like that. But if we actually look at the one I kind of want to focus on here, though, again, is R squared. We got a proportion of total variance in the dependent variable explained by our model. We've got our adjusted R squared, which is a version of R squared that adjusts for the number of predictors in the model. And then we have our F statistic and p-value. The F statistic and its associated p-value will test the null hypothesis that all coefficients are equal to 0. So looking back at this, sometimes you'll see your F statistic here, depending on what you're modeling and what kind of model you're doing, stuff like that. You can actually extract specific components of your linear model objects, such as coefficients or residuals, using a money sign operator by using the functions such as coef, resid, fitted, or predict. And these will give you different parts of your actual model, right? So if I did something like names model, you will see these are different things we can call on. We can call on our coefficients, residuals, effects, rank, fitted values, assign, QR, DF residuals, X levels, call, terms, model. So if I wanted to just get the coefficients, I could do something like so when it gets like for example, the coefficients, I could do something like model money sign coefficients, and I could run that and it would give me all my individual coefficients. Or I could use the coefficients function, which is coefficients, parentheses, and then whatever you're trying to pull the coefficients of. So in this case, model, and you will get the exact same thing. We can also use the shorter version, which is coef model, which will give us our coefficients. If I wanted my residuals, which again is the error, I could do model money sign residuals, or I can use the residuals function on model, and I will get my individual residuals. If I wanted to, I could use a shorter version for resid model, and it will give me the exact same thing. Similarly, if I want the fitted values, I could do model money sign fitted.values, or I could use the fitted values function, which would then give me my different fitted values. Apparently, I capitalized it. There you go. And it will give me my fitted values for each of these. Or I could just do fitted on my model, and it also will give me the exact same thing. For our next example, we're going to be looking at creating a model with interaction effects between all variables. So looking at our code, actually, let's just jump straight to our code. You're going to see that I first set a seed, just because this one, I'm using randomized data, so I'm not using data from a data set or anything like that. So I set the seed using 42, and our data is going to be set as data.frames. We're creating a data frame. We're going to have our y values, which we're going to do r norm 100. So we're just going to pull 100 values from a standard normal distribution. X1 is also going to be r norm 100. X2 is going to be a factor. So we're going to sample A and B 100 times with replacement. And then our third X value, so X3, is again going to be r norm. So if we run this, we will get our data frame, which is going to look like this, which I should have changed this. We talked about our clean code and all that. I shouldn't have put data. I should do something like my data or something like that. But you'll see that we have our Y column. We have our X1 column, which again, these are both from a standard normal. We have X2, which is a factor of A or B. And then X3 is also from a normal distribution. Okay, so this is what we're actually modeling then. We're going to do Y tilde X1 star X2 star X3. So what this is saying is that I want to take all of the individual parameters, so x1 plus x2 plus x3, and the interaction between x1 and x2, x1 and x3, x2 and x3, and the interaction between x1, x2, and x3. So this would be all interaction effects between all three variables. So let's do that. Okay, this is, by the way, the reason you don't want to name data, because now this term kind of doesn't make sense because we've defined what data is. It does work, but it's bad practice. My data should have been my data. In fact, I updated later things, but we now have our model and we can look at it right here. If we load up model, we can see that it's calling on x1 star x2 star x3 and it's pulling data from data. And you will see that we have our intercept. We have our x1 term. This is our coefficient. We have our coefficient for x2b. We have our coefficient for x3. We have our coefficient for x1, x2b. We have x1, x3. We have x2b, x3. And we have x1, x2b, and x3. And this is because our baseline for our factor, right, our x2, is A is 0, B is when x is equal to 1. It's a dummy variable. It's either on or off. So what it did is it uses A as our baseline, and B, that's why every one of them says x2b, because it is x2 and it is B. Now, one thing I want to point out very quickly is this is the one place you have to be careful when you are comparing between different languages or programming environments or whatever analysis tool you're using, because R will use the first point as your baseline. Other programs, for example, SAS by default might use something else like the last term as your baseline. And both of them are completely accurate, but you will get different models. And this is where it's important to understand that. Now, you can change when you're using dummy variables which of the factors is your baseline. So let's say it was A, B, and C. A can be my baseline, and then B and C are compared to that. Or I could have C as my baseline, and A and B are compared from that. So now let's actually look at our summary. And this one is a little bit cleaner to look at. So you can actually see all the coefficients together, but we got our x1, we got our x2, we got our x3, we got x1 interacting with x2, x1 interacting with x3, x2 interacting with x3, and x1 interacting with x2, interacting with x3. And if we look at all of our information that we have, right, same information is going to show up, just going to be more variables. If we look at our p-values, you can see that our interaction between x1 and x3 is a little bit significant. It's weakly significant. And our interaction between all three of them, x1, x2, and x3, is significant to a 0.05 level. So pretty strong significance there, which we know that is just complete happenstance because this was randomized data, meaning that we actually know that this is nonsense. And this is where you have to be careful about adding more variables, because if I add enough variables, something is likely to be significant. Now, when it's actual data, if there's any sort of correlation or multicollinearity, this might not happen, because what's happening then is, instead of having all the significance go to one, it's kind of splitting it. But it's just kind of stuff to keep track of. And this is why a lot of times you'll have people, when they're trying to like do stuff like p hacking and stuff like that, they'll just throw different variables to see if something seems to be significant. They're not coming in with an actual hypothesis. They're just seeing what seems to have a significance according to the data they have. And that's not a good practice to do. That's called p hacking, and literally can ruin entire careers. So go in with a hypothesis first. Don't just create a model that's as complex with everything you can and see what seems to be significant. Because from there, I could basically say, okay, now I'm going to create a model where it's just those specific interaction terms, and it's probably a much stronger model. But again, I didn't go with that hypothesis. This is just due to dumb luck and random chance. And we know this because I specifically used random data. Nothing on this has any actual significance to each other. So when we find that statistically significant in modeling this, that is purely based on randomness. For our next example, it's going to be the same idea, except for this one, we're going to change our formula. We have y tilde x1 star x2 plus x3. So notice now, because only x1 and x2 have the star, what this means is it's going to model x1 plus x2 plus x1 colon x2. It's going to take the interaction of those two. But x3 is not included on that now. So now if we were to model this, so model 2, what's going to happen now is you'll notice that it's only x1, x2, x3, and then the interaction between x1 and x2. When you are using star, if you star multiple things back to back to back, it will take the interaction of any and all of every combination of them, from single term up to all of them combined together. But by having x3 with a plus afterwards, it is actually not part of that interaction for this. For our next example, we're going to be looking at ordered categorical variables. So in the previous example, we had x2, which was a categorical variable, but we were treating it as a dummy variable. So it was basically on or off. So when it was A, it was 0. When it was B, it was 1. Well, in this case, now we're going to have a specific variable that is going to act as a sort of factor, where it's going to have, in this case, low, medium, and high. And we're going to be looking at, so we're going to have one coefficient. So as it goes from low to medium, it's going to go up by that amount. If we go to medium to high, it's going to go up by the same exact amount. So this is going to be an ordered categorical variable. So let's actually jump in and look at the code. So first things first, just like before, I'm going to set the seed this time to 1, 2, 3. And our data is going to be a data frame made up of R, again, Y, which again, R norm 100. Our data is going to be a data frame, which again, Y is going to be R norm 100. So it's just going to be 100 data points pulled from a standard normal. X1 is also going to be R norm 100. But now we're going to have an ordered categorical variable. So I call it ord cat var. And this is going to be, I'm going to sample these different factors, low, medium, and high. I'm going to pull 100 of them with replace equals true. So let's do that and see what we get. Okay, so now let's look at our data. And you're going to see that we've got our y and our x values are going to be these random numbers from a standard normal. But then ord cat var is going to have, just going to randomly be high, medium, and low. So it's now this factor where it's going to be looking at it as an ordered factor. So now what we're going to do is, if we look at our data for ord cat var, we're just going to replace it with an ordering of our levels being low, medium, and high. Basically, we're just putting it in, we're just telling the factors what order we kind of want them to be in, right? Because we just look at it currently, these are going to be our factors. But if you remember from before, when we had these factors, it is going to automatically by default put them in alphabetical order, which means that high will be before low, right? Because H comes before L. Low will be before medium because M comes after. So now what we're going to do is we're going to reset that with ordered. We're going to take our data money sign ord cat var, and we're going to set the levels to low, medium, high. Therefore, setting the baseline as low, then medium, then high. So we're not going to have high, low, medium, which is what it would be by default because, again, alphabetical order. Okay, so next what we're going to do is we're going to change these to numeric values. So if we look at it right now, you're going to see that our data looks exactly the same, except for it got rid of the quotes because it's no longer the character string low, medium, and high, but now they are factors. So we're going to change those factors into numeric by using as.numeric and then replacing this object. So we're going to call this data ord cat var numeric. Okay, so by doing that, we now have a new variable, which is just going to be 1 for low, 2 for medium, 3 for high. Now we're ready to actually make our model. So our model is going to be LM for model. Y is going to be modeled by x1 plus ord cat var numeric, and our data is going to be equal to data. So looking at our model, you will see that we have an intercept, we have x1, and we have a coefficient associated with ord cat var numeric, meaning that as I go from low to medium, it is going up by a value of 0.09075. As I go from medium to high, it is going up by another factor of 0.09075. So let's look at our summary. And just like before, we'll have all the same information. We've got our intercept, we've got our x1, and we've got our categorical variable with its associated coefficient. And of course, you'll notice that none of these are statistically significant because, again, it's made up data that I just randomly created. The idea of this was to practice putting in the formulas, modeling, using linear models, not specifically like for the specific data for these. You can also use predict function to generate predictions for new data using a fitted model. So what we're going to do in this example is I actually, instead of writing it as predictions like I did in this, what we're going to do is we're going to have some new data, which is just going to be a data frame where we're going to take weight is equal to these three values, 2.5, 3.0, and 3.5. So I actually went back and reran the original MT cars model where we had miles per gallon being modeled by weight. Then I'm going to use predict. I'm going to put the model that I have created, which is, again, miles per gallon being modeled by weight. And our new data is going to be equal to this new data that we created. So let's run that and let's see what happens. So we have our new data, right? So if I look at this, you're going to see that it's just those three values. Weight is 2.5, 2.0, 3.0, and 3.5. And then I'm going to set pred as predict using our model. Now, if I were to actually run this, you'll see that it gives us our prediction. So when our weight of our car is 2.5, it is predicting that the miles per gallon will be 23.92395. When my miles per gallon is, when my weight is 3.0, my miles per gallon are 21.25171. And when the weight of my car is 3.5, I would have a miles per gallon of 18.57948. So these are the predictions based on this new data. And this is actually how, when we're doing modeling, we actually test our model, is that we take our known values and we create our model based on that. So let's say you're doing some prediction algorithm or classification algorithm. Then I bring in new data, that'd be your holdout if you're doing a holdout method. And this is what you were then going to use that model to predict. If I plug this in, what's the answer that my model would find? And because I'm using data that I have the answers for, because it's my holdout, I could then compare that, create a table to determine which ones it got correct, which ones it got incorrect. Now, there's one thing I want to note is that you want to keep in mind that when you're working with multiple linear regression models, interaction terms, or polynomial terms, you need to specify these terms in the formula when fitting the model using LM. Also, you want to be sure to pre-process new data in the same way you did with the original data if you applied any data transformations or feature engineering steps before fitting the model. For example, let's say that you want to do a linear model, but there were some outliers and you decided to do the log function. So you did natural log of your data, and then you did a linear regression. Well, guess what? If you get new data, you also need to take the linear regression. Whatever transformations you did, you also need to do with your new data. I want to do another example using categorical variables because there's actually an easier way we can do this. So instead of having to take my factor and then changing it specifically into an ordered factor and then changing it to numeric, instead I'm going to do this. So I'm going to set my seed as 1, 2, 3. My data is going to be a data frame, again, of y was r norm 100, x1 is r norm 100, and our cat var is going to be a sample of, in this case, I'm going to do the strings a, b, and c. And I'm going to randomly sample that with replacement equals true. So again, we can see what our data is. In fact, actually, I'm going to be a little bit more precise in this. I'm just going to do head data. Okay, and this will just be an example of the first 6 outcomes. Great. Now, what we can do is we want to use categorical variable directly. We can do model 1, which is going to be lm y tilde x1 and as.factor cat.var. And what this is going to do is it is going to treat it as a factor where it is going to give us x1, and then it's going to have as factor cat var b and as factor cat var c. So this actually created the dummy variables automatically. So in this case, when it is a, the first one will be 0. So x, the factor, the cat var will be 0 for the first one, and cat var c will be 0. If we have it, if it's b, then cat var b would be 1, and then cat var z would be 0. If it is c, cat var b would be 0, and cat var c would be 1. Of course, now we do our summary, and you can kind of see same idea. So I just wanted to show you that because there's an easier way. If you wanted to do dummy variables, you could just do as.factor, and that's a quick way to do it. So a lot of times you don't have to go through as much. Now, the other one was ordered, so that's why we did the extra steps. And this is where, again, if you study categorical data analysis, you'll learn more about when to use which ones, stuff like that. And a lot of times you'll be using generalized linear models for what you're doing. For our next example, we're actually going to pull in some data. So I'm going to have my data, and I'm going to do read.csv for the file called height weight. And what this is we're going to suppose we have a data set that contains the height in inches and weight in pounds of 20 individuals. We want to model a relationship between the height and weight using a simple linear regression in R. So now I've actually pulled in some data. So if I were to do names, my data, you'll see that we have height and weight. And then if we wanted to, I could do the dimensions of my data. And we get it's a 20 by 2, which makes sense, right? We said there's 20 individuals and we have 2 different categories, height and weight. So what we're going to do is we're going to model this with linear model. So LM, my data, money sign weight, tilde, my data, money sign height. And then I just put my data. Did I have to put the my data for each of these? No, I could just put data equals my data and it would work just as fine. But I also wanted to show that you could specify. In fact, if we do this, I don't even have to say where the data is coming from because it's explicitly stated when I did this. So now if we look at our model, you're going to see that just like before, we have our intercept and we have our coefficient associated with how height affects weight. So let's do our summary. And you are going to see, again, just like before, we have our we have our coefficients, we have our standard errors, we have our t-values, and we have our p-values. Both of these are very statistically significant. Below this, we can ignore this for the most part. This is just if you wanted to create the same data, you could actually create it in this way. So what I did is you have height, weight, which is a data frame of height, and then it's just the vector of all the different heights, comma, and then you have the vector of all the different weights. So of course, if I go left, you'll see that we just concatenate vector of height, comma, concatenate, or weight is concatenate all the vectors of weight, and then we create this data frame. If you wanted to then create a CSV, like I just used, you would use the write.csv function. This will tell you what are you actually writing as a CSV. This would be height underscore weight. This is the data frame that we just created. Next, we are going to have where is it actually going to save? So this is where you would put like the actual path, something like C:\\, whatever, but it has to have the CSV. So it'll be height underscore weight.csv. And then we have row.names equals false because we don't have row names in this data. So again, if we look at when I pulled it in, this is exactly what I did. So I do write.csv and I wrote it to this location. Like technically I wrote it to a different location. I pasted it there, but it's C:\/ temp /height_weight.csv. So if you wanted to create your own height weight data, you could do the same sort of thing here using the write.csv. By the way, this is something I do a lot of times, like when I'm doing data manipulation and then I want to write a CSV for it, I just do write.csv. One thing to be careful about though is if you write it the way I have written here, it is going to go wherever your working directory is. So if you do git working directory, it is going to tell me exactly what my working directory. Or you could do set working directory, and you could set a specific directory that you want to be working in. So right now I've got mine set to my documents. That's perfectly fine. So if I were to write this, it would show up in my documents. And then this slide is just kind of showing the code, so it'd be a little bit easier to read. So if you want to make this yourself, recreate it, you can just pause this, add these numbers in, and you're good to go. In our next example, suppose we have a data set that contains the exam scores in percentages, study hours, and sleep hours of 50 students. We want to model the relationship between the exam scores and study and sleep hours using multiple linear regression. So in this case, again, I'm going to read my CSV, but if we go to the next slide, you can see, again, you can pause here if you want to create this yourself. This is how you can actually create this data. We've got our exam data, which is a data frame with our exam scores. So it's got all the exam scores. And then we've got our study hours, which you can put all the study hours, and then we've got our sleep hours. If you do that, that creates your data frame. Then you can write.csv exam data, that's this data frame. And then I put it as exam_data.csv. And then again, row name is equal to false. So let's go to this example. I've already got this created. So what I'm going to now do is I'm just going to load it up. My data, read.csv. I'm going to pull the data from c:/temp/exam_data.csv, where header equals true. What does the header equal true do? It tells it that the top row are the names of things. So if I did names my data, you're going to see that we have exam score, study hours, and sleep hours, which those names were created when I actually create the data frame, right? Because if you look at it, exam score, that's the name. Study hours, that's the name. Sleep hours, that's the name. So now what I'm going to do is I'm going to model this linear model where I'm going to look at my exam scores modeled by the study hours and the amount of sleep that everybody got. And I'm going to delete this data because I don't need it because I'm explicitly calling on my variables. So looking at my model, you can see that these are the coefficients for our intercept, the study hours, and the amount of sleep. So looking at our coefficients, the intercept is going to be 50, right? So 5.e, so 10 to the negative 1, or positive 1. Study hours is going to add 5 for every hour that they study. Sleep, on the other hand, they're going to lose a tiny bit of points for the less hours they sleep. It has a negative, or rather, if they sleep too much, it's actually going to decrease their score, something like that. So if we were to run this summary of this model, you're going to see here we have our coefficients. We have that for our exam scores that our intercept is significant. The amount of study hours is significant, but the amount of sleep that students are getting does not seem to be significant on their study scores, according to this data that we made up. Now, one thing I want to point out though here is in summary.lm model, essentially perfect fit, summary may be unreliable. Why does it say that? Well, because if you're getting such a perfect fit, it usually leads us to believe that something went wrong. If you ever have a model that gives you like a perfect fit, that is a red flag. Now, this one, of course, is a perfect fit basically because I created the data and I just, if you look at it, it's very linear. This warning doesn't mean that it's not correct. It just means it's something you want to look out for, right? If you have a model that models anything and it's correct 100% of the time, red flag. Just be leery of it. Not saying it's wrong, but it's not likely with the noise and randomness of real data. We've got another example, again, using mtcars. I use this one oftentimes because it's one of the built-in data sets for regression, right? Because we have something like, we could do Old Faithful. That's another data set built into R. Iris data set is built into R, but that's more for classification algorithms. So I just like to use mtcars because it's got a good variety of variables. So in this case, what we're going to do is we're going to create our model, which should be a linear model of MPG modeled by displacement, and our data is going to be mtcars. So let's run that. And we'll do our summary, and you can see that both of them are very significant. We got our R squared of 0.7183 with an adjusted R squared of 0.709. Generally, adjusted R squared is always going to be just a little bit lower. If it's significantly lower, that's when you might, be having some issues with like variable selection. So the last thing I want to talk about is assessing your model. So the model summary provides information about the coefficients, standard error, t-values, p-values, and the model's overall performance, including the R squared and adjusted R squared. R squared is a measure of how well the model explains the variability in dependent variable. Adjusted R squared takes into account the number of predictors in the model and penalizes for additional variables. If your model is not doing very well, there are some diagnostic and remedial measures you can take. So it's essential to check the model's assumptions and diagnose any issue. So some common diagnostic plots will include residuals versus fitted values, normal QQ plot, scale location plot, and residuals versus leverage. If you were to just plot the model, it would show each of these. So let me actually show you that real fast. So I'm going to skip this line right above. I'll talk about in a second. So if I did plot model, what's going to happen is you'll see down here it says hit return to see next plot. So when I hit enter, it's going to show me my first plot. When I hit enter, it's going to show me the second plot, my QQ plot. When I do enter, it's going to give me my third plot. When I do enter, it's going to give me a fourth plot. So what we can actually do, if you ever want to show multiple plots, you can use this current command. Par, so basically parametric, mf row equals, and then C, we can do 2 by 2. And this is going to give me a 2 by 2 grid that is going to model. So it's going to do the first model here, second, third, fourth. Now, when you do this, it is going to do this every time, meaning that if I created 3 plots, it is going to put the first plot in, then it's going to fill in the second plot, third plot, things like that. So because I have 4 plots, I'm doing it just like this. And then if I do plot model again, now you'll see that we get those 4 plots together. And you can make this MF row anything you want. So for example, I could do a 3 by 3. And it's going to fill in the first, 1, 2, 3, and then it's going to the next one. So if I were to plot another model, it could go there as well. I could have as many as I want. I could have a 2 by 3 if I wanted to do 2 by 3. Oops. If I wanted to do 2 by 3, then it would do, 2 rows, 3 columns. And this is just the way that you can kind of show it all at once. So I just wanted to show you this because sometimes when you're doing like diagnostic plots, you can do something like this. You can see all of it at one time. You can see the QQ plot. You can see the fitted values versus the standardized residuals, versus the scale location. You got the residuals versus leverage, things like that. These are all ones that you can quickly see by doing this. Now, if you want to go back to just plotting one single plot, the way you do it is you do the same sort of thing, par mf row equals, and then instead of doing like something like 2 by 2 or 2 by 3, just do it by 1 by 1. So now doing that, if we were to go back into our plot again, you will see that it is just going to be a 1 by 1 plot, which means a single plot. So in this lesson, we introduced linear regression. We looked at assumptions and how to implement and assess it using R. Specifically, I did focus a lot on things like the formulas and things like that. And the reason is because what you've learned for creating these linear models can be translated to whatever else you're looking at. So I actually want to look at a quick example of that, and then we'll finish up. So I'm going to do this example by looking up RStudio Blur Earth. Let's do that one. So this is for multivariate adaptive regression splines. Now, if we look at the formula, just like before, there's a lot of different options, but notice it says here, Earth, first part, formula. Okay, that formula is where you put those arguments, just like everything else. So when I was doing the x1 plus x2 or x colon x2, guess what? That's exactly what you're putting here. Anytime you just see formula, this is what it's asking you for. For example, if I wanted to do something like mixed effects models, this would be LME4. So an example of this would be something like this. This would be for like LM4E, which would be, or LMER. There's different ones you can do for mixed effects models. But notice here, it's blah, 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 formula. Just like before. Notice they have formula reaction minus days plus days. This is, again, remember the vertical bars for mixed, so grouping by subject. Once you've learned how to really understand formulas, this translates now to pretty much almost any modeling you're doing, whether you're doing classification algorithms, whether you are doing more advanced regression, anything like that. If it asks you for formula, this sort of translates into all of that. Now, a couple of things I want you to kind of look at and explore on your own is I would look at further knowledge in the topics of multiple linear regression, right? Try it out, get some data, create some data, go online, find some data, try to create some linear regressions, things like that. At testing out interaction effects, regularization methods, things like ridge, lasso, and elastic nets. I would even look up stepwise selection methods. This is another variable selection method, which can actually be very interesting. So if you have a lot of variables, like for example, used on MT cars, you can see what it would think is the most optimized model. And you can do forward stepwise or reverse stepwise or robust and see what models you get, see how they fit, see how they work. And then last, I would look into generalized linear models, because again, if you have a lot of categorical data, this is oftentimes what you're going to want to do. This lesson where we focus on linear regression is kind of giving you the building blocks for modeling in general in R. With your understanding of being able to look at the documentation and this understanding of formulas, you can basically do any modeling you want now. And the big part you just need to include in that is using your statistical knowledge to go in and find the assumptions that those models rely on to figure out if they're an appropriate model or not, how robust they would they be reliable, and then maybe some pros and cons to determine what's the best model for what you're trying to do. Hello, everyone. In today's lesson, we're going to be looking at analysis of variance, or ANOVA. So analysis of variance is a statistical technique used to compare the means of multiple groups in order to determine if there is significant difference between those groups. So just like when we were doing hypothesis testing, we're going to have a null and an alternate hypothesis. The null hypothesis states that all group means are equal. So basically no change, right? We're going to look at the fact that these two groups are equal. While the alternative hypothesis will be that at least one of the groups means will be different from the others. As with any other method we've looked at in statistics, there are always going to be certain assumptions that are underlying this model. So before conducting an ANOVA, it's important to ensure that the data meets the following assumptions. Independence. The observations within and between groups are independent from each other. Normality. The dependent variable is normally distributed within each group. And homogeneity of variances. That is to say, the variances of the dependent variables are equal across all groups. As the name implies, analysis of variance is specifically looking at variance. So ANOVA is based on two sources of variance. We've got between group variance, which is the variability of the group means, that is to say, between group A and B, and within group variance, the variability of observations within each of those groups. We can calculate the F statistic, which is the ratio of the mean square between group variance to the mean square within group variance. So that is to say, our F statistic equals mean square between groups divided by mean square within groups. And if the null hypothesis is true, the F statistic should be close to 1. If the F statistic is significantly greater than 1, this would give us evidence to reject the null hypothesis. Unlike our last few lessons, we're going to not be doing a ton of theory. We're just going to be jumping straight in on this one. So first, we're going to look at an example where we're implementing ANOVA in R. So looking at this, you can see that we have 3 groups of data. We're going to set the seed as 42 so everybody can follow along. So let's go to R so we can actually do this example. So looking at our code, like I said, we set our seed to 42. We've got group 1, which is just going to be 10 data points from a normal distribution with a mean of 5 and a standard deviation of 2. Group 2 is going to be normally distributed data, 10 of them, with a mean of 6 and a standard deviation of 2. And then group 3 is going to be data from a normal distribution, 10 of them, with a mean of 7 and a standard deviation of 2. So we're going to create these 3 data sets. So if we look at group 1, you can see that we're going to have 10 normally distributed numbers. If we look at group 2, 10 normally distributed numbers. And if you look at group 3, 10 normally distributed numbers. Next, what we're going to do is we're going to combine all of this into just our data. So we have data, we're going to concatenate group 1, group 2, and group 3, giving us our full data set. You can see that we have all 30 data points. Now we're going to factor our groups. So we're going to do groups, which is going to be a factor. We're going to repeat 1, 2, 3, so 1 to 3, and we're going to do each of those 10 times. So it's going to be 1, 1, 1, 1, 1, 10 times, then 2, 2, 2, 2, 2, 10 times, so on and so forth. And then we're going to do group means, which we're going to use the tapply command to take our data by groups and then focus by the mean. So if we look at this, we'll get group means, which is going to be 6.094594. For group 2, we have 5.673087. And for group 3, we have 6.643841. Now, as always, because we're using a new command we haven't looked at before, let's just do a quick question mark t apply. And looking at it quickly, all it's doing is it's applying a function to each cell of a ragged array that is each group that's non-empty of values or data rows given by unique combination of the levels of certain factors. So basically what we're doing is we're just grouping them, the data, by group, and then getting our mean. That's the function we're applying. Next, we're going to get our grand mean. This is going to be the mean of all of our data together, all 30 data points. Next, we're going to get our between group sum of squares. And we're going to do this by taking the group mean minus the grand mean. So this would be sort of like your x minus x bar. And we're going to square that. And then we're going to take the sum of all those values. So we get the sum of square within between groups, and we get a value of 0.4739016. Next thing we're going to do, we're going to calculate our within group sum of squares, which is going to be, again, we're going to take the sum, we're going to use t_apply again using our data by group, and we're going to use our function of x, which is just we're going to take the sum of x minus mean of x squared. So we're going to take within group 1, x minus mean of x squared. We're going to sum all those up. Then we're going to do 2, then we're going to do 3. And then we're going to sum all those values up. So looking at our value, we get 168.957. Next, we need to calculate our degrees of freedom. So our degrees of freedom for B, which is going to be our between groups, is going to be just the length of our group means, that is to say, how many group means we have, which is 3, minus 1. And then we have the degrees of freedom from our within groups, which is going to be the length of our data, 30, minus the length of our group means, 3. So that means it's going to be 27. So if we look at these, degrees of freedom for between groups, 2, and degrees of freedom for within groups is going to be 27. Next, we need to calculate our mean square values. So the mean square of our between groups will be the sum of squares of between groups divided by the degrees of freedom of our B. So that'll be the sum of squares for between groups minus, divided by 2. And the mean square between groups is going to be the sum of squares between within groups, divided by the degrees of freedom within groups. So if we look at both of these, we're going to have mean square error between and our mean square values within. Finally, we're going to calculate our F statistic by taking the mean square between groups divided by the mean square within groups. Okay, just like before, let's look at our F statistic. Now, we said that if we have a value that's close to 1, this means that we would fail to reject the null hypothesis. If we have a value that's much larger than 1, we would fail to reject. So now let's find our p-value, which is going to be 1 minus, we're going to use pf, right, because p function, where f is what we're actually doing this on. We're going to take our F statistic, and then, of course, we're going to have our degrees of freedom between groups and our degrees of freedom within groups. So looking at our p-value, you're going to see that we have a p-value of 0.9628933, which means that we would fail to reject the null hypothesis. Because remember, if the fish is smaller than the pond, we would fail to reject. If the fish is bigger than the pond, which is our alpha, this doesn't make any sense. We have to reject. So therefore, this pond is pretty big. So if we were at an alpha of 0.05, this p-value would definitely be bigger than that alpha of 0.05. So then we're just going to use our concatenate to write out both of our values that we just looked at. In our next example, though, we're going to do it a little bit easier. So as always, what I like to do is I like to focus on how you could implement this using just the basic commands that you've learned in any statistics course, and then actually how to implement it using the functions within R. So this next example is going to be using built-in R functions to perform ANOVA. So first thing we're going to do is we are going to create a data frame. We're going to call this data frame df. So df is going to be a data frame where value equals data and group equals groups. So if we look at our data frame, you will see that we have we have the same data, but now what we've done is we've broken it into a data frame, right? So we have our first 10 values and they're associated with group 1. We have our second 10 values associated with group 2, and our third 10 values which are associated with group 3. We're then going to label the object lmfit using a linear model where value is going to be modeled by group, and our data is going to be this df, this data frame that we just created. So looking at our linear model, right, we have a linear model just like we did in the linear models lesson. Now to actually do ANOVA, we're going to set ANOVA results as, we're going to use the ANOVA command, and then we're just going to apply it to this linear model lm_fit. And then we're going to print those results, and you'll see what we get here. So we have analysis of variance table. The response value, we have group, degrees of freedom is 2, residuals 27. That matches what we had previously. Our sum of squares, 4.739, 168.957. This matches what we had. Our mean square values, our F value, and our P value. And you'll notice that the values are a little bit different. Just like everything we've done before, the method that we teach in class will be a little bit different. And also, it could be because of our arguments, right? Because I didn't add any arguments to this. But if we do what we always do and do ANOVA, we can look at the documentation for how ANOVA actually works in R. So we're just going to compute analysis variance or deviance tables for one or more fitted model objects. Okay. And this one doesn't really give a lot of information. It's just object. There's also another command which will give us more information if we do question AOV, which will also give us an analysis of variance. This one, it says to fit analysis of variance model by call to LM, which is what we did. And then you can see that its AOV is formula data equals null by default, projections equals false, QR equals true, contrast equals null. And then you can look at what each of these things are. You've got projections, which are logical flag, should the projections be returned. QR, logical flag, should the QR decompositions be returned. And contrast, listed contrast, things like that. As I mentioned previously, we saw that our results, when we did it basically by hand on the computer, versus using the ANOVA command, or even if we used AOV, that it's going to differ a little bit from what we actually got, even though it agrees with our final answer. This is where I think it's very important that people understand the underlying statistics and dive deeper into what R is doing under the hood versus what we learn in a statistics class or some sort of statistical environment. This is one of the pitfalls that people oftentimes run into, is that they learn how to code and they learn how to do things like ANOVA, hypothesis testing, confidence intervals, using R or Python or whatever it is. They get an answer and they run with it without understanding what it's doing and why it might actually be different than what you've learned in class, and knowing where those pitfalls are. Because you might have seen that while they did agree with each other, those minor differences, if we were on the cusp of whether making a decision to reject or fail to reject, we may have gotten a different response. And this is where your statistical background, your statistical knowledge can be so important for these kind of topics. This is where statisticians can really stand out in the field of data science, because this is where your expertise comes into play to make sure that the analysis that's being done, which you can see it's very easy to do on the computer, but it's where the analysis being done is properly interpreted. So now let's get away from the example I did where I just made up some randomized data using a normal distribution for each group, and we're going to use a real data set. And this data set is going to be the plant growth data set. So first thing we're going to do is we're going to load plant growth. And let's just do the head command. This will give us the first 6 entries to give us an idea of what it looks like. So we've got weight of the plants, and then we've got what group they're in. So they've got control, and you've actually got treatment 1 and treatment 2, if I remember correctly. Let's double check that. So we're going to do names, plant growth, run that, and you'll see that, again, we have weight and we have groups. So let's do plant growth. And let's look at our groups, our group data. Okay, so you can see here we have control, we have TRT1, which is treatment 1, and we have TRT2, which is treatment 2. It's basically, there's plants, they had the control group, they had one treatment they were doing another treatment, and seeing if the treatments cause the plants to grow better than without the treatment. So next thing we're going to do is we're going to create our ANOVA using AOV this time. So AOV, we're going to take the weight of the plant. It is going to be modeled by the group that it's part of, so control, treatment 1, and treatment 2, and our data is going to be from plant growth. And then let's run a summary, and you can see here that we got the group and residuals, right? They have a degrees of freedom for group of 2, which makes sense because we had 3 groups, so n minus 1. We have our residuals is 27, which makes sense because, again, if we actually looked at this, length of plant growth, and then I'm just going to do weight. You'll see that we have 30 data points. So 30 minus the 3 groups gives us 27. We have sums of squares. We have our mean squares. We have our F value, which in this case is 4.846, which is decently above 1, meaning we got a p-value of 0.0159. This means that we could reject our null hypothesis at the 0.05 alpha level or 0.1 alpha level, but not the 0.01 level, which is why, if you look at this, it has 1 star, which is representing anything with an alpha level that is greater than or equal to 0.05, but it would fail, not getting 2 stars, for 0.01. The next type of ANOVA we're going to look at is what's called a two-way ANOVA. So the idea behind it is a two-way ANOVA is used when there are two independent variables or factors in a study. It allows you to analyze the main effects of each factor and any interaction effects between factors. The null hypothesis for the two-way ANOVA are, so there's actually a couple of them, that there's no significant main effect of factor A on the dependent variable, there's no significant main effect of factor B on the dependent variable, and there's no significant interaction between factors A and B. So this one's a little different than the hypotheses we've done before because this one is a composite hypothesis. So for this example, we're going to be using the tooth growth data. So in this case, we're going to load it just like before, and we're going to do our head to get an idea of it, and we're going to have the length of the growth. We're going to have the supplement that is being implemented and the dosage. So let's actually look at the entire data just so we can get a better feel for this. So we're going to do tooth growth. And if we run this, you're going to see that we have a couple different supplements. We have VC, and then we've got OJ. Okay, so this has to do with what sort of supplement they're adding to this growth. Then we have the dosage. For each of these, they can get 0.5, they can get 1.0, or they can get 2.0. So what we're looking at now is we're not just looking at, is there some effect of the supplement that's being added or the dosage? We're looking at both of them at the same time. We're looking at, is the supplement effective? Is there a difference with the dosage? And is there an interaction between the two? So we're going to do this with tooth growth ANOVA. This is an object that we're going to assign using AOV. We're going to create the model where the length of the tooth is modeled by the supplement, and we're going to use star as dot factor dose. So if we do this star, if you remember from the linear models lesson, this is going to say that we're going to do supplement as dot factor dose and the interaction term between both of them. If you look at my original code I had on the right when I did a screenshot of it, I didn't have the as dot factor for the dosage, which was a mistake on my part because this should be something that is a factor because it's going to be, basically factor A, B, or C, which dosage. It's not a numeric value of some continuum. And then finally, we have our data is coming from tooth growth. And it just like always, if you ever writing something like this, if you wanted to do like I oftentimes do, the tooth growth and then money sign, you could add that to each of these variables, and then you don't have to include where the data is coming from. By doing that, that means we don't have to refer every single variable to which data it's coming from. Let's do our summary. So looking at our summary, you can see that we have our supplement. We have degrees of freedom is 1. That's because we had 2 different supplement types. We had, so n-1 gives us 1. As dot factor dose. So we had 3 different doses, 0.5, 1, and 2, or 1.5 and 2, which means n-1, we have 2. For our interaction term, we have a degrees of freedom of 2, and then for our residuals, we have 54, which would be the entire 60 data points minus the 6 for the individual and the interaction. Each of these, we have our sum of squares, we have our mean square, we have our F statistic for each of them, and then we get our p-values. So for our supplement, we have a p-value of 0.000231, and it means it has 3 stars, which says that we can reject the null hypothesis at the 0.001 level. For our dosage, we have a p-value less than 2 times 10 to the negative 16, which again, 3 stars. We can reject the null hypothesis at a 0.001 level or smaller. And for our interaction terms between the two, so our interaction between the two, we have a p-value of 0.021860, which has 1 star, which means that we can reject it at the 0.05 alpha, meaning that we cannot reject it at the same level. So this means, based on this, that according to our ANOVA, there is an effect of the supplement on tooth growth. There is an effect of the dosage on tooth growth. And there is some evidence showing that the interaction between the two affects tooth growth. For our next type of ANOVA, we have a repeated measures ANOVA. So repeated measures ANOVA is used when there is one within subject factor and one or more between subject factors. It's appropriate when the same subjects are measured more than once on the dependent variable. This would be things like at different time points or under different conditions. The null hypotheses for the repeated measures ANOVA are there's no significant main effect of the within subject factor, there's no significant main effect of the between subject factor, and there's no significant interaction between the within subjects and between subjects. So this one is actually kind of combining the ideas of a one-way ANOVA and a two-way ANOVA, right? Because we're looking at null hypotheses, but instead of it being factor one, factor two in the interaction, it's within groups, between groups, and the interaction. And this is one that we would oftentimes do if we're doing some sort of, as the name implies, repeated measures. An example of this would be if we're doing some sort of test on children, we have like a pre and a post test, or maybe pre-test, post-test 1, and post-test 2, then this would be the same child as being measured. They're being measured in the first test, the second, and the third test. So we want to see, is there a significant difference between those tests, between those groups, and between things like that. So this would be really important if we're trying to see, did the students do better based on whatever we did between the pre-test and the post-test. So for this method, we're not going to be using a built-in R function. So we're going to be using the easy package in R. And I've already installed it, so I'm just going to jump straight to library. But if you haven't installed it, you would first want to run install.packages and within quotes, easy. So I'm going to load library, easy. And then I want to simulate some learning data. So again, just like before, I'm going to set seed as 42. So if you want to follow along, you can do the same thing. You should get the exact same results. My subjects, I'm going to repeat 1 through 20 each 3 times. So these are going to be our subjects, just like before. It's going to be 1, 1, 1, 2, 2, 2, 3, 3, 3. And it's going to do this, repeat each number 3 times all the way to 20. Then I'm going to create a variable time, which is a factor of, we're going to repeat pre, post 1, and post 2, just like I'd mentioned. We're going to do this 20 times. So then looking at our time, you're going to see we have pre, post 1, post 2, pre, post 1, post 2, pre, post 1, post 2. And we're going to have each of those for each of the groupings, the subjects that we have above. Now we're going to create our groups. This is going to be a factor where we're going to repeat, and then within that repeat, we're going to repeat control and experiment. So we're going to have control and experiment, and that's going to repeat each 10 times. So control, control, control 10 times, experimental, experimental, experimental 10 times. Then each of those are going to be repeated 3 times. So it's going to be control, 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 control 10 times, experimental 10 times, and then it's going to repeat that 2 more times after that. And that will give us our groups. So now let's look at our groups, and you'll see exactly that. Next, we're going to actually create the scores that the students had. So this one is going to be some randomized data. We're going to take our norm, which remember is our pulling data from a normal distribution, where we're going to get 10 times 3 or 30 different data points with a mean of 50 and a standard deviation of 10. And then we're going to get another R norm, 30 data points with a mean of 55 and a standard deviation of 10. Next thing we're going to do, we're going to put all this together. So we're going to take our data frame. It's going to be subjects, time, group, and score. So now let's look at our data together. All this was just making some data so we could do this problem. So looking at our data here, we have our subject 1. They've got a pre-test, a post-test 1, and a post-test 2. They're part of our control, and their score in pre-test was 63.7, post-test 1 was 44.35, and post-test 2 was 53.631. Person number 2, or subject number 2, is, again, pre, post 1, post 2. They're part of the control. They've got their scores. And then we come down. Then we get to subject 11. Same thing, pre, post 1, post 2. They are part of our experimental group. So now we have the individual subjects. We have their 3 different scores for each of them based on pre-test, post-test 1, and post-test 2, and whether they're in the control or whether they are in the control experimental group. So to actually run our ANOVA, we're going to assign the object easy ANOVA, and the function for this is easy ANOVA, where ANOVA is capitalized. And we are going to do data is going to be equal to our learning data, which we just defined here. We're going to have dv equals score. We're going to have WID is going to be subject, within is going to be with time, and between is going to be by group. And just like always, if you want, we'll just run our question mark easy ANOVA, and you can find out what all of this stuff is here. So you can see here that we define DV, which is going to be the name of the column of the data that contains the dependent variable. That's going to be the scores. The WID is going to be the name of the column of the data that contains the variable specifying the case identifier. Within is going to be the name of the column of the data that contain the predictor variables that are manipulated or observed. And then we have within full, same as within, blah, 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 within covariates, between, and you can look all of this up based on the type of ANOVA you want to do. So let's actually run our ANOVA. And it's going to say, warning, converting subject to factor for ANOVA, because I must have left my subject as not a factor. So it's just going to do it for me. Cool. And then let's get our results. So you can see here that we have a lot of information. So we're going to have our ANOVA information, just like before, by group, time, and the interaction between group and time. Of course, you're going to have degrees of freedom, stuff like that. Then we've got our Muchley's test for sphericity. And then we're going to have our sphericity corrections. So I actually have a slide so we can break down what each of these actually mean. So first things first, let's talk about our ANOVA table. So we had F118, and this is going to give us a level of 0.984 with a p-value of 0.334. So the interpretation is that there's no significant difference in scores between our control and our experimental groups across all time. For the time that is with our within subject effect, we have our F score of 0.069 or a p-value of 0.934. So interpretation, there's no significant change in the scores over time when considering all the subjects. Then we have our interaction effect, which has an F score of 0.173, giving us a p-value of 0.842. So again, there's no significant interaction between the time and the group. This means that change in the scores over time does not significantly differ between the control and the experimental groups. Now let's talk about those two types of tests that I didn't talk about yet. So Muchley's test for sphericity, it tests the assumption of sphericity, which is crucial for the validity of within subjects effects. Since the p-values are above 0.05, the assumption of sphericity is not validated, meaning that the variances of the differences between all combinations of related groups are equal. Then we have sphericity corrections, which provided corrections. So you have different ones, right? You've got the Greenhouse Kessler, you've got the Hunfeld, and corrected p-values. If the sphericity was violated, which it wasn't in this case because we didn't have to do a correction, since it wasn't violated, you can rely on the uncorrected p-values in the ANOVA table. If it was corrected, then you would have updated p-values based on the correction. So none of the effects in this case, group, time, or the interaction between the two, are statistically significant in this example that we just did for our analysis, meaning that there's no strong evidence to suggest that the groups behave differently, that the scores change over time, or that the change over time differs between groups based on the data set and our chosen significance level of 0.05. And this can actually be very powerful because it allows you to test multiple things at one time. You're testing, was there a difference between our control students and our treatment students? You're testing whether the scores got better over time, and you're testing to see if there's an interaction. And this is something we actually would do. If we were doing some sort of intervention, let's say, we want to know not only did the experimental students do better or were different from the control group, we want to know, did all students increase over time? Because while we're doing this test with the intervention and stuff like that, over time, children are still going to school. That means that they're still learning. So we might have seen an increase in the scores based on some intervention, but all students' scores increased. So this allows us to see, like, is there a difference of our control and our experimental group? Is there a difference of scores over time? Is there a difference of scores over time given the group that the subjects are a part of? The next type of ANOVA we're going to look at is mixed design ANOVA, which is also called a split pot ANOVA. This is used when there's one within subject factor and one or more between subject factors. This design combines elements from both within subjects and between subject designs. The null hypothesis for the mixed designs ANOVA are similar to those for the repeated measures ANOVA, with the added consideration of the within subjects factor. As with the last example, we are going to need to install another package. So the install.packages, this one is going to be Aphex. So you put that within quotes. I've already installed it, so I'm just going to load this package. And then to do our mixed ANOVA, we're going to have the object mixed ANOVA, which we're going to assign, and it's going to be AOV underscore car. Our score is going to follow group times time, plus our error is going to be subject over time, and our data is going to be learning data. So first things first, let's look at our learning data. So if we run that, right, we've got our learning data just like before. We're going to now do our question mark AOV underscore car, and we're going to look at this. So convenient analysis of variance estimation for factorial designs. And you can see that there's a bunch of different options you can choose here, things we didn't even touch on, like fun aggregate. We've got our type, factorize, observed equals null, ANOVA table, list, stuff like that. And then we also have AOV4, which is a different command we can do, which will be kind of similar. You can look this stuff up. We've got AOV-EZ, and these are all different ones where you can pick which one you need based on the type of ANOVA you're doing and what sort of data you have and question you're asking. And this is where, again, I really suggest you dive deeper into this. I'm only touching the surface while we're doing this kind of stuff. So if we look at what we have our model score, which is being modeled by group star time, meaning we're going to get group, we're going to get time, and we're going to get the interaction, plus this error term, which means we're going to get that as well. So let's do our mixed ANOVA, and let's do a summary of that. Which, real quick, we have a warning: contrast set to control.sum for the following variables group. Okay, no big deal. It didn't stop us from actually doing our ANOVA. Let's get our summary of our mixed ANOVA. Okay, so you can see, again, we have a lot more here. We have our univariate type 3 repeated measures ANOVA assuming sphericity, and it's going to give us our intercept, group, time, and our interaction between the two. We're going to have our sum of squares, our degrees of freedom, our error, sum of squares, the degrees of freedom. We have our F value, and we have our P values. So according to this, the only thing that is significant is our intercept. Then we have our Moduli tests for sphericity. It's going to look at time. We have our test statistic and our P value. And we have our interaction between group and time. Again, we have an F statistic, or our test statistic, and we have our P value. Then we have our Green-Geisser and whatever correction. This one does include our corrections for sphericity. So you can see again that we have time and group interacting with time. And we've got our GG-EPS. We've got a P value associated with that. And then we've got our HF, which associated with, GG is greenhouse geyser. And our HF is going to be our Hunfeld. And these are going to be looking at corrections. Okay. And let's, again, do a breakdown of what all these things actually mean. So looking at our univariate type 3 repeated measures ANOVA, assuming sphericity, we have an F value of 1120.73, which had a P value of less than 0.001. So this means that the model intercept is highly significant, like I mentioned. This means that the overall mean score across all groups and times is significantly different from 0. For group, we had an F statistic of 0.984, which is very close to 1, meaning it's going to fail to reject. We have a p-value of 0.334. This means that there are no significant main effects of the group on the scores. This means that the control and experimental groups are not significantly different when averaged across time points. Next, we have time. This has an F value of 0.069 and a p-value of 0.934. This again means we have no significant effects of time. This implies there isn't a significant difference in scores across different time points when averaged across both groups. For our group time, that is our interaction rather, we have an F value of 0.173 with a p-value of 0.842. This means we have no significant interaction between group and time, suggesting that the way scores change over time does not significantly differ between control and experiment. Our Moduli test for sphericity, both p-values are greater than 0.05, suggesting that the assumption of sphericity is met. The variance of differences between all combinations of related groups is equal, and no correction is needed. And then we have our sphericity corrections. This means since the sphericity assumption is not violated, there's no need to rely on these corrected values. However, these values show the significance levels adjusted for any potential violation of sphericity. And as you can kind of see, when we were looking at our last method, that there were different types of ANOVA, even on top of this. ANOVA is a very commonly done test in statistical research. I didn't dive as deep into the theory because I wanted to focus a bit more on the computational side of stuff, because this is a much heavier topic, which would take a lot more than the short amount of time I was going to be able to give it justice. So this is why I just gave a brief introduction. But if you'd like to know more about ANOVA, I really do suggest you dive more into the theory behind it. And then from there, you could start looking at how to implement it even more in R. Because I will tell you from personal experience, this is something that is done quite a bit. It's a very powerful tool. And hopefully this introduction to how to implement it computationally can help when you get to that point of implementing it on your own data. Hello, everyone. In today's lesson, we're going to be looking at logistic regression. Now, before we actually begin this lesson, I do want to briefly state that, as with many of the lessons in this course, I'm only going to be scratching the surface because we're going to be looking at the computational side of stuff. Logistic regression and generalized linear models in themselves are actually a much deeper topic. In fact, I've taught an entire course on this called categorical data analysis, and anyone who is one of my students and sees that class available, it really is interesting and it uses a lot of R and learning all this kind of stuff. So if you're interested, I just wanted to kind of start by saying that. So let's start now by introducing logistic regression. So today we're going to explore the concepts of logistical regression, a fundamental and analytic tool in statistics and machine learning for solving classification problems. Unlike linear regression, which will predict a continuous outcome, logistic regression is going to be used for binary classification tasks where the outcome is categorical. Now, I will actually preface this by saying that you do get an output, which is a continuous output outcome, just like you would with linear regression. The difference is that you are actually going to have a cutoff point. Anything below this point, it will count as 0. Anything above this point, we will count as 1. And this is actually a factor you may have to take into account when you're doing a logistic regression, not just whether you want to classify it as 0 or 1, but also where is that cutoff point for the classification change. So let's look at understanding it now. Logistic regression is a statistical method for predicting binary classes. The outcome or target variable is dichotomous in nature. This means there are only 2 possible classes. For example, it can be used to classify if an email is spam or not spam. Or the example they use whenever you're learning about machine learning is spam or ham. Or if you have a tumor that is either malignant or benign. So why not just use linear regression? So while linear regression might seem like an appropriate choice for binary outcome, right, 0 or 1, it has significant drawback. It is that it can predict values that are below 0 or above 1, which are not possibilities, right? Because you have to think of these like probabilities. Logistic regression, on the other hand, ensures that the predictions are within our range of 0, 1, since, again, as I mentioned, they're probabilities. In fact, I'll look at graphing this at the end, where you'll see that we get what's called an S-curve or a sigmoid curve, which actually will show the shape of the actual graph and where that cutoff is based on your logistic regression model. And let's actually look at this sigmoid function to begin with. So a logistic regression model uses the logistic function as part of the generalized linear model to squeeze the output of a linear equation between 0 and 1. The logistic function is known as a sigmoid function. So the logistic model that we use is structured around this logistic function. That is to say, the probability that our output y is equal to 1 is equal to 1 over 1 plus the exponential, so e to the beta 0 plus beta 1 x1 plus so on and so forth up to beta n xn, where the probability y equals 1 is the probability that y will equal to whatever your class 1 is. The beta values are the coefficients associated with each of those variables you have. E is our base of our natural logarithm, and x1 through xn are our independent variables. The coefficients, or beta, of the logistic regression algorithm must be estimated from the training data. This is typically done through maximum likelihood estimation. Again, another thing in a class that I teach is if you take mathematical statistics, we have a good chunk of it focused on maximum likelihood estimation, and I actually do plan on doing videos on that, stuff like that. But again, this refers to a bunch of other stuff that I've taught elsewhere. Then we have our odds ratio. So in logistic regression, we often talk about the odds ratio, which is the odds of an event happening versus not happening. The odds are calculated as the ratio of the probability of success to the probability of failure. So once you've figured out those probabilities, you can actually figure out what the odds ratio are for each of these outcomes. So how do we actually do logistic regression in R? So it estimates the probability that a given input point belongs to a certain class, then making it suitable for binary classification problem. We're going to use the GLM for generalized linear model function. Our syntax will be that we'll use GLM, and then we'll have our formula, which follows the same exact rules and functions of our linear models lesson. our data that we're going to be using, and then family. This is where you can dive deeper into generalized linear models, and you could pick different families such as binary, Poisson, things like that. So we're going to need a couple things. First, we're going to need our formula. This is going to be our symbolic description of our model to be fitted. We already know how to do that. The data, this is optional data frame containing the variables of the model. It's optional because, as you've seen before, you can use the money sign. You can actually refer to where the data is coming from and kind of skip that data phase if you want. And then the family is going to be a description of the error distribution and link function to be used in the model. If you want to learn more about link functions, I do highly suggest you dive deeper into categorical data analysis. So now let's do an example. So as always, I'm going to start by setting a seed, in this case, of 1, 2, 3, so that if you want to follow along, you'll get the exact same results. So we're going to start by setting our seed, and we have data. We're going to create a data frame where we have y, x1, and x2. So we have two variables that we're going to describe our output y. So y is just going to be a sample, 0 to 1, with a size of 100 and replace equals true. So we're just going to randomly select 0 or 1. We're assigning the group that they are a part of. X1 is going to be from a normal distribution with a mean of 200 and a standard deviation of 50, and we'll get 100 X1 values. X2, we're going to again sample 0 to 1 of size 100 with replace equals true. This would be our categorical variable. Now, if we look at our data, let's see what it actually looks like. We have 100 data points, and you can see that for each of our Y values, we either have a 1 or a 0. We have some X value from a normal distribution, and then we have some categorical factor, which would be our X2. Now, in order to model our GLM, we're going to use GLM. We're going to have Y is modeled by X1 plus X2. Family equals binomial, and data equals data, right? Because again, this is bad naming convention. I should have put something like my data, but I wasn't really thinking about it when I did the code. So now if we do our summary of our model, you're going to see the output that we get. First, it's going to do call, which is going to tell us the formula that we used, including our family and link function. We have our coefficients, just like you would with a linear regression. We're going to have our intercept, x1 and x2, and our estimates. You're going to have the standard error, you're going to have their z value, and you're going to have your p value, which of course none of our p values are good here for rejecting our null hypothesis, but that's fine. It's just for an example, and it's made up data. Under this, you're going to have your dispersion parameter for binomial family taken to be 1. You're going to have null deviance and residual deviance and their degrees of freedom. And then the AIC. These are for fitting models, because a lot of times you're going to be creating models where you might want to have a lot of variables, and there's two ways you can kind of do it. You can start with no variables and then add 1, and you'll get what the deviance is from the null model or the full model, depending on which one you want to do. And then you can see which variable causes it to give you the best model. Then you can try adding a second variable, try each of them, figure out which second variable gives you the best model. And you can do this up to some point where your deviance stops getting better. The AIC, as I kind of mentioned previously, is a measure of a model's performance by how well does it model the whatever Y variable you have using the X variables, while also keeping complexity low. So you want a low AIC because higher means that you have a more complex model. And then last thing it's going to give us is the number of Fisher scoring iterations, which would be 4. So looking at our output of our summary model will provide some insight into the significance of our predictors and the overall model fit, which of course this one did not fit well because again, it's just completely made up random data. Now let's look at how would you actually make predictions based on this. Let's say that you did get a good model, had a good fitting, and you wanted to take some new data and predict where it would classify those inputs. So what we're going to do is we are now going to create some new data, which is going to be x1 is going to be the values 120, 205, 290, 150, and 240. X2 is going to be the categorical variables 0, 1, 1, 0, 1. So now we have our new data. We can look at our data frame right here, and you can see right there. So what we're going to do is we're going to set our probabilities. We're going to use the predict function, which is going to use our model that we modeled creating our logistic regression, and then our new data, which is going to be this right here. Our type is going to be response. So if we do this, I'm just going to look at it real quick. Our probabilities would be, you'll notice that for each one, we get a probability. Remember how I told you that it is technically a continuum, it's just between 0 and 1? Each of these represent a probability of it's being classified as 1. So the first one is 0.3899, second one is 0.488, third one is 0.48, 0.388, and 0.486. So doing this, then we can do our predicted classes where we're going to use an if-else statement. Our probabilities, if they are greater than 0.5, we will classify them as 1. Otherwise, they'll be classified as 0. We'll combine those together, and then we can print our results. For our new data, each of these was predicted to be part of class 0. Let's say instead, though, I decided to change my cutoff to 0.45. So in this case, doing the same thing, what's going to happen now is the first input is going to be classified as 0. The second input and third input will be classified as class 1. The fourth input would be classified as 0, and the fifth input would be classified as class 1 again. So this is what I was kind of talking about, is not only are you getting your predicted probabilities based on your actual analysis that you're doing, you may actually want to have some different cutoff for where you consider it becomes high enough probability that you would consider it class 1, right? You might want to be more conservative and err towards classifying 1, or you may want to have a higher threshold where you're less likely to classify as 1. As per usual, now that we've done our generic made-up data example, we're going to do another example using the mtcars tried and trusty data that we have. So in this example, we're going to load our mtcars data, and I'm going to set mtcars AM, this is our automatic or manual transmission of our cars, as a factor of mtcars AM, where levels are going to be 0 or 1, and our labels will be automatic or manual. So all we're doing is, instead of it just being 0, 1, we're actually putting a factor with it. So looking at mtcars AM, it is now going to say manual or automatic. Actually, let's go back real quick. Let's reload the data. You'll see originally it was 0, 1. So all we did was we just replaced it with manual or automatic. Now we're going to create our model, which is going to be a generalized linear model, so GLM, where automatic or manual is modeled by miles per gallon interacting with weight. Remember, so using our syntax from our formulas, that means we're going to be looking at miles per gallon, we're going to be looking at weight, and we're going to be looking at miles per gallon interacting with weight. Our data is coming from mtcars, and again, our family is binomial. So we're going to create our model, and this will be model 2. Let's get our summary. So you can see here, again, none of these are significant. And our AIC, though, a lot lower than our previous model. So if we had done something simpler, let's say we switch this up to, instead of being the interaction, we just do the the miles per gallon and the weight modeling it. You'll see here that now our intercept is significant up to a 0.05 level. Our weight is significant up to a 0.05 level. Our miles per gallon is not significant, and our AIC is actually lower. So I'm going to go back now and I'm going to change this for our predictions. So I'm going to put this back to star and then run it again. Okay, now we're going to do predictions where we're going to predict model 1 type equals response. And let's see what our predictions are for this data. So for each of these cars, I put them back into the model, which is actually a bad practice. You should have new data you've never used, but I'm just doing this to kind of make the example. Each of these then will get a probability associated with them, whether they're going to be an automatic or a manual transmission car. And then I'm going to create a confusion matrix or a table to determine how well the classification was done. So what we'll do is we will take our predict, which is this. If else predictions were greater than 0.5, we will say that it was manual. Otherwise, we will say it was automatic. And then we will compare that to the actual results from mtcars. And this will give us what is called a confusion matrix, which shows us that. So here on the left side, we have our predictions, automatic or manual. At the top, we have our actual results of those cars, automatic or manual. So this means that when our model predicted it was an automatic transmission, it got 18 of them correct. When it predicted automatic, it got one of them incorrect by saying it was automatic, but it was actually a manual. When we predicted that it was a manual transmission, we got one incorrect but it was actually an automatic transmission, and we got 12 correct by correctly saying it was manual transmission, and it actually was a manual transmission. Once you have done this confusion matrix, this is actually a lot of times how we're going to determine how good a classification algorithm is. Because what we'll do is we'll be able to look at things like its positive predictive rate, its accuracy, its precision. These are all things that are part of our confusion matrices calculation. And I actually plan on doing a mini lesson on that with that what are called rock curves and area under the curve, AUC, and stuff like that. The last thing I kind of wanted to do then is I wanted to show you a visual of what this actually looks like. So we're going to use the package visreg to do this. So now what I'm going to do is I'm going to do visreg. I'm going to take my model 1, which is the model we just did earlier, and then I'm going to do miles per gallon and scale equals response. So if we run this, you can see our sigmoid curve right here. Notice that our y-axis for automatic or manual is a continuum from 0 to 1, right? This is what I was talking about. It is actually, you do get a probability involved. And this curve represents where our actual values are. So this means that if I have a car with miles per gallon that was at 25, then it would be here on the line, and I could go over and I would get a probability of like 0.86. If I have a value that's, let's say, right here at 23 miles per gallon, I would go up to the line and I would get a probability of, let's say, 0.3. And this is how you actually get those probabilities. Use the sigmoid curve, this S curve, which based on whatever your X value is, it can then give you an associated probability with it. And that's what changes whenever you're making these logistic regressions. You might have an S curve that's really slow slope, or you might have one like this where it kind of is basically 0 and then almost instantly jumps up. So this one has a pretty hard cutoff, but you might have one which is much more gradual. When I'm picking my cutoff point, this is exactly what I'm doing. I'm saying, okay, anything above this value would be 0, anything below this value would be 0, anything above would be predicted as 1. In this case, I did 0.5, so it's going to be anything above this value is going to be 1, and anything that's below it would be predicted as 0. So that's going to be it for looking at logistic regression in R. I know, again, we didn't dive super deep into it. I just wanted to introduce the actual how to implement a logistic regression in R. If you want to dive deeper into different families and different link functions, things like that, there's quite a bit to it, and R is able to do all of that. You can see that overall, though, the actual modeling follows the same syntax we've been using since we did linear regression. And pretty much everything in R will. So once you have a strong understanding of how to write the syntax of models in R, whatever method you're using, whether it be ANOVA, logistic regression, ridge regression, support vector machine, it's all going to follow that same syntax. So you have these basic tools that you can use for almost anything. And logistic regression is a very strong tool to understand because it's very strong for binary classification. In this modern era of superbly complex and advanced methods of machine learning and statistical learning, logistic regression still consistently does really well for this one thing, for binary classification. And you can actually take it even further. If you wanted to do some sort of grouping classification, you could almost create a system of logistic regressions. So just know that I wanted to introduce this topic, show you how to do it in R, show you the similarities to what you've already been doing, and just kind of introduce you to another strong tool to have in your toolkit. Hello, everyone. It's time to start preparing for your project for STA 4102, Computational Methods for Applied Statistics. So let's jump in and go through the project form together of what you're going to be doing, what your expectations are, and what steps you'll need to take. So if you look at the project document, which you can find in Canvas, either in Files and then Project, I'll have it in the module for the week, and also I will have an announcement about it. But if we look at our timeline here, for July 5th, this is where you're going to need to post what your project topic is and the data set that you're going to be using. So you don't have to go into great detail here. It's just simple, like 1 or 2 lines about what the project is and where you got your data and what data it is. So it could be something like, I'm going to be looking at trend analysis of how housing prices are affected by something, and I'm getting data from, National Institute of Housing or Kaggle or something like that. On July 12th, this will be where I want you to post, and I'll have an assignment for this, a project outline. So this will be the outline of, what you're doing, the steps you're taking, all the kind of stuff that you would have in a general outline, right? Your introduction, what methods you're using, stuff like that. On July 20th and 22nd, we're going to have project presentations. This is where you'll actually present the work that you've done. Now, the way that I actually will assign everybody their position in the project presentations is I'm going to be using randomization in R. So remember we talked in the videos and in class about sampling methods. Well, I'm basically going to do that. I'm going to take the roster of everybody in the class. I'm going to sample without replacement for the entire class. It's going to just randomly order everybody, and that will be your position in the presentations. Now, the presentations, and I'll talk more about this later, will be 10 minutes long. So you can kind of figure out where you're going to be day one or day two based on that. But if you're kind of in the middle, you need to be ready to do it on day one. Because if anything happens, let's say a student is out because they're sick or something like that, you might think you're going to be first on day two and you actually need to be on day one. On July 26th, this will be when your final project report is due. Now, the reason I focus on doing a project instead of a final exam is because as statistics students, especially going into software heavy fields, you're really going to want these portfolio projects to show your skills and what you can do. Having a degree alone is not enough. You need to actually have certain skills that employers are looking for. So this kind of acts as, two parts. One, it allows us to sort of go through the research and programming process, but also it allows you to have an early project that you could start adding to your portfolio. Now, this may just be a starting point where you do this project and then you learn a lot from it, and now you're going to start making real projects. This could be a pretty well polished project that you're going to actually put into whatever it is you're showing this on, something like GitHub or something, or it might be the start of a bigger project. And I've had all three outcomes from students. Some, it's a one-off, they do it and then they don't go back to it. Others, they'll come back to me semester after semester because they're expanding on it and they're doing something more with it. And this could lead to either A, building out some big project that you could show an employer when you're interviewing, things like that. Or if you were jumping into graduate school afterwards, this might be the beginning of something you're interested in researching that could be your foundation to jump deeper into the topic. So now let's jump into the objective. The objective of this project is to equip students with the necessary skills to explore real-world datasets, analyze them using computational statistics in R, and develop predictive models to uncover trends and insights. Students will be encouraged to select a topic of interest and appreciate the significance of data-driven decision-making in their chosen field. They will integrate techniques covered in class and also employ advanced techniques that we did not cover, things like ridge regression, logistic regression, or support vector machines. Now, this is for two parts. One, again, this is kind of acting as your final exam. I want to see that you can implement the things that we're doing in class in a real-world sort of scenario, right? Because these tools that you're learning in class are applicable in actual analysis. This isn't like some class where you learn some skills, but you never actually use them. But I also want to include something that we've never done, because a big part of working in technology is you're oftentimes going to be using tools you've never touched or seen before, or packages or things like that. So you need to practice doing that. And this is why I added things like, again, like ridge regression, logistic regression, SVM. If you're interested in time series, you might do something like that. And again, the reason is because you're going to have to use the skills you picked up in class. You're going to have to look up the documentation. You're going to have to figure out how to implement it. You're going to have to see if it's appropriate. So as I kind of showed in the timeline, there's 4 parts to this project. First is the easy one, just what's the problem you're interested in doing and what is your data set. This problem should be something that you're interested in based on your interest, career path, whatever it is. So if you plan on going into an insurance industry, this is a good chance to dive deeper into that. If you plan on working in finance, then great, do something with financial data, whatever it is. Or it could be something you're interested in. I've had students who do things ranging from figuring out who has actually more wealth between Rihanna and Taylor Swift. I've had people who actually go out and gather their own data to figure out how different statistics affect your damage per second in World of Warcraft, up to like your general ones. How do things affect housing prices, area code, bathrooms, whatever it is. And the world is really your oyster in this regard, right? The only big thing with this is it needs to be something that you can actually get data for. And this is why I include that part in the original submission. Not only do you need to say what your problem is, you need to find out, can I actually feasibly get some data that I could use to answer the question that I have? Now, your outline is where you're going to go a little bit more in depth. So the first part is you are going to have your topic, right? It's your topic and your data source. Just like the first part, you're just going to include that, maybe go a little bit more in depth on it. So students should choose a topic that aligns with your interest or major. And then you should identify a reliable data source for the chosen topic, such as government websites, data repositories, or reputable organizations. Things like University of Michigan has a lot of data sets, Kaggle, government websites, census, all sorts of things like that. Next, you need to formulate a problem statement. So this will define the specific research question or problem to be addressed using that data set. And then you want to write a concise and clear statement about what your problem is. Then you're going to talk about the steps you'll be taking for data cleaning and wrangling. So you want to import the data into R and assess its quality. You want to address any data issues, things like missing values, duplicates, inconsistencies, possibly it's in the wrong data type, right? So you might get data that looks like it's numeric, but it's actually character strings. This would be part of your data cleaning and data wrangling. You also then want to apply your data cleaning and wrangling techniques to prepare the data set for your actual analysis. Once you've done your data cleaning and wrangling, this is where you want to now do your exploratory data analysis. This would be things like using R to perform an exploratory data analysis to gain insights about your data. You can create summary statistics and visualizations, things like histograms, box plots, scatter plots, to give you a feel for what the data looks like. This could be something like using a summary to look at mean and median, max, min, all that kind of stuff. You could do things like look at kurtosis and skew. Whatever information would help you have a better understanding of the data. Because generally when you're doing these projects, these are going to be a larger scope of data than you've dealt with previously, where you could look at the 172 and get a feel for it. This could be something with possibly millions of data points. And then you want to identify potential relationships or trends within the data. Part of this project also is to try to apply analysis to real world or realistic data. The reason is because when we're doing examples in class, a lot of times, there's two things. One, either I'll have a clean data set so we can focus on the specific thing that we're doing, right? Or I'll just hand wave away certain problems with it because it really doesn't matter for my example. An example of this would be when I was recording the video for a proportion confidence interval. I hand waved away the assumptions that NP is greater than or equal to 5 and NQ is greater than or equal to 5 because it failed, but I was just showing the example, so it really didn't matter. I did talk about it though. So these would be things you need to check out. Another thing would be correlation or specifically multicollinearity. A lot of models fail under multicollinearity, which will bring us to our statistical analysis. So here you want to discuss the application and theory of relevant statistical tests or models based on your EDA findings and address in a problem statement. What we mean here is I actually want you to give some detail about the analyses you're doing, not the analysis you did. Meaning I don't want you to just say, I did a linear regression, here's what I got. I want you to explain, why did you choose the linear regression? What are the pros and cons? What are the assumptions of a linear regression? And why is this an appropriate analysis for what you actually are trying to answer? So if you're doing multiple regression, for example, it is assuming that you do not have multicollinearity. If your data shows you do have multicollinearity, what are you going to do about that? You either need a different method that does not have that assumption, or you have to find some way to deal with this multicollinearity. That's part of what you're being tested on. Next, you need to integrate techniques covered in class, such as hypothesis testing, correlation analysis, regression analysis, stuff like that. You then need to incorporate an advanced technique not covered in class. This is the one that we specifically didn't cover. This could be something like for time series, you've got ARIMA, you could do support vector machines, you could do random forest, whatever method would make sense for your analysis, but is not something we specifically covered in class. Again, this is to test your ability to go out and actually get the information, figure out how to implement it, and then actually do it. Once you have that, we jump into modeling and prediction. So you want to develop a predictive model using the cleaned and analyzed data set, and then choose from various modeling techniques, including those covered in class and chosen outside advanced techniques. So this basically just means now actually do your analysis, right? This part is more focused on the models themselves. Which models did you choose? Why did you choose them? What are their strengths, weaknesses, assumptions? Why is it appropriate? Things like that. This is the part where you're actually looking at the coding itself. Do the analysis. Take your data, get it into the state it needs to be, and then run the two analyses or whatever it is you're doing. Then you jump into model evaluation. You want to evaluate the performance of the predictive model using appropriate metrics. This could be things like R squared, mean square error, accuracy, or you could use something like a confusion matrix to do a ROC curve. Whatever you would do based on the type of problem and question you have. So this would be something where you might want to go out and see what sort of things people report. And it will depend on this, right? If you're doing Bayesian analysis, you're going to have a very different report than somebody who's doing a classification model, which is going to use a confusion matrix with ROC curves, things like that, or AUC curve. You also want to discuss the limitations of the analysis and suggest possible improvements or future research directions. Sometimes students will go through all this work and it doesn't work out. That does not mean you need to start the project over. This is a learning experience. So when you are doing your analysis, you might find that your model that you thought would work great fails miserably. Or it might contradict your initial hypothesis, and that's okay. This is where you would talk about what were the shortcomings. An example of this would be, I had a student one time where the data she had gathered had a lot of categorical data. This would mean things like, do you have diabetes? Yes or no. Are they a smoker? Yes or no. A lot of binary operators. The problem is most modeling techniques don't do well with categorical variables. Now, I had taught an entire course on categorical data analysis. It's a lot more complicated than you might think. Right? When we introduce it in something like Intro to Stats, we talk about things like you've got your nominal variables, which are things that are classified by name only. So, red, green, blue, and then you got your ordered values like first, second, third place, or, best, average, worst. But when it comes to actually doing analysis, most techniques are not built for this. You have to do a lot of special, things to make it work. And it also can make it very complicated. So by choosing this data set, she kind of almost gave her a, project on hard mode, and it led to a lot of complications. So that was a big part of her write-up, was where were the shortcomings? How could she approach this better in the future? Are there things she could have done to better analyze this data? Right? Because remember, she chose her methods before she knew she was going to run into this. She could have changed what analysis she was going to do, or she could spend a lot of time focusing on why this is inappropriate and actually what a better analysis would be. And then once you've done this, you're going to create a comprehensive report detailing all aspects of your project, including problem statement, data source, data cleaning and wrangling, exploratory data analysis, statistical analysis, modeling, evaluation, conclusion, and recommendations. So again, I want you to kind of think of this like you are a researcher doing a research project. So you are having a couple steps to it. You're going to just tell me what your problem is and your data. You are then going to outline what steps you're going to take, how you're going to set it up, however you want to do your outline. It's not set in stone. It's more just get all the information in one place of this is what we're doing. Your final report is going to be much more formal. Okay, so let's talk about your project report. Your project report should be treated as a small research paper about the problem. You want to use the following as an outline for what to include in your report. And by the way, the final report should include anything and everything. So you want to have a title page. This will be things where like title of your project, your name, class, stuff like that. Then you want to have an abstract. So an abstract, if you look at research papers, is a brief summary that should provide context for the research and state the research question or hypothesis. This section should explain why the topic is important and what the research is expected to contribute to the field, which of course, this is a learning thing, so it'd be more of it doesn't have to be as grandiose as I created something new of like, it'll help our understanding of this system, blah, 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 make decisions, something like that. But also include some introductory information to the topic or field of the problem. So your abstract is usually like 250 to like 350 words. It's not meant to be long. It's meant to be like, you make some grandiose statement a lot of times, like, in the modern era, people commonly have this issue. We hypothesize that this is a thing, blah, 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 blah. We implemented this and this analysis to check this and found that there is some validity to it or to contradict it, something like that. It's just to kind of set the whole paper up. Then you want to do your introduction. The introduction should provide context for the research and state the research question or hypothesis. This section should explain why the topic is important and what the research is expected to contribute. Also include some introductory information about the topic or field of the problem. Remember, whoever's reading this is not going to be an expert in the field. So if you are very interested, okay, I mentioned like the World of Warcraft example earlier. Most people who look at this project might not have played WoW or something like that, or be MMO players. So you need to introduce this. Why is this a topic? Why are we looking at this? Why would this be interesting? Things like that. So give a brief description, right? Don't expect someone understands the insurance industry just because you do and you find it interesting. some people have probably never thought about any aspects of it outside of I need insurance in my day-to-day life. You want to include your data description. So you want to describe your data set used in this project. Discuss where the data came from, how it was collected, and any potential biases and limitations in the data. Include your data exploration and transformations here. This would also be where you talk about some of the details of it, the mean, the median, the mode, how many data points you have, right? Do you have 18 million data points, or are you dealing with a small data set of only 1,350? Those are kind of important things because it could actually impact, how strongly, you believe in the outcome of your project. But also it could lead to other aspects of it. Like if you started with 15 million data points, but after doing cleaning, because there was so much missing data, you're down to 170,000, still a sizable, data set, but you lost a lot of data. Is that going to affect your analysis? Are you going to get erroneous results because you had to cut so much of the data? And this is where you could also think of things more advanced. For example, a lot of times students, when they have data sets like this, they'll find missing data, they'll cut all the missing data, and they'll really pare down their data set. But you might want to look into other topics that could be interesting to learn. Things like maybe you want to do some sort of EM algorithm to impute the values, or multiple imputation, or things like that. You might have some method where you don't have to get rid of all the data, but you're going to use some sort of statistical method to kind of estimate what the values should be. You also want to include your methodology. This will be a detailed explanation of the statistical techniques and models applied to this project. This section should be detailed enough that someone could replicate the study using your description. This would be talking about the actual models themselves, why you chose them, what they are, what their limitations are, pros, cons, all that kind of stuff. This is not the actual computer part. This is the statistical part, right? If you're using multiple regression, explain multiple regression, explain why it would be appropriate here, explain its limitations, explain, the basics of it. This would be where you use the tools I showed you and how to type in math into a Word document to be able to expand on the actual statistics. Then you actually want to include your actual analysis. Because this is a class project and we're actually testing you on your ability to implement the coding, be sure to actually include some of the R code and things like that you did, right? And this is where, again, you could use something like writing in a markdown, at least for the initial document, to get the R code there, or you could copy in things, however you think would be appropriate based on what you're trying to show. But the reason I bring this up is because here's two factors you need to consider. What do you need to support enough, to give you enough support that you actually understood the topics, showed that your analysis was done correctly, but also not to just fill it with pages and pages of random numbers. An example of this would be, I would not print a data set with 10,000 data points. So what you might do, if you want to give an example, would use like the head command. Show like the first 15. Now you've got enough to show what you're doing, but also not so much that you are, just filling pages and pages and pages of worthless numbers to whoever's reading this. So you want to present your findings of your analysis. This can include things like your statistical outputs, such as tables or charts, and you should clearly indicate whether the results support or contradict your original hypothesis or the final answer to whatever your research question was. Then you want to have a discussion or interpretation of results. You want to discuss what the results mean in relationship to your question that you had or your hypothesis. And this would be an opportunity for you to interpret the results and sort of draw inferences from them, right? So if you find that, if you're looking at like how housing prices are affected by different aspects, and you find that houses with more bathrooms tend to have much higher values, then you could infer that a house with more bathrooms up to a certain point is more valuable, something like that. And then your conclusion. Summarize the project's key findings and suggest areas for further research. Discuss the implications of your findings and whether or not they could be generalized beyond the data you analyzed. So this would be, because again, this is a final project, not like you're trying to actually write a paper that you're going to publish. This would be something like possibly what you could do if you were to take this further, right? So if you were using this as the foundation of your portfolio, what steps could you take to either create a new project that builds upon this or to expand upon the project that you've already started? And then finally, I do want you to have references, right? Again, treat this like you would a research paper. Reference your data. Reference, whenever you're looking at your method, let's say you're doing support vector machines, reference where you got that information from. Show your references. Now, I'm not telling you to use a particular style because it should be appropriate in your field. If you're doing a research project on something in the field of psychology, you may have a different citation style that you generally use than somebody who does research in engineering or medicine or something like that, right? But if you want to, good go-to, just use APA. And then the last part we're going to talk about is your actual presentation. So the presentation, you should aim for being 10 minutes. Because remember, we have to get through everybody, which means you're going to have the opposite issue of when you're writing your paper. When you're writing your paper, more is better. Generally, you want to be thorough, make sure everything is there. In the project, you do need to talk about all these aspects, but you also need to keep it in a limited time, a time limit, because one, we have to get through everyone, and two, this is the part about trying to figure out how to distill the data down while not losing it entirely. So this is where you're going to give detail, but not go into as great of detail on certain parts. So the goal of this is to effectively communicate the life cycle of your data science project to your peers. While your final written report is highly formal, this presentation is an opportunity to practice technical storytelling. You are required to address all components below, but you have full creative ownership on how you structure and visualize your slides to best showcase your work. This means that I am not limiting you to it has to be a PowerPoint. I'm not limiting you to any aspect of you must use this format or you must have this. No, everything is at your discretion. You are a researcher or worker, and you have to present this to your boss or your peers or the research community, whatever your scenario is in your head. What are you doing? How do you do this? What do you need to show? And again, there are some, of course, guardrails of I need to see certain things. Grading criteria. These are the things I do need to see, though. Project introduction and your data. You do need to provide a brief introduction to your chosen topic and clearly state what your core problem is or your hypothesis, and identify where your data came from and address its baseline structure and collection limitations. So this would just be basically, I'm doing a topic on housing prices in the Tampa Bay area. This is important because as students in Tampa Bay, a lot of us may get jobs here and we may be in the market for a home in the near future. So I wanted to look at how this aspect affects this. Or my hypothesis is that home prices are going up by this amount. So by the time we graduate, it'll be whatever it is. So just quickly present what's my problem, give just brief description so that people kind of are on the same page with you, and then your data. And this could also include some things like some limitations. I was not able to actually get up-to-date information. The data I was able to get ends at 2024. So from there, we're kind of inferring about, current time in the future. I need to see your exploratory data analysis. So walk the audience through your exploratory data analysis, show the meaningful summary statistics and unpolished or custom visualizations you use to discover trends, explain the necessary cleanup, wrangling, and variable transformations you performed in R to get the data set ready for modeling. Now, this is the part I said where you need to show, but also not go as great in detail. For example, if you did a lot of cleanup where you were looking through and dealing with NAs and transforming your data into from characters to numeric, and you could just kind of briefly talk about these are some steps I had to take, and here's my mean, my median, my mode, here's my skew, here's a graph to kind of show, here's a histogram. Again, you need to be brief, but also somewhat precise. For statistical modeling and methodology, you want to present your analytic pipeline. So you must feature both modeling approaches. This would be your one that we did in class, and also your new one that we didn't cover. A standard method covered in, I talked about that. Justify why these models were appropriate for your data structure and explain how you evaluated or validated their performance. This would be things like, did you do holdout method validation? Did you do k-fold cross-validation? How did you validate this? Did you look at the accuracy of your model? Did you look at the positive predictive rate? Did you do RMSE to see that your trend line was appropriate? Things like that. And then I also want you to compare the insights you gain from both models, right? Because both of these models should be at least somewhat appropriate. An example, linear regression might not be as appropriate because you have, a specific type of data, but you need something that regression makes sense. You can compare why your more advanced method was the better method. You got better results, how you validated, stuff like that. You need to include your conclusions. This would be connecting your model results directly back to your original problem statement, summarize your key findings, candidly address the limitations or boundaries of your current analysis, and propose where the research could go next if you were to expand or iterate on this project. And then finally, you need to focus on your delivery and your pacing because we are going to have some questions at the end. So effectively manage your 10-minute time window. Your slides should complement your spoken narrative rather than serve as a script, right? So don't try to just read off the script like I'm doing right now for this project. And speak clearly, assume that we have a technical audience so you can be, more thorough. Everyone that is going to be seeing this has taken this class with you, meaning you can be more technical in your presentation. Because this is a big part of presenting data is you need to kind of tailor it to your audience. If I'm giving a talk to researchers at an AI conference, I'm going to have a very different way of speaking and language that I use than if I'm giving the same sort of talk at something like ASHA, which is for people audio, speech, hearing, and language science. Be prepared to actively engage with the class during a brief Q&A session. This is all the aspects of this project. You've got your initial, what's your problem, what's your data? Then an outline, here are the steps I'm taking, here's the analysis I've chosen to do, here's a brief description why I'm doing these steps, things like that. Maybe an outline of like how I'm going to set up, abstract this, that, and the other. Then the next part, time-wise, is your presentation. Your presentation needs to be done before your final project report. And this is because when you're doing your presentation, Q&A, stuff like that, there might be parts where it adds something to it. You're like, oh, I hadn't thought about doing that, but I could add that in, no problem. So this is why like your actual report is due last. So you'll have your presentation, which again, remember, I will be randomizing this. I'll post your position in the presentation order, but kind of have it ready for day one. And some of you, of course, will be in day two. And then the last thing will be your project report. This is your formal report where you're writing it like a little mini research paper and you're including anything and everything that is relevant to your research topic. Hello, everyone. I wanted to kind of come to the end of this course by covering a little bit more that we didn't really focus on, but sort of where you could go from here. So in this course, we've covered a range of topics from introducing R from the very beginning, installing it, basic functionality, all the way up to using statistical methods like logistic regression and ANOVA. We looked a little bit on how to import data, specifically read.table and read.csv. But there's a lot of different data types that you can actually use in R. So this lesson is going to be a little bit different than prior ones, where I'm not going to be jumping into R and showing a ton of examples, because everything I'm going to be showing here could be a lesson in and of itself. So what I'm going to do is I'm just going to go through some of the different packages that you might use to import those different data types, knowing that there also will be other packages that do similar things, depending on what works for you and what sort of functionality you're looking for. So in the domain of statistical analysis, the process of importing data is a fundamental element that precedes empirical investigation. The instructional session is dedicated to the methodologies of data importation within the R statistical environment. R, recognized for its statistical rigor and graphical capabilities, requires data as a prerequisite for analysis. The importation process, however, is frequently confronted with the challenge of diverse data representations and sources. So to pretty much sum up what this means is that if you want to do analysis in R, which is a really strong and robust tool, you need data. But the problem is a lot of times data is going to be in different forms from different sources. So how do you get that data into R? Right? Whenever we're doing a class, it's super easy where I have some CSV that I give to my students, and then they all just use read.table or read.csv, or maybe even just do the import function on the graphical interface, something like that. But a lot of times you're going to want data from sources where you need to pull from an API, or it's coming from a SQL database, or maybe it's an XML file, or maybe it was an analysis that was done in another program like SAS or SPSS, but you want to bring it into R to be able to do something a little bit more sophisticated. So the objective of this lesson then is to briefly introduce various mechanisms through which R can assimilate data irrespective of its origin or format. We're going to explore R's capacity to manage an extensive array of data types, from rudimentary text files like we've done in class to more intricate structures such as JSON or XML. Additionally, the lesson will encompass techniques for interfacing with databases and procuring data from web resources. To begin with, we're going to start with our tried and true read.table and read.csv approaches that we've done before. So we've already talked about this in the class, but we can use read.table, and then we can put the file that we actually want to import into R. So this would be a file on your computer, for example. Or you could actually put a web address there if you have some specific place where a file is. We would use header to determine whether there is in fact a header in the data, so that way R knows whether to treat that first row as the header, which would be the names of each of your columns, or whether it actually just jumps straight into data. And then you've got your sep equals, which is what your data is separated by, right? So in my example here, I have it divided by /t, which would mean that it is a tab. But oftentimes it's going to be a tab, a space, a dash, or most importantly, a comma. This would lead you to your CSV data, comma separated value. So you could do read.table and then just tell it to separate by a comma. So within the quotes, put a comma, or you could use the command specifically for it because it's so often used, which is read.csv. So for this kind of importing, we have first our file. This is just going to be the name of the file or connection. Like I said, you can connect online to read the data from. Now, this is important because whenever I was teaching this, when we're in Windows, for example, I usually just go to the actual file, right-click it, hit properties, get the file path so I don't have to type it all out. Or if it's in your working directory, you don't even have to do that. But you have to remember that R uses a different file system. So you have to change the backslashes to forward slashes, things like that. Then once you have that path, you need to put the actual file name exactly as it's written. So if it was something like height_weight.csv, you need to write it that way. Capitalization does matter. Next, we have our header is a logical value indicating whether the first row contains column names, right? So you could have header equals true if you have column names, or header equals false if there are no names in the first row. Sep is the field separator character used to explain how it's going to separate your different data points. Quote, this is the set of characters used to quote fields that may contain special characters, such as field separator or new line characters. So the default, of course, this would be backslash, but you've different file systems, you may have something else. Next, we have DEC or DEC. This is the character used as the decimal point in the numeric data. So in America, generally, we will use a comma to show that it's 1,000, but oftentimes we can leave it if we're dealing with data in the computer, but we will put a decimal using a dot. So if you have like 206.52, you would put period 52. But you may instead want to have some other system. For example, some other places, they will use a comma to represent the separation to the decimal. So this is where you could change that. Skip is the number of lines to skip before reading data. By default, it's set to 0. You might wonder, why would you need this? Well, a lot of times when you go online, for example, to grab files, there's going to be some text or information at the top. This might be how the data is going to be used. This might be where the data came from. This may be something that's giving credit to those who created or collected the data. So this would just be, okay, how many lines do I want to skip? Okay, start here. So that's what the skip is for. And then string as factors is a logical value indicating whether character variables should be converted to factors. And by default, this is set to true. So if you have character strings, let's say it's names, do you want it to be factors or do you want to treat it as a string, in which case you would want string as factors to be false? And then following that, I just have a brief example of what this might look like, right? We have our data, which again, I would name it something not data, because data is something that we use within functions in R. So I'd call it something like my data. You have read.table, you got your data.text, that's where the data is coming from. Header equals true, meaning it does have that column, that first row that counts for the column names. Sep equals \t, so it's going to separate data with a tab. Quote is backslash, so that would say that's how you would do your character breaks. Dec equals period, so that means that our decimals will be separated by a period. Skip equals 0, so we have no lines being skipped. And string as factors equals true, meaning that if I have any character strings, it will treat them as a factor. If we specifically look at the read.csv importing tool, this is just a wrapper function on read.table. Like I mentioned, it's not its own thing. It's basically just read.table, but with some of the settings kind of set up by default for you. So it's designed to read comma-separated values, or CSV files, a common format for storing tabular data. The read.csv function sets the sep argument automatically to comma by default, making it suitable for reading CSV files without specifying the sep argument. All other arguments are exactly the same as read.table. And then, as before, I have an example of what this might look like. But again, you could do the same thing with read.table. You would just then want to include what the separation between your values is. Now, one of the main methods that we've used in class is a lot of times we'll just create data. So the most common ways you can do that is you name some object, you put your arrow operator, and then from there, you can either put, C for concatenate and make a vector, you could put a single value, or you could create a data frame like here. So we have sample data, which is going to be data.frame, and then we're going to have whatever the names of the columns are. So name equals, and it's going to be Alice, Bob, Carol, and David. So name is the first column name. It's going to have 4 data, which are Alice, Bob, Carol, and David. So A, B, C, D. The second column, the name will be age, and it's going to have 25, 30, 35, 40. The third column will have a name of height. It'll be 5.6, 5.9, 5.5, and 6.1. And then the fourth column would be weight, which has values of 130, 160, 120, and 170. You don't always have to import data. Sometimes you want to create data, which I do a lot of times in class, because it's easier than trying to go find a data source that works for what I'm trying to show, if I'm not trying to show that specific thing. So I just make up some data, even if sometimes it's nonsensical data. Like a lot of times I'll use R norm and I'll just create some data from a normal distribution just to show how a function works. If you have data that's loaded into R, whether it be something you imported, maybe you made some changes to it, maybe it's data that you created yourself, you can actually write this using something like the write.table function. So now we'll use the write.table and write.csv functions to save a sample data to data.txt and data.csv. So the way that they will work is pretty much the same way you work with importing, except for now you're saying what the file will be named. In fact, I actually do this. I did this earlier. I was creating the roster for the class on who's going to do which projects, presentations, in what order. So I imported the data from the grades. I deleted all the stuff I didn't want, so I just had names. I sampled it without replacement, so each student got selected once, put them in a certain whatever order it gave me because it was randomized. And then I wanted to write this to a CSV where I can add the topics of the projects. So I use the write.csv function. And then I need to name what it's called, right? So I use write.csv, and then I need to specifically say which data am I going to be writing as a CSV. So in my case, it was something like 4102 roster. And then after the comma, within the quotes, this is going to be what your file is actually called. So in this example, I have data.csv. So if I did this, it would save in my current working directory as data.csv. But just like when you're importing, if you want to put a file path, you can tell it to write to a specific place. So rather than putting data.csv and it going to my working directory, I could put something like c:/temporary files/ and then data.csv. And then I have row names equals false. This would be your first column. Do you have row names or not? And in my case, because it's a roster, I just have, my column names are name and project. And then I don't have row names, so for me, this would be false. If you have row names, then this is where you would set it equal to true. The next package I want to talk about is the readxl package. So the readxl package provides functions to read data from Excel files, both XLS and .xlsx formats, into your R frames. So the two main functions you will use for this are read_Excel or read_XLSX. Now you might wonder, what's the difference? Because when I pull up a CSV, it pulls up an Excel anyway if I have it on my computer. Well, as I kind of showed previously, really a CSV, you can think of like a blank notebook with just the numbers separated by commas, and then every time you're on a new line, that would be how you separate rows. An Excel file actually has a lot more information in there. It's got all the formatting and metadata. So if I go into Excel and I add highlighting, I change the column widths, the column heights, I add formulas, all of this, when I save a CSV, is gone. It goes away, none of that is kept. But if I save it as an Excel file, right, either XLS or XLSX, then it's going to save all of that metadata. So this is why you might want to just, if you have an Excel file, rather than trying to import a CSV and dealing with that sort of whatever you lose, it's better to import the Excel file. I will tell you from personal experience, this is where oftentimes you're going to want to do this. Someone's going to send you an Excel file, and at the bottom, you see all the little tabs, right? So you have different tabs for different things. Maybe they could be groups, group 1, group 2, student cohort, school district, whatever the case may be. Well, if I try to save this as a CSV, all it's going to save is the active tab that I'm in. So I would have to save, let's say I had 4 tabs, I would have to save as 4 separate CSVs. But if I save that as an Excel document, then I can actually import that and all of that information will still be available. So if you want to install this, you do install.packages. It would be the readxl package, and then of course you load it with library. If you wanted to pull in an XLS document, it would be read_Excel and then whatever your file path is. Or if it's an XLSX file, then you want to do read_XLSX. Next, we have the Haven package. The Haven package allows you to import files from SPSS, SAS, and Stata into R. So the main functions are read.sav for SPSS, read.dta for Stata, or read_SAS for SAS files. So this is again where you might want to bring in a file from someone else's analysis to continue on the analysis or expand on it. So for example, I've done this specifically with SAS myself. I've had people in other departments who they learned how to use SAS. They have some SAS code. Maybe they copied it from from some prior work, but they don't really completely understand it, or they want me to do some further analysis on it. So they might output the file and they'll send it to me. I can read it into R using the read_SAS function. So we have read_sav for SPSS, we have read_DTA for Stata, and we have read_SAS for SAS document. Then we have the R-MySQL package. So the R-MySQL package provides an interface between R and MySQL databases. This will allow you to connect to MySQL database, query the data, and import it to R. So now this one is going to be a little bit more complicated because you're not pulling in a file like you would when you're doing the other imports we've looked at. What you're actually doing is you are connecting to a MySQL database, meaning the data is on the database. You are then going to query the database, ask it for specific information, and then that is what you will have in R. So you're not getting the entire database. So what you would do first, again, install.packages, you would do R-MySQL. Notice that R, M, and all of SQL are capitalized in this. Capitalization does matter for this. And then you need to establish a connection with that specific database. So you would use dbconnect, and then you're going to put MySQL. And then your user is whatever your username would be within that database. You have to actually have access to the database. Password equals, within quotes, you put your password. DB name, this is where you actually specify the database name. And then host, this would be, for example, where the database is located. An example of this, I do something similar. I use a different package I'll talk about later. Whenever I'm doing the stats project that I created for my intro to stats class, I have a PostgreSQL database that all of the data goes into, and I pull it whenever I'm doing analysis. So what I need to do is exactly this. If I need to do anything to that database, whether pulling the data, analyzing it, or even making changes, I first have to connect to my PostgreSQL database, and then I can query the data, all that kind of stuff. So once you've connected to your database, then you need to actually do your query. This is where you'll use your, in this case, MySQL commands. Things like select, star, which will tell you to select everything, or you can specify exactly what you want to select. And then from whatever table it is, right? So this would be where you need to dive into the syntax of how to use MySQL. And I do think this is tremendously important because, as we mentioned in the very beginning of this course, the number one skill you oftentimes will need when working with data, whether it be data analyst, data scientist, or anything else, would be how to use SQL. But this is how you can use it, get the data within R. You can directly query the database instead of having to go into SQL and then somehow output the data, anything like that. Now, last thing is, because you are connected to this database, the last step you want to take is you actually want to disconnect from the database. So you can do this with db disconnect and then whatever connection you created within R. If you want to connect to other SQL databases, not just MySQL, you can use the RODBC package. So this package allows you to connect to various databases such as SQL Server, Oracle, or MS Access. And then you can query the data just like before, and you can import it into R. So same thing, you're going to have some sort of connection. In this case, you would use ODBC connect. You would then say your DSN name, which is your data source name. You've got your user ID, which you do with UID, and then you've got PWD for the password. So just like before, you connect to the database, then you can do your query using whatever SQL commands that type of database would accept. This is something you would need to know based on your type of SQL, right? For example, if you're using SQLite, it's still SQL, but it might have certain functionality the other one doesn't, or vice versa. I think, for example, SQLite doesn't have left joins or right joins. I can't remember which one it is. Then from there, once you've selected that data, you can then put the data from your query into your data, run some analysis in R, and then just like before, you want to disconnect using the ODBC close command. There's also the reader package or readr package. The readr package is part of the tidyverse collection, and I actually do plan on making a lesson about that. But specifically, most people in R are using tidyverse, and it will provide functions to read various text file formats such as CSVs, TSVs, and fixed width files more efficiently than R-based functions. Okay, so one thing I actually want to point out here, because CSV, yeah, it does that. You can use that instead of using read.csv. Cool. But the TSV, so this is one that I personally had to use for a project where I was doing natural language processing where we had statements that were being made. The problem is those statements, because, human language, English, is that it has commas in it, meaning I couldn't use comma separated value data because it would see each of those commas, where you might say something like, she thought the boy was smart, fast, and whatever. Well, between that, you're going to have commas. Well, it's going to see that she thought the boy was, smart, fast, and it's going to see those as separate data points within, instead of just one with commas within it. So this is where I needed to actually use TSV files. So once you have this readr package, what you can do is you can use read_CSV if it is a CSV file. You could use read_TSV if it is a TSV file, or you can use read_FWF if you have a fixed width column or fixed width file that you want to access. One of the most common file types you will find online, especially if you're doing anything with JavaScript, anything online databasing, stuff like that, would be JSON files. So JSON-Lite package can provide functions to work with JSON data in R. You can use the JSON function to import JSON data into R as a data frame. So you would, again, install or load JSON-Lite, and then you can use from JSON, where J, S, O, and N are all capitalized, and then you just put your data like you would before. You put the path of it, which of course could be a server. If you have a JSON file locally, whatever you want to do. If you have XML data, the XML package allows you to import XML data into R. You would use the XML to data frame, where the T, D, and F are all capitalized. It's using camel case. And use the XML to data frame function to be used convert XML into R data frame. So again, I have personal experience with this as well. This one was more personal, less professional, but I used to play this game called EVE Online, and I was creating a spreadsheet where I could actually look at pricing in different markets in the game from any location, and then from that do sort of market analysis, all kind of things like that. Well, I was using online spreadsheets, specifically Google Sheets, which used a lot of XML data because I was constantly pulling in from these databases that are run by people for the game, and this is something I could even import into R, right? So I could use my my XML package to then get that data into R, and I could do the analysis there. So in this case, we would use XML parse to import our data, and then XML to data frame is what will then convert it into a data frame that you can use in R. The data.table package is an extension of the data.frame package that provides improved performance and additional functionality. So you would use fread function, and it can be used to read files that are CSV, TSV, or others into a data.table object. So what you would do is you would use fread, and you would read that data, whatever it is. In this case, I have data.csv, and it would put it into table data. The next package I wanted to bring up is the feather package. It provides a binary file format for fast and efficient data storage and sharing between R and Python. You can use the read_feather function to import feather formatted data into R. Now, personally, I've never used this one, but it is a thing in case that's something that you are interested in. And while the feather package was, game-changing at the time, it's actually kind of been replaced more often than not by the arrow package. So the arrow package provides an interface to Apache Arrow, allowing you to read and write Parquet files. These are highly compressed columnar storage format that has become the industry standard for fast, large-scale data science machine learning workflows. It's highly efficient for big data and serves as a modern successor to that feather format. So what you would do is you would just install the packages, use Arrow, load up your library, and then you can use the read Parquet, and then whatever file it is you want. And of course, this is fast and efficient, because a lot of times what we're doing at this level in the course is we're just focusing on getting the data in. It's just mostly it's made up, or it's very small data. But when you start getting into that very large data, remember we talked about this early in the course, that's where you start getting into things where scale becomes a problem, where you have to focus on speed, efficiency, storage, transfer rates, all that kind of stuff. And this is a modern package that is built to do that. So while Feather was the gold standard for a while, Arrow has since replaced it. But I wanted to keep both in there just in case. Feather does still exist. You can still use it. But nowadays, most people would use Arrow. There's also the Rio package. So the Rio package is a convenient wrapper for various data imports and export functions. It allows you to read data from multiple file formats without loading in multiple packages. So this one isn't anything particular like some of the ones we've looked at previously. It's more just a collection of different types of import and export tools. So it can read CSV files, it can read Excel files, it can read SPSS files. It has just a whole bunch of collected different tools kind of available to you. Another way to import data that might be very useful is the HTTR package, which provides functions for working with HTTP connections. So specifically, if you're dealing with anything online with hypertext transfer protocols, this allows you to import data from APIs, from web services, things like that. So this one is actually much more commonly used than when I first started doing R. It was a thing, but now a lot of times you're going to be calling on APIs. If you ever plan on doing work with AI systems, guess what? You're using an API. You don't just jump onto and connect to something like OpenAI system. What you would do is you would have to create an API key, and then you use R, something like the HTTR package, to then access that from your R environment. So the way you'll use this is for whatever response you have, you'll use the get command. So get, and then you will put the location that you want to. Now you may have to put more information depending on what kind of API it is. For example, when I've used OpenAI for some of the work I've done, I had to have a specific special key that I had to use so that not anyone could connect because it would be using my tokens. So I had to have extra information. You can read more into that if something you want to get into, but just know that it does exist and R can do all these things. So once you actually have done that get, then what you can do is you can pick your content using content, your response, and then of course you can have it as parsed or whatever functions. Again, you would look this up depending on what kind of data, what kind of API your call you're doing. And then from there's going to be more arguments just like there always are. And anytime you start using one of these, do like we always did in class, do the question mark, learn more about it, see what arguments there are, because you might need different ones depending, right? Because this is not a single source like a read.csv, or even then, that's really not. You can pull from websites or from direct file. But depending on if you're doing an API call versus a web service, you may have some different arguments you need to use. The foreign package allows us to read data from various statistical software, file formats such as Minitab, S+, and others. The main functions are read.mtp for Minitab or read.export for SAS export format. So just like before, use one of those. If someone sends analysis in one of those different programs, you can pull it directly into R using these. This next slide is actually a newer slide I had to update because it used to be that there was the Google Sheets package, which you could use to pull up Google Sheets. It has since been replaced with Google Sheets 4. So if you try to use Google Sheets, it is no longer going to work. It's been deprecated. It no longer exists. So the Google Sheets 4 package, so don't forget the 4, provides functions to read data from Google Sheets into our data frames. You can use the read_sheet function to read data from a Google Sheet given its URL or key. So in this case, again, you would load it up. You would use read_sheets. Within your quotes, this is where you're going to put the path to your actual Google Sheet. And then, of course, again, there's going to be arguments if it's something like, if you need permissions, something like that. Another way you could get data is you could use something like the rvest package, which allows you to do web scraping. So it's a web scraping library for R that allows you to extract data from HTML and XML documents. So we'd use the HTML_nodes or HTML_text function to extract specific data from web pages. So this one kind of falls into that gray area because you're not going out and making a call, going through any sort of permission process. And a lot of sites have started, especially with the advent of AI, which constantly scrape websites, to sort of start blocking this kind of stuff. But if not, what you can do is if you have a website, you pull up like a web page, for example, you could use something like you could read the HTML_text saying, go through this website, pull all the text from it, and you're going to get some other artifacts from it. I will warn you, you're going to have to clean it up quite a bit. But this is one way you could do that web scraping. And there's other ways you can do web scraping. Now, here's why it's a little bit of a gray area, though. Remember I just said a second ago that AI companies specifically went out and they've scraped anything and everything. Well, first of all, there's always been some question about whether that's ethical or not, because who owns the data? Should you be able to just grab it? It's publicly available. You should, stuff like that. But there's also the factor of cost. If you have some small website, let's say that you make a website about the game Warhammer, and it's a personal website for you and just fans of the game. You get a certain amount of traffic, maybe 1,000 visitors every month. No big deal. You pay your cost for web hosting and everything's great. But then suddenly, and this is actually something I've read an article about, you have these services where not only do they scrape your site, they constantly ping your site. They just constantly go to it. Like you're suddenly getting millions of views even though your actual viewers hasn't gone up. But you know what does go up? The cost, because your web host costs are going to have costs that are built into how much traffic you get in your site. Higher traffic sites pay more money. So a lot of times people and companies now are starting to put the do not crawl functions within their robot text and stuff like that. Basically telling systems do not allow them to crawl and do web scraping, stuff like that. So this one is kind of iffy whether it even work at this point with most places, but it is something you could possibly still do. The read text package is specifically designed to read text from data from various file formats, including plain text, CSV, JSON, XML, PDF, and others into our data frames. So again, this one has a lot of overlap with these other things we've talked about, but one I specifically wanted to focus on here is PDF. And this is one that I personally have used because I have like a PDF and I might want to pull in the data. Again, if I'm doing like natural language processing, let's say that I have a text page with a bunch of text from a story and I wanted to extract the keywords. Specifically, we were doing research on tier 2 vocabulary words. In that case, I need to pull the actual text from the PDF. So I could use something like read.txt. The OpenXLSX package is another option for reading and writing Excel files. Again, both XLS and .xlsx formats without the need of Java dependencies. Now you might wonder, I already talked about a way to read Excel files. Why would I talk about another? Well, I specifically chose this one because I wanted to bring emphasis on the fact that there are going to be many other packages that do the same stuff that I'm showing you. And there's going to be certain advantages to each of them depending on what it is you're trying to do. What sort of data? Where's the data source? What sort of arguments do you have? So just because something has been done in R does not mean that it's not done somewhere else. And it might be done better in a way for whatever you are trying to do. This next one is one that I have a lot of experience with. This is the DBI package. So the DBI package provides a database interface for R, allowing you to connect to various databases such as SQLite, PostgreSQL, and others using a consistent API. You can use the DB connect, which is just like the other one we did previously, and DB get query functions to import data into R. So the reason, again, I said I've used this quite a bit is for my intro to stats projects, I have PostgreSQL databases set up for them. This is how I actually do it. I use the DBI package. So just like before, if I want to install it, install.packages DBI, where DBI are all capitalized, load it into my library, and then I would do my connection using db connect. And this is where you would say what type of SQL you were using. In my case, it would be PostgreSQL. And then I would put the path of where it is. I would also include the information, like I said, like my key and stuff like that. Once you've done your connection, now you need to actually do the query. So it'd be db get query, and this is where you would say, I'm going to use this connection, the database I'm connected to. You need to say what the function is that you're using within your SQL database. So again, select, if you did star, it's going to select everything, and then from what table, something like that. So for mine, it would be something like select, instead of like star, I would have something like, I don't remember how exactly I set up because it depends on what I'm querying, but a lot of times I'll query it by date because I have prior projects on there, but I don't want to pull those projects. I only want to pull the new ones. So I'll query based on date, stuff like that. And then once you're done, as always, you want to disconnect. And you would do this with the DB for database disconnect. And you would select your connection. In this case, we wrote it as con, and it would disconnect from your database. And then the last one I wanted to just bring to your attention is the R list package. This provides functions for working with lists in R. It's useful for importing data from JSON and XML files when the data has a hierarchical or nested structure, right? So if you're doing from JSON, it's from JSON. And then if you wanted to parse that data, you do list.parse. That would put it into your data list. This is just a small sample of the different packages available in R to import data. Because what is R without data? Right? The whole point of doing statistics is to answer some question. And the way we answer that question is using data. In any definition you look at about statistics, it all revolves around data. Well, just like that, R is a programming language made for statistical analysis. It can do other things too. I've seen people make games like Snake and stuff like that in R, but that's more exception than the rule. Its hardcore purpose is for statistical analysis. And the way you do statistical analysis is you need to get data first. And a lot of times you're going to have disparate data sources in different file formats from different locations. And R has functionality that you can get in these packages to deal with any of them, right? So what you'll need to focus on, this is why I always say project-based learning is really the best way to get better at programming, because you're going to have to find that data. Then you're going to have to figure out what format and where is that data and how can you get that into R. And then once you've done that, then you can start doing all the stuff we've been covering in the class. So like I said, every one of these, I could make an entire lesson on how to use and implement these different packages. But I just wanted to introduce them to you so that you know that there is this huge R ecosystem out there and tons of functionality. And this is where using that documentation, ability to read documentation that we've looked at, can be so useful as you expand using R. Hello everyone. I wanted to finish off this course by not talking about another topic in this course, but more looking at what comes next. So oftentimes when you've got your strong understanding of statistics and you've gotten a decent amount of understanding of programming, the next step is people want to get into machine learning. So I wanted to briefly introduce these topics. We're not going to go in depth into them, but I will tell you that I actually do plan eventually going much deeper into this, both creating an advanced computational course where this will be the main focus of it, and also creating videos to go along with it. I will tell you from the beginning that this is actually my main area of expertise. I got my PhD specifically in statistical learning methods. Most of my research is on this, though I have branched off since then doing more Bayesian analysis and other approaches like this, causal inference, stuff like that. But my main focus, my main core skill is within statistical and machine learning. So let's first look at what is statistical learning. So statistical learning is a field at the intersection of statistics and machine learning, which focuses on understanding and modeling the underlying patterns and structures in data. Its primary concern is with the development and application of various statistical tools and methodologies to analyze and interpret complex data sets. So its goal is to make informed predictions or decisions based on data. So you might think that sounds just like statistics. And it really is. In fact, if you pull out a statistical learning book, the first method they will always talk about is going to be linear models, which we've covered in this course. That is a part of statistics because statistics is learning something from data. The difference oftentimes is the approach, because a lot of times when you're dealing with statistical learning, we are going to use methods like we did for our validation sets, where we are going to hold some of the data out, and we're going to be testing it against that to try to see how well would it work under some unknown data conditions. And then the thing is also with this is that oftentimes these terms get thrown around and the definitions are kind of loose. Like the difference between statistical learning and machine learning or AI are all kind of nebulous, because statistical learning and machine learning are basically the same thing. But oftentimes statistical learning is the underlying theory of the machine learning, the algorithms, stuff like that. Machine learning is more the applied side. It's the actual creating systems that do this. So an example of this might be, and I'll talk about this a little bit later, is we have something in statistical learning called association rule mining, which is also called market basket analysis. When doing market basket analysis, if you were to implement this to actually create a system where it's going to keep track of people's data and it's going to analyze it, determine shopping habits, let's say at a grocery store, and then you can make decisions from that, guess what? Now you've created a machine learning system. That's really the only difference. You're using market basket analysis. It's just one is the underlying theory of it, the association rule mining, and one of them is the actual system of implementation, which is why they're kind of interchangeable, because oftentimes we'll just say, oh, I created this machine learning algorithm, which you haven't done anything with. If you created the algorithm, it's statistical learning. And then you get into like the area of like AI, which a lot of AI systems are really just machine learning, right? And where you kind of draw that line. Nowadays, it's gotten more focused on AI because of large language models, but this all predates that by a long shot. In fact, these slides are older than the oldest LLM that anyone's been using commercially. So why is it important though? It helps to decipher patterns and relationships in data, and it's crucial in many fields from business to science to engineering. So a lot of times now, when you see some company claiming that their system uses AI, what they really mean is machine learning. But we'll get to that in a minute. So what is machine learning then? Machine learning is a subset of artificial intelligence, or AI, that enables computers to learn from and make decisions based on data. That's the key point, that decision making, not just how does it learn, but then from that, how does it actually make a decision, right? When we're doing logistic regression and we figured out that cutoff point, anything below here is a 0, anything above here is a 1. And then your machine learning algorithm might have that underlying statistical learning in there. And then from there, it might deny or approve something. Or if it's, let's say it's a spam filter, it's going to make a decision. Is this spam? Yes, block. No, let it go through to your inbox. It focuses on the development of algorithms and statistical models that enable computers to perform tasks without explicit instructions, relying instead on patterns and inference. So your key aspects are that it emphasizes algorithmic model development and prediction accuracy. So why machine learning? It enables automatic improvements over time, right? Because it learns from data. This is the difference between it and just normal statistics. In statistics, we usually have some set data. Now, it's not always true. If you have time series data, you have things like moving window kind of algorithms, things like that. But the idea generally is statistics usually is a little bit more static. We get data, we analyze, we infer. We try to get the simplest model possible. Machine learning, on the other hand, is going to learn from data, and it's going to be a system that is set up to be in place to make a decision based on that data. And as new data comes in, it will continue to update and iterate to learn to make better decisions in the future, right? If I have some company and I'm getting customers in and I need to make a decision whether to put a product on sale, when I have 10 customers, it's not going to be easy for me to make a good decision based on that data. But as I get 1,000 customers, 100,000, 1,000,000 customers, it will learn from that and it will get better at actually determining when the right time is for that decision. It can solve complex problems that are difficult to program explicitly. And that's the key part here. When you are doing programming, like we did with our if-else statements, our where statements, our for loops, even our functions, we were explicitly programming what it should do. In machine learning, you are trying to solve problems that would be difficult, where you don't have to put so many if, else, if statements to try to figure out every possible condition. So when you are doing machine learning, there are two main fields of machine learning. There's supervised learning and there's unsupervised learning. So supervised learning is learning from labeled data to predict a specific outcome. That is to say, when you have data where you know your output variable y, you know the answers. This would be something like if I'm creating a classification algorithm and I know what the actual outcomes are, right? So one of the famous examples that I always used to show my students, and this was early days of machine learning vision, was muffin or dog. And actually, let me pull that up real quick. So if you just do a quick image search and I looked up muffin or chihuahua, you can see this would be the sort of thing that you would test a system on. So if you look to the right, you can see this image where you've got, muffins and chihuahuas, and then a system would have to try to determine, is it a muffin or is it a chihuahua? Now, as a human, we could label this data. Muffin, chihuahua, muffin, chihuahua, muffin, chihuahua, muffin, something like that. So this would then be labeled data. And then from that labeled data, the system could then learn what different factors actually would lead it to make a decision to correctly say when something is a muffin, when something is a chihuahua, something like that. So this is what we mean by supervised learning. We know the answers. And then usually what we'll do is we will have 80% of the data that is going to learn from, and then that 20%, which is also labeled, we will then predict those. We will test the system's predictions versus the actual outcomes, which we know. And then we can look at how well is it doing things like positive predictive rate, accuracy, precision. You can use ROC curves, all that kind of stuff. So an example of this might be something like predicting housing prices based on their features. You might say, okay, houses with 3 bedrooms tend to sell for the extra amount, houses that are above this square footage. And basically you could create a machine learning system that will predict a housing price based on the different features of a house. But you know the price of the house, right? You can look that data up, and then from there, you can look at how accurate was your machine learning method. Next, we have unsupervised learning. So it's finding structure and patterns in unlabeled data. So those are the key two aspects. Supervised, we have labeled data. We know the answers. Unsupervised learning, we do not know the answers. So oftentimes, instead of having a hard decision, what you would do is you will group things first And then oftentimes we'll have a person come in to try to analyze what groupings it made to see if they make sense. We call this an oracle, someone who comes in and with their domain expertise or subject matter expertise would explain, yes, these groupings do make sense. And oftentimes, the fun thing about unsupervised learning is that it may actually give you groupings that you didn't expect. So now, this is different from just your typical unsupervised supervised. There's also there's type of algorithms called clustering algorithms. And oftentimes they're used in unsupervised learning. So one time I did clustering algorithms on different politicians' speeches, I think for the upcoming 2016 election back in the day. And I grouped them. I was thinking, okay, it's going to group people by political party, left and right, Democrat, Republican. But it didn't. What it did is it grouped some Republicans and Democrats together, and it grouped other Republicans and Democrats together. And looking at the groups it did, it wasn't grouping them by political party. It was looking at the language they used, and it was grouping them by the extreme language that they used. People who talked about this being devastating or crushing or extreme language were all grouped together. Those who used more moderate, neutral language were then grouped together. So really what my clustering algorithm did is it actually looked at middle ground candidates versus populist and or extreme candidates, if you want to consider it that way. It found this grouping that I wasn't thinking of. I was thinking of, again, left or right. I just wanted to see, could use natural language processing to predict someone's political views based on their speech. And instead I found you could predict how politically extreme they were. An example of an unsupervised learning algorithm would be something like grouping customers based on purchasing behavior. So again, this would be clustering. On top of supervised and unsupervised learning, we also have what's called reinforcement learning. So an algorithm learns to make decisions by performing actions in an environment to achieve a goal, learning from rewards or penalties, and it then receives while it's doing its actions. So this would be something like if you've ever watched somebody online where they create a bunch of AI systems that try to figure out how to play a game. Let's say it's trying to get through a maze or get through obstacles without being, defeated, or climb, jump up some paths, or even play a game like Mario. What it's going to do is it's going to send out thousands of different iterations of the system, and it's going to rate how they did somehow. And you could either reward those that do well, or you could penalize those that do badly. And then what you usually will do is you will take the best performing systems. You will then iterate off of those, create a ton more, and you will keep doing this over and over again until you get a system that can beat the level or whatever. An example of this might be something like genetic algorithms. If I have a system that I want to teach how to play chess, instead of explicitly writing all the different chess moves and going through chess history and trying to figure out the best move to everything, all I would do is I would create a system that knows the basic rules of chess. And then I would make millions of those systems and have them play against each other. And every time a system loses more than some number of games, it gets eliminated. You get down to the best, let's say 5 algorithms. You then, again, propagate out, have them play against each other, and you do sort of a survival of the fittest. And this would be genetic algorithms. They are learning by reinforcing the positive or negative behavior to eliminate those that don't perform and then learn the task at hand. This is how a lot of systems that you see are actually done, right? When you see a robot that is learning to walk, and the first time you see the iterations, they're not very good, but over time, eventually it starts to look more natural, looks better. This is what they're doing. They're doing reinforcement learning. As it performs better, it gets rewarded. If it performs badly, there might be a penalty. And whether you use reward or penalty would depend on the system you want to use. Which one of these you are doing will depend on what kind of data you have and what your goal is. If you have labeled data, you want to do supervised learning. If you have unlabeled data, but you still want to be able to find out something about what you have, unsupervised learning. If you have a system where you are trying to train up to a certain outcome, you might use reinforcement learning. And within each of these, you are going to have different types of problems, right? When I'm doing supervised learning, generally the problems are, we've got regression problems, just like statistics. You've got classification problems. You can do clustering with supervised learning, though you already know the grouping, so this would be something you compare it to. And then, of course, there's other things you can think about, time series, all that kind of stuff. These are different ways of approaching the same thing, which is to use data to learn from it and get to some goal. Now, some of the key concepts that we want to focus on in machine learning are training and testing data, right? We already talked about this some in our class, but training data is used to build machine learning models, and then testing data, which again, usually we already know the answer to, it's part of our original data, but we separate it out, is used to evaluate a model's accuracy and performance. And this oftentimes can be useful when you don't necessarily know why something is, but you know what the outcome is. You could then try to get a system that is pattern matching to get to an algorithm that can actually give you those correct answers, but you want to test it on data it's never seen before to see, will it actually work if you had some new data. Another concept you need to consider is overfitting versus underfitting. So overfitting is when a model is too complex. It performs well on training data, but then it does very poorly on new data. This is where we were looking at things like AIC, BIC, deviance. These are all ways of penalizing overly complex models because, as I talked about previously, if I have 100 data points, I can make an algorithm that hits all 100 perfectly. But the second I put in new data, which isn't exactly on that line, which is not a straight line, it's going to perform poorly. This would be an overfit model. And in fact, a lot of models, this is something that we actually built into them. For example, there's the multivariate adaptive regression splines algorithm. It has what's called a forward pass, where it builds out this overfit model. And then it does a backwards pass, where it starts eliminating parts of it to create the most robust model while still being accurate, but not overfit. Then you also have to worry about underfitting. If a model is too simple, it does not perform well even on the training data. So an example of this might be something like linear regression. It doesn't mean that you can't get any insight out of it, right? If I have a linear regression, I have an upward facing line, it tells me that there's some changes. X increases, Y also increases. But it's not giving me the nuance that there might be in it, right? So this would be an underfit model. And this is why when I talk about statistics, I say we want the simplest model that still gives us good results, because simple is good. But if it's too simple where you're not getting that information, then this is also a problem. You want to find kind of that Goldilocks zone of not too complex, but also not so simple that you don't get any of the good information from it. So examples of these algorithms would be things like decision trees, neural networks, or support vector machines. And I'm just following up with a couple examples of those. So let's say you have like decision trees. You might want to classify data into different categories. The image I have here is a spam filter. So first thing it looks at is it might have something like, does it contain the words urgent, winner, or free? Yes. Okay, if it does, is the person on your contact list? If yes, it's not spam, send it to your inbox. If it's not someone on your contact list, that means it goes to spam. If it doesn't include those words, if it contains suspicious links or attachments, and there's something like this, it could be branching logic that you figured out. So this would be a simple decision tree for classifying emails as spam or not spam. You also get something like this, neural networks. This could be something like doing complex pattern recognition, things like speech or image recognition. And by the way, even this gets much deeper. Neural networks are the foundation of deep learning. If you've ever heard of convolutional neural networks or anything like that, this is the basic idea behind them. So its basic structure of a neural network has input, hidden, and output layers. Which, fun fact, by the way, both of these images that you see on the screen right now, I actually did create in R. Now, as I mentioned, there's a lot of overlap in machine learning and statistical learning. And oftentimes people will just lump it all into saying machine learning. So while it overlaps with machine learning, statistical learning traditionally puts a greater emphasis on model interpretability and understanding compared to often more black box method approach in machine learning that focuses on prediction accuracy. Some of the best out-of-the-box methods or models you can use would be things like random forest or gradient boosting machines, which you might see something as like AdaBoost if you're focusing on the computer science programming side of stuff. Both of those methods work great for a lot of things, but they are considered black box methods. They don't have high explainability. They're easy to interpret the results, but they're hard to interpret why. Statistical learning oftentimes will focus on the underlying interpretability, understanding the algorithm side of it. And this is really kind of where they differentiate. But again, even that's kind of fuzzy. Like if you pull out your statistical learning book, I guarantee that it's going to have random forest in there because it's black box. Because the way it works is if you create like 10,000 trees, I can go into my code and I can pull out the results of every individual tree. I can see the individual branches of the decision trees that make up that random forest. But because it reaches a certain level of complexity, it becomes very hard to interpret. So therefore, we consider it black box, meaning we don't know what's going on under the hood. We can just see, here's the input, this is the output. We test the output oftentimes in machine learning versus the actual underlying method. So an example of this might be if I'm doing some sort of classification and it classifies as this, what I'm going to do is I'm going to use a confusion matrix. How well did it do? If it did really well, then great. Seems good. If it didn't do well, go back to the drawing board. You're looking at the result. You're using the results for your comparison. So now let's talk briefly about bridging the gap in R between stats and machine learning. So your statistical approach would be, again, inference. In some previous lectures, we used base R functions like LM or GLM for the entire data set. And then what we did is we focused our primary goal at looking at summary for getting things like its p-value, its coefficients, and the true relationship between those variables. In a machine learning approach, if we were trying to do like prediction, for example, the goal is predictive accuracy of some unseen data. So instead of using the whole data set to check our p-values, we would explicitly split our data 80% into training, 20%, let's say, into testing. We use the training set to build the model, then we would use that testing set to see whether it seems to work. So while we can split data manually, modern R data scientists use packages like caret or tidy models framework to automate machine learning pipelines, cross-validation, and performance tuning. And then I just kind of put an example of some code here, even though it's kind of generic. If you were doing like a statistical setup, you might do something like a GLM where you have Y being modeled by x1 plus x2. Your data comes from my data, and our family is binomial. So this would do our generalized linear model using a binomial link function, and then we would use summary to interpret the relationship between the variables, get the p-values, and then we could infer something about the population. In machine learning, you might use something like tidy models to then take the data, split it into your 80% training, your 20% testing, and then create your model using that, test it, and then see how well it did on that test. But what about AI? So artificial intelligence, or AI, is a branch of computer science that aims to create machines capable of intelligent behavior. It involves designing computer systems with the ability to perform tasks that typically require human intelligence. These tasks can be reasoning, learning, problem solving, perception, language, understanding, and many other things. Now there's two main types of AI. There are narrow AI. So the characteristics of narrow AI are they trained for specific tasks. They operate under limited context. This would be things like virtual assistants or recommendation systems. So for example, I mentioned the association rule mining, also market basket analysis, which is a recommender system, right? It would make recommendations then that companies could use. In fact, a lot of recommendation systems could be based on something like this. When you're looking at Netflix, what it's doing is it's looking at people's, viewing habits. People who watch this also tend to watch this and this. Okay, great. You watch this and this. Here's other things like that. It'll find association between different things. General AI is a theoretical concept of a system with general cognitive abilities similar to a human. And I know that things have gotten more fuzzy with that with large language models, but a lot of it is a trick, okay? And this is one thing I do want everybody to understand is that large language models are just very, very sophisticated learning algorithms. They use tokens, a system called RAG, and what it does is they call them oftentimes a stochastic parrot. It is like advanced autocomplete. It is looking at, based on what you gave it, what is the best response, the highest probabilistic value of the next thing it should say, which is why it will always give you an answer typically, even if it hallucinates and makes that stuff up. And there are other aspects that are added to it by the different companies. For example, they tend to be what are called yes men, where they will always flatter you and tell you how great you are and you're so right, because they know that if they use this sort of positive back and forth with you, that you are more likely to continue using it. But realistically, it's just a really advanced system of predicting based on what you had and the data it has and the associations that it's made. That's where the tokens come in. Then it can figure out these things are associated with each other. It creates a probabilistic model of what the most likely correct values are, what's the best choice. And then it does that with some stochastic nature, which means randomness, to give you different responses each time. So that way you don't just get the exact same response every single time. So this is still, again, kind of in the realm of science fiction. We're getting closer, but we're not even remotely there. So it's still a very big topic in research. So this would be, examples of this would be autonomous vehicles, chatbots, and personalized content. again, we've made great advances in that, right? Autonomous vehicles are currently on the road. We've got Waymo and whatever Tesla's is on the road right now being tested out. You've got chatbots. We all use them every day now. Again, these slides predate the large language models that exist right now. And also you have personalized content. Well, guess what? You get that kind of stuff. You can get that stuff all the time now. These things are becoming reality. But don't put more into it than is actually there. These are very sophisticated models. They are not intelligent models. Okay, so this is where you gotta be careful with that intelligence. And I will actually tell you straight up, I am actually a proponent of the narrow AI focus. I tend to think that a lot of times a more narrowly focused and specially trained system for particular tasks will outperform a generalized system that does everything well, right? It's the idea we always kind of come back to is from the Jetsons, you had Rosie the robot, the maid who could do every cleaning thing in the world. But the problem with that is to create a system that does all the different cleaning, it has to know how to do a lot of things very well. And it also has to be able to move around like a human. It has to be able to use tools. There's a lot to it. Where I could create a Roomba, it's a very specific specialized tool. It vacuums floors. That's all it does. It has sensors, it's got wheels, it's got little brushes, it's got everything to do that one task very well. And that's the idea behind a narrow AI focus versus a general AI focus. Narrow AI, the idea is that you would have multiple systems that do different things. An example of where general AI fails. Recently, we've actually submitted a paper for publication where we tested a bunch of large language models on their ability to read children's stories, find appropriate words for children to learn, and give child-friendly definitions. And while doing this study, we found the systems were okay at picking words. The definitions were tremendously precise, but they were terrible for being child level appropriate. They gave adult level definitions, which oftentimes had other advanced words or even cyclical definitions, but they weren't appropriate for what we wanted. We didn't want a system that gave precise Webster's dictionary definitions. We wanted one that you could actually use with 4 and 5-year-old children. It's not a specialized system. Whereas if we created something maybe like a small language model, which is specialized only on children's word learning, then we could probably get better results than a general model, which does everything well, but nothing exceptionally. One of the other big considerations you have to have with AI are the ethical considerations. So the importance of ethics in AI. As AI technologies become more integrated into society, ethical considerations are increasingly important to ensure that they benefit humanity without causing unintended harm. So these would be things like we need to focus on key ethical AI issues. We need to focus on things like privacy and data security, right? AI systems often rely on large data sets where it raises concerns about people's privacy and security of their personal information, right? For example, using facial recognition technology and its implications on privacy. And again, I want to emphasize, these slides predate the stuff that's going on right now by about 10 plus years. So anything that's happening right now with these particular topics, I want to point out that these were things that we were considering way before this time period right now, where these systems are starting to be implemented more and more. So what are some of these AI, ethical considerations we have to consider, right? We have to think of things like bias and fairness. AI algorithms can inadvertently perpetuate and amplify biases present in training data. And you can look up many examples of this. For example, there was a case where they tried to use a machine learning system to try to determine the recidivism rate of inmates when they were let out on parole. And they implemented the system and it led to bad results. You can look this up. I'm not going to go into great detail because it didn't look at recidivism rates as who was more likely to commit a crime when they went out. It looked at things like, where do people live? Do they live in places that are over-policed, overcharged, things like that? It wasn't finding who was more likely to commit a crime. It was finding who was likely to be arrested because of other societal type issues that might be the case. So sometimes these are things you have to consider. Another example would be something like AI in hiring processes, potentially reflecting historical biases, right? Because again, these machine learning algorithms are not smart. They are making decision on data. Remember we talked about garbage in, garbage out. If I give you biased data, I'm going to get an algorithm that gives me biased results. That is how it works. So understanding how AI makes decisions, this would be, again, where explainable AI comes in, is crucial for accountability, especially in critical applications like healthcare and law, right? We need clear explanations in AI-driven medical diagnosis, for example. You don't just want to say, here's the diagnosis, move on. You want to know, why did it make that decision? Another ethical consideration would be things like job automation and employment. AI's role in automating tasks raises concerns about job displacement and the future of work. Examples of this might be the impact of automation in industries like manufacturing and customer service. Some of the aspects you might look at are its ethical use and/or if there needs to be regulation. This would be focusing on balancing innovation with ethical use, including how AI should be regulated to protect society. Examples of this might be things like debates over the use of AI in surveillance and law enforcement. And what I'd like to leave you with is to consider this. How can we ensure the ethical development and deployment of AI technologies? What roles should governments, industries, and educational institutions play in addressing these ethical challenges, right? So your ethical considerations in AI are complex and multifaceted. They require ongoing dialogue and collaboration between technologists, ethicists, policymakers, and even the public, right? And this is why I wanted to kind of end on this because, as I mentioned, while we've been doing this course, we've been learning about how to start programming R, statistical analysis, and the next step from there is statistical learning, which is the foundation of machine learning. Machine learning, in my slide, says is a subfield of AI, but really I would consider it the foundation of AI. There is no AI without machine learning. But as we make these systems that are more advanced and can make decisions, these are things we need to consider, even as those developing them. Oftentimes we push those off to other people to make that decision. But what we need to consider is, even if it's just as simple as, should this person be approved for a loan? Yes or no? And we put that into a decision-making system. As soon as you take a human out of the loop, you need to make sure that your system isn't giving biased results. You need to understand why it's making the decisions making, and you need to have a person who can audit the results to make sure that it's doing what we want. And these are the kind of ethical considerations and things we have to think about when we're learning about systems, when we're building systems, and when we're implementing systems. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.